Hello friends, hope you are having a fantastic day today. This is going to be part 3 of our 50-hour long mega DSA course that contains every single thing there is to know about technical interviews, data structures and algorithms. Now, due to YouTube's restrictions, I can't upload full 50 hours in one video. That's why I have to break it down into a bunch of different parts. You can find part 1 and part 2 right over here. And now, without any delay, let's get started with part 3. Hello friends, hope you are having a fantastic day today. So now we are going to do a full course on the tree data structure, and trust me, after this you would become a master in all sorts of tree related interview questions. In this course we will learn what is the trees, what are different types, characteristics, when to use it, benefits, limitations, and what are going to be the time and space complexity of different operations, plus how to do different types of traversal, how to solve different kinds of questions. We are going to cover every single topic. So without any delay, let's get started. Tree is a very unique data structure, and if we see the categorization of tree, it is defined as a non-linear data structure. It is very closely associated with graphs with some differences that we are going to learn later in this course. Typically, we use trees to define relationships, and these relationships are typically hierarchical in nature. Now, these can be anything. You can think of a family tree, or you can think of a file system, or you can think of a structure inside a company or an organization and stuff like that. But typically, a tree usually comprised of two entities. First one is called nodes that we typically define by these circular items, and then second one is the edges between the relationships. And these relationships inside a tree are parent and child based relationship, where every single node can be a parent, or it can be a child, or it can be a both. So in this case, the very first child would be the root node, and then it has two subsequent children, and then these children can have children of their own, and so on and so forth. Now let's learn some terminology associated with trees that will help us understand better about different concepts. So first, let's understand that what are the different types of nodes available. Now, very first one is a root node. Root node is parent to every single node. That is going to be the top node inside a tree, and this is going to be the gateway point through which we can enter tree and then traverse over all the other remaining values in different fashion. Next is a parent. Now, any node can be a parent as long as it has child of its own. So in this case, this is a parent node, this is a parent node, this is a parent node, and this is a parent node. But these two nodes, or these three nodes, are not parent node because they don't have any children associated with them. Next, we have child. So every single node can be a child node except root node, because root node would be sitting at very top, so it does not have any parents of its own. But currently, like, these two nodes are going to be children of the root node, then these two nodes are going to be children of this particular node, so on and so forth. So that can keep on going on and on. Next is a leaf node. So leaf node are the nodes that sit at the very bottom of the tree that does not contain any child of their own. So these are defined as the leaf nodes. Now the concept of subtree. So subtree can be part of any existing tree. So we can define that for any particular parent. So for this particular root node, we can say that this is one of the subtree of this particular node because it is part of its hierarchical structure. Same way, for this particular node, it only contains this node as part of its subtree, nothing more than that. Then there is a concept of height of the tree. So height of the tree is the longest distance we can make for any particular node from its root. So in this case, if we have to calculate height, at this level height would be 1, at this level height would be 2, and now notice we still have one more node at this level, so height is going to be 3. So in this case, we can define height to be 3 even though we still have nodes that are going to be at lesser heights. Then we have depth of a tree. So depth of a tree is that for any particular node, what is the distance from its root node. So we can say for this node, the depth is going to be 2 because it is 2 steps away from the root node. Same way, this node is going to be 1 step away from the root node. So the depth of this node is going to be 1. And last one is a degree. So degree is defined by the number of child any particular node has or any particular tree has in their structure. In this case, we can define that this node has a degree of 2 because it has 2 child. Same way, this node has a degree of 2, but in this case this node only has degree of 1 because it just has 1 child. So these are the terms that you will need to understand. Now let's learn that what are the different types of trees available. First one are the general trees. We can have a root node and then it can have any number of child of its own from 0 to n. It can have one child, some nodes can have like 5 childs, some node can have just no child at all, some nodes can have like 50 child, so on and so forth. So there can be many relationships and these can be very complicated, but we see all sorts of scenarios where we need to implement trees like this. Second one is a very restrictive tree that is highly used in technical interviews and also in real life, and that is binary tree. So binary tree has a simple formula that every single node must have at most 2 child or less than 2. So let's say in this case, this is going to be an example of a binary tree where we have nodes like these, where each of the node either has at max 2 child or less than 2 child. And this is like a good example because every single node either has 2 child or less than 2 child. Next one is a ternary tree. This is just for an example sake. In this case, every node are going to have 3 child at most, nothing more than that. So they can have 2 child, 1 child or no child at all, but overall not more than 3 child. So this is a very similar example to binary tree, and same way we can define as n array tree. So where n can be any value. If we define n to be 5, then at any given moment any particular child can have at most 5, any particular node can have at most 5 children and nothing more than that. So there can be many examples. And then there is a special type of tree, that is binary search tree. This contains a very special property where we are going to have a scenario where the value is going to be determining the structure of the tree. And of course this is a binary tree, so at most every single node can have either 2 or less than 2 child. Okay, that is a given fact, but on top of it, for every single type of node value, we are going to follow a strict principle that any particular value that is currently present on the left child has to be less than the root node, and any particular value that is currently present on the right child has to be greater than root node. So root node, the value is going to be that left child is going to be lesser than the root node, that is going to be lesser than the right node, right side node. And let's see an example of this in action. Let's say currently we are given a value 5 as a root node. So we can guarantee that no matter how many entries are currently present on the left side of it, all of these entries are always going to be less than 5, value number 5. Let's see an example of this. Let's say we can have a node like this, that is value is 3. Once again, for this 3, we are going to follow the same principle that everything on the left of the 3 is going to be less than 3. So this can be value 2, and then this can be value 1, and then this everything on the right of this 3 has to be greater than 3. So this, let's say this value is 4. Now we can think that 6 is also greater than 3. So can we put 6 over here? No. Why? Because we are still following the same principle all the way up to root level. So even though this value is going to be right of this particular tree, it is still going to reside on the left side of this particular 5 tree. So this value also has to be less than value number 5 as well. So this value can be 4. And same way on the right side, we can follow the same principle where every single value is going to be greater than 5, but there can be some like variations on its own. So let's say that this value is currently 8. Then the left of 8 is going to be value number 6. The right of 8 is going to be value number 9. And then the value at the right of this 6 can be value number 7, because notice now in this case for 8, every single thing on the left of the 8 is still going to be lesser than 8, and where we are following the same property. So now notice that if you traverse this particular tree in like this fashion, then you will find a sorted entry. And let's just try to quickly see that the very leftmost value is going to be the smallest value, and then its subsequent way. So we are going to traverse like left, then if there is nothing left on the left, then we are going to iterate its root, and then we are going to iterate its right child. And this traversal mechanism would actually allow us to get a sorted result or a sorted value for all the values that are present, and we are intentionally maintaining this property. So now I went a step ahead and actually just showed you that what does traversal mechanism looks like, and this is actually an in order traversal. Don't worry about the word. I'm going to explain this in very much detail in subsequent parts. But remember that we can have a binary search tree that is going to allow us to have a sorted property being stored amongst different values that are currently present inside the tree. Now let's quickly learn that what are the different types of binary trees, because sometimes there can be questions being asked from these topics. So first one is a full binary tree where every single node either has 0 child or 2 child. So we can notice an example like this where this particular node has 0 child. Apart from that, and also this node has 0 child, this node has 0 child, but apart from that every other node has exactly 2 childs at the moment. We never have a scenario where we have only one child hanging. Okay, next one is a complete binary tree where all the levels are completely filled except the last level that is filled from left to right. So we can notice that, okay, this level root is completely filled, this level has 2 child, that is completely filled. Now this is the last level, so all the nodes are filled from left to right, and then we have one node that is currently not present. So basically there can be many examples. Next is the most beautiful type of tree, that is called perfect binary tree. So all the internal nodes has exactly 2 children, and last level is all leaves that are completely filled. So basically this is like the most good looking tree out there, that where every single node has exact 2 child, and then leaf node has no child at all. So this is perfect binary tree. And then we have a balanced binary tree, which is actually a very popular LeetCode problem that we are going to solve later on. But over here the thing is, height difference between left and right subtree is at most 1, nothing more than that. So we can notice that for this particular node the subtrees are going to be this one and this one, and we can see that the height of this particular subtree compared to root is going to be 3 for this node, and then for height of this is going to be 2. So at most we have difference of 2. But if we had one more node like this, then the height of this would have become 4 and this would have become 2, so that would not work. So that is like an example of different binary trees. Now for this tree data structure, we will need to find a way to iterate over all the nodes and then try to find the meaningful information. So there are different tree traversal techniques available to us. We are going to learn all of these in depth. So they are in order, pre-order, post-order, and then an extra one, level order traversal. We are going to use this example. So notice that this one I have taken as a binary search tree as part of the example, but overall it makes no difference on whatever type of tree we are trying to traverse over. So first one is an in order traversal. We follow the technique that first we are going to traverse the left child. So as long as left child exists, we are going to keep on going in that direction. Then we are going to visit the root node, and then we are going to visit the right child of the node. And notice that root comes in between left and child, and that's why it is defined as in order traversal. Position of root is defined as what it is. So notice that currently we are going to be starting our journey at the root node. We have a left child, so we will go to the left child. Once again the left child also has a left child, so we'll go to that left child. And now notice that this does not have any more left child to visit. So now we are going to mark this node or traverse this node. So first node we are going to visit is going to be value number 1. Then we are going to continue our journey in the same fashion, and we are going to go back because this does not have any more subsequent children. Now we are at this position number 2. Once again we will follow the method of left, root, and right, but notice that for this particular 2 we have already visited left node, so now we can visit this node. So then next node would be 2, and it still has a right node that we haven't visited, so we will once again visit node number 3 and mark it visited. Then for this, now notice for 3 it does not have any subsequent children, so we will go back. We already visited 2, so now we will go back again. Now this 4 we haven't visited, but we visited all of its left child, so then we will visit 4. And now after this we will start visiting its right subtree or right child. So then we are going to come at value number 6. 6 also has a left child 5, so we will visit 5 first, and then we will visit 6, and then we will visit 7. So notice that because this was a binary search tree and we did in order traversal, we basically sorted all the values that are present inside the tree. So look how beautiful it looks. Now let's understand the pre-order traversal. Now the positioning of root slightly changes. First we are going to visit the root node, then we will visit its left child, and then we will visit its right child. And so now let's logically start iterating. Now notice that the entry point towards this iteration is going to be through the root node. So first we are going to visit node number 4 over here. After visiting 4, 4 does has left child. So then we will go to the left child. Once again, we are going to follow the same method and we will visit node number 2. Then we will go to left child and we will visit node number 1. Now after visiting this does not have any more children of its own. We will go back. We have already visited 2, but it does has a right child that we haven't visited. So we will visit this. And then once again we will go back. We have already visited this, and now we will repeat the same thing with its right subchild. So first we will visit node number 6, then we will visit node number 5, and then we will visit node number 7, and this is going to be the visited path. Same way we have post order traversal. Now this one is slightly different because first we are going to visit left child, then we are going to visit its right child, and then in the last we are going to visit the root node. So as long as left or right child exists, we will have to visit both of them. So our entry point would be at the starting position 4. It does have a left child or left children and right children, so we will have to visit each one of them. We go to 2. Once again it has left child, so we will have to go and we commit value number 1. 1 does not have any child of its own, so now we will visit 1 as the first node. Then because remember we will go back, but this for this root number 2 we still have a right child that we haven't visited, and remember the order is left, right, and then root. So we'll visit the right child, and then we will visit node number 2 because we have visited all of its entry. Once again we will go back. Now though for this 4 we have visited everything on the left, we haven't visited the right subtree, so we will repeat the same process. We will go down to 6. 6 still has a left child that we haven't visited, so we will go to value number 5 first. After that we will visit value number 7 first, and after that we will visit value number 6, and in the end very last value would be visited, value number 4. So this would be the post order traversal. And last one is a level order traversal. We can also define this as a breadth first search as well approach, because we are going to go down in breadth for any particular node. So once again we are going to start iterating in the root, but now we will iterate level by level from left to right. So first we will visit node number 4, then we would visit its child, so node number 2 and node number 6. Then we will visit all of these values from left to right fashion, so 1, 3, 5 and 7, so on and so forth. This is also another technique that is pretty popular with basically graph related problems, but can also be applied to tree problems as well. Now let's understand that what are the different operations we can do on trees and what is going to be the time complexity. Now the binary search tree is a special case, and the regular trees are a separate case. So we will treat both of them slightly differently, and I would provide time complexity for each of them. In the example I have only shown you binary search tree, but it can be true for regular trees as well. So if you have to search for any particular element in a binary search tree, it is going to be very simple, because we are simply moving away for 50% of all the nodes in one single go. If I have to search for node number 3 at root position, I simply have to check that whether 3 is less than 4 or not. If it is less than 4, then I can only need to check in this portion. I can completely eliminate all of these values. So that is going to be very powerful. So basically for binary search tree, the search operation is going to take on an average log n time, so which is pretty fast, significantly. But for any regular tree where we don't have such structure being maintained, it is going to take big of n time in the worst case scenario. Same way for insertion, it can be typically done in log of n time, because we need to find where we need to add that value, and we can do it quite quickly. Sometimes we will have to adjust the existing nodes, but overall on an average case this will work in log n time. But for regular scenario, now how you are inserting the value is also a concern. If you are just inserting value at any position randomly, we can typically do it in big of 1 time on an average case. But if you need to add it only on the available leaf nodes with some condition, in the worst case scenario this can become big of n time for different tree operations. Same way for deletion, it is going to be log n time, but for this one it is going to be big of n time, because first we'll need to find the value where it exists. So finding will take a lot of time, And traversal will take big of n time no matter what, because we need to iterate over every single node that is currently available. So these are the common operations that you can typically do with different trees, and it has different time and space complexities. So typically trees and graphs fall under the same categorization and both deals with relationships. The only difference is with trees, all the nodes are going to be connected and all the nodes are guaranteed that they won't be forming any particular cycle. So there are no cycles in a tree and all the nodes are basically connected. Graph does not have any such conditions, which means we can have a graph that looks pretty similar to a tree, but we can have some more nodes that are basically not connected with each other, or we can have graph that has all the nodes connected but it can have some cycles as well. So trees does not have any such kind of condition, and typically for trees we are only dealing with parent child relationship, so there is no room for cycles. Now there are two pretty popular type of trees or variations of trees that is real use cases, and they are quite popular with all sorts of popular applications and interview questions. First one is a structure called tries, where we have a parent child relationship, but this is typically working in tandem with strings. And for each of the string, every single character is being treated as if it was a node inside that particular string, and then it has subsequent children of its own. So let's say if I have to talk about a string that looks like ret, that is going to store the value for ret, then I would have a root node that is going to be empty, then it is going to have a subchild that contains value r, and then another subchild, and then another subchild. Now let's say that I want to create another value that is rattle. Then in this case, for this I'm also going to have one more variation where this is going to be pointing towards a null value. This is where it defines that this is one of the variations of the word, and then it is also going to have subsequent words as t, and then l, and then e. And same way you can store bunch of different applications, and then there is going to be a null value over here to point that this is also a full word on its own. Now you can imagine that there are thousands of applications or companies that are currently using this principle to generate something called autocorrect, where based on your current input we can autocorrect or auto suggest that whatever you are trying to type, and then automatically adjust those values. You can think of applications and all sorts of mobile and web and iMessages and WhatsApp, they all use the same principle. So you can imagine how popular this technique is. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do maximum depth of binary tree lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like LinkedIn, Amazon, Microsoft, Google, Facebook, Apple, Bloomberg, and Uber. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode easy problem and also very well liked problem on LeetCode. If we understand the problem statement, basically we are given the root of a binary tree and we need to return its maximum depth. Now we are also given the definition of what a maximum depth is. It is basically the number of nodes along the longest path from the root node down towards the farthest leaf node. That is the depth of the tree. And if we try to understand this with an example, suppose we are given a tree over here that looks like this. In this case, the maximum depth is going to be 3. Why? Because the nodes at the root level is currently at position 1 or height 1. The root at this level is at depth 2 or height 2, and root at this level is actually at depth 3. So in this case we need to return 3 as the answer, because 3 is the maximum depth we can get from this root node. So let's see that what would be the different approaches to solve this problem. Okay, suppose this is the input we are given and we are trying to find the maximum depth for this particular given tree. Suppose this is the root of the tree. If you want to find the maximum depth for this tree, the answer is going to be 4 because of these two nodes. We can see it clearly over here that over here the value is 1, this is 2, this is 3, and this is 4, and this is the answer we need to return. The question is, before we return this answer, we will actually have to build some intuition behind it. And the intuition is, suppose at this position number 5, if we want to determine that what is the maximum depth over here, well, what we can do is we will check on the left side, we will check on the right side, and whatever has the greater number of nodes on either side, we will actually take that as maximum depth and we will do it +1. Well, in this case, the 6 and 7 both are located at the same position. 6 and 7, none of them has any children, which means that over here we can determine that this is actually 1 and this is also 1. So on the left side and on the right side, both values are actually 1. So what we can do is we can do 1 plus 1. So 1 plus 1 will give us the answer that the maximum depth at position number 5 is going to be 2. So in this case, okay, we have found the maximum depth over here to be 2. Well, if we take this value number 4, well, at this value number 4, it does not have any more children. If it does not have any more children, which means we can determine the maximum depth in this case is going to be 1. Well, now we have these two values. That now based on these two values, it becomes pretty easy for us to identify that what is the maximum depth at this position number 2. All we will have to do is we will take whatever the maximum value amongst these two is. Maximum value is actually 2. So what we can do is we can do 2 plus 1, and 2 plus 1 is actually going to be 3. So we can determine that 3 is going to be the maximum depth we can achieve at this node number 2 if this was to be the root of the given tree. And for this position number 3, the maximum depth we can achieve is only 1 because it does not have any more children. So that is a given fact. Now we have these two information. Now it becomes pretty easy for us to identify that what is going to be the maximum depth at this position number 1. And all we will have to do is take the maximum amongst these two values. So maximum value is going to be 3, and all we need to do is just plus 1. So if we do 3 plus 1, we will get the answer 4, and 4 would be the correct answer in this case, and that is what we are going to return. So the maximum depth we need to find, we can simply do it by using this method. Well, now if you see, for this particular solution, we are actually able to achieve this solution, but what we are doing is that at any given position, we are seeing that what is the left max value or right max value, and whichever is greater amongst either one of them, we are taking that and we are adding 1. Well, now again, we are repeating the same process, that we are taking the left max and right max value, and again we are adding 1. So which means that in order to solve a bigger problem, we are actually solving a smaller problem and then again a smaller problem. So basically we are doing it recursively, and that is how we are going to solve this problem using recursion, which is very powerful and it is highly used in different kinds of tree problems. So that is how we are going to solve this problem, and this would be the optimal solution we can use. If we see the time and space complexity, in this case the time complexity is actually going to be big O of n, because we will have to iterate over every single element in order to get the answer. And if we see the space complexity, in this case the space complexity is also going to be big O of n, because we might have to store all the values inside our recursive function. And this approach is actually very good. It works as expected. There is also one more approach which uses stacks, and that does not use recursion. It actually use iterative function. So let me know in the comments if you want to see the stack solution as well, and I can also explain that. But for now, if you show this recursive solution in any interview, the interviewer would be more than happy. So let's move on to coding now. So first of all, we are going to take care of a edge case. If that is not the case, we will have to call our recursive function. First of all, we are going to have an integer called left max that is going to take care of the left subtree for any given root position, and we are going to call our recursive function again. And same we are going to do for the right subtree as well. We are going to create a parameter called right max. And in either case, all we have to do is simply return whatever the maximum value we are able to find, and then we will add 1 to it. And this should be it. Once we get out of the loop, our solution would be done. So let's try to run this code. Okay, seems like our solution is working. Let's submit this code. And our code runs as expected, and it's actually pretty fast compared to a lot of other solutions. So I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do same tree lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like LinkedIn, Amazon, Google, Bloomberg, Apple, Microsoft, Facebook and Uber. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode easy problem, and as the name suggests, same tree, the problem is self-explanatory, but let's go over it. That basically we are given two roots of a binary tree called P and Q, and we have to write a function to check if they both are same or not. So let's try to understand this with a couple of examples that are given over here. Here we are given this two trees P and Q, and in this case we can see that both of these are 1, both of these are 2, and both of these are 3. So we can say that okay, they are actually same, and we can return true in this case. But for the second example, if we see the P and Q values over here, for 1 is same, so root values are same. But if we see over here, this is actually 2 and this is actually 2. Despite being the same value, the positioning is not same, because this is actually the left child of this given P tree, and this is actually the right child of this given Q tree, which means that these two are not same. So in this case, we will return the false, and this is what we have to achieve. So let's see that what would be the different approaches to solve this problem. So solution of this problem is actually quite simple, and if we see the approach one, we are going to use an iterative approach. In the iterative approach, what we are going to do is we are going to iterative over both of these given trees in the same manner, and we are going to keep on checking subsequent nodes of every single position. At any given moment, if we identify that any single node does not match, we can return false immediately, and if somehow we can reach out to the end of the tree and iterate over every single nodes, we can return true in this case. So let's see that in action. So first of all, we are at this for this P and Q tree. Currently we are at this root position, so we will check that value, and both of them are actually 1, which means we are good so far. Now we are going to iterate over on the left side. So on the left side, this value is actually 2 and this value is also 2, so again we are good. Now again on the left side, this value is actually 3 and this value is also 3, so again we are good so far. Now we go back, and now for this position number, we also have a right subtree, or so we will check that right position. This is 5 and this also has a right position, which is also 5. So far we are good. Now again we go back to this root node. We still have this right side that we haven't traversed, so this node is 4 and this node is also 4, so again we are good. And at the end, this node is 6 and this node is 6. Now we don't have any more nodes to go back to, so essentially we have traversed over all the nodes inside given both the trees, so we can return true in this case. And this is the approach we are going to take. Let's see what would happen in a scenario where trees don't match up. So here I have drawn that example as well, that over here all of these nodes are same, but actually this node and this node, these two are not same. So because these two are not same, the moment we iterate over all of these nodes and eventually we would reach to these positions, we can return false immediately in this case. So this approach would work as expected. And if we see the time and space complexity in this case, the time complexity is actually going to be big O of n. Why big O of n? Because we will have to iterate over every single node inside the given tree for both P and Q trees. And the space complexity would be big O of log n. That is because this is a binary tree. Well, in the second approach, we are actually going to solve this problem recursively. And the idea is at any given moment, we have to identify that whether given two trees are same or not. The thing we are going to do is we are going to compare their root nodes. If they both are same, we will have to compare their entire left subtrees, that they have to be the same, and also we will have to compare their entire right subtrees, that as they also have to be the same. And if that is the case, we can define that tree to be the same. But if we take a look at for the left subtree, again we are going to repeat the same process, that even for the left subtree we are going to compare the root nodes. If they both are same, then we are going to compare their left subtrees and their right subtrees to be the same. So essentially we are doing the same thing repeatedly for different kinds of input, and recursion is the best way to approach that. And also your interviewer is going to expect you to do this recursively, because that would be more efficient way of doing it. So let's see that in action. So the idea is at any given moment we are going to compare the root node. So over here root node is same. Because root node is same, we will have to check that whether the left subtree is same and right subtree is same or not. So first we will do the left subtree. So now for the left subtree, we have these two trees for P and Q respectively. So again we will check the left node. So left node is this 2 and this is also 2, so they both are same. Now we are going to check the left subtree and right subtree again. So this both of these are 3, so we are good. Now we will have to check the right subtree. So right subtree is also 5 and 5, so again we are good. Now again, so far we have calculated the entire left portion, but we haven't calculated the right portion. So now we will do that. So again for the right subtree, this value is 4 and this value is 4, so again they both both are equal, so we are good so far. And then these values are 6 and 6, so again we are good so far. Now we have iterated over every single node recursively, that is the important part, and we have found all the values to be the same. So because they were same, we can return true in this case, and everything is good. And at any given moment, suppose we identify that any single node does not contain the same value as its counterpart, then the moment we are comparing these two values, we can return false immediately, and that would be the solution for this problem. If we see the time and space complexity, in this case the time complexity is also going to be big O of n, because we will have to iterate over every single value, and the space complexity is going to be big O of log n. So the time and space complexity is not different than the iterative approach, but recursive approach just is a lot less coding, and I will also be showing that in the code. So first of all, we are going to check that if the given P and Q both are null. If both are null, we will have to return true, because essentially they both are same. If that is not the case, and if any of either P or Q is null and the other one is not null, then in that case we will have to return false. And if both values exist, then we will have to compare their values. And if both values are not same, we can return false immediately. If that is not the case, we will have to iterate over left and right subtrees of a subsequent P and Q trees. So now we are going to make our recursive call. And that's pretty much it. Let's try to run this code. Okay, seems like our code is working as expected. Let's submit this code. And our solution runs pretty efficiently. It's actually 100% faster, but if that is not the case, because runtime is 0 millisecond, that's why it's showing 100% faster. I would be posting this in the comments, so you can check it out from there. Hello friends, hope you are having a fantastic day today. So now we are going to do a very popular LeetCode problem. So without any delays, let's get started. So the LeetCode problem we are going to solve is called Symmetric Tree, and we can see that this is a LeetCode easy problem and also a very well-liked problem on LeetCode. The problem statement is very straightforward. We are given the root of a binary tree, and we need to check that whether this binary tree is a mirror of itself or not, which we can see it from the example. Where notice that ignoring this root node, if we compare the subtrees of this root node, we can see that they are exact mirror copies of each other, which means this left node is same as this right node. Once again, this left node is same as this right node, and once again, this right node is same as this left node, which means we need to check that for any single given tree, whether this symmetric property is true or not. And this is actually very simple to do. So we are just going to do what we just used to explain this problem. If we understand we are given the root, then since this is a binary tree, it can either have a left node and right node, and once again this left node can also have a left node and right node, and same goes with the subsequent trees, and there can be many layers, as many layers as we want. The only condition we are checking is that for any single root value, we can only say that the tree is symmetrical if its entire left subtree is also symmetrical with entire its right subtree. And in that case, we need to check that whether the left child is the same as right child. And once again, even at this subchild level, we need to check for the grandchildren. So once again, even at this level, we need to check that whether this left tree is same as this right child, and also this right child is same as this left child. If that is the case, then we can determine that this is a symmetric tree, and we can keep on repeating or going down as many levels as we want, but the core logic remains the same, which means number one, we are doing two things. Number one, we are taking a bigger problem and we are actually breaking down into sub problems, and we are keep on repeating the same process for all of its children. So we are going to be using recursion to solve this problem. That is number one thing. Now number two thing is that we know in the recursion we need two items. Number one thing is that what is going to be the base case. So base case is quite simple. If any particular child does not have any more children, or if there does not exist any left or right node to check, then we can get out of the loop. And if we do get out of the loop and everything remains the same, which means we can return that this is a symmetric tree. That is option number one. Option number two is that at every given moment, we need to have a recursive function based on which we are going to be making our recursive call. And what is going to be the recursive function in this case? That at every single root node, we need to check that whether the left child of root is same as the right child of root or not. And we are going to be keep on repeating the same process. Once again, at the root node, we are going to check that whether the left grandchild of the root is going to be the same as the right grandchild of the root or not. So this is going to be our base case, that the left child is equal to right child and right child is equal to left child. This condition has to be satisfied, and then only we can keep on repeating the same process in the recursive manner. And basically that's it. So just the way I explained that, let's understand this with some example. So suppose we are given a value like 5, and then we are given subsequent values 3 and 3, and once again we are given further subsequent values. Let's assume like 4, 5, and then this is also 4, 5. So is this a symmetric tree? Yes, this is a symmetric tree because both of these values are same. This is also equal to this one, and this is also equal to this one, which means in this case we can return true. If we are given some other value, let's assume that over here we are given one extra child like 6, then we cannot complete the recursive call because this right subchild still also has a left subchild, but that is not present over here. So we can say that this is not symmetric. But in this case, if we did had another child like this, then we could have said that this is also symmetric. So this is the logic that we are going to apply. Now let's see the coded solution for this one. So first, this is the definition of our tree node, where every single node has a value. It has a left child and it has a right child. Now let's see our solution. So for our isSymmetric method, we need to return true or false or boolean value, and in the input we are given the root of the given existing tree node. Now first we are going to check for the edge case, that if the given root is equal to null, we can simply return true. If that is not the case, we are actually going to call our recursive method that is called isMirror, where we are going to pass in the left child and right child of our root node. Now let's see the recursive method isMirror. So as an input, we are having two tree nodes. So first condition we are checking is that if the given left is equal to null and right is equal to null, so both of these entries are null. If that is the case, we can simply return true, that saying that the tree is symmetric. If that is not the case, we are also going to check that if only one of them is null and the other one is not. If that is the case, then the symmetry has been broken down, so we can directly return false. If none of these cases are true, which means we still have to perform our iteration. So first we are going to check that if the given left dot value and the right dot value, so value of this left node and the right tree node, if both are same, then we are going to recursively call this isMirror method. For this isMirror method, we are going to take the left child of this left tree and we are going to compare it with the right child of this right tree. And same way, in the next iteration, we are going to compare the right child of this left tree with the left child of this right tree. So I know that this portion might look confusing, but if you just try to understand this using the image, things will become much more simpler. And I forgot to mention one thing during the code, that this code actually runs in big O of n time, because we are simply iterating over every single node just one time, nothing more than that. And in terms of space complexity, this is also going to be big O of n, because in order to fulfill this recursive stack, we might have to use big O of n space. Okay, so let's try to run this code. Okay, our solution seems to be working as expected. Let's submit this code. And our code runs 100% faster than all the other solutions, which is awesome and pretty good. So once again, I would be posting this solution in the GitHub repository where we have, which contains all of the LeetCode problems that we have solved so far. Also, I wanted to show you one more thing that might be helpful for your preparation. That is this Google document that I have created, which contains information about some of the popular courses that I have created. But this is the most important part. This is the collection of 130 most popular, most asked and most promising questions that has been asked at interviews. I have broken down these questions based on different topics. And also I have provided the information that how many times these questions were asked at specific companies. So this is going to be really helpful if you are targeting any specific companies, or if you are just targeting different topics, or depending on the different difficulty level. So if you want, you can start leveraging this, and I would be posting the link of this document inside the description of this video, so you can easily check it out from there. Thank you. Hello friends, we are not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to invert a binary tree lead code problem, and if we see some of the companies where I want to work at who have already asked this question, there are companies like Amazon, Facebook, Google, Apple, Bloomberg, Microsoft, Uber, Goldman Sachs and LinkedIn. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is the LeetCode easy problem and also very well liked problem on LeetCode. Basically we are given the root of a binary tree and we need to invert the tree and return its root back. So let's try to understand this with a couple of examples. First of all, we'll take this example. So over here we are given a tree that looks like this, where this 2, 1 and 3 are part of the tree, where 1 is the left child and 3 is the right child. So if we invert this tree, we will get an answer that looks like this, where 2 remains the root because it is the root node, but this 3 that was originally the right child will become the left child, and this 1 that was originally the left child will become right child, and this is what we need to return. Let's take a little bit more complicated example. So over here we are given the root to be 4. Now we are given that the left child and right child of this 4 is actually 2 and 7, and further down we are given more left child and right child for this 2 and 7 as well. Now if we invert those all of them, we will actually get a result that looks like this, where 4 remains the common, this 7 that was originally the right child will become the left child, and this 2 that was originally the left child will become right child, and same thing will happen for these leaf nodes as well, and this is the answer we need to return in the answer. This is what the problem is asking us to do. Let's see that what would be the different approaches to solve this problem. Before we come up with the optimal solution, let's understand a very important concept. Suppose this is one of the kind of a binary tree we are given and we need to invert this tree. Well, if we see over here, we are given a root node, then again we are given some left child and we are given a right child. Now further down for this left child and right child, they also have the children of their own and they also form a bigger binary tree. So at any given moment, suppose we are given this root node, we are given this left child and we are given this right child. So if we want to invert this tree, all we have to do is whatever this right child is and whatever this left child is, if we just swap them or if we invert them, basically we are at least done with this root level and with this left child and right child level. Now again, if we further break down that, suppose this is the left child, now we are treating this left child as a root. So suppose now this is the root and this is the left child and this is the right child for this root. So again, if we want to invert them, what we can do is we can take whatever the left subtree and right subtree is. So in this case, for this root, the left subtree is going to be this, the right subtree is going to be this. If we swap them, essentially we have taken care of up until this level for this inverting part, and same way we can keep on repeating the process. So now this becomes our root. Again, we flip these two values, and even for this level we have taken care of inverting the binary tree. So this is what exactly I'm suggesting us to do in order to solve this problem, that we starts breaking this given input into bunch of smaller inputs and start inverting binary tree in that manner. So the idea is that for every single time we will have a root node, we will swap its left and right child, then again for if there exists any left or right child, we will repeat the same process and keep on swapping those values, which means that we are actually doing the changes recursively. We can actually solve this problem pretty efficiently. Let me quickly show you how. Suppose this is the input we are given and we are trying to invert this binary tree recursively. So what we are going to do is, suppose we will take initially this as the root node, and for this root node we actually have a left child and we actually have a right child. So what we are going to do is we are going to swap its values, and we are going to swap the entire left subtree and entire right subtree. Then at any given moment, as long as we have some nodes, we are going to keep on treating them as different root nodes, and then we will keep on flipping their values or their children's values, and at the end we should have a completely inverted binary tree. So let's see that in action. So first of all, this is the root node and this is the left and right subtree. So what we are going to do is we are going to swap the values. So we will have a tree that looks like this. Okay, so far treating this as root tree, we have actually swapped these left subtree and right subtree, and we will get a tree that looks like this, where you can see that this value 3 and 2, they are actually inverted, but their subsequent children values, they are not inverted, and we will still have to repeat the same process. So let's see that in action. So now again, what we are going to do is we are going to treat this 3 to be root child, and we are going to repeat the same process with the 6 and 7. So if we invert them, we will get a tree that looks like this. Now we are going to treat this 7 to be the root node. If we treat this 7 to be the root node, actually it does not have any children, which means we don't need to flip any more values. Now again we will treat this 6 to be the root node. If we treat this 6 to be the root node, again it does not have any more children, so we can skip that. Now we will treat this 2 to be the root node. So if we treat this 2 to be the root node, it has children, so we will have to swap their values and we will get a value that looks like this, and we would have taken care of both of them. Now again this 5 and 4 does not have any children, which means we can't do anything about it, and then in the end this is going to be the answer we need to return. So we can simply return the root value, and basically we would have inverted the entire tree recursively. So that is the approach we can use as an optimal solution. There is also one more way to iteratively approach this problem, but the thing is, I believe that for tree kind of problems the recursive approach is better than the iterative approach. Let me know in the comments if you want to see the iterative approach as well, and I can make a separate video on that. If we see the time and space complexity, in this case the time complexity is actually going to be big O of n, where n is the number of nodes that are present inside any given tree, because we will have to iterate over every single tree to invert them. Now if we see the space complexity, well, at any given moment, because of the recursive function, we might have to store bunch of different node values, and that would depend on the height of the tree. So basically the space complexity is going to be big O of h, where h is the given height of any binary tree. So because we are going to solve this problem recursively, first let's create the terminating condition, that if the given root is actually null, we can return. If the given root is not null, we are going to make the recursive call for right and left values. So for right tree, we are going to make the recursive call to the same function with the right child. Same thing we are going to do for the left subtree. After that, we are going to replace the values of left and right subtree. So now that should have taken care of all the cases, and now we can simply return the root value. And that should be it. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our solution is actually pretty efficient. It's actually 100% faster than all the other solution, and that is because the runtime is actually 0 millisecond. I would be posting this in the comments, so you can check it out from there. Thank you. So the LeetCode problem we are going to solve is called balanced binary tree. Now we can see that this one is a LeetCode easy problem and also one of the most liked problems on LeetCode. The problem statement is quite straightforward, that we are given a binary tree and we need to determine that whether it's a height balanced binary tree or not. So the question is, what does height balanced tree means? It's actually quite straightforward. Height balanced tree means that at any given moment, the height of left subtree and the height of right subtree, if they do not difference more than 1, so which means that there is the maximum difference of heights is like 1 or 0. If that is the case, then we can say that this one is a height balanced binary tree, okay, or balanced binary tree. But if we identify, so let's try to understand. In this case, currently this one is our root node. Now if we see the left subtree, we can see that the height of this left subtree is 2. For the right subtree, the height of this right subtree is 3, which means the difference between left and right subtree is no less than or equal to 1, which means this one is a balanced tree or like height balanced tree. But in the same scenario, let's imagine that if we had one more nodes like this, then the height of this right side binary tree is going to be 4. Meanwhile, this left subtree is still going to 2. So if we do the difference of the height, we get the answer as 2, which is definitely greater than 1. In this case, we can say that now this binary tree is not a not a height balanced binary tree. Okay, so this is what we need to determine. Now this is like a very straightforward problem. Basically, at any given moment, we need to check that for any given node, what is the height for both left and right subtree, and this we can calculate very easily by simply traversing over the given tree in like any BFS or DFS fashion. And once we do the traversal at any given moment, we will have to keep track that for any particular root node, what is the height of its left subtree, what is the height of its right subtree. And if the moment we identify that the difference is actually greater than 1, then we can clearly say that this is not a balanced tree. If we identify that we iterate over the entire tree and we did not find that the height to be greater than 1 at any given moment between left height and right height, then in that case we can say that this one is a balanced tree. So that's it. This is all what we need to do. The approach is quite straightforward, and the idea we are going to use is that we need to traverse over the given binary tree. So for traversal, we know that there are iterative methods and recursive methods. Let's try to do it recursively. So recursively, we are simply going to iterate over the given tree. We need two items for the recursive case. First recursive condition is the base case. So base case is going to be that if the given current node is equal to null or 0, then we have basically exhausted every single child that we can visit for that particular tree. So we can do that. What is going to be the recurrence call that we need to make for the recursive level, that we are going to check that for any particular root node, first we are going to traverse its left child and then we are going to traverse its right child. So that is also good. Now while traveling, the moment we enter a new height or a new left child or a new right child, we are going to have a counter that is going to keep track of the left height, and we are also going to have a counter that is going to keep track of the right height. We are going to update it sequentially with every single level that we are increasing, and during every single update we are simply going to check that if the difference between left height minus right height, and we are going to do an absolute difference. So we don't care about which one is greater, as long as the delta is greater than 1. The moment we find this one, we can say that this one is an invalid or not a proper height balance binary tree. And if we reach to the end, we can say that this one is a height balance binary tree, and we can return this answer very easily and very simply. So the approach is quite straightforward. If we see time and space complexity, in this case the time complexity is simply going to be big O of n, where n is the number of nodes that are present. For the space complexity, because we are using recursion, we will have to induce or create a new recursive stack, so that might increase the time complexity to big O of n. And if you try to do this recursively, you can also do this in big O of 1 space complexity as well. But I don't think like any interviewer is going to have any issue of you using recursion, because that is a great way to save some time. And now let's quickly see the coding solution for this one. So if we see the solution, it's quite straightforward. We need to return a Boolean answer that whether the given tree is balanced or not, and in the input we are given the root. Now first we check for our base case that if the given root is equal to null, we can simply return true. If that is not the case, we are going to calculate the left height and we are going to calculate the right height. For that, we are going to use a helper method called getHeight, and we are going to pass in the root value. Now inside the getHeight method, we are also going to check recursively that whether if the given node is equal to null, we can return 0. If that is not the case, we are once again going to recursively call the same method for the left child and for the right child, and at every given instance we are simply going to calculate the maximum height we have been able to find both for left height and right height, and we are going to add +1. So this is going to give us the height at any given left subtree and right subtree that we are going to fetch values over here. Then we are simply going to have our math.absolute formula that if the difference is greater than 1, then we can simply return false. If that is not the case, then we simply need to say that yeah, if this given tree is balanced. So that's it. This is the whole solution. We can simply run the code, and then I think it should be working fine. Okay, seems like our solution is working okay. Let's submit this code. And our code runs 100% faster because there are very few test cases. So this is pretty awesome. Now, once again, this whole solution is actually posted on our GitHub repository that you can find over here. Now, this GitHub repository contains hundreds of very popular every single LeetCode problem that you can imagine, and for each and every problem I have also provided that what is the LeetCode problem statement for that particular problem, what is the Java solution, and for some reason if you cannot understand the solution on your own, you can actually go to the video solution as well. I have provided the link. So this is a great resource for anyone trying to prepare for LeetCode or DSA problems. The other thing is, I also want to show you one more resource that I have created, or not the LeetCode one, but the document that I have been able to curating. Now this document contains two very important lists. First list is the most popular and liked technical interview questions of all time. Now over here I have created a list of 130 questions. For each of these 130 questions, I have divided them based on the topic that you need to prepare. And I have also provided the key important information that how many times that particular question has been asked at what type of company. So this will help you in a couple of ways. Number one, you would be able to understand if you're targeting any specific company, you can find that how many times that question has been asked at that company. Number two, based on just looking at the question, you can understand that how important that question in general is. So some questions have been asked like literally hundreds of times by many top tier companies. So you should be able to identify that as well. And each of the topics are distributed based on like easy, medium and hard LeetCode problems. So that is one option. Second one is the LeetCode 150 list that I'm currently working upon. So this is like the 150 most asked questions list created by LeetCode. That is an addition to blind 75. Now this is also a very pretty and very important list. Once again, all the questions are based differentiated based on topics. We can also see that for most of the questions, I'm trying to go through them and generate solutions for them as well. So yeah, if you want, you can also check out this resource. Maybe it can be helpful with your prep journey. Okay. Hello friends, we are not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do binary tree level order traversal LeetCode problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like LinkedIn, Amazon, Microsoft, Facebook, Bloomberg, Google, Apple and Uber. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given the root of a binary tree. Now we need to return the level order traversal for this binary tree, and we need to return the nodes values. Now we are also told that we need to return them in left to right fashion and level by level. Basically we are given a binary tree over here. Now for any binary tree, basically we always have two things. We have a root node or a parent node, and that parent node has some children nodes. So, and furthermore, this children node can have children of their own as well. So every time a new set of nodes are being added at the bottom, essentially we can define a new level being created. So if we see this example over here, essentially this is level 1, this is level 2 and this is level 3. And we need to return the nodes level wise from left to right. So let's try to understand this with this example over here, where we are given 3 levels. So this is level 1. These two nodes, they are located at level 2, and this two nodes, they are located at level number 3. So in the answer, first of all, we are going to return this node 3 because this is the only node at this level. There are no other nodes. Now at the second level, we have two nodes 9 and 20, and we need to return them in the same sequence of 9 and 20. And in the third section, we have two nodes 15 and 7. First we'll return 15 and then we'll return 7, and that is the answer we are going to return in this case. Let's see that what would be different approaches to solve this problem. So when it comes to tree traversals, there are mainly two subcategories. First one is a depth first search and second one is a breadth first search. Well, in the depth first search, we actually expand upon the depth of any given tree and then we keep on iterating over all the nodes. While in the breadth first search, we actually visit the root node first and then visit its children and then keep on repeating the same process. So in this portion, for depth first search, there are three further subcategories: Inorder, Preorder and Postorder, which I'm going to show you first, and then I'll explain you how breadth first search work. And in this problem, actually we are going to use breadth first search to solve this problem. So during the in-order traversal, basically first we visit the left side of the tree, then we visit the root node, and then we visit the right node. So first of all, for this root node, we will keep on expanding until the left node exists. So left node exists over here and then left node again exists over here, which means this is the first node we are going to visit. So we start our visit traversal at 4. Now 4 does not have any more children, which means we can't go downwards anymore, which means now we go back to the root node. So root node for this 4 is actually 2, and then we again expand on the right side. For this 2, we still have right side 5 that we haven't visited, so we will do that. Now again we have visited all these 3 nodes, so now we are done with these. Now we again go back to the root node, which is 1, so we visit 1, and then again we repeat the same process, left, root and right. So again we go on the right side. So this is the strategy for in order traversal. Now for the pre-order traversal, basically we follow the principle of root, left and right node, and this is the way we visit the node. So first of all, we are going to visit the root node, which is 1 in this case. Then again we are going to visit the left node, which is 2. Then again we are going to visit the left node, which is 4. Then again we are going to visit the right node, which is 5. Again we come back, and now in this case we again go back to this root node, which is 3. Then again we go to the left, and then again we go to the right. So this is the strategy for using a pre-order traversal. Now for the post order traversal, basically we follow the principle of left node, right node, and then root node. So first of all, we are going to visit up until left node exists. So this is the leftmost node. So we are going to visit that first. So we start our traversal at this position number 4. Then we visit the right node, which is 5, and then we visit the root node, which is 2 in this case. Now after this, we actually don't visit this node 1, because for this node 1 there exists a right subtree that we haven't visited. So we again go to the right side, and again this also has a left node, which is 6. So then we visit the node 6 in this case. Then we visit the node 7, and then after visiting the 6 and 7, then we visit its root node, which is 3, and in the end, after visiting all the nodes, we visit the main root node, which is 1. And this is going to be the traversal strategy for the post order traversal. So when it comes to breadth first search, we actually expand upon its neighbors or its children for any given tree, rather than going in depth in any one particular direction. So if we see for this particular tree, the breadth first search traversal is going to look like this. So first of all, we are going to visit the root node, which is 1 in this case. Then we are going to visit its children. So its children are actually 2 and 3. So we are going to visit this node 2 and 3. Now for this left child, again it still has children of its own, so we are going to visit them first. So we are going to visit this node 4 and 5, and then for this node 3, it has children of its own as well, which is 6 and 7. Now in this case, we cannot further expand because this 4, 5, 6 and 7 does not have any children of their own. So we are done with the traversal. Basically we have iterated over all the nodes that were given. But if you see these nodes and the fashion we have visited them, it actually gives a very interesting perspective for the problem we are trying to solve. Well, first of all, we are visiting the node that is located at this position number 1. Then we visited its children, which are actually located at this level 2. So first we visited the level 1 node, then we visited all the nodes that are present at level 2, and then we visited all the nodes that were present at level 3. If we had any further nodes, then we would have visited them that were for the nodes that were located at this level number 4. So this breadth first search is actually a very good solution for the problem we are trying to solve, where we are trying to see that what would be the level order traversal for any given tree. Basically we are anyways iterating the nodes in particular levels. So all we will have to do is just simply make tuples of the levels that we are visiting and the nodes we are visiting at. So that is how we are going to optimally solve this problem. Now we are going to use the same tree that we have been using so far, and we are going to see that what would be the answer. So first of all, we will have to create an array list where we are going to store the answer. Now at any given position, whenever we start iterating over this tree and whenever we jump to a new level, we are going to create a new node inside our array list. So first of all, we are at this level 1, right? So now for this level 1, we are going to create a new node over here, which is this one. And for this level, because this node is located at level 1, we are actually going to create an entry over here. Now for this one, we are actually going to iterate over its children. We are going to call its children 2 and 3. Now because these are children of this node 1, they are actually going to be located at level which is whatever the level of this 1 is plus 1. So the level of this 1 is actually 1. So 1 plus 1 is going to be 2. So these nodes, they are actually going to be located at level 2. Now the moment we identified a new level, we are actually going to create a new node inside our array list. So over here we would have created this new node. Now in this new node, because we visited these values 2 and 3, we are going to actually add the value 2 and 3 over here. Now again we will have to further go down for this level 2 and 3. And remember that initially we only had this one node and we visited its children. Now again we have a node and we are visiting its children, and again we have a node and we are visiting its children. And suppose these had, if the new nodes, we would have visited their children as well. So basically we are doing the same work for different set of inputs, where initially this was a child, but now this becomes a parent for these nodes. So we are basically doing recursion, nothing special in this. So now from this level 2, whenever we will call these left and right children, basically what we would have done is we would have increased whatever the value of level was for this value 2 plus 1. So this was located at level 2, which means these nodes, they are actually located at level 3. So now again we created a new level. So because we created a new level, we are going to create a new entry inside our array list, and then all the values located at this level, we are actually going to store them in this portion of our array list. So now first of all we are going to visit node 4. So we are going to add node 4 over here. Then from this 2 we are going to visit its right children, which is this node 5. So we are going to add 5 over here. Now we still have nodes that we haven't visited. So now we have this node 3. So we are going to first of all visit its left children, which is this node 6, and this is also located at level 3 because this 3 originally was located at level 2. So this is also because this is at level 3, we are adding it in the third portion or third placeholder inside our array list, and then in the end we are going to visit this node number 7 as well at the end. Now this does not have any further children, so we are good up until this point, and we can stop our traversal and return this new array list that we have created as the answer. So this is the approach we are suggesting. And if we see, we did the breadth first search traversal, and basically we did it recursively. Now we could have done it iteratively as well, nothing special in there. So you can discuss with your interviewer what is the strategy you want to use, and 9 out of 10 times your interviewer is going to ask you to do this problem recursively because it's lot less code. If we see time and space complexity, in this case the time complexity is actually going to be big O of n, where n is the number of nodes that are present inside this given node. And if we see space complexity, well, basically we will have to create recursive, we will have to make recursive calls, and that takes some space, and that space is actually dependent on height of the given tree. So space complexity is actually going to be big O of h, where h is the height of the tree. Now first of all we are actually going to create a list of lists where we are going to store the answer, and we are going to declare it as a global variable because we are going to create a new method for our recursive call. So first of all, let me create this global variable called answer. Now we are going to create a new public method which is going to be acting as our recursive function, and it does not return anything. We are going to name it as order, and as an argument it is going to take any tree node and the level we are currently at. And now inside this method, first of all, what we are going to do is that whenever we are at any position or whenever we are creating a new node, basically we are going to add a new entry to our answer. After creating a new value for a new level, now all we will have to do is whatever this tree node is, based on its level value, we will have to add that value to our answer. Now after doing that, basically all we will have to do is for any single given node value, first of all we are going to check that whether it's left child and right child, if they exist or not. If they exist, basically we are going to call the same order method with this left child and right child, and we are going to increase the value of the levels. That is all we need to do for this order method. So now from this main method, first of all we are going to check for an edge case that if this given root is null. If this is null, we can simply return the answer. And if this given root is not null, basically we will have to call this order method with our root information and the current level that we are at. And now at the end, we simply have to return whatever the answer we get. Let's try to run this code. It seems like our solution is working as expected. Let's submit this code. And our code is actually pretty efficient compared to a lot of other solutions. And I would be posting this in the comments so you can check it out from there. Thank you. LeetCode problem we are going to explain is going to be binary tree zigzag level order traversal. This is a really popular problem, and this has been asked in some of the top tier companies such as Amazon, Bloomberg, Microsoft, Facebook, Apple, LinkedIn, Google, Samsung, Goldman Sachs, and TikTok. So that is why I'm paying my utmost attention. I highly urge you to pay your attention for this problem as well. If we see that this is a LeetCode medium problem and also very well like problem. Now in this problem, we are given the root of a binary tree, which means a binary tree means that any single parent can have at most 2 children, nothing more than that. So now we have the root of this binary tree, and now we need to return the zigzag level order traversal from its nodes values. So what does a zigzag level order traversal means? So first of all, before understanding the zigzag level order traversal, let's understand what does a level order traversal means. Level order traversal simply means that first we go through the first level, that is level 0, then level 1, then level 2. So if we see the level order traversal, first we would it go through value number 3, then second level, so that is value number 9 and 20, and then the third level, that is 15 and 7. But since in this case the level order traversal that we were making was pretty simple, we were going from left to right. So we went from here, we went to left to right, again from here we went from left to right. But in this case we are making our lives easier and we are going in the zigzag fashion, because that is the current trend. And zigzag fashion is that first we start over here from left to right from the root node, then we go in the zigzag fashion. So we go like this, and now again we repeat the zigzag pattern, and now we go from left to right again. So for one level we go from left to right, next level we go from right to left, and again next level we go from left to right, and we keep on repeating the same process. So in this example, if you see, first we went through level 3 left to right, this was the value. Second we went through the right to left, so 20 and 9. So from after 3 we visited 20 and 9, and then we went through 15 and 7. And let's see what would be the solution for this problem. Okay, suppose this is the input we are given. Now first let's see what is the level order traversal going to be. First we are going to visit value number 1, then we are going to visit in this fashion, so the value is going to be 3 and 2, then again from this fashion, so value is going to be 4, 5, 6, and then again from this fashion, so the 8 and 7. This is going to be the answer for sure, we already know that. But how we are going to come up with the answer? In order to come up with the zigzag level, first we need to go through the simple level. How to go through simple level order traversal? Well, for what we are doing in a simple level order traversal is that we are iterating the parent, then we are iterating its child before iterating its grandchild. So in this case, first we are going to we are at this place, we are going to iterate over its child. After iterating both children, we are going to iterate its grandchildren or the children of these children. So first we would be covering this level, then after covering this level we would be going through the children of these nodes, and so going in this fashion, and again repeating the same process with this one. And this can be achieved using breadth first search, because it's pretty simple to do, and this is how how traversal is done in trees using breadth first search. That is a level order traversal. So even in this case we are going to use the breadth first search to run in a simple level. But how do we use breadth first search? Well, from our experience we know that in order to use breadth first search we need two items. We need a queue and we need a visited hash set. But the thing is, we only need visited hash set in a graph kind of a problem where there is an issue of us running in an infinite loop. There is no issue of us running in an infinite loop inside a tree, so we are not concerned about using a graph. In this case we are only going to use a queue. And currently I'm just showing you how to do a level order traversal, and then we will do zigzag level order traversal. So first let's just see the level order traversal. For that we are first of all going to start at the root position, and we are going to populate that value inside our queue. So this is currently value number 1. Now we are going to visit the children of 1 before visiting the grandchildren of 1. This is the whole logic of the BFS, that we are going to visit the children before visiting the grandchildren. So who are the children? Obviously 2 and 3. Again we are going to add values 2 and 3 here because it has 2 children and we are going to mark them. Now we visited all the children of value number 1, so we are going to pop value number 1 out, and we are going to put it in the answer that we traversed this part already, and now we only have values 2 and 3 inside the input. Now again for 2 and 3, 2 has children that we haven't iterated over. So who are the children of 2? 4 and 5. Mark them here, and same way get rid of 2. So 2 has been taken out, and now currently the entries are 3, 4 and 5 inside our queue. 3, 4 and 5. Again 3 can be kicked out by adding 6 at the end of the queue. We added 6 at the end of the queue. Awesome. Now 3 is also out. currently the entries are 4, 5 and 6. Now even for the values 4, 5 and 6, starting at position number 4, it does not have any child, so 4 can be kicked out without any repercussion. 5 currently has a child 7, so adding 7 at the end and getting rid of 5. So we can put 5 over here. Again values are 6 and 7 in place. Again for value number 6, it has a child called 8, adding 8 in the end and getting rid of 6. And now after that there are only two values left, 7 and 8. Currently 7 does not have a child, so we can get 7 out, and also 8 does not have a child, so we can also get 8 out, and this would be the solution. But in this problem what we did is we went in the normal level order traversal, not the zigzag level order traversal. So let's see how can we make zigzag level order traversal possible. Currently what the concept we are using inside the queue is, currently we are using the first in first out principle that gave us the level order traversal. But what happens is that when we move from left to right, this concept is absolutely true, that we can get we can have like first in first out, and that would give us the proper level order traversal. But when it comes to reversing, imagine that in this case, rather than getting 2, since 2 was already inside the loop before value number 3, if we pop 3 out before 2, then we would have been able to accomplish our mission. So since in this case we are going in the zigzag fashion, remember zigzag fashion is going to be like this, where and on one iteration we are moving from left to right, next iteration we are moving from right to left, and again for the next iteration we would move from left to right, and we would keep on repeating in the alternate fashion till we reach to the or to all the nodes inside the given input. So now let's see that what are some of the adjustments we can make to make our lives so much more easier and fix this issue that we were having in the level order traversal. The solution is quite simple, and the solution is that whenever we have to find from left to right, we can use the concept of first in first out. So this first in first out is going to use on these two occasions, but when we need to move in the reverse order or right to left, in this case we will have to use the concept of last in first out, because logically what was happening in this case is that logically we were traversing in last in left to right for every single one of them in the level order traversal. So typically we were going like 2 and 3, but imagine since 3 was last added, if we took the last in first to approach, then inside the solution we would have values such as this one. So 1 is following FIFO, first in first out, so 1 was added first and 1 was removed first. But for this particular position we are using the concept of last in first out. So even though 2 was in the queue before value number 3, we are going to have 3, that was the last value, come out before the value of 2. So 1, 3 and 2, such like this. Again we are going to use first in first out for this particular level, so the solution is going to be 4, 5, 6. That is pretty simple. But for these two, again we are going to use LIFO principle, and that is going to give us the answer of 8 and 7. Now if we see this sequence 1, 3, 2, 4, 5, 6, 8, 7, this matches with the original answer we wrote at the beginning, 1, 3, 2, 4, 5, 6, 8, 7, and this is the whole solution. So let me clean this up a bit, walk you through my solution, where we are simply arranging the way we are entering the values inside the inside the queue and popping the value out of the queue. Okay, so now we are going to have our queue, we are going to add all the entries, and the only simple thing we are going to do is whenever we have to move from right to left, we are going to pop the value at the from the end of the queue rather than popping from the beginning of the queue, because we are flipping between FIFO and LIFO principle. And the one data structure that is capable to do this is actually a DQ data structure in like both Java and Python languages, so you can use either one of them. Okay, so let's start iterating, starting from value number 1. 1 is placed here. Currently 1 has 2 child, 2 and 3, so we are going to mark 2 and 3 in this position, Currently for 1 we are iterating from left to right, so we are going to get the last in first out, so 1 would come out. Now the values are located as 2 and 3. Even for 2 and 3, currently we need to get them out in the zigzag fashion or right to left fashion. So for that, first we are going to pop it from the end, but before popping it from the end, we will first add the children of 2 and 3. So the child of 2 is 4 5, so let's add 4 5 here, and child of 3 is 6. Let's add 6 here. After doing that, we are going to pop 3 out first, and then we are going to pop 2 out first. So 3 and 2 has been out because 3 was value before 2. And again for 4 5 6 we need to do the same thing, but we need to do in the left to right fashion. So 4 5 6 are going to come out as as themselves, but before that we are going to iterate through it their children. So 4 currently does not have a child, so we can pop it out without any repercussion. But 5 has a child, the value is 7, and 6 has a child, the value is 8. Again we pop 5 out, so popping 5 out should be simple, and popping 6 out should be simple as well because we already took care of them. But for value 7 and 8, again we are moving in the right to left direction, so last in value 8 is going to come out first before 7 coming out, and in the end we would not have any values inside our queue, which means we can get rid of it. And now you see the traversal is being done in the level order and also in the zigzag fashion, and that is the most important fact, and this is how you solve this problem. Again, if we try to see the time and space complexity, the time complexity is going to be big O of v plus e, or vertices plus edges or nodes plus edges, because we are using our BFS. And space complexity, since in order to use the BFS we will have to use a queue, the space complexity is going to be big O of v, or the number of nodes or number of vertices inside our given tree. And this is the whole solution. Let's see the coding solution for binary tree zigzag level order traversal. So first of all, for this one, we are given the method that to return a list of list that contains the zigzag level order traversal of the given input tree, and as an input we are given the root node. So first of all, we are going to check for the edge case that if the given root node is null, we can return an empty new array list immediately. If that is not the case, first we are going to initialize the array list. Inside this array list, first for the first node, we are going to add the root node, and we are going to add a null node as well, and we are also going to use a new tree node linked list to iterate over the given input tree. Now we are going to mark the level list because every single level is going to contain a different set of answers, and we are going to use this boolean parameter to keep track that whether we need to traverse from left to right or right to left. So is order left is initially set to true, which means currently at the beginning we are moving from left to right. Now inside the while loop we are going to do our BFS function, where if this given boolean is order left is true, which means we are going to use the last in first out and add all the elements inside the level. If that is not the case, then we are going to use the first in first out and also add all the values that are present on that particular level. After adding all the levels, we are simply going to populate our result list based on the level list we have created, and then we are going to initialize a new level list for the next level, and again we are going to change the ordering from left to right to left for the next level. And after repeating the same process again, even for the next level, the ordering is going to be again left to right. In the end, after this BFS operation doing loop ends, we would have our result linked list populated, and we would be able to return that as the answer. So let's try to run the code. Seems like our solution is working as expected. Let's submit the code. And our code runs pretty efficiently compared to a lot of other solutions. And don't worry, I'm going to post the solution of this code inside my GitHub repository that is open to public, so everyone would be able to see that. So the LeetCode problem we are going to solve is called binary tree right side of view. Now we can see that this one is a LeetCode medium problem and also an extremely well-liked problem on LeetCode. The problem statement is actually quite straightforward. We are given the root of a binary tree. Now we need to imagine that as if we are standing on the right side of the binary tree, and then we need to return the values that we see from the right side, and we need to return the top to bottom values. So let's try to understand this problem. Currently we have a binary tree over here. Now imagine yourself that as if you are standing on the right side of the binary tree. So from the right side of the binary tree, you can see only this portion of this given binary tree, which means currently you are only looking at these 4 nodes, and all of because this node is being blocked because of this one, and these 2 nodes are also being blocked because of this one. Okay. So in this case, what is your right side view or your right side vision of this tree? Well, first we need to return the answer in top to bottom manner. So first we are seeing node number 1. Next we are seeing node number 3. Next we are seeing node number 6. And lastly we are seeing node number 7. And this is what we need to return as part of the answer. Now let's first try to understand that what the answer looks like in each of these 3 different scenarios, so we have a clear understanding on what is being expected from our side. So if we take a look at this first tree, well, the answer is going to include, this is going to be the first node, this is going to be the second node, this node would be blocked, so we would not be able to see it, and then once again this node would also be blocked, so we will include this node. So these are the 3 nodes that we are dealing with. Okay. Next, in this particular scenario, we can see that we need to return the right side view. The thing is, hey, there is no node on the right side of the tree. So well, in that case, we can still see the left side of the node as well. So we are going to include this node, and we are also going to include this node in our answer. Okay. And in the lastly, this scenario is slightly tricky. So of course, this node is going to be part of the answer, but then at this particular level, we will have to include this node. Once again, at this particular level, this one is the right child and this one is the left child, but still, because we are standing on the right side, we need to take the value that is closest to us on that particular level. So once again, this node, and then lastly, on this last level, we don't have any particular nodes, so we are going to use this node. Now in each of these 3 scenarios, we can see one very clear distinction in terms of answer. That is, we are seeing that at any given level, we will have to take one node from that particular level. We are going to select the node that is the last node in that particular level. That is the same case for this one, because this is one level, there is only one node. So this is the last node. Over here we have 2 nodes, but we are only going to consider the last node. Once again, we are only going to consider the last node over here as well. This one, there is no explanation needed. This one is slightly trickier example where we can, okay, so this one we understood why we take it. Amongst these 2 nodes, we are closest to this one, so we are taking it. Amongst these 2 nodes, even though these nodes are close to each other, we are once again closest to the right side node, so we are going to take it as part of the answer. And this one once again is still the last node at that particular level. So we are able to establish that for any particular binary tree, the right side of the view is simply going to be doing the level order traversal and finding that what is the last node at that particular level. So in either case, we simply have to do a level order traversal. Now level order traversal for trees typically refers as breadth first search. So we know how to do breadth first search. It's a very common and popular tree traversal techniques. If you don't know what breadth first search is, let me just quickly explain. We are at the root position. So what we are going to do is, for root position, we are going to put it inside a queue. Now we know the property of a queue, that it is a first in, first out type of scenario. For each level, we are going to iterate over all of the children that it has. And if it has the children, we are going to put them on the queue as well. And once again, repeatedly, we are going to keep on subsequently doing the same thing with their children as well. So logically, we would be iterating over in one particular level by level across the entire tree. And that is called breadth first search. So let's try to see our solution in action. So in this case, let me give values to these particular nodes. And we know that the answer in this case is going to be 1, 3, 6, and 7. But currently, let's say that this is our queue. Now in our queue, we are going to keep track of 2 things. Number 1, that what is going to be the last element at any particular node. And number 2, that for every single level, we will have to keep track of that at what level these particular nodes belong to. Okay, so we can very easily track that, because every time we add a new child, we can just mark it as like a new level that we are adding inside the queue, and apart from that we can simply move forward as it is. So currently the first value is going to be node number 1. For node number 1, because it has children, so we are going to add node number 2 and node number 3 inside our array as well, inside our queue as well. Once again, for both node number 2 and 3, they also have the children of their own. So for node number 2, they have 4 and 5, so we are going to add 4 and 5. For node number 3, they have 6, so we are going to add 6. And lastly, we are going to have value number 7, that is the child of node number 6. So once again, let me just add one more entry over here, 7. So now we can see that I have color coded every single different level based on all the elements for that particular level, and in that particular color coded pattern, we need to find the last element. So this is basically going to be by default last element, so we are going to add this to our answer. Next, we have two values at this particular level, so we are going to pop this element out because we don't care. This is the last element, so once again we are going to add that to our answer. Once again, we have 3 elements over here, we are going to pop each one of out, and the moment we reach to the last element, we are also going to mark it as the answer. And then this is also the last element at this particular level, so once again we are going to mark it as the answer. And that's it. This is the whole solution. Now at first glance it looks complicated, but all we are doing is just doing the breadth first search in a common fashion and trying to find the answer. Now in this case, since we are standing on the right side of the binary tree, we are selecting the last element. But same can be said that if we are given a question where we need to find that what is going to be the left side view, where you are standing on the left side of the binary tree, same logic is going to apply. The only thing is now you are going to be dealing with the first entry that pops up inside of your queue for every single new level, and that is what you need to put it in the answer. So basically these are like two questions in just one question by just changing the direction of where you are standing. If you see time complexity, in this case, this is going to be big O of n. If you see space complexity, this is also going to be big O of n, because we are using an extra queue to keep track of all the elements that we have iterated so far. Overall, this is like a decent time and space complexity, because this you have to go through this in any of your tree programs, unless it's a binary tree and you're trying to search an element. So now let's quickly see the coding solution for this one. Okay, so this is the coding solution. First, we are going to initialize our new array list to store the answer, and we are going to mark it as result. We are also going to check for an edge case that if the given root is equal to null, we can simply return the result. If that is not the case, we are going to initialize our queue, and inside our queue, we are going to populate the very first element, that is going to be the root node. Now we are going to iterate over the tree in the breadth first search manner by stating that while queue is not empty, do this. So first we are going to define that what is the current size of the given queue. Then we are simply going to have a for loop to run over the given queue, where we are going to keep on polling elements at every single position, and we are going to mark the last node of the current level inside the result that we are going to populate. Okay, then we are going to check that for this particular given root value, do we have any left child and do we have any right child? If we do, add the left child and right child to the current queue as well, and this is going to iterate over the entire binary tree in breadth first search manner, and we would have our result array list populated as well. In the end, we can simply return results, and this is the whole solution. So let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions. Few things can be improved in terms of space complexity, but anyways, this is a good enough solution. I would be posting this in the GitHub repository that we have created. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do Subtree of another tree LeetCode problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Microsoft, Google, Facebook, Apple, Bloomberg and Tesla. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode easy problem, and basically we are given the roots of two different binary trees called root and subroot. Now we need to check that whether there exists a subtree of this original root tree where the structure is completely same as whatever the subroot binary tree that we are given. If that is the case, we will return true. If that is not the case, we will return false. So let's try to understand this with an example. Basically, we are given two different binary trees called root and subroot. Now over here, we can see that the structure of the subroot, which contains the root value as 4, left child as 1 and right child as 2, where 1 and 2 does not have any more children of their own. The same structure is also present in this example as well. And because it is a subtree of this original root binary tree, we can return true in this case. So now let's take one more example to make things a little bit more clear. So in this second example, we are also given two different binary trees. Now if we see the structure of the subroot, we have a node 4. It has a left child and right child of 1 and 2 respectively, and they don't have any more children of their own. Now if we see this original root, we can also see a similar structure, and I'm focusing on the word of similar, not exact same, because in this case we also have 4, 1 and 2 present. But the thing is, notice that this 2 actually has another node or another left child 0 that is present over here, which is not the case in this scenario. So because this is not the case, we cannot say that these two are same and these two are actually not same. So in this case we will return false. And basically we are trying to see that whether one tree is a subtree of another tree or not. So that's why the name of the problem is subtree of another tree. It is self-explanatory. And now let's see what are the different approaches to solve this problem. So this is the root and subroot we are given. Now over here we are trying to see that what would be the optimal solution for this problem, and basically we can clearly see that the answer in this case is going to be true, because this 9, 1 and 2 is also present as a subtree in this original root tree. So that's why we can return true in this case. The thing is, let's see that what is going to be the strategy. Well, the idea is we are actually going to iterate over this given root tree in BFS fashion. Now if you don't know what BFS is basically breadth first search, and you can see more details about that in this video I have done previously. Now let's focus on the problem at hand. So the idea is that at every single time we are going to iterate over this root node, and we are going to iterate in BFS fashion, which means we are also going to iterate its neighbors for every single node. Now at every single time we are going to compare it with this subroot tree, and the moment we find a match, we are going to iterate over both the trees in BFS fashion. So let me quickly show you what I mean by that. So first of all, in this root tree I'm going to iterate over this root number 5. Now this root number 5 is not same as this root number 9, so which means I can't do anything over here. I have already iterated this value. Now I'm going to iterate its children. So first of all, I'm going to iterate over this root value 8. So this 8 is again not same as this 9, so we can ignore this case. Now we are at this position number 9. So this 9 is actually same as this 9. So because these two values are same, now I'm going to do BFS traversal for both of the subroot and root trees. Now from this 9, if I see the BFS traversal, basically I'm going to go to the left child. So left child in this case is 1. So again I'm going to see the same thing. Even in this case the left child is also 1. So yeah, I'm good up until this point. Now I'm going to go to the right child. This is 2, and the right child in this case is also 2. So yeah, again I'm good until this point. Now I'm not going to stop my traversal. I'm going to keep on iterating till I find all the null values. So in this case this 1 does not have any children left or right. So in this case I'll encounter a null value. So I'll try to see the same thing over here. So over here this does not contain any subchild of its own as well. So this is also null. So I'm good up until this point. Now if I try to see this portion, so this is also null and this is also null. So because all the values are same and I found no other children that I can iterate over, in this case I can simply return true. Now there are two ways to do this problem. I can do it iteratively or I can do it recursively, and if you know my videos, I like the recursive method better, so I'm going to show you the recursive solution. Now let's see one more case where the answer is going to be the false. So suppose for the same example we do everything right, but over here this 2 actually has a subchild called let's just say 7 over here. Now because this 2 has a subchild called 7, now the moment I am done iterating these values and I don't find anything, I'm good up until this point. But now at this portion at this node 2, I'll find a value 7 over here, but when I try to find the same value over here, I won't be able to find, and because I won't be able to find, I'll return false. Now the time complexity is actually going to be big O of m plus n. Why m plus n? Because we will have to iterate over all the nodes that are present inside this given tree root and subroot, and m is the number of length of all the nodes that are present over here, and n is the number of length of all the nodes that are present in this subroot. And if we see space complexity, well, basically because we are doing it recursively, we might have to iterate over all the values, and the space complexity in the worst case could be m plus n as well. And now let's move on to the coding. So before we start working on each subtree method, first of all, we are actually going to have to create a new method where if we pass in the value of any root node and subroot node, it can determine that whether both values are same or not. So first let's do that. So we created an isSame method which takes in the value of two tree nodes. Now first of all, we are going to check that if both values are null, which would be the terminating case for our recursive call. So if both values are null, we can simply return true. Now if that is not the case, we will also have to check the scenario where one value is null and other value is not null. If that is the case, we will have to return false. Now there is also one more thing we'll have to check, that and that is the value of this s and t. So if the value of s and t, if they are not the same, we can return false immediately. And if everything is not returned by this point, which means that the value of s and t is same, so now we will have to check the left subtree of s and left subtree of t, and same thing we'll have to do for the right subtree of s and right subtree of t. So let's do that. Now from our main method is subtree method, first of all, we are going to check that if the given root is null. If that is the case, we can return false immediately. So if that is not the case, we will have to call our isSame method for this root node and subroot node. So let's do that. And if we get the answer to be true, we can return true immediately. Okay, so if this does not return true, which means this current root and subroot, they are not the same. If they are not the same, we will have to iterate over this node root for its left child and right child to see if they are same with this subroot or not. So let's do that. So now for that, we will have to call this isSubtree method again, and we are going to run BFS on this tree node root. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit this code. Our submission failed. Let's try to diagnose. Oh, in this isSame method, we will have to check that whether the answer of both of them, if that is true or not. So we'll have to use AND condition. Let's try to run the code again. Okay, seems like this is working. Let's submit this code again. Okay, and now our code runs perfectly fine. It's faster than a lot of other solutions, and I would be posting this in the comments so you can check it out from there. Thank you. The problem statement is called count good nodes in a binary tree. We can see that this one is a relatively new problem, a medium problem, and also a very well-liked problem. On top of it, this has been asked at tons of different companies. So let's pay some attention that what the question is asking us to solve. Basically, we are given the root of a binary tree and we need to return the number of good nodes in a binary tree. The question is, what the heck is a good node? Well, a tree node is deemed good if in the path from root to that particular tree node x, there are no nodes with value greater than x. If that is the case, that node is a good node. So let's try to understand this with an example. Currently, we can see that there are 5 different nodes or 6 different nodes in this particular tree. Now we are being told we need to find the good nodes. The definition of a good node is that path from root to any particular node. If that particular node is contains the maximum value, then it is deemed good node. So let's try to see what are the good nodes, starting with the root. Now root in itself is a good node because path from root to root is the biggest value. So we find one good node. Okay, now let's consider value number 1. What is the path between root to value number 1? This path. Is 1 the largest number on this path? No, which means 1 is not a good node. Then let's consider the path 6. So for 6, the path is 5, then 1, and then 6. So in this case, 6 is the largest number from the direct path to the root, which means 6 is also a good node. So let's mark that. Once again, now we found everything we could. Let's try to move to next value number 5. So is 5 a good node? Yes, 5 is also a good node. Why? Because the definition of 5 is that from root to that particular x, there are no nodes with value greater than x. So in this case, the nodes we have is value number 5, 1 and 5. So there are no other nodes that has value greater than 5, which means 5 is still a good node. So we will also mark this as good. Then we will jump to value number 7. So once again, the direct path from 5 to 7 is this one. So in this case, 7 is the largest node. So 7 is also a good node. And next value is once again 7. So once again, even in this path 5, 7 and 7, there are no values greater than this 7 as well. So 7 is also a good node. So in this case, in total, we found 1, 2, 3, 4 and 5 good nodes amongst these 6 nodes. So we need to return 5 as the answer. And this is what the problem statement is asking us to solve. So now let's try to understand the logic on the solution we can build for this particular problem. The logic is quite straightforward, that we need to iterate over the given tree in some fashion, and we will have to keep track that around this iteration, what has been the largest value we have been able to find so far, keep track of it, and using that particular value, we are going to make some important judgment calls. So the logic we are going to do is that we will have to iterate the given tree in depth first search fashion. Why depth? Because we will have to keep track of the entire path from root to any particular node. So for that, we will have to go into the depth first search order. Now, what are the considerations? Number one thing is, first we are going to check the root or at any given position, because first we are checking the root, then we are checking for its left entire subtree, and then right entire subtree. Same thing we are doing at every single level, that first we are checking that for this particular root, whether it is the largest number. After understanding this, we are checking its left subtree and then right subtree. So basically we are doing the pre-order traversal in this case. And pre-order traversal is quite straightforward. The logic is root, then left, and then right subtree. So we are once again going to do a pre-order traversal, in this case in depth first search fashion. We are going to keep track that what has been the maximum value we have been able to find inside the current path. If the current node is equal to or greater than the maximum value we have been able to find, so in this case we are going to deem this node as a good node. So we also need a variable to store the good node as well. So let's assume that, okay, we are going to have our count variable to store all the good nodes we have been able to find so far, and this is the whole solution we need to create. So let's try to understand, or let's try to iterate over our given solution, and let's just arbitrarily give some values to these particular trees or these particular values. So in this case, we can see that these are the different values. Now let's start with value number 3. 3 in itself is a good node because we are doing the depth first search pre-order traversal. We are going to take care of the root first. Okay, now we took care of this root. Now let's take care of the left child. So left child is once again 1. So once again, even at the left child position, we will have to follow this position of root, left and right. So once again, now left child in itself is a root. So we have value number 1. What has been the, and also we have our maximum value we have been able to find on the current path. So maximum value so far has been 3. This value is 1. So current node is not greater than maximum value, which means this is not a good node. Now we will need to check for the left pointer. So left pointer is once again 3. So 3 is same as the maximum value on this path we have been able to identify. So we are going to mark this 3 as the answer that we have been able to find so far. Now 3 is also going to be a good node. So we are going to add our count of good nodes. Now we are going to do a backtrack. Now for the backtracking, once again, we have a right node that we haven't checked. So we are going to take care of the right node as well. The value of the right node is 5. So currently at this particular position, the right node is actually greater than the maximum value we have been able to identify. So we are going to store, once again, count this 5 as a good node as well. Apart from doing that, we will also have to update the maximum value we have been able to identify. But this particular node does not have any subsequent child nodes of his own. So because it does not have any child node, there is no point in updating the value of the maximum node. But say for an example, if we did had one more child like this, where we need to check for the value of this node number 6, then this 5 would have been the maximum value we have been able to identify so far, but that is not the case. Once again, coming back, now we took care of 5 and we took care of 3. It does not have any children. We are going to do the backtrack. We already took care of 1, which means now we have to taken care of this entire left child. Once again, in our pre-order traversal, we took care of the root very first, then we took care of the left child. So this is the entire left child portion of this root. Now we need to take care of the right child. So once again, we are going to do the same thing. We are at position number 4. So we are going to first check that whether 4 is a good node or not. So in this path, the current maximum value we have been able to identify was value number 3. So 4 is a good node. But in this case, because we are checking for the subsequent children of 4, we will have to update the maximum value we have been able to identify along this path to value number 4. So this is the maximum value we have found so far. Next value is value number 2. So 2 is not is less than the maximum value we found. So 2 is not a good node. So in this case, we found in total 4 good nodes. So we are going to return 4 as the answer. And that's it. This is the whole solution that we need to return. Basically, we need to understand that why we need to use DFS in this case, because we are going in one particular direction. We will need to keep track of the maximum value at any given track. And we also have to do the pre-order traversal because we are following the principle of root, then left, and then right. And you can do this recursively or iteratively, it's up to you. We will see that in the coding. If we see time complexity, it's pretty straightforward. It's going to be big O of n because we are iterating over every single value. In terms of space complexity, if you use the recursion method, it will take big O of n. If you use iterative method, it would not take big O of n. And let's quickly see the coding solution for this one. Okay, so we are going to use a helper method called count good nodes to keep track of the good nodes we have been able to identify, and we are going to pass in the root value we found so far. Now this count good nodes is actually going to return an integer value that defines that how many number of good nodes we have been able to identify for this particular root node. Then we are in the initial input, we are just returning like the minimum value possible, because root in itself has to be greater than that. So root is going to be the first good node. Okay, now we are going to check, okay, that we are taking in as an input the tree node and the maximum node so far. We are checking for an edge case that if the given node is equal to null, we can simply return this 0. If that is not the case, we need to initialize our count to 0. Then we are going to check that if the given current node value is greater than the maximum value we have been able to identify. If that is the case, then we are going to update the counter to 1. And we are also going to update the maximum so far to the current node that we just found out. Once again, we are going to repeat the same process for the upcoming subsequent left child and for upcoming subsequent right child, and we are going to add the values of the left child and right child to our existing count value as well. So whatever count they come back with, we are going to add them to our existing count, and in the end, whatever the final count we found, we are going to return that, and that would be written as part of the answer for this one. So that's it. Let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs 100% faster, which is pretty awesome, because this has to be some of the fastest code, because the runtime is also not 0 millisecond. So we are doing something really awesome over here. Once again, solution is posted on our GitHub repository. So feel free to go ahead and check it out. Thank you. Hello friends, so now once again let's do an awesome LeetCode problem that is going to solve all of your problems. So without any delay, let's get started. So the LeetCode problem we are going to do today is called diameter of a binary tree. We can see that this one is an easy problem and also a very well-liked problem. The problem statement is quite straightforward. We are given the root of a binary tree and we need to return the diameter of the tree. Now the question is, diameter of a tree is the length of the longest path between any two nodes inside this tree, and we are told that this path may or may not pass through the root. But it's gonna pass through the root. Okay. Now the length of the path between any two nodes is represented by the number of edges between them. So let's try to understand that how does a diameter of a tree is being calculated. Let's say that we are given a tree like this. So in this case, what is the longest path we can make? Well, let's just give them the number. So 1, 2, 3, 4, and 5. These are the numbers of this given nodes. So we can see that the longest path over here is this one. So 3, 2, 1, and then 5. This is one path. Second longest path is once again 4, 2, 1, and 5. So in either case, the longest path we are able to make contains 3 edges. This is going to be the first edge, this or this, either one of them. Then this is the second edge and this is the third edge. So the answer is going to be 3, that this is what we need to return. Now the problem statement is quite easy to understand, but the thing is, how do we actually calculate the diagram? And if we start iterating over every single path and then try to find the answer, then this becomes a lot of complication. So we need to avoid that. And if you look at it from the other way, at any given moment or at any given node, the diameter of that node is nothing but the height on the left hand side. So left hand height and the height on the right hand side. That's it. This is all a diameter is. And we can see that in action over here, that the height on this left subtree is actually going to be 2, because this is the first level and this is the second level, and the height on the right subtree is going to be 1. So if we do 2 plus 1, the answer is going to be 3. So this is what we need to calculate. Now we need to understand that how we are actually going to be able to calculate that for any given binary tree. And for that, we simply have to iterate over any given tree, nothing more than that. Now, iterating over the tree is actually quite simple, and we can use the common logic of recursion in this problem. Now for recursion, we need 2 items. First item is a base case. So base case in this case is going to be that if the current node, if that is equal to 0, which means we have reached to the very end and now we cannot go anywhere further. So then we start to do the backtracking. This is the first base case. Now what is going to be the recursive equation or recursive scenario? Well, recursive scenario is quite simple, that at any given moment or at any given node, the height or the diameter of that node is actually going to be the sum of the left diameter and the sum of the right diameter. And same way, even at subsequent left node, the diameter at that node is going to be sum of the left diameter and right diameter. And that's how we should be able to calculate the answer we are looking for. So in this case, the height on the left hand side is going to be 2. The height on the right hand side is also going to be 2. So the longest path we are going to be able to make is going to be of size 4. And we can also see some examples of that. So one of the longest path starts from this node and then once again to this node, and once again to this node, and then once again to this node, and once again to this node. If we see the number of edges included, this is the first edge, this is the second edge, this is the third edge, and this is the fourth edge. So this is exactly what we are looking for in terms of finding the answer. So we also found out the recursive solution, that the diameter at any given node is going to be the sum of the left node and plus sum of the right node. Okay. And then we can have a recursive function to recursively call our entire tree and then return back the answer. So this is actually going to be the whole solution. We are simply iterating over the tree, calculating the height, and whatever the sum of the height is, we simply return that. If we see time complexity, in this case, the time complexity is going to be big O of n, where n is the total number of nodes that are currently present inside the tree, because we will have to iterate over every single node. And in terms of space complexity, well, this is also going to be big O of n, because we are using the recursion, and in order to store the recursive stack, we might use big O of n space. So if you want, you can also do this problem iteratively, and in the iterative solution, we actually don't have to do or use the stack. But the only reason I am using the recursive solution is because it's good to do it like recursively. It's small amount of coding and also looks cool. Okay, so now let's quickly go to the coding. So the coding solution is quite straightforward. we are going to initialize our variable maximum diameter, and we are going to have our method diameter of the tree, from which we are going to call our get height method for left and right subtree for the given root element. Okay, now this our get height method is our recursive method. So let's quickly see what is happening. As a part of the base case, we are having the scenario that if the given node is equal to null, we need to return 0. If that is not the case, then we are going to find the left height and the right height. For both, we are going to recursively call the get height method with the left child and with the right child. Now for every single position, we will have to check that have we reached a new maximum diameter. So for that, we are going to do a simple equation of the current maximum element or maximum diameter we have been able to find. If that is greater, or if we find that the current left and right side subtree's height is greater than the current maximum diameter we have been able to find, then we need to update the max diameter. If that is not the case, then we can simply leave the max diameter as it is. Next, we need to return the height that we have been able to find. So in the end, we are simply going to return 1 plus the maximum value of either left height or the right height. And why are we doing 1 plus? Because at any given root node, we also have to consider the node by itself before propagating the height to its previous level. So that's why this 1 plus is there. Okay, with every new level, basically we add one value to the height. And this is the solution. Let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. So our code runs 100% faster than all the other solutions, and that's because the code actually operates on a very simple principle, and it runs in 0 milliseconds. So that's why it's 100% faster. It's nothing magic. Now, once again, the coding solution is present inside our GitHub repository. Let me quickly show it to you that this is the GitHub URL where we have actually stored hundreds of LeetCode questions and their answers. These are some of the most popular questions in the entire world. These questions has been asked at tons of different companies multiple times. So for each of the problem, you can go ahead and see we have the Java file for that. You can go and find the LeetCode link. If you don't find, you can also find the subsequent video solution, and also a list of most asked problems at the FAANG companies, which is this list, which contains a lot of important LeetCode problems. They have been differentiated based on the topics, and for each of the topics I have provided that how many times they have been asked at different top tier IT companies. So there are 130 of most fabulous questions that I have been able to find. Then also I have solved most of the LeetCode 150's problems, and they are also provided over here. So both of these resources are amazing. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do validate binary search tree LeetCode problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Microsoft, Bloomberg, Facebook, Uber, Google, Apple, ByteDance, Lyft, LinkedIn and Netflix. So that's why I am paying my utmost attention. I hope you also enjoy the video. This is a LeetCode medium problem and one of the most liked tree problems on LeetCode. Basically, we are given the root of a binary tree and we need to determine that whether that given tree is a valid binary search tree or not. We are also given the definition that what a valid binary search tree is. Basically, for any given tree, if this root value or the node value, so if this is the value of the node, basically every single value that is present on the left of the node should be less than whatever this node value is, and every single value that is on the right side of the node should be greater than whatever this node value is. So if that is the case and that is true for the entire given tree, we can define it as a valid binary search tree. So let's take a couple of examples that are shown over here. So in the first example, well, basically the node value we have is 2. So in the left subtree we only have one value, that is 1, which is less than this 2, and on the right subtree we only have one value again, which is 3, which is greater than this node value 2. So in this case we can consider this to be a valid binary search tree, and in this case we will return true. But if we take a look at the second example, so in the second example we are given this root value as 5. So this node value is 5, that is okay. If we see on the left subtree we only have one child, and that is the value is 1. So this is again less than whatever the value we have for the node value. Now if we see on the right subtree, the value of this is actually 4. So 4 is again less than 5. So because this 4 is less than 5, and remember that we have the definition of valid binary search tree, that everything on the right subtree should be greater than whatever the node's value is. So in this case, this value is actually not greater than the value of this root node. So in this case, this is not an valid tree. So in this case, we will return false. And this is what we have to define basically. Now, based on the definition, we can define that what a valid binary search tree is. That for any particular given node, if its entire left subtree, if that is less than that node, and if its entire right subtree, if that is greater than that node, we can define that to be a valid binary search tree. Well, if that is the case, the first intuition that comes to our mind is that for any given node value, what we can do is we can check its left child and right child. If the left child is less than it and right child is greater than it, if that is the case, we will keep on repeating the same process for all the subsequent left child and right child with its root node, and in the end, if we reach to the end of this tree, we can return true immediately, saying that this is a valid binary search tree. Well, let's try to apply that same logic for this particular example. Basically, we are given this node 5. So this 3 is actually less than 5 and 8 is actually greater than 5. So in this case, this portion is actually valid. Now again, for this 3, this 1 is less than it and 4 is greater than it. Again, this portion is also valid, and same is true for this 8, 6 and 9 as well. So in this case, we can define this to be a valid binary search tree, and we can return true in this case, saying that this is a valid binary search tree. But the thing is, this solution is not the most optimal way to solve this problem, and let me quickly show you why. Because based on the same logic for this 5, this 3 and 8, again, okay, this is less than, this is greater than, so far this is valid. Again, for this 3, this is 1 and 4, so this is less than, greater than, again this is valid. But now for this 8, this is also 2 and 9, so this is less than, greater than, again this is valid. So all three portions are valid. By definition, we would treat this to be a valid binary search tree, and that would actually be a false positive. Why? Because remember that by the definition for this node, everything that is on the right side of this tree should actually be greater than this node 5. But in this case, this 2 is actually less than this 5, and because of that particular case, we will need to return false in this case. The thing is, based on our previous method, we would have returned true. So let's see that what would be the actual optimal solution to solve this problem. So the idea for the optimal solution in this case is that we are actually going to do in-order traversal on the given binary tree to determine that whether it's a valid binary search tree or not. Well, if you want to learn more about different types of tree traversals, you can check out the video over here. Now let's get back to the question at the hand. So basically what the idea I'm suggesting is that if we do in-order traversal in any given tree, basically the idea for in-order traversal is that first of all we visit the left subtree, then we visit the node, and then we visit the right subtree. Also, this in-order traversal is a depth first search kind of a traversal, where we are actually going in the depth first and then we are visiting the different nodes. So in this case, the traversal that we are going to do is that first of all we are going to go for the left subtree. So for this node, left node exists. Again, for this node, left node exists. So first of all we are going to visit this left child. Then this child does not have any more children of its own. So now we are going to visit its node. So we are going to visit this node 3, and then again we are going to visit its right child, which is 4 in this case. After doing that, we are going to visit the node, and then we will keep on repeating the same process. So let's see that what is the path we are going to take for this in-order traversal. Well, for this problem, basically the path we are going to take is that first of all, as mentioned, we are going to visit this node number 1. So first node is going to be 1, then we are going to visit node number 3, and then we are going to visit node number 4 in the fashion of left node, and then right sub node. Then we are going to visit the node, so we are going to visit node number 5. Now we are going to keep on iterating on the right subtree. So even on the right subtree, again we are going to follow this method of left node and right. So for this left subtree, now this becomes the root node or the node, and this also has a left subtree existing. So first of all we are going to visit this node number 6, then we are going to visit node number 8, and in the end we are going to visit this node number 9. So this is the in-order traversal for this given binary tree. Now the thing is, if you see this traversal, basically everything is going in increasing order, and this whole thing is actually sorted. And this is the property of this in-order traversal that we are going to make use of, and we are going to solve it optimally. The idea is for any given tree that we are presented with, we are going to do an in-order traversal, and during the in-order traversal, basically the only thing we have to keep track of that any given node that we are iterating indicating whether that node is actually greater than its previous node or not. If it is not greater than its previous node, immediately we can return false. So in this case, because this was a valid binary search tree, we were able to get an in-order traversal that is completely in increasing order, and all the previous nodes, they are actually less in value compared to its next subsequent node, and this property is maintained throughout the entire journey. Now let's see one example where this is not the case. So in this example, we can clearly see that this node 2 is at the correct place, and this is not a valid binary search tree. So let's see the in-order traversal over here. So in this case, the path is going to be, the next node we are going to visit is actually 2, and if we compare this node 2 to its previous value, the previous value is actually 5. 5 is actually greater than this 2, which should not be the case, and immediately at this point only we can conclude that this is an invalid binary search tree. We will return false immediately in this case, and that is the answer we are going to use. Now actually there are two ways to do in-order traversal for any given binary search tree. There is an iterative way and there is a recursive way. If you know me, I like the recursion better, so I'm going to show you the recursive way in the coding, but it can be also done iteratively as well. And the tricky part in this problem is to identify that we need to solve this problem using in-order traversal. If we see time and space complexity, in this case the time complexity is actually going to be big O of n, where n is the number of nodes that are present. For the space complexity, we are using recursion, and we might have to store n characters in the worst case scenario. First of all, we are actually going to define a global variable called previous to store the value of the previous element. Now let me create a new in-order method that would be our recursive method. So now I have created a new in-order method that returns a boolean answer, and we are taking just a root value as the input. Now first of all, we are going to create the terminating case that if the given root is equal to null, we are going to return true. If that is not the case, first of all, for the in-order traversal, we will have to call the leftmost function or leftmost value. So we are going to do that. So first of all, we are going to see that if the answer for the root dot left, if that is false, we will return false. If that is not the case, we will move on towards our next condition. Okay, so if we did not return false from our left side subtree traversal, then we are going to check our condition. So the condition we are going to check is that whether the current root value, if that is less than or equal to the previous value. If that is the case, which means that we have actually found an invalid binary search tree, so we can return false immediately. So if we don't return false by this point, which means the previous value was actually less than whatever the current root value we had, which is a good sign. So now what we are going to do is we are going to update the value of our previous variable. So that is going to be the current root value, and then after that we are going to call the right side subtree as well. So we can simply return the in order for the right subtree. Now from our main method, all we will have to do is we will have to set up the value of the previous character. So initial value is going to be the null, and then we are going to call this in order method. Okay, seems like our solution is working as expected. Let's submit this code. And our submission runs pretty efficiently compared to a lot of other solutions, and that is because the code runs in 0 milliseconds. I would be posting this in the comments, so you can check it out from there. Thank you. Hello friends, we are not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do the lowest common ancestor of a binary search tree LeetCode problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like LinkedIn, Facebook, Amazon, Apple, Google, Microsoft, Uber, Reddit, and Twitter. So that's why I am paying my utmost attention. I hope you also enjoy the video. This is a LeetCode easy problem, and basically first of all we are given the definition that what a lowest common ancestor means. The lowest common ancestor is defined between any two nodes P and Q, such as that the lowest node in given tree that has both P and Q as the descendants, where we allow a node to be a descendant of itself as well. We are given a binary search tree, and we are also given two nodes in that binary search tree, and now we need to find the lowest common ancestor between those given two nodes. So let's try to understand this with this example. Basically we are given a binary search tree over here, and we are also given the value of P and Q to be 2 and 8. So subsequently, if we see over here, 2 is located at this place and 8 is located at this place. So the most common element, or the immediate common element that we can find, is actually 6 in this case. So that's why in this case we are going to return 6 as the answer, because that is the lowest common ancestor between the node 2 and 8. If we take one more example in this case, so over here we are given this p is equal to 2 and q is equal to 4. So p is located at this 2 and q is actually located at this 4. Now if you see in this case, actually this 4 is a descendant of this 2. So that's a given fact. But remember, we are also told that we allow a node to be a descendant of itself as well. So in this case, since this 2 and 4, so 4 is already a descendant of this 2 and 2 is already a descendant of its self. So in this case, we will have to return this 2 as the answer. And that is what is given over here. We are given one more example where we are given only 2 nodes for this given binary tree. So the binary tree looks like this, 2 and 1. And in this case, we are given the value of this p to be 2 and q to be 1. So again, we can see that in this case, this 2 is already a descendant of itself and this 1 is actually a child of 2. So because of that, 1 is also a descendant of this 2. So in this case, we will again return this 2 to be answer. Now, I hope that this makes understanding the problem more easier. And now let's see that what is the approach we are going to solve this problem. Okay, first of all, I'm actually going to show you a bunch of different binary search trees, and for all of those binary search trees, I have created some p and q values, and we are going to see that what was the lowest common ancestor and why that was the lowest common ancestor. Right now, we already know that important property of binary search tree, and that is that for any given root value, everything on the left subtree of that binary search tree is actually less than that, and everything on the right side of that binary search tree is greater than that. We already know this important property, and we are going to take it to our advantage based on this given root value or any root value and with subsequent p and q values. So if we see over here, in this case, the given value of p is actually 6, and if we start traversing through this binary search tree, immediately we would find the 6 to be present over here. So because we find the 6 to be present, there can only be one possibility, that this q, or whatever the value of q, that would either be on the left side of the subtree or right side of the subtree. But we already find the value to be 6 over here. So immediately we can return 6 to be the lowest common ancestor, because anyways this value of q is somewhere supposed to fall inside the remaining binary search tree, and in this case it is on the right side of the subtree. So we will return 6 as the answer. This makes sense, right? Now the next example, again we are given the same thing. We are given this value p to be 11 and q to be 9. So we know that this p is over here and q is over here. 11 is going to be answer, but let's go ahead with our algorithm. So first of all, we'll start iterating over this root. So the root value is actually 8. Now for this root value, we are going to compare it with the values of p and q, right? In this case, the value of p and q both are actually greater than this 8. So because both are greater than this 8, we know based on the property of binary search tree that they are meant to fall somewhere on the right side of this given binary search tree. So we will start iterating over the right side of the binary search tree to either find the values of p or q, or if we can't find, we will try to find the lowest common ancestor. So when we start iterating over on the right side of the subtree, we will ignore this left side of the subtree. We don't care. Now this value is 11. This value is 11 is actually matches the value of this given p. So immediately, whenever we find a match with either p or q, we can return that to be the lowest common ancestor immediately. And in this case, this is going to be the answer, because this 9 is meant to be somewhere below this binary search tree, and in this case it is immediately right here present. So we will return this 11 to be the answer, which is the lowest common ancestor. Let's take one more example which is very similar. So in this case, this value is p is equal to 3 and q is equal to 1. Now again, based on our algorithm, we will start traversing over this binary search tree. Now the first value we traverse, whenever we compare its value with this p and q, immediately we find a match with this p to be over here. So because we find a match over here, do we really need to iterate over this given binary search tree? Well, the answer is no. Why? Because we know that this q value is somewhere going to be down below, and that is always going to be this descendant of this p. So again, we are going to return the values 3 as the lowest common ancestor. So far it makes sense that whenever either we identify the value of p and q, we can return that to be the lowest common ancestor immediately. But what happens if the case is a little bit different? So in this case, I have given the value of p to be 6 and q to be 9, right? Again, let's start with our algorithm. So we'll start iterating over this binary search tree. So first of all, this value is actually 5. So because this value is 5, we'll try to see that, okay, we'll compare it with this value of p and q, right? So actually this 5 is less than p and less than q, both p and q are greater than this root value, so immediately it is meant to fall somewhere on the right side of the subtree. So now we'll start iterating on the right side of the subtree. We'll ignore these two because we don't need them. Now again, this value is 7. So let's compare this 7 with this value of p and q. Well, if we compare this 7 is actually greater than this p, and this 7 is actually less than this q, right? So we can conclude this 7 actually falls somewhere in the middle, because on for the 7, on one side 6 is meant to be because 6 is less than 7, and somewhere on the other side 9 is meant to be because 9 is greater than the 7, based on the property of a binary search tree. And if we utilize that to our maximum advantage, we can immediately determine that this 7 is the common point between this 6 and 9, where on one side 6 resides. So 6 resides on the left side over here, and 9 resides on the right side of the subtree. So on the right side of the subtree, this is where 9 resides. So we will return 7 to be the answer in this case. And this is the approach we are going to follow. So every single time for any given tree, we will start iterating over that tree, and we are going to compare its value with p and q. Based on that, we will decide that whether we go on the left side of the subtree or right side of the subtree. The moment we find a match between p and q, whatever the value we found, if we find that, we will return that to be the lowest common ancestor. If we don't find a match, and if we are in a situation where this value of p is on the left side of this any root value and q is on the right side of any root value, then immediately we can return that value to be the answer. And this is the approach we are going to take to solve this problem, and this is the optimal way to solve it. Now there are two ways to solve this problem. We can either solve it recursively or we can solve it iteratively. Now I like recursion better, but iterative method will also work as expected in this case. Now for the recursion, if we see the time and space complexity, the time complexity is actually going to be big O of n, because we will have to iterate over all the values in the worst case scenario. And for the space complexity, the space complexity is actually going to be big O of n as well, because we will have to maintain the runtime stack for this recursion method. Well, one good thing in iterative method is that for iterative method, the time complexity is still going to be big O of n, but for the space complexity, we can actually use a constant space complexity for the iterative approach. But in the coding, because I'm trying to improve my recursion, I will be showing you the recursive method. But just remember that iterative approach would be the better option in this case. So we are going to use the same method as our recursive method. And first of all, in this method, as an input, we are given this root value, we are given the value of p and q. So first of all, because we don't need to deal with this tree node, we will actually have to deal with this integer value. So I'm going to initialize three variables called the parent value, p value and q value, and I'm going to assign the values based on this whatever the input we get. Now we will have to check that whether this parent value, if that is the common point between p and q, or either p and q falls on one side or other side of this binary tree. If that is the case, we will call our recursive method again. So first of all, we are going to check that if this p value and q value both are greater than this parent value. If that is the case, which means we will have to iterate on the right side of the subtree. So we are going to call the iterative method on the right side of the subtree. If that is not the case, we are going to check that whether this p value and q value both falls on the left side of this parent value. So again, we are going to do that. So if both p value and q value are less than the parent value, which means we will have to search the left side of the subtree. So we are going to do that. Okay, if that is not the case, which means that whatever this root value we are at, that is either p or q value, which means we can return root immediately. That's it. That should be working. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently compared to a lot of other solutions in terms of time complexity. I already mentioned you that for the space complexity, this recursive solution is not the most optimal, but I want to practice recursion, so that's why I did that. You can find an iterative solution that works as well. And I would be posting this in the comments, so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do Kth smallest element in binary search tree LeetCode problem. And if you see some of the companies where I want to get a job who have already asked this question, there are companies like Uber, Amazon, Microsoft, Facebook, LinkedIn, Apple, Google, and Bloomberg. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given the root of a binary search tree, and we are also given an integer called k. Now we need to return kth smallest value from all the given values inside any given binary tree. So let's try to understand this with couple of examples that are presented over here. So this is a binary search tree we are given, and if you notice the important property of binary search tree, where for whatever the root node, everything on the left subtree is less than that root node, and everything on the right subtree is greater than that root node that is present for this BST. So that is the definition of binary search tree. I'm just making it clear. And now for this example, this is the binary search tree we are given, and we are also given the value of k to be 1, which means we need to return first smallest value. So in this case, the first smallest value or the smallest value is going to be this value 1, and this is what we need to return as the output. Let's take one more example. So in this case, again, we are given a binary search tree, and we are also given the value of k is equal to 3, which means we need to return third smallest value. If we see in this case, this 1 is actually the first smallest value, same with this 2 is the second smallest value, and same with this 3 is actually the third smallest value. So in this case, we will have to return this 3 as the answer. So I hope that you have understood the problem by now. Now let's see that what is going to be the optimal approach to solve this problem. Okay, suppose this is the binary search tree that we are given, and we are trying to find the kth smallest value at any given position. So the idea I'm suggesting is that for this particular binary search tree, if we make the sorted array of all the values and we sort them in increasing order, then whatever this array we have created that is already sorted, based on this, it becomes pretty easy for us to find the kth value. How? All we have to do is just look up in this array, and we will be able to find the value. Let me quickly show you what I mean. So for this particular binary search tree, if we see the sorted path where the first value is 1, then we have the value 3, then we have the value 4, and then we have 5, 8, and 9. And this is the sorted path that we have been able to generate. Now once we have this value, it becomes pretty easy for us to find any kth position. How? Suppose we are given k is equal to 2, we can immediately return second smallest value, which is the second value in this case, which is the value number 3. If we are given k is equal to 5, then we simply need to return this value number 8. If we are given k is equal to 3, we can simply return this value number 4. So now you get the idea that once we have this sorted path, it becomes pretty easy for us to find any kth position. So all we will have to work on is that from this given binary search tree, how can we actually create this sorted path? And if you know, or if you have followed my previous video, you know the answer. The answer is actually Inorder traversal. So let me quickly show you the optimal solution using Inorder traversal for this problem. Okay, so Inorder traversal actually a depth first search kind of a traversal, which means that first of all, on the left side of the subtree, we go to the leftmost position, then we visit its node or its root value, and then we visit its right subtree, and we keep on repeating the same process. So let's see that what is going to be the path in this case. So path in this case is, first of all, we are going to visit the leftmost element, which is 1. So we'll visit node number 1, then we will visit node number 3, then we will visit node number 4 based on following this left node and right more formula. After that, we will visit the node again, which is 5, and then we will be on the right side of the subtree. So again, on the right side of the subtree, we will have to follow the same path, left node and right. But in this case, since this right side of the subtree does not have any left children, so we won't be able to update or traverse any left value, but we would be able to traverse the node value. So again, we will travel the value 8, and then in the end we would traverse the value number 9. So in this case, this is the path we are able to generate from this given input binary search tree using this Inorder traversal. And if you see this path, this is actually increasing order, and this path is actually sorted, which is very good for us. So suppose we are given the k is equal to 3. So if kth value is 3, we can simply return 4 immediately. If we are given k is equal to 5, then again we can return this value number 8 immediately, as mentioned earlier. And this is the approach we'll have to take to solve this problem optimally. Now if you want to learn more about different kinds of tree traversal, check out my video over here. Now let's see the time and space complexity in this case. The time complexity is actually going to be big O of n, where n is the number of nodes that are present inside any given tree. And if we see space complexity, the space complexity is also going to be big O of n to accommodate our Inorder traversal. There are actually two ways to solve this problem. One is the recursive way, and second one is the iterative way. Now since you know me, I like the recursion better, and even in the coding, first of all, we are going to create our recursive method called Inorder, and that is going to return an array. So I have created the Inorder method that takes in a root value and also that takes in an array list. Now, first of all, we are going to check the terminating case. So if the given root is equal to null, we can simply return whatever the array value we have. Okay, if that is not the case, first of all, we are going to call the Inorder function again, and we are actually going to call for the left subtree. So we are going to call with the root dot left child, and we are also going to pass in the value of whatever the array we already received. Once that is done, we are also going to add whatever the node value we have. So we are going to add the value for that particular root, and in the end we are also going to call the Inorder method again for the right side of the subtree, because remember, for the Inorder we are actually following the method of left node and right. So with this time we are going to pass in the value of the right child, and we are also going to pass in the value of the whatever the array we have created. Now once this method runs, simply we need to return this array list that we have been creating. Okay, now from the main method, first of all, we are going to create a new array list called nums. In order to populate this, we are actually going to call our Inorder method, and we are going to pass in the value of the root, and we are also going to pass in the value of a new array list. Once that is done, all we will have to do is basically from this array list we simply have to return whatever the k minus 1th position element is, because remember this k is actually one index, meanwhile the array list we have been creating, that is 0 index. So that is one tricky thing that we will have to take care of. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code, and our code runs pretty fast compared to a lot of other solutions. It is also very efficient in terms of space complexity as well, and I will be posting this in the comments so you can check it out the solution from there. So the LeetCode problem we are going to solve today is called find leaves in a binary tree, and this one is actually a LeetCode premium problem, and that's why you see that the UI looks slightly different. Now let's try to understand the problem statement. We are given a binary tree and we need to collect trees nodes as if we are doing the following, where we are collecting and removing all the leaves inside the given tree, and we are going to repeat this until the entire tree is empty. Now we all know that what does a leaf node in a tree looks like. Basically, the node that does not have any children is referred as a leaf node. So what we need to do is that for any given binary tree, we are given the root of it. We need to iterate over the entire tree, find that what are all the leaves that it currently has, collect every single leaves in one order, and then repeat the same process with all the remaining nodes. So in this case, we can see that at the beginning, these three are the leaf nodes. So we are going to mark these as the leaf nodes, and we are going to collect them in the answer. So we will collect 4, 5, and 6 as part of the first set of leaf nodes. Then we would get rid of these nodes. Then once again, we would be left with another set of leaf node that are going to be nodes 2 and nodes 3. So that they would come in the second portion of like collecting leaf nodes. Once we get rid of them, in the end we will only be left with the root node, and that is going to be value number 1, and that is all what we need to return. So this is the whole problem solution. Now you can imagine that solving this problem seems quite trivial. All we are doing is that at every given instance, we are basically iterating over the given tree, and we are trying to find that what are the leaf nodes. So we know that what is the condition of any particular node to define that it is a leaf node or not. Well, we can check that if for any particular node, if the left child is equal to null, and if it's the right child is also equal to null, and the node is currently not equal to null, which means the node exists. So in that case, we can define any particular node to be a leaf node. So we know that how to identify a leaf node. Second thing is we need to store every single leaf nodes that we collect, which means we will have to create an array list where we are going to store bunch of different array list for every single piece of LeetCode leaf nodes that we found. Okay, that is second thing. Third thing is how are we going to iterate over the given input, and for that there are actually couple of ways, but in this case recursion would be a very good approach to reach out and solve this problem, because we know that in the recursion we basically need to repeat the same process, and same goes in this problem as well. That first of all, for this entire given root node, we will need to find the leaf nodes. Same thing happens when we do go to the left child and right child. Once again, at the left child and right child level, we need to find the leaf nodes. So currently this one is a leaf node in itself, so we will mark it to the answer. At the right child level, left child level, once again we will still repeatedly try to find the same things. Once we find the all these three leaf nodes, we will mark them into the answer, remove them from the existing tree, so declare that the current node is equal to null, and then once again repeat the same process from the root. So let's try to understand the solution I'm suggesting in action. Let's just give some arbitrary values to these particular nodes. Okay, so in the recursion, we know we need two items. We need a base case. So base case is quite straightforward. The definition on how to define any particular leaf node that we just saw, that if the given left child is equal to null and the given right child is equal to null for any particular node, we can define that node to be null. That is the first base case. Second base case is that if the node in itself is null, then we are simply going to return null in that case. We don't need to do anything. But if we do identify at any particular moment that if left child and right child both are null, then we need to add that particular node to the answer array list that we have created for the current set of leaf nodes. Okay, and what would be our recursive case? So recursive function is going to be quite simple, that if the node has some left child and if the node has some right child, then recall the same recursive method once again until we reach this base case, and we would have added every single value inside the answer. So let's try to see the solution in action. First, we are at this root node. Currently root node does have left child and does have right child. So once again we are going to do the recursive function. So if we apply the recursive function, we are going to reach over here. Once again, for left child, we once again find it does have left child and right child. For right child, it does not have any other values. So we, and also for these subsequent values of left child and right child, we see that they don't have any children of their own, which means all of these are identified as the leaf node. So we are going to mark values 4, 5 and 3 in the answer as first set of leaf nodes. After declaring them, we are going to eliminate them from the given input. And now once again we are going to repeat the same process starting from the root node. So currently for this root node, it still has a left child. Once again for this left child, it does not have any child of its own, so this is going to be another set of leaf node. And in the end we will also get rid of this one. And finally we are at the root node. So once again recursively we find out that root node does not have any children. It meets the base case, so we are going to add it to the answer as well, and this is the answer we are going to return in the end. So logically this is a very simple tree traversal problem, but with every single traversal we just want to repeat the same process by eliminating few nodes and keep on doing it again and again till the entire tree is empty. So this is the whole solution. If we see time and space complexity, in this case the time complexity is simply going to be big O of n, where n is the total number of nodes present, because we will have to do it for each one of them. Even for the space complexity, in order to maintain the recursive stack, it is going to be big O of n, and also we need to create an extra array list to store the answer, and that is going to be completely dependent on the total number of nodes that are currently present. So overall this is a very good question and a good amount of time and space complexity. If you do encounter this in any of your interview, don't get afraid or don't worry, because this is like a simple approach on how you can traverse the tree and find the best solution that is asked. Now let's quickly see the coding solution for this one. So here is the coding solution for this one. Once again, we are running it in an online compiler and not in the LeetCode, because this is a premium question. So here is the definition of our tree node. It's just a standard tree node. Now let's quickly take a look at our class solution. So first of all, we are going to create a method that calls collect leaves method that provides in the root of the tree, and in the answer we are going to return an array list that contains list of values where we have all the leaves connected based on the edge cases for every single iteration. Now first of all, we are going to define the result where we are going to return as part of the array list, and we are simply going to run a while loop that while the given root is not equal to null, we are going to repeatedly do this, where first we are going to create a simple array list to collect leaves in that particular iteration of that tree. So this is going to provide us the leaves level by level. then we are going to provide the results by calling the remove roots method, where in the remove leaves method, we are taking in a tree node and we are also taking in the current set of leaves as an input. And this is going to be our recursive helper method, where first we are checking that if the given node is equal to null, we can simply return null. If that is not the case, we check that if the given node is a leaf node. If that is the case, we are going to add it to our leaves array list for now, and then we are going to remove it. And if that is not the case, both for left and right child, we are going to call the remove leaves method once again, and in the end we are simply going to return the node. So this is our helper method, where we are recursively iterating over the any instance of the tree based on the given node that we are provided. And once we return that back to root, we are simply going to add those results that we found inside the leaves as part for the in the result array list that we have created. In the end, we can simply return the results. Now I have also created a main method and just created like some dummy cases to see that where what is the answer we find. And we can see that the root node is 1, and then it has a left child 2, and the right child is 3. And once again, for left child, it has 4 as its left child and 5 as its right child, and so on and so forth. So if we try to run this code, we should be receiving the answer as expected. And we can see that in the first iteration we remove 4 5 6 as leaf nodes, then we remove 2 3 as second set of leaf node, and lastly the root node of 1. So this is the answer. Once again, the solution is present in our GitHub repository, so feel free to go ahead and check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do construct a binary tree from pre-order and in-order traversal LeetCode problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like Microsoft, Amazon, Bloomberg, Apple, Uber, ByteDance, Google, Facebook, and LinkedIn. So that's why I am paying my utmost attention. I hope you also enjoy the video. Now this is a very hated LeetCode problem, and let me show you why. This is from the solution tab of the LeetCode problem, where people have expressed their views very abruptly. Some people are saying why God why, some people are saying that it's time to leave for Himalayas, some people are saying that if you get this question they do not want to hire you, and things like that. There are many other comments. The thing is, we do not want to focus on the negativity. Let's try to see that what is the approach to solve this problem, and then we are going to see that how can we be able to solve this problem if we encounter this in any interview, because our aim is to get into FAANG, not just dream about it. Now this is a LeetCode medium problem, but in my opinion this should have been a LeetCode hard problem. Now let's try to understand the problem. Basically we are given two integer arrays called preorder and inorder, and basically they are the preorder traversal of a binary tree and inorder traversal of the binary tree. Now based on these two arrays that we are given, we need to construct and return the original binary tree. So let's try to understand this with an example. So over here we are given as an input, we are given two different arrays, pre-order array and in-order array. Now somehow if we iterate over this pre-order and in-order array, there is only one combination of binary tree we can make, and which is this one. So that is the example that is given over here. Now let's see that what is going to be the different approach to solve this problem. But before we do that, the important thing in this problem is to understand that what is a pre-order traversal, what is the in-order traversal, and how can we use their properties to our advantage. So first of all, I'm going to show you pre-order and in-order traversal, how it works. So first of all, we are going to learn about pre-order traversal, and basically pre-order is a DFS kind of traversal, which is depth first search. If you want to know more about different kinds of traversal, you can check out my video over here. Now let's focus on the pre-order traversal for now. So basically in pre-order traversal, first of all we visit the root node, then we visit its left subtree, and then we visit its right subtree, and we keep on doing that until the nodes exist. So let's see that for this given example, what is going to be the path that we are going to follow. So first of all, we are going to visit the root node. So in this case, the first node we are visiting is going to be node number 5. Then we are going to visit its left child. So left child in this case is 3. So again we are going to visit node number 3, and then again we are going to visit its left child, because remember it's root, left subtree, and right subtree. So left subtree still exists over here, so we are going to visit node number 1. Now left subtree does not, nothing more exist in the left subtree, so now we will start visiting the right subtree. So we now will visit the node number 7. Now after visiting the node number 7, now there is nothing exist over here, so again we are going to go back to the root, because we still have to visit its right subtree. So when we start visiting the right subtree, again we are going to follow the formula of root, left and right. So root node in this case is going to be 8. So now we are going to visit node number 8. After that we are going to visit node number 6, and then we are going to visit node number 9, which is the right subtree, and this is going to be the traversal path that we are going to take. Now let's see that what would be the in order traversal in the same manner. So again, as mentioned, the in order is also a DFS kind of traversal, but in this case the methodology we follow is that first of all we visit the left node, then we visit the root node, and then we visit the right node. So for this given example, what we are going to do is, first of all we are going to go to the left node all the way possible. So left node in this case is 1. So first node we are going to visit is going to be node number 1. Now for now we can't go left anywhere, so now we are going to visit its root node. So root node is in this case is going to be 3, and then we are going to visit its right node. So right node in this case is going to be 7. After doing that, after visiting all 3 nodes, now we don't have any more nodes to travel on the left subtree. So now we are going to visit the root node as mentioned over here, because we have already taken care of this left part. So now we are going to visit node number 5. Now again we still have values that we need to visit on the right subtree. So again we are going to take on the same initiative. So now the first thing we are going to visit is going to be the leftmost element for this right subtree. So leftmost element in this case is 6. So we are going to visit the node number 6 over here. After that we are going to visit the root node, which is 8, and then in the end we are going to visit the node 9 over here, which is this one. So this is how in order traversal works. So after understanding both the values and both the different traversal mechanism, let's see that what would be the optimal solution and how we are going to approach that. Okay, suppose this is the binary tree that we are given that we need to iterate over, and we are given the pre-order and in-order traversal for both of them. So in this case, the pre-order traversal for this tree is going to be, and the in-order traversal in this case is going to be. Now once we have both the values, let's see that what is the approach we are going to take. So if you closely observe both of these values for pre-order and in-order traversal, they both have something to offer. The thing they have to offer is that this pre-order allows us to determine that what the root of any section of the tree is, and this in-order allows us to determine that what is the left subtree and what is the right subtree of any given tree. How? Let me quickly show it to you. So if we see this pre-order traversal, the first value in this case is actually the root of the binary tree, which is 5 over here, which you can clearly see that the 5 is the root of the binary tree. So well, that is interesting information, but the thing is this alone is not helpful. If we see with this in order traversal for this 5, if we see the left side of this 5, there is only one entry over here, which is 3. And if we see in this tree, actually this 3 is the left subtree of this entire tree where the root is 5. Now if we see on the right side, the values are 6, 8 and 9, which is these 3 items, and this is actually the right subtree of this original given tree where the root value is 5. So now we actually have something meaningful that we can use. If we keep on repeating the same process, now for this pre-order traversal, again we see, okay, so the next value is 3. So 3 is already the left subtree. Now if we again break it from this in-order traversal, for this in-order traversal, we only have 3 value over here. We have nothing on the side, we have nothing on the right side, because the right side value is actually 5, which we have already identified that that is the root of this original value 3, which means we can determine over here that for this 3 it does not have any values on the left subchild and right subchild, because the very next value of this 3 is actually 5, which was already the root of this value 3. So now again we have some meaningful information. So far let's backtrack. The information we have found so far, that let me create an answer value over here, where we have already found that the first value is 5, the leftmost value or the first left value or left subchild of this value number 5 is actually 3, and for this 3 it does not have any more children. So now we can add the values null over here. Okay, now we are done iterating up until this point, but we still have some more nodes that we need to iterate over. So based on this pre-order traversal, now the next node we have is 8. So now we know that the current root we are iterating over is actually 8. Okay, so we have this value 8. Now from this in order traversal, we actually have these three values where this 8 is actually in the middle, because remember, this in order traversal allows us to determine that what is the left subtree and right subtree of any given root. So in this case, if the root is 8, then the left subtree is going to be the value 6 and the right subtree is going to be the value number 9. So we are going to use it to our advantage. Now for this value number 6, again we are going to try to see that what is on the left of 6 and right of 6, but in this case, since we don't have any more information for this value number 6, the left value is 5, which was the original root which we have already iterated over, and this next value is 8, which was the root of immediate root of this value number 6, which we have already iterated over. So now we can determine that for this 6 we don't have any other value, so which means that we have two null values. So again, now let's, and same thing we can determine for this 9 as well, that for this 9 the leftmost value is actually 8 and in the right there is nothing over here, which means this 9 also does not have any more children. So now let's again backtrack based on the information we have found so far. So now on the right side, the value we got was 8, that was the root we iterated over, and we found that information based on the pre-order traversal. After finding this 8, now we started iterating over the left and right children of this 8. So left children was 6, so we iterated the value 6. Now the 6 did not had any more children, so we had the values null over here. And now then we had the value number 9, and 9 also did not have any more children, so now again we had the two more null values over here. And this is the actual binary tree that we were able to create based on this original given pre-order traversal and in-order traversal, and that is the solution that your interviewer is expecting, and that is what is needed for this problem as well. Now there are actually two ways to do this problem. There is an iterative way and there is a recursive way. If you know me, I love the recursive solution, so I'm going to opt for the recursive solution. Basically what we are going to do is, initially we are going to find the root value, and then we are going to find the left subtree and right subtree. Now again we are going to pick one value, so we are going to pick the left subtree. So now even for the left subtree we will have a root value and its left child and right child, and again we are going to keep on repeating the same process, and we will be continuing to building our answer, and same thing we are going to repeat for our right subtree as well. So basically we are taking a bigger problem and then dividing it into a bunch of different smaller problems. I know this looks really messy, but you get the idea of what I'm trying to convey over here. And let's see the time and space complexity in this problem. So time complexity is actually going to be big O of n, where n is the number of nodes that are present inside any given tree, because we will have to iterate over both in order and pre-order traversal, and originally it's going to be 2n traversal. The thing is, generically we can write it to big O of n. If we see space complexity, well, space complexity is also going to be big O of n, because recursively we might have to iterate over all the nodes, and worst case scenario it could take big O of n space. This is a wonderful time and space complexity given that how complex this problem was, and based on the pre-order and in-order traversal we were actually able to build the solution for the binary tree. Now let's see the coding. So before we start coding, we will actually have to define that how we are going to use this pre-order and in-order array. Well, we are going to use this pre-order array to determine that what is the root value for any subsequent positions. And once we have the root value, we are actually going to use this in-order array to determine that what is the left subtree and right subtree for any given root. And once we have both the information, we are actually able to build our tree. Now the thing is, if you clearly understand that for this in-order array, we will have to look up at information much in much broader fashion than compared to this pre-order array. So what we can do is, in order to iterate over this in order array, rather than iterating it just by considering this to be an array, we are actually going to create a hash map where we are going, which is going to allow us to iterate over this in order array pretty fast. And so let me define two global variables over here. First of all, once we have these two information, now from our main method, first of all we will have to iterate over this in order array, and then we will have to populate this in order index map that we just created. So let me quickly run a for loop. Now we have our hash map ready to go. Now we will have to create a separate method where we are going to call the recursion. So first of all, let me create a new public method. So now I have created a new method called array to tree that returns a tree node, and as an input I'm taking the pre-order array, the left portion and right portion, and now we are going to create this recursive method. Now before I do that, I will also have to initialize the values for this pre-order index and also for this in-order index map, so that I'm going to do it. Okay, now back to our recursive method. So for recursion, first of all, we will have to create a terminating case, and the terminating case in this case is going to be that if the value of left is greater than the value of right, if that is the case, we break out immediately and we will return null. If that is not the case, first of all, we will have to define our root value, and root value we are going to define from our pre-order array. So our root value is actually going to be the whatever this pre-order index value that we have, and then we are also going to increment the value of this pre-order index as well. So this is the root value, and after that we are going to increment the value of pre-order index. Now since we have our root value, we are actually going to create a new tree node called root, and for this root node we are going to assign the value that we received over here. Originally, the value of this pre-order index is 0, which means that the first value we are getting from this pre-order is the main root of the tree. Once we get that value, we will have to create the left subtree and right subtree. So we will have to call this array to tree method again, and we are going to populate the value for left and right child. So for the left child, we are again going to call this array to tree method. Inside the input, first of all, we are going to provide this pre-order array as we found as it is. Now for the left subtree, we are going to keep the value same for the left value, but for the right portion, the value is actually going to be different, and that is going to be different based on whatever this root value we had. So in this case, for the first value for this pre-order array, the root value is actually 3. So now for the left part, we already have the value, but for the right part, we are going to have to provide all the values that are present after this root node. So we are going to do that. So for that, now our in order index map is very helpful. Now we have both the information ready to us. Now we are going to call the right subtree in the same manner, but in this portion we are going to treat whatever the right variable we had already, but now we are going to change the left variable. So for the left variable, we are actually going to use whatever the value we had for the root value, and we are going to do it +1, and as the right limit, we are going to keep whatever the right limit we originally had. And after this recursion ends and after this function ends, we simply need to return the root variable. Okay, so now our recursive method is ready to go. Now all we will have to do is, from our main method, we will have to call this recursive method that we just created. That should be it. So we are calling this pre-order method, but we are providing the pre-order array, and as the left position we are providing the value 0, as the rightmost position we are providing the value of whatever the pre-order length is -1, and that should do the trick. Now let's try to run this code. It seems like our solution is working as expected. Let's submit this code. And our code is pretty efficient compared to a lot of other solutions. I would be posting this in the comments so you can check it out from there. So today we are going to do serialize and deserialize binary tree LeetCode problem. And if we see some of the companies where I want to get a job who already asked this question, there are companies like Amazon, Microsoft, LinkedIn, Uber, Google, Facebook, DoorDash, TikTok, Apple, Snapchat, Splunk, and Goldman Sachs. So that's why I'm paying my utmost attention. I hope you also enjoy the video. Hello friends, the reason I have not been uploading in recent days is because I just had twin baby girls, and so yeah, that's the update. And now let's move on to the video. So LeetCode thinks that this is actually a hard problem, but in my opinion, this is not a hard problem. It's actually a very creative problem. Basically, we need to serialize and deserialize the given binary tree. Now, first we'll have to understand that what does serialize and deserialize means. Well, serialization is the process of converting the given data structure, which is tree in this case, and we need to convert that into a sequence of bits so that it can be stored in some memory or file buffer, and then we can transmit it across any network. Now in this problem, basically we need to design an algorithm where we are actually serializing and deserializing a binary tree. So serializing means that first of all we are finding a way to convert the given binary tree in some sort of bits, and in this case we are told that we need to convert it in strings, so we are familiar with that. And then deserialize means that we are given this string and we need to write an algorithm to convert this string back to a binary tree. So we'll have to do both the things. And if you see this problem? This is actually very similar problem that we did earlier with strings. This is the solution of that problem, so go and check it out first. We are also given a clarification that we can be as creative as we can with the serialization and deserialization process. So we can have different way of serializing the tree and different way of deserializing the tree, as long as we maintain the tree data structure. So let's see that what is the approach I am suggesting, and you can also come up with your own creative approach. Well, basically in this problem, we are only given the root of a tree, and then somehow we will have to go over the entire tree and then traverse it, convert this given root and all of the entire tree into a string. And after we have converted it to string, we will have to find a way that, suppose if we are given the string as the input, how can we convert from the string this binary tree as well? So we are doing both the processes. So the important thing in this case is that we will have to traverse over the given binary tree. There are mainly two strategies to traverse over the given binary tree, DFS and BFS, and I have explained this very carefully in the previous video. You can check it out over here. So basically in this video, what I'm suggesting is that we actually go with pre-order approach with using DFS to serialize and deserialize this given binary tree, and I would be showing you that what is the process we are following. So first of all, we are going to serialize this given tree, which means we are going to take this binary tree and we are going to convert it to a string. Now, as mentioned earlier, we are going to use the pre-order traversal for that. So if you are not familiar with the pre-order traversal, basically we visit the root node first, then we visit the left child of this root node, and then we visit the right child of this root node. And that is how we are going to end up creating the string from this given binary tree. So let's see that in action. So first of all, let's create a variable called s or string where we are going to store the string value. So first of all, we are going to visit the root node. The root node in this case is 1. So we are going to add an entry called 1 over here. Now we need to visit the left child of this root, and then we need to visit the right child of this root. Now remember, this is actually a DFS policy. So in the DFS, we go in the depth first. So first of all, we are going to visit the left child. So left child in this case is 2. So we are going to add an entry that 2 is the left child over here. And then again for this 2, because we still have left child left, so we are going to visit that. So for this 2, the left child in this case is actually 4. Now for this 4, we don't have any more left child and we don't have any more right child, which means that first we try to visit the left child. For this 4, there is no left child, so we enter a value called null over here. And then for this 4, again there is no right child, so again we add value null over here, saying that for this 4, the two left child and right child is actually a null value. Now after that, we still have nodes left that we haven't visited. So now for this node 2, we have this node 5 and it's right. So again we are going to enter the value 5 over here. After entering the value 5, we are again going to check the left child and right child for this 5. So left child in this case is null, and again right child is also null. So we will add 2 more entries, null, null again. And now we go back. So now we have visited all of these nodes, but the thing is we haven't visited the right portion of this original root node. So again we will have to iterate over the right subtree. So right subtree in this case is going to be 3. So we add 3 over here. Now for this 3, again we don't have any more children nodes, so again we add 2 null values. So this is the answer in this case that we have to return for this given tree, that this is the string value that represents this given binary tree. Now let's see that what would be the deserialization process. So now we are going to work upon the deserialization. So basically we are going to convert string into binary tree. So the idea is this is the string we generated from the serialization process. Now again because we are using pre-order traversal, we are actually going to apply the same logic. So we are going to treat the first node to be the root node, then the next node would be the left subchild of this root node, and the next node is going to be the right subchild of this root node, and we are going to keep on iterating this process in reverse order. So the idea is that first of all, okay, we identify this node. So this node is actually our root node. Okay, so root node is actually 1 in this case. Now again this 2 is actually the left child of this root node. So because this left child exists, the next node is again going to be the left child of this node 2. So again we are going to create a node 4 that is left child of this node. Now for this 4, the next 2 nodes are actually null. So because we encounter 2 null values, which means this 4 does not have any more children, so we can just ignore that. Okay, now we still have a node 5, which means that this 5 is actually the right child of this 2, because we have already visited the left subtree of this 2. So now because we are done with the left subtree, now we are visiting the right subtree. So we are going to create one more entry 5 over here as the right subtree. Again, we have two more null values, which means that this right subtree is done. Now we don't have any more values. Okay, now we still have values, which means that this actually refers to a root node where we haven't visited the left and right subtree. Because remember that this is the left subtree we have visited for this 2, and this is the right subtree we have visited for this 2, but we haven't visited the right subtree for this original one. So now we are going to do that. So now we are going to add one more entry 3 over here, which is the right subtree of this original given one, and this 3 actually has null values, which means 3 does not have any more children. So we won't be adding any more entries over here, and we can just ignore that. Now we have reached the end of the string. So because we have reached the end of the string, we have created the binary tree that we are supposed to create, and we have completed the deserialization process, and we have converted this string into the binary tree. So this is the approach we are going to take. If we see the time and space complexity in this case, for the serialization process, the time complexity is actually going to be big O of n, because we have to iterate over n characters that are present, and the space complexity is also going to be big O of n, because we will have to create a string where we are storing all the n values. Now for the deserialization process, again the time and space complexity remains the same. Now we will have to create two methods for serialize and deserialization. So first of all, we are going to work upon serialize process. So I'm actually going to create a new public method that returns a string where recursively we can apply the pre-order traversal. And as an input, it is going to take the root value, and we are also going to pass the string value. Now inside this recursive function, first of all, we are going to find the terminating case. So if the given root is equal to null, then simply add the value to the string as null. If that is not the case, which means that root still has some value and it could have left subtree and right subtree. So now we are going to call the recursive function. So first of all, we are going to add the value to our string. Now we are going to call the left subtree and right subtree. So we are again going to call this recursive serialize method. Again, we are going to repeat the same process for the right subtree. Once this ends, we are simply going to return the string. Now from our main serialize method, all we have to do is just call this recursive serialize method and return whatever the answer we get. We are going to pass in root as an entry, and we are going to pass in an empty string. So now we are done with our serialize method. Now let's work upon deserializing method. Now again, for the deserializing process, first of all, we will have to create a recursive method to iterate over this given string data, and then we are going to convert all the string values into binary tree. So we are passing a list of strings in this case for this recursive deserialize method. And now first of all, we are going to work upon the terminating case. If the given node is null, we can simply remove the value, and then we can return null. Okay, if that is not the case, first of all, we are going to note the whatever the value of this current string is, we are going to treat it as a root node, and then we are going to call the left subtree and right subtree. So we are going to create a new tree node called root. So whatever the current value of this string is, we are going to treat it as a root node. Then after adding the root node, we are actually going to remove that value. Okay, now for the left value, we are again going to call this recursive deserialize method, and that should be it. After this ends, basically we should have a root variable, so we can simply return root. Now from this main method, first of all, we will have to create an array of string where we are actually splitting the string based on the comma that we initially created. After doing this, we are actually going to convert the string array into a list of strings. Now we will simply return whatever the answer we get by calling this recursive method. That should be it. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. So I will be trying to see other faster approaches and see I can make a future video on that. But so far you can find this code in the comments, so you can check it out from there. Hello friends, we are not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do binary tree maximum path sum lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, DoorDash, Facebook, Microsoft, Google, ByteDance, TikTok, Snapchat, Twitter, Apple, Uber, and LinkedIn. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So despite being a hard problem, this is a very well liked problem on LeetCode. Basically, we are given the root of a binary tree and we need to return the maximum path sum for that particular non-empty path. So we will have to understand a couple of terminologies over here. We'll have to understand that what a path sum is, and before we understand that, we will have to understand that what a path is. Lucky for us, we are given definition of both of them. So a path is a binary tree sequence of nodes where each pair of adjacent nodes in that particular sequence has an edge connecting them, and we are also told one very important thing, that any single node in that sequence can at most appear once. We are also given the note that it is not necessary that path has to go through the root of the node. Okay, so over here I have drawn a couple of different trees and I'm going to show you some examples of what a valid path is and what an invalid path is. So first of all, this is a valid path. And for that we'll have to understand that why this path is a valid path, because all the three nodes that are connected in this particular path, they are adjacent to each other. They all have an edge connecting to them and they all appear at most once and nothing more than that. Now this is also a valid path and this is also a valid path. This is also a valid path and this is also a valid path. Both paths are valid as well. And the path that looks like this is also a valid path, and the path that looks like this is also a valid path. Now let's see some examples of an invalid path. Suppose I start my journey over here. I go up, I go down, I go to the left child, and then again I try to go to the right child. Again, this is an example of an invalid path because this node appears twice as well. Now we know many examples that what a valid path is. Now let's see that what the problem is actually asking us to solve. After understanding the definition of a path, we are going to understand the definition of a path sum. Basically, it is the sum of all the nodes that are present inside this given path. So that is actually quite simple to understand, and the problem is actually asking us to find the maximum path sum that we can make out of given binary tree. So now I have drawn three different trees to understand the maximum path sum for each one of them. So first of all, for this particular tree, the maximum path sum is going to be this path. And why? Because all the nodes are positive, and if we take the sum of these three nodes, it's actually going to be 5 plus 4 plus 9, which becomes 18. And this is what we need to return in the answer. If we take the second example, things are not as easy as the first one. Why? Because we are dealing with a negative value over here. So in this case, even if we try to do the same path that we had drawn over here, this won't work because the sum of this is actually going to be, which is not the most optimal path we can achieve. The most optimal path in this case is going to be this one, and the sum is actually going to be 5 plus 4 equals to 9. And in this case, we will have to return 9. So in this case, the maximum path actually is going to be this one between these three nodes. Why? Though there is a positive value over here, if we were to include this positive value, the path we would make would looks like this, and that would actually go through this root value which has the value of negative 11, which actually brings the total path down or total sum down. So that is why it is not in our best interest to include this node, and that is why the maximum path in this case we can achieve is amongst these three nodes, where the sum is actually going to be 10 plus 8 plus 2 equals to 20, and that is what we need to return. Now before we come up with the optimal solution, I'm going to show you a few different concepts with various examples. So first of all, we have an example of tree that looks like this, where in this case all the nodes are positive, which means things are a little bit easy for us, and our aim is to find the maximum product sum we can achieve, right? So the idea is at any given portion we have the root information. Now from this root information, what we are going to do is we are going to see that what this left subtree has to offer and what this right subtree has to offer, and then addition of all of them should give us our maximum product sum. So in this case, this left subtree does not have any more children. It only has one node, which means it can, the maximum value it can contribute towards the maximum path sum is going to be 5. So we have the value 3 already from this root. Then we gain this 5 from the maximum path sum, and then again we gain this 2 from this right subtree. So the total maximum path sum we can achieve is going to be 10, which is the answer in this case. And since all nodes were positive, it is in our favor to include all the nodes. So that is one way to do it, right? And this is a very simple example, so we are able to understand it quickly. Now let's try to see that what would be the approach in a little bit more difficult scenario. So suppose we are given a tree like this. In this case, we actually have a negative value. So if we apply the same logic over here, this left subchild has minus 5 to offer, this right subchild has plus 2 to offer, and this root value is actually 3. So maximum path sum based on the previous logic would actually become 0 if we just do sum of all the values. But that is not what we are going to do. We are also going to check at any given moment that whether the value that is being contributed, if that is less than 0 or not. If that is less than 0, immediately we are going to discard this value, which means that we are not going to consider this -5 to be part of this maximum product sum. And in this case, what we are going to do is we are going to do this 3 plus 2, because both values are positive. So in this case, the answer we are going to get is 5. So we gain one more important thing, that whenever we see minus values, we are going to ignore that from our maximum production because they don't add any more value over here. Now one more thing we need to consider. What if we have multiple nodes, and then what should be our approach in that case? Okay, suppose we are given an example like this. In this case, what should be our approach? Well, we want to find the maximum path sum. So again, we are going to repeat the same process. We are going to see that for this root node, what is this left subtree has to offer? It has to offer maximum 5 value. So we are good up until this point. For this right subtree, actually we will have to calculate that what is the maximum value it can offer. And how we can do it? We are actually going to take this root value, because that is going to be the part of this right subtree for sure. So we already have value as 8 over here. Now from this 8, we actually have two options to be included for our maximum path sum. We can either do 8-2 or we can do 8-1. So in this case, obvious choice is going to be 2, because this value 2 is actually greater than with this value 1. So in this case, we are going to ignore this 1 and we are going to keep this 2, which means that we can do 8 plus 2 to be 10. So in this case, we can determine that this actually has the value 10 to give towards maximum path sum. Now the question will come to your mind is that why in this case we only choose value 10 and why not we chose value 11? Well, what if under what circumstances can this value become 11? It can become 11 if we include all these three values to be part of this maximum path sum. But we already know that this goes through the root value, which means that if we were to include all these three values to make the value 11, it won't work, because then the path would look like this. It would go from 5 to 3. Okay, so far we are good. Then again through 8. Now from this 8, we cannot include both 1 and 2, because suppose we try to do it, we include this 1 and then we try to go back to 2, we come up at this 8 again, and we know that that cannot be part of a path sum. So that is why we only have the option to choose either 1 or 2. So that is the important detail over here. That is why for when we were calculating the maximum contribution this right subtree can make, we only had two options. Either we could do 8 plus 2 or we could do 8 plus 1, but not both of them. So just remember that is why I showed you this example. So in this case, the maximum contribution we can get from this right subtree is going to be 10. So now let's calculate the maximum path sum in this case. So the maximum path sum is going to be the root node is 3 plus this left subtree can contribute value 5 and plus this right subtree can contribute value 10. So the answer is going to be 18, and this is what we need to return in this case. So far we have understood, we had gained very good understanding of many different cases. Now let's consider one more case where the things become a little bit more interesting. And why it becomes interesting? Because so far we are under the impression that we have to take this root value as part of the answer. But what if that is not the case? What if we encounter some possibility where this root value does not need to be part of the main maximum path sum that we take? Then how do we approach that? So let me quickly show you an example for that as well. Okay, this is the last complicated example. Now in this case, we are again going to apply the same logic to find the maximum path sum, but we are going to do some interesting things. So first of all, we have this root value to be -3, right? Now we are going to see that what is the leftmost contribution it can get. It can get 3 as the contribution in this case. Now again, for this portion, we are going to see that what is the rightmost contribution it can get. The rightmost contribution it can get in this case is going to be this 8 plus 2. So 8 plus 2 is going to be 10 so far, right? Now if we see over here, actually this is not the most optimal way to approach this. Why? Because this path actually gives us the maximum path sum. So let's see that how can we actually determine that. Well, when we are traversing, we are actually going to have a variable called path, to keep track of what is the current maximum value we have found so far and whether do we need to include a new root. And new root in this case is going to be the condition where we actually refrain away or move away from the original root we were using, because if we were to use this root node, there is no way for us to use all of these three nodes. So that's why what we are going to do is we are first of all going to see that if we use this current root, what is the maximum value we are gaining. So the maximum value we are gaining in this case is going to be 3, which is this one, plus 10, which is the contribution we can get from this right subtree. So 3 plus 10, and let me get rid of this maximum path sum for now. So 3 plus 10 plus whatever the root value. So root value in this case is minus 3, which is in this case the total value is going to be 10. But now when we are traversing or when we were calculating the maximum contribution we can gain from this right subtree where the root node is actually 8, the value maximum we can gain from over here is actually going to be this value 8 plus it has its left subtree is contributing value 1 and its right subtree is contributing value 2, so which both are positive values, and their total is actually 11. So this is 11 and this is 10. Then why are we so keen to keeping this root to be part of the optimal solution? We should not put it in the maximum path sum, and this is exactly what we are going to do. Then we are going to choose a new path, and this new path, the value is 11. So then we are going to have a maximum path sum variable where we are going to keep on updating the value, and we are going to update the value to be 11. And now it does not have any further no more nodes to check for, and then we are going to return this 11 to be the answer. And at any given moment, whenever we find that the new path we are getting that gives us better answer than whatever the previous answer we were getting, then we would update the new path and we will update the value of the path variable. So that is one tricky part that we have to understand in this question. And now let's see that after understanding all the concepts, now let's see that what would be the way to solve this problem. The idea is let me clean this up a bit. Now I'm going to use the same example to quickly walk through this problem. So first of all, we are at this root position. What is the left contribution we can get, which is 2. The right contribution we can get, in this case it's going to be 10. We actually calculated all of them. Now the sum of these these three is actually going to be 10 only, but when we were calculating that, we had this path variable where we actually calculated the value of this to be 11 and we updated this path variable. And then we are going to have this maximum path value where we are going to keep track of the maximum path we have found so far, and in the end, because it does not have any more children, we are going to return the maximum path to be 11, and this is what the answer we need to return. So basically we are taking a bigger problem and then we are dividing it into bunch of different parts. That for this root we are actually trying to calculate this left subtree and right subtree. Then again for this root value we are again calculating this left subtree and right subtree, which means we are solving this problem recursively, and that is how we are going to approach it. And also let me show you the time and space complexity. So time complexity in this case is actually going to be big O of n. Why big O of n? Because at any given moment we will have to iterate over all the nodes that are present inside this given tree, and the space complexity is going to be big O of h, where h is the height of the tree. So first of all, we will need a separate method called max gain to calculate that what is the maximum value we are gaining. So for that, we are going to create a new method that takes in a node as an argument. We will also need a maximum sum value. So we are going to initialize it as global variable. We are going to assign it to the most negative value possible. So okay, now let's start implementing our max gain function. So first of all, we are going to have the terminating case that if the given node is equal to null, we will return 0. If that is not the case, we will need the values of left gain and right gain for any given tree node. So we are again going to call the recursive function for that. We are going to create a variable called price new path that we are actually going to calculate by using the node value plus whatever the sum of left gain and right gain is. Now that is done, we are actually going to calculate the max sum. We are going to compare it with whatever this new path we are calculating. And once that is done, basically all we will have to do is simply return the node value with whatever the maximum value is amongst this left gain or right gain. from this max path sum method, we will have to call this max gain function. So let's do that. After all the calculation, we are simply going to return whatever the max sum we are able to achieve. Okay, and now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our solution is actually pretty efficient and faster than a lot of other solutions. And I would be posting this in the comments so you can check it out from there. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today actually we are going to learn about a new data structure, and we are actually going to learn to implement a trie or a prefix tree. And if we see some of the companies where I want to get a job, who already asked this question, there are companies like Amazon, Google, Twitter, Microsoft, Oracle, Apple, Facebook, Goldman Sachs, Uber and Bloomberg. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are going to implement a trie over here or a prefix tree. So first of all, in the problem statement, we are given the definition that what a trie is. And actually I'm going to show you very eloquently that what a trie is and how it works. But let's understand the definition first. Basically, a trie is a prefix tree, which is a tree data structure that is used to efficiently store and retrieve keys in a data set of strings. There are a bunch of different applications of this trie data structure, and I'm going to go over all the applications soon as well. Now, if we see that what is needed in this problem, basically we need to initialize a trie object first of all. Then we need to create three different methods which are mentioned over here. So first method is the insert method, which does not return anything, and basically we are only given the input as a string word, and we need to insert this word inside this new trie object that we are initializing. After doing that, we could be given a search method where again as an input we are given a string called word, and we need to return true or false, which means that whether if this word exists inside this trie object that we have created, we need to return true, otherwise we need to return false. And there is also one more method where again we are returning true or false, and the name of method is starts with, where we are actually given a string and the name of the string is prefix. But basically we need to check that whether this prefix actually exists as a part of any existing word inside this trie object, and if that is the case, we need to return true. If that is not the case, we need to return false. So here is an example that we are given. So suppose we are given as an input where actually first of all we are creating the trie, we are inserting some word, we are searching for some words, we are doing the start with operation, and this is the explanation. So basically we initialize the trie object as mentioned. Then first of all we insert the word apple. So okay, so currently apple exists over here. Now again we search for that whether apple exists or not, and because it exists we return true as the answer. Again we search for with the word app. But the thing is, remember, so far we have only inserted the word apple. App does not exist as a whole word, so that's why we return false. Again we search for starts with method for this word app, and remember, because this app is actually a prefix of this apple, so we return true in this case, and so on and so forth. We can do bunch of different operations. So this is what is needed. Now let's understand what a trie is. Okay, so first of all, let's try to understand that what a trie actually is. Basically, a trie is a tree-like data structure, but it's a little bit different and a different variant of a tree. Now, if we know for any single tree, the basic properties are that every single tree has a root node. Now, this root node has some subsequent children nodes. There could be n number of different children, and those children can have some children of their own, and their links actually found some meaningful relationship. So that is what we are going to use to generate this trie, but we are actually going to generate this trie to store different string values per character. That is the important property, per character. So it makes us easier to understand or find different words or different strings, and there are a number of applications of a trie. Let's try to understand trie with some example. So first of all, as any different tree, we are actually going to have a root node, right? Now suppose for this root node, what we are trying to do is we are trying to add some different string value. So let's take a string value. Suppose the first string we are trying to add is actually the word FAANG. So if we take this word FAANG, first of all we will have to add the word f, because remember I already told you we are going to do it character by character. Then we will add a, n and g. We are going to add it in this sequence. So in order to do that, logically speaking, for this root is going to remain common. The thing is, first word we will have to add is fan. But the thing is, first we will check that whether is there any children of this root node which is actually f. If that is the case, we are actually going to leverage that. But this does not have any children. So if this does not have any children, we are actually going to create a new children f. Now again, with this f, there is no children, that is a. So again we are going to create a new children, then again we are going to create a new children, and then we are going to add the values of n and g as well. After adding this, we have actually created a root inside this trie data structure which represents this word FAANG that we were originally trying to create. After creating that, we will have to find some way to identify that this FAANG word has actually ended. So what we are going to do is we are actually going to create a special character or a special node over here which we are going to denote as an end node, which defines that the word has actually ended over here, right? After doing that, let's try to add one more word. So suppose rather than FAANG, we are trying to add the character mang. So let's try to again add mang over here. Now for this mang, first of all we are going to check that whether this m exists as one of the children of this root node. So m is also no children, so first of all we are going to add m, and then we are going to add subsequent characters, and we are going to link them with this path. After that, in the end, we are actually going to add a special character and denote that the word has actually ended over here. So let's do a quick recap. Basically what we have done so far is we have actually created two separate branches where if we go depth first search diving in those branches, we would actually find those subsequent words in those particular branches. So it makes pretty efficient for us to identify any string and to see that whether it exists or not and predict that what the person is going to copy. Now suppose I'm trying to add the next word fan. Now for the adding this next word fan, what we are going to do is first of all we are going to check f exists or not. So f exists over here. So because f exists, we are actually going to leverage that. So now we are not going to add any entry over here. Again, this a also exists as one of the children of f. So again, we are not going to add any entry over here. Now this n. So n is not a children of this original a. So we are actually going to create an entry over here. So we will create an entry over here. And we are actually going to name it as n. And now since this word ends over here, we are actually going to create this end node over here. So again, remember, if we go depth first search in this direction, we will actually be able to find this word fan, and that is the whole purpose of a trie. Now let's try to add one more word which is man. Sorry, maa, ma. So if we try to add this word ma, so first m also exists over here, a also exists, and a also exists. So because these three exist, we are actually not going to break this link and create this end word over here, or we are not going to do that. Actually, we are going to keep this as it is, because this maa is actually a prefix of this original word mang that we have already added to our trie, and that is why a trie is also called a prefix tree. So now the word makes sense that why a trie is called a prefix tree. And basically this is what we are trying to implement. There are a bunch of different applications of a trie, and let's see some of the applications that are really cool in real life world. So before we start implementing the method, first of all, let's understand that what are different applications of a trie. So applications like autocomplete, where you type something and it automatically gets completed or understood by that particular product, that is implemented using trie. So features like Google Chrome, Amazon, where you type few words and then it automatically understands that what you are trying to do and automatically gives you the answer, that is implemented using that. All the spell checks or all the dictionary related mechanisms, they are also implemented using some versioning of a trie. Games like word search, word puzzle, wordle, they are also implemented using a versioning of a trie. And features like predictive text search or expected text search, that you type something, it automatically expects that what could be the next potential words. You see that in YouTube, Google all the time. They are also implemented using tries. So these are only few but very powerful applications of a trie, and there are hundreds of them. I haven't mentioned them. So that's why trie is important to understand. Now let's move back to our question and start implementing those three methods. So first method they are asking us to implement is an insert method, where we are not returning anything, but we are inserting different strings into our trie. So for this example, we are actually going to implement these 4 different types of strings into our trie, and we will see that what would be the logic behind it. Now, as mentioned earlier, that every trie actually has a root node. So again, with our trie, we are also going to have a root node. Now from this root node, the idea we are going to use is that whatever string we are trying to insert, first of all, we will check that whether the first word that we are trying to implement or the first character we are trying to implement, if that is present as one of the children of the existing root node or not. If it is children of that particular root node, we would keep on branching for that particular child and keep on updating the number of characters that we are trying to implement. If it does not exist, we will actually create a new node or a new branch, and we will add that entire word into that branch. Now, as mentioned earlier, the moment we reach to the end of that particular node, we will actually have to create an end node to denote that this word actually ends over here. So let's start implementing what is being asked over here. So first we are trying to implement the word apple. So A does not exist as any of the children of this root node. Currently it has no children, so we will have to create a new node. So first we are going to create a new node for apple. Okay, so let me create a new node A, and then I will keep on appending all the remaining characters. And after adding all the word, because this word ends at this E, I am actually going to create a special node, and I am going to denote it as an end node. So that is for us to understand that this word actually ends over here and we don't need to move any further. Okay, now next word we are trying to implement is G. And also remember one thing, I forgot to tell you that this root can have potential 26 different children, right? And this 26 different children can have 26 different children of their own. So the mechanism we are going to implement to find that whether a node contains any particular children or not is actually going to be used based on some key value mechanism. And because it's a key value mechanism, the whole operation of searching that whether any node or anything, if that is part of any children of that particular node or not, that is being done in constant time, so that it helps us understand, helps us to maintain the consistency and speed of our data structure. Now let's move back to adding the word Google to our trie. So for the word Google, we do not have any children that is starts with G. So we are also going to create a new node over here or new branch over here where first character is G, and then we will add all the remaining characters. As previously mentioned, at the end of the word we are going to create an end node. Okay, now things become a little bit interesting with this word Amazon. So for this word Amazon, when we start checking that whether this A is a children of this root node or not, we find that A is already a children. So we will keep on updating the value over here that okay, we have already find a word or a character that is already a children, and then we will keep on moving to the next character. So first this A is already present, so we ignore that. Now next character we want to find is M. So for this M, we will try to see that whether this A contains any children that starts with M. But the thing is, currently this A only contains one children that starts with P and not M. So we will have to create a new branch over here. So let's create a new branch. So new branch starts with M, and then we will add all the remaining word characters over here. Okay, and now the next word we are trying to implement is amazing. For the amazing, okay, we already have a children of this root that starts with A, so we have taken care of this. M is also present as one of the children. Okay, now A is also present as one of the children of this M. Okay, so that is also good. Now this Z is also present over here. Now for this I is actually not present as one of the children of this Z. So we will actually create a new branch over here that starts with I, and then we will add this N and G over here, and in the end we will create, or we will add the end node over here. And now we have actually inserted these 4 characters as these 4 strings into our trie. And if you see, we can find each one of them by going in DFS motion in any particular branch. So first of all, this gives us the value Google, this gives us Apple, this gives us amazing, Amazon, and this gives us amazing. So that is how tries typically work. Now let's move on to the next method that is being asked. So for this search method for our trie, we will be actually given a word as the input, and we will have to check that if that word exists inside our given trie, we will have to return true. If it does not exist, we will have to return false. So let's start implementing the same method, and actually we are going to use the same trie that we have created. Okay, so let's use the same trie that we have created earlier, and we will try to see that whether these 4 strings do they exist inside this given trie or not. So let's understand the logic behind it. Well, if the string exists, basically all we will have to do is, first of all, we will check that, okay, whether the first character, if that is the one of the children of this root node or not. If that is the children, we would keep on checking its children for this next subsequent words and try to complete this entire word. If we are able to complete this entire word without this try breaking or not able to find the children, if we reach to the end, we can conclude that this word exists. If we cannot come to the end, we will conclude that this node does not exist. So first of all, let's try to see in this example. So for the first word is A. So A exists over here as one of the children. So we will ignore this one. Now next word is M. M also exists, so we will again ignore this one. The next one is A, again this word exists. Now Z, I, N, G, they all exist in this particular fashion. So this word amazing exists inside this given try. So because it exists, we will return true as the answer in this case, right? Now let's try to search for this word good. Now for this word good, the first character is G. So first character is G present over here. So okay, we are good up until this point. Next character is O. O is also present. Again, O is also present. So we can ignore first three characters of this good. Now for this next O, we do not have a children that starts with value D. So because of that, we do not have any new branch over here that starts with D. So we can actually conclude that the word good does not exist in this case, and because it does not exist, we will return false over here. Okay, now let's try to search for the word Googler. So again, for this word Googler, okay, G also exists, O exists, O exists, G exists, L exists, and E exists. Okay, up until this point, all the words exist. But when we try to search for the next word, we actually encounter that, okay, this is the end node of our try or of our DFS search for this particular direction. So because it is the end word, we will actually return false over here, because this word has not been completely searched, because it does not exist inside our try, and we are actually able to do it pretty quickly and pretty efficiently. Okay, so now next word is app. So let's try to see that whether this word app exists inside our try or not. So first of all, we check for this word A. A exists over here. Then this word P. P also exists and P also exists, right? So we are good up until this point, and our mind will say that, okay, because this word exists, we need to return true. But the thing is, that is not the case. The idea we are trying to do in this search method is that we are trying to see that whether the whole word that is given as the input exists as only a word inside this given try. But for this app, if we try to see the next node is actually the SL and E. So there are still some characters that exist inside this given DFS path that we are traversing, and the next node is actually not the end node. So because the next node is not the end node and there are still some more nodes that exist, this app is actually a prefix of original word apple, but not the whole word as it is. So that's why in this case we need to return false as well. And this is the important thing that is differentiating between this method, search method, and the next method we are going to implement. Now if we see the time and space complexity, in this case the time complexity for this method is actually going to be big O of n, where n is the number of characters that are present that we are trying to search in any given word. If we see space complexity, for the space complexity we are actually not using any additional space, so that is going to be the constant space complexity for this case, which is pretty efficient in my opinion. So now let's understand our starts with method, and we are also going to use the same try that we have created before, right? And we are going to see that whether the words that starts with these characters, are they present inside our given try or not. So again, this is very similar to the search method, where we are going to iterate over word by word or character by character for any given word, and we will see that whether that is present inside our try or not. If that is present, we can return true. If that is not present, we will return false. So let's see that in action. So first of all, we have this character A. So A is already one of the children of this root node. So okay, we are good up until this point. Then we have M. M is also a children over here, and then we have A. So A is also a children of this one. So we can conclude that because this word ended, we do not have any more things to search for, and all of the characters, they were present inside this given try. We would actually return true. In this case, they are saying that the word that starts with AMA is actually present as one of the children or one of the branches of this try. Now let's try to search for this word APK. So A exists and P exists, but thing is, for this P we do not have any children that starts with K. So because of that, this K is not present. We can actually return false in this case, saying that we do not have a word that starts with APK as the prefix, inside our trie. And remember, because we are searching through prefix, that is why this is also called prefix tree. So yeah, mind blown, right? Mine as well. Now let's try to search the word good. Well, there is Google, but there is not good. But the thing is, Google is pretty good. Yeah, so that's why it's one of my dream companies. But let's try to search that. So okay, this is GOO. So GOO is present over here, but this D is not present as one of the children of this O. So because of that, we will also return false in this case. Okay, now we have this word apple. So apple is actually the entire word that is present over here. And if you look at it, we do have a word that starts with the word apple, even though it ends at apple, but the thing is also it starts with apple, right? So and the name of the method is actually starts with, so why should not we return true in this case? So this will also become true, that okay, word that starts with apple is present inside our given trie, and that is the logic we are going to use to implement the starts with method. Again, very similar to the search method, just a little bit different variations. Now if we try to see the time and space complexity, in this case the time complexity is also going to be big O of n, that is where n is the number of characters that are presented inside any word that we are trying to search. If we see space complexity, the space complexity is also going to be big O of 1, or constant space complexity, because we are not storing anything in our text stack. This problem is asking us to implement insert, search, and starts with method. But before implementing these three methods, first of all, we'll have to define that what a trie node is. This is only a trie class. So I would be creating a separate class called trie node. Now in this trie node class, first of all, let's go over some basic methods that we are going to use that will enable us to do a lot of things. First of all, we have defined a finite number of cases R, which is 26, because any single node can only have up to 26 distinct children, because each children represents a character inside the alphabet. Now every single trie node has a certain set of links, and links are defined by the children of that particular node. We also created some more methods, so let's go over them. So one method is contains key method, where we pass in a character and we get the answer that whether any particular link or any particular node does that contain that particular character as one of its children or not. And we can get the answer in a constant time complexity, because remember, we are using array indexing, and the maximum possibility of indexing can be 26, and we can get the answer immediately. Same, we have a method get, where we provide the character and we get the answer that whatever the value of that particular character is inside any of the children of any trie node. We also have a method put, where we provide the value of a character and the node we are trying to put it as. And we also have set end and is end method, that is to define that whenever we run out of words that we need to put in any single trie block or any single trie branch, the last node is going to be is end node, and we will mark its value to be true. So now let's start implementing the trie node. So first of all, we will have to create a trie node root. So let's do that. Now since we have our root node, first of all, for this public trie method, we are going to initialize the root. After doing that, first of all, let's start working on our insert method. So for our insert method, we are going to have a root node. Now we are going to iterate over the given input word. We will define that what is the current character we are at. Now first of all, we will have to check that whether the given node we have, if that contains that particular key or not. So if the given node does not contain that key, we will actually have to create a new entry over here. So we will use our node.put method, and inside that we are going to pass in the value of the current character, and we are going to pass in the we are going to create a new trie node for that, and then we are going to update the node's value. And once this loop ends, basically the last node we are at, we will have to set its value to be the end node. So we are going to mark its value to be the set end value, and which would basically, so it defines that this is the last node. Before we work on the search and starts with method, remember, both search and starts with method, they are pretty similar to each other. So we are actually going to create a supporting method called search prefix. Once again, we are going to initialize the node to be the root node, and now we are going to iterate over the given word. So now we are going to check that if the current node, does it contains the given character or not. If it contains the given character, we can actually set the value of node. If it is not present, we simply need to return null, and that's it. And if we somehow reach to the end of this loop, we can simply return whatever the node we are at. Now from this our search method, basically what we are going to do is, first of all, we are going to initialize our try node and we are going to pass in the value of the word. Now we simply have to return that whether the current node we get in the return, and if it is not null and it is end, we can simply return true. And same thing we are going to do for our starts with method. So again, for our starts with method, we are again going to call the search prefix method, and basically all we will have to check that whatever the return value we get, if that is not equal to null, if that is not equal to null, we can simply return true, and that should be it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently compared to a lot of other solutions, and it is also very much efficient in terms of space complexity. The thing is, I was not able to come up with the solution on my own. I actually had to use a lot from the solution tab, so I just want to make it clear. So yeah, everyone has to go through it, and I would be posting this in the comments so you can check it out from there. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do word search to lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Uber, Microsoft, Google, Snapchat, Facebook, Apple, Twitter, TikTok, Bloomberg, Spotify, Twitch, and Airbnb. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is the LeetCode hard problem, and basically we are given an m cross n matrix of characters. Now, and we are also given a different list of string called words. Now we need to return all the words that are present on the given board. We are also given one more thing, that each word must be constructed from the letters that are adjacent to each other. So, and we are also given the definition that what adjacent cells are. Basically, any cells that are horizontally or vertically neighboring to each other, we can consider them to be a part of the consecutive sequence series, and we can use them to create words. So let's try to understand this with an example over here. Over here we are given a 4x4 matrix, and for this matrix we are told that these are the list of words. We need to check that whether they are present inside this given matrix or not. So if we try to just look at this example, basically we can see that this first word oath is actually present over here, where O, A, T and H, they are creating or forming this word, and if you see, they are all sequentially adjacent cells to each other. So that's why we can use them to form this words and see whether it's present or not. So in the answer, first of all, we are going to add the word oath as one of the answer. Then if we look at the answer, we can also find this word eat to be present. So E, A, T, that is present in this manner. And again, though this is on the left side, this is not the conventional way to write it, but still based on the adjacent cells, we can actually form this word eat, and that's why this eat is also going to be part of the answer. So we will add eat in the answer as well. Now for this two, PEA, P and rain, these two are not present inside this given matrix, so we will not include them in the answer, and this is the answer we will have to return. So basically it is one kind of a word search game or word search puzzle. So that is why the name is word search 2, and this is the little bit of advanced version. So first we will see that what is going to be like a basic, very trivial approach, and then we will try to improvise using a different set of data structures. Okay, so most basic idea we are going to have is that we will start iterating over all of the characters that are present inside this m cross n matrix, and then for every single character we are going to see that whether that matches with any of the starting words or not. If we find a potential match, then we will try to find the subsequent character and the neighbors of that particular character to see if we are able to generate any exact word or not. And the moment we do that, we will actually put it in a new variable called answer, and that is how we will be able to generate our answer. So let's try to see this in action. So first character in this case is X. So X matches with this character over here in the given set of words. So next we will have to see that whether any neighbor of X is actually Y or not. Neighbor of X is actually H and A. We do not find Y over here. So because we do not find Y over here, this X does not lead to anywhere. So we can mark this as visited. That does not lead to any answer. Next character is H. So H matches with this first character. And then we will have to see that whether B exists as one of the neighbors of H, and B also exists as one of the neighbors of H, and then the subsequent character O also exists as one of the neighbors of B. So in this case, this HBO is actually a complete word we are able to make based on subsequent characters that are present adjacent to each other inside this given matrix. And because of that, we are going to create a new variable called the answer, and in the answer we are going to add the value HBO over here. Now we will start iterating over this A. So again, A is the starting point over here, and next character B and C, we are able to generate this pair using sequentially iterating over. And if we see over here, we can also generate this A, B, C in this fashion. Now this character is Y. So again, Y is not part of starting character of any other word, so we cannot do anything about this. Our next character is again C, that we have already visited, so we don't need to visit this. And next character is Z. Z again is not the starting point of any of these characters. So in this case, this is the answer we are going to have, and we can return this one. This solution works as expected. There are no issues with this one. But if you just see, we only have a 3 by 3 matrix, and for every single character, in the worst case scenario, we might have to iterate over every single word and check that whether it matches the starting word or not. We can maybe simplify using a hash map, but the thing is, this is still going to lead to a very bad solution. In terms of time complexity, this is going to be disaster, because for every single character, we might have to iterate over every single word that there is. And once we find a match, then we will have to iterate over all the neighbors of that particular character as well. So that leads to nowhere. So let's try to see that where we can find a better time complexity. And the solution to achieve a better time complexity is actually using a new data structure called Trie. Now I have already extensively worked on Trie, and you can find all of those solutions over here. Check out this video if you want to learn that what a Trie is and what are its applications. Now let's see that how we are going to use Trie in this case to improve our performance. Okay, so the previous example we see, basically what we are doing is we were iterating over every single character, and then we were trying to see that whether that character matches the first element or not, and sequentially we will have to check every single word that was present. And if we find a potential match, then we will have to check all the neighbors to see if the next consecutive element is present or not. And that was the major reason that why we were having a disastrous time complexity. So in order to improve that, if we can find some way to eliminate this checking procedure, that for every single character we might have to look up all the elements or all the words that are present, because imagine if there are million words present, we might have to check million times, and then that is going to be very disastrous. The idea we are going to use is that whatever the words that we are given, we are actually going to convert these into a Trie. And because we are converting them into a Trie, for any character, searching that whether it is the starting point of any word or not becomes pretty easy for us, and we can actually do it in nearly constant time. Because in the Trie, it is very fast and efficient to find that whether any word exists or not, and if it exists, it is very easy for us to iterate over that particular word or not. So first of all, let me quickly create a Trie block based on these three words. The Trie block is going to look like this. So based on the words that we were previously given, we actually created a Trie block. And now using this Trie block, we are going to make things pretty easy for ourselves. Basically, we are going to iterate over in the same fashion for the given matrix. But this time, all we will have to see is to look up in this Trie that whether the current character, if that is any children of this given root node or not. And if that is the case, we will keep on iterating. So first we find this character to be E. E is not part of any children, so we can ignore that. Next one is F. F is actually part of a children. So okay, now we have found F to be part of the children. Now we will have to see that what is the next character in this Trie block. So this next character is A. So we will have to see that whether any neighbors of this F is actually A or not. So we will have to check on three sides, and we find a match over here that this is A. Okay, now again next character is A. Again this neighbor is actually A. Okay, now this character is N. So again neighbor of this A is N present over here. And again the next character is G. so G is also present over here. And since we have reached to the end node inside our trie, because of that we can conclude that the whole word was actually present inside this given matrix, and we can return true in this case, and we will add it to our answer list. So inside the answer list, the first word we are going to add is FAANG, that is present inside this given matrix. So see how easy it is for us to find these things. And okay, now the next character is R is not children of any of these root nodes. Next one is T is also not a children, L is not a children, these are all visited. Now this G is actually a children. So now it becomes easy. Now we will have to start iterating over. Okay, so we are at this position G. Now the next element is O. The next element is O, and O is also a neighbor over here. Okay, so which is good. Now the next element is O. Again, O is a neighbor over here. So which is good. Now this next element is G. G is also a neighbor of this O, right? So we are good up until this point. Now we have to find this L. Now, if we look at this G, we do not find L to be a neighbor of this G. So because of that, we will actually have to roll back, and we cannot move forward with this path. So now we would have visited this G, and that did not lead us to anywhere. So again, we will start with our routine procedure. Okay, now this next character is O. O is not starting point of anything. T is also not starting point of anything. G is, we have already used it. Now this is again G. So again, G is the starting point of this one. Next character is O. O is present over here. Next character is O. O is also neighbor of this one. Next character is G. G is neighbor of this one. Next character is L. L is neighbor of this one. And next character is E. E is the first character. And because we reached to the end character over here, we can conclude that Google is also present inside this given matrix, and we will add it to our answer. So we will add one other entry called Google. Okay, and now next again this character is L. So L does not lead to any children of this root node, and F does not lead to any children of this root node. So in the answer, we are going to return this FAANG and Google to be the answer, and this would be the most optimal way to solve this problem. Remember, because we used a trie block, things becomes much more faster for us, and we can immediately look up that whether any single character that leads to an answer or not. Okay, now let's do the tricky part. We will have to do the time and space complexity analysis. So for the time complexity analysis, it's actually a little bit tricky. The first thing that is a given fact is that we will have to iterate over every single character that is present inside this given m cross n matrix. So that's a given fact. Suppose that the total number of cells that are present are actually m. So now, okay, we already know that is whatever the time complexity is going to be the factor of m. Now for this particular m, imagine that for any particular character, what is the maximum work we will have to do in the worst case scenario? Well, the maximum work we will have to do in the worst case scenario is that any particular character, suppose this F matches this character that is present. Now, whenever we find a potential match, we will have to look for the next element in all three directions of that particular word. So suppose this O was a potential match, we will have to iterate over all four directions in any given case. So for any single cell, we might have to iterate over in all four directions, and for all four directions, the number of traversal that we will have to do for each one of them would depend on the next three or the next remaining three characters. Because remember, for this Google, suppose we find a match, this O to be a match. Now the moment we find this O to be a match, again we find this O to be a match. So now because we find this to be a match, we do not have to look for this particular element. We will have to look at the remaining three positions. So then we will have to, for any single character, we will have to look in the four directions, and for all the subsequent elements, we will have to look in the remaining three directions, and that we will have to do depending on the length of that particular word. So for the remaining three elements, we will have to iterate over to the length of that. So that's why 3 to the power of L minus 1. And why minus 1? Because for this first character, we are actually looking in the worst case scenario in all four directions, and for all the subsequent length parameters. So suppose for this particular FAANG, for this F, we might have to look in four directions, and for this A, we only have to look in the remaining three directions because one adjacent cell is already F. So that we do not have to look at. So this is going to be the time complexity. So if I write the final time complexity, it's actually going to be big O of m into 4 times 3 to the power of L minus 1, and that is the final time complexity. This is a very difficult time complexity analysis. So yeah, it gives you an idea that why this problem is pretty popular. If we see space complexity, that is pretty simple. Space complexity depends on the total number of words that are present. So suppose we sum that up to big O of n, where m is the total number of characters that are present in the or initial word list. So after doing this time and space complexity analysis, now let's move on to the coding. Before we implement our solution, we are actually going to create our class Trie node. In the class solution, we are going to define a couple of global variables. Now inside the find words method, first of all, we are going to initialize our Trie block, and we are going to add all the words to our Trie block. After creating the Trie node, now we are going to start working on backtracking, starting with each cell in the board. So first of all, let's create the board variable. And now we are going to initialize couple of loops to iterate over this full board matrix. So now for every single position inside this given matrix, we are going to check that whether that is actually any of the children of this root Trie node that we have created. And if that is the case, then we will create a helper method called backtracking, where we are going to iterate over all the adjacent cells of that particular row and column position, and also that particular entire DFS traversal for that particular branch inside our Trie node. After this loop ends, basically we should have populated our answer inside this answer variable that we have created. So we can simply return that. And now let's create our backtracking method. So this is going to be our recursive method. First of all, we are going to define a couple of variables. First of all, we are going to check that whether the current node is actually a word or not. If that is a word, we can immediately add it to our result. Okay, if that is not the case, we will have to start doing our traversal. So how we are going to do our traversal? Remember, whatever the current row and column is, we cannot use the same word again. So we are actually going to mark this as hash in a way for us to identify that that is the node we have already visited. Now for any given row and column, we will have to iterate over all of its neighbors. So we are going to use couple of variables to our advantage. Now with the help of row and column offset, it becomes pretty easy for us to iterate over all the neighbors of any given node. So now we are going to run a for loop, and we are going to iterate over all the neighbors of given row and column position. First we check that whether our new row and new column, if they are going out of bounds or not. If that is the case, we just simply ignore that. Otherwise, if we are at the correct neighbor, we need to check that whether that neighbor is actually subsequent character that we have already stored in our Trie or not. And if that is the case, we are going to call our backtracking method again. So now after our exploration ends, basically we will have to put back this hash to its original position, and that should be it. There is one more optimization we can do, and that is to incrementally remove the leaf nodes, which means that whenever we identify that the current node's children, if that is empty, then basically we can just remove that from our parent. That should be it. Let's try to run this code. We will also have to update the value of the node in the else condition. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently. I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do design, add and search words data structure LeetCode problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Google, Microsoft, Apple, Facebook, ByteDance, Twitter, Uber and Lyft. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and as the name suggests that we are actually designing a data structure where for this data structure we have to support that we can add new words to this data structure, and if given any string we can actually find the previously added words or strings as well. So we are being asked to implement the word dictionary class. Now in the word dictionary class, first of all, we'll need to initialize the word dictionary object, and then we need to create two different methods. First method is add word method that takes in a string word as an input. Being done, it adds the word to our data structure that we can use to match it later. And then there is a boolean method called search, where again we provide a string word as an input, and that returns true or false if that word has been previously added or not. We are also given one more condition, that for the search method there could be dots provided as inputs, where we can conclude dot to be any letter. So if we are given the word something like bad, that is already being added, and then we are asked to search for the word using b.d, actually these two words we can consider same, because this dot we can consider it to be a. So let's try to understand this with an example. Over here we are given a bunch of different add word, and search word mechanisms, and this is the explanation provided. So basically, first of all, we initialize the object word dictionary. Now for that, first we add the word bad, dad, mad. We add all these three words. Now first of all, we search using pad. So pad is not present, so we return false. Then bad is present because we have previously added it. Then we are also given a word which is dot ad. So this dot can actually mean anything, and if we see, we already have a word like bad and dad, that both, and even mad, that all three of them, they actually match with this string, so we can return true in this case as well. And we are also given one more search criteria, where we are only given b dot dot, which means for these two dots we can conclude any other word, and since we already have a word bad added, we can conclude these two to be similar, and we need to return true in this case. So before we start the solution, first let's understand that what a trie is. If you want to check the full explanation, you can check out my previous video over here. Now let's move back over here. So basically, a trie is actually a form of a tree, whereas any given tree, it has a root node. Now this root node can have many subsequent children, and each children can have some children of their own, and based on that, we actually use trie to search, store, and iterate over different strings. And for any given strings, we actually use it character by character to store distinct values inside this given trie, and based on per character, we actually store it in a manner where it becomes pretty fast for us to find that whether any particular parent node contains some character as one of its children or not, and then we iterate in some particular fashion, in DFS fashion, to find any words. So suppose these four are the strings we are trying to add. So let's initialize our trie data structure. So first of all, we are actually going to have a root variable. Now for this root variable, we are going to store all of these values one by one. So first let's store the value hello. As mentioned, that for any given string, we are actually going to go character by character. So first of all, we are going to take the character h, and we are going to see that does this root node has a child that is actually starts with h. It does not. So we are actually going to create a new node over here, and this node starts with h. Now we are going to add all the values of subsequent characters because they don't exist. So I'm going to add append e, l, l, o, and after adding all of these values, actually we are going to have an end variable that denotes that this word has actually ended over here. So far, if we iterate in this direction in this given trie, we can actually form the word hello, and when we reach to this o, we will actually encounter a special node that denotes that this is actually the end node, and if whenever we identify that, we can conclude the word has actually ended. Now let's add this word hi. So if we want to add word hi, basically first of all we will check that whether this h exists or not. So h already exists as one of the children of this root, so we do not need to create a separate branch for this one. But the thing is, for this particular h, I does not exist as one of its children, so we are actually going to create a new branch over here, I, and we are going to denote that this represents this word h, and then because this word ends over here, we are actually going to denote an end node over here. Let's add one more word, that is pop. So if we want to add pop, again p does not exist, so we are going to add, or we are going to create a new branch, and we are going to add all of these values, and we are going to add the end node. Now this next word is pond. So again we are going to use the same methodology. So p and o exist as the children, so first two characters we are done with. Now from here we will have to create a new branch, so we will do that, and after that we will add our end branch, and this is the logic we are going to use to implement our insert or add method. to add different strings inside our word implement data structure. And this is the logic we are going to use. That first of all, we are going to check that any character exists as the children of the root or not. If it exists, we are going to leverage that particular branch. If it does not exist, we are going to create a new branch, and then we will keep on making separations, and based on that things becomes pretty easy for us to find different words. Okay, so for our search method, suppose this is the try that we have actually created, and these are the words we have added. Let me quickly go over them. So first word is pen. If you look at this direction, we have the word pen, then we have the pot. So P is common, so then there is a branch out and we get the word pot as well. Same, we have cat, cars and bed in the similar sequence, and these are the words we are trying to search. So couple of words are just regular words. Then I have added some examples with the dots in it, so because they are more complicated ones, so we can understand that. So let's quickly start to go over and see that what would be our search policy for this given try that we have created. So for this character pot, first letter is P. So from this root we are going to see that does there a children that contains the character P, and yes, we have a child that contains the character P. So based on that, we will keep on iterating in that direction. So next character is O, so we have O as well, and the next character is T, so we have T as well. Now we don't care about this end node, because as long as we are able to generate the word that we were given, we are good up until this point. So over here we will actually return true to be the answer, that yes, this word is present inside the try that we have created. Second word is pots. So again, for the pots, we up until this pot we are going to go in the same direction, but this S is not present as one of the children of this pot, and because we encounter an end node over here, so we can drop out immediately and we can return false in this case, that yeah, we don't have any character that matches the word pots. Now this is a little bit interesting example. So for this dot AR, the policy we are going to use is that whenever we encounter a dot to be a character, we will actually have to iterate over every single possible route using this dot to be the character, and see that can we make this AR to be part of that sequence or not. So let's quickly do that, and let me clean this up a bit. For this dot AR, the strategy we are going to use is, for this particular dot, we are going to consider it that every single child of this root can be used over here, and then we will try to see that whether is there any place where second character is actually A. So first we go down this path. Okay, so P, we consider P as dot, right? Then we check that okay, this is E and this is not A, so we cannot go on this path. Okay, now we backtrack. Now we keep this P to be dot. Now again we try to repeat the same process. This is A and this is O. So again, this is not the path we are going to choose. That is going to lead us to this answer. We come back. Now okay, we are at this position. Again we check this child. So this child is actually C. We consider C to be the dot. Okay, now from the C, the next character is actually A, and all over here the next character is also A. So that is good sign for us. So now we can continue in that direction. So now from this A, we will try to see that is there a child that is actually R, and yes, from this A we also have a child that is R. And since we reach to the end of this word, we can return true in this case, that yes, this dot AR is present inside this try that we created. Okay, so yeah, that's a wonderful news. Now let's focus on the next example. So next example is dot dot T. So for the dot dot T, actually we will have to branch out even more. So for this second dot dot T, what we are going to do is, again we are going to repeat the same strategy. We will have to go over every single child that is possible. So first we'll consider this P to be the first dot. So this dot is this P. Okay, now from this P, we will also consider two child to be separate dots. So for both the childs, okay, this is going to be the first dot. So we are good up until this point, but this value is actually not T, this is N. So we will have to backtrack. From this E, we do not have any child, so we will again backtrack and we will come back to this P to be one dot. Now from this P, we still have one more root that we haven't considered. So we will consider this O to be the second dot. And from this O, we actually have the last character T present, and that matches the string dot dot T. So if we go down this path, we will be able to generate this word, and that's why we will also return true in this case as well. And the same thing we are going to repeat for this dot ey strategy. So for this dot ey, what we are going to do is, first of all, we are going to consider this to be the dot. We will see, okay, this is E. so that is good. But this is not y, so again we cannot go down this path. Again, this is dot, this is not the path, this is not the path, this is not the path. So this dot ey is actually not present inside this entire try block that we have created. So over here we will return false. But before returning false, we will actually check every single possible route to see that whether we can find a match or not. Okay, so that is how we are actually going to implement the search mechanism. Basically, the only tricky part is to take care of the dot values. Apart from that, it's pretty simple. Now let's talk about time and space complexity. So for the add function, the time complexity is actually going to be big O of n, that depending on the number of characters that are presented inside the input. And also for the space complexity, it's also going to be big O of n, depending on the size of the input. For the search mechanism, things become a little bit tricky. Over here, the time complexity is actually going to be big O of 26 times n. Why 26 times n? Because remember, for any given dot, there can be 26 child of any particular root element that we might have to iterate over, and again in the bottom we might have to keep on repeating the same process, right? So basically the maximum time and space complexity we might have to go over is going to be n times 26, but since 26 is a finite number, we can also consider this to be big O of n only. Okay, and for the space complexity, it's also going to be the same. It's going to be big O of 26 to the power of n. So for this problem, we are being asked to implement three things: word dictionary, add word, and search method. The thing is, before that, we will actually have to define a try node. So I'm going to create a separate class for to defining a try node, where every single try node has a different set of children, and we can easily quickly look up those children because we are actually using hash map to define them. Okay, now from our main method, first of all, we are going to create a new try node. So now to implement our word dictionary, first of all, we are actually going to create an instance of this try. Now for this add word method, first of all, we'll have to create a node. So we are going to create a try node. We are going to run a for loop across the given word. If the current node, if that does not contain any children with this character, then we will have to create a new entry inside our node. And if the entry exists for this given character, we are actually going to go to the next element, and in the end we are going to define node.word to be true. So before we start our search method, we are actually going to create a helper method called search in node. That is going to take the input word and the try node as the input, and that is going to help us to iterate over the given try node. So first of all, we are going to create a for loop to iterate over this given word, and inside this given word we are going to iterate over character by character. So I'm also going to create a new character variable. So first of all, we are going to check that if the given node or does its children contains this word or not. If it does not contain, then we are going to check that whether the given character is dot or not, and if that is the dot, then we might have to iterate over all the subsequent characters of this node. Once we determine that the children does not contain this character ch, we are going to check that whether the ch is actually dot or not. If that is dot, then we are going to run a for loop across all the children for every single character value, and then we are going to define a new try node called child, and basically we are going to call this search in node method iteratively for the next character in that particular word, because remember we are already eliminating the dot character and providing its child as the try node, and we will keep on repeating this we will keep on iterating this process, and we are going to return true. If that is not the case, and if this given ch character is not a dot, then in that case we can return false immediately. Somehow this ch is actually a child of this node. If that is the case, then we simply need to iterate over the next value inside this given node, and in the end we simply need to return that whether the node.word is present or not. And remember, we are storing this node.word value inside our this add word method as well. So the moment we identify a matching word, it would return true, otherwise it would return false. Now from this our search method, all we will have to do is we simply need to call the recursive search in node method that we have created, and as the input we are going to provide the value of the word, and we are also going to initialize a new try node, or we are also going to provide the try node that we initialized earlier, and that's it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. Okay, seems like our solution worked as expected. It was not the fastest solution in terms of time complexity, but in terms of space complexity, it was pretty efficient. I would be posting this in the comments so you can check it out from there. Thank you. Graphs are one of the most popular data structures that I personally struggled a lot with. So today I have decided to create an entire course on graphs. We will understand that what graphs are, when to use it, what are the different types, their applications, how to store them, and we will learn 22 most asked, most popular and most like LeetCode problems that has literally been asked at hundreds of companies thousands of times. So without any delay, let's get started with this course. Graphs are one of the most powerful tools we have in computing and also in real life to establish connections and define many of the relationships. We all have studied graphs in our schools and in our past careers. But now let's try to understand that what the graph is from the point of view of data structure and algorithms. So the idea is quite straightforward. Typically, a graph is defined by connection between more than one parties, and these parties are connected with each other in some sort of fashion. And this is an example of a graph that I just created. Now we can notice that graph contains two entities. There are these circular entities and there are these lines that are connecting them. And this is actually defined by nodes. So these circular entities are nodes and they can also sometimes called vertices. So we can use vice versa. And the connection between these are defined as the edges. That's it. If you master nodes and edges, you basically master graph, but it's not as simple as it seems. Now let's say that I want to show you some practical examples of what a graph is in a real life scenario. Let's say that I want to explain that how does my Facebook or Instagram looks like in a picture or in a diagram. So how would I represent it? Well, one way to represent it is that this I can define it as my profile. So my name is Parth, so I'm defining it as P. And let's just say that I am currently friends with 5 different people on Facebook. So I can define these 5 people as dots and their own, and these edges define that I am currently friends with them and they are also currently friends with me. So that's why there are no arrows pointing towards each other. Now these friends can have their own friends, and it could be possible that I might have some mutual friends who are also friends with each other. So this creates a whole big new social network where everyone is connected with everyone and many people are not connected with everyone. Now in this example, let's say that I want to build a recommendation system, that I want to recommend new friends for myself because I currently only have 5 friends. So one logical way I can go about is that whoever are my friends or like immediate friends of my friends could also be potentially possible that they might be my friends as well. So I can start recommending these people to my profile who are not my friends but friends of my friends. But I would not recommend people like this who are friends of friends of friends of my friend. So that would be like 1 degree advance. And this is just one practical application. Now think the companies like Facebook, Twitter, TikTok, they all completely run on the concepts that are currently generated by graphs. So that's why they are so significantly important. Now, when we talk about graphs, there are actually 4 different basic types that we can talk about. First one are the trees. And yes, trees are a different data structure on its own, but the thing is, they are also a type of graph. The only difference between a graph and a tree is that trees are connected, which means every single value or every single node inside a tree is connected and they do not have any cycles. That's the only difference. Next type of graph that we can think about is that is typically a directed graph. So what does a directed graph means? Now let's try to understand this with an example of Twitter. There is a very famous profile for Eminem. Now Eminem has millions of followers. He has a lot of people following him, but Eminem does not follow anyone. So if I have to represent the graph of Eminem, I can define that currently Eminem, let's say I want to define whoever is following Eminem, I just mark their profile arrows pointing towards Eminem. So this defines that all of these people are currently following Eminem, but Eminem does not follow anyone. So there would not be any arrow pointing out where Eminem is following someone. So this is one way to define relationship where one party is connected with the other party but other party is not connected with the other party. Next is undirected. Now same way we can see the example of Facebook, where if I am friends with A, where A is friends with B, then B is also friends with A. So in this case we can say that there are actually two directed edges that are going or pointing towards each other. Or if I have to just mention it simply, I can just simply say that there are two nodes and they are just connected with each other where there is no direction specified. Then there are two more distinctions of graph, and for that is connected graph and unconnected graph. So what does a connected graph means? Well, as the name suggests, let's say that if there are all of these different nodes, and we can define that all of the nodes are connected with each other in some sort of edge, then we can define it as a connected graph. But if we have a graph like this where there are only three nodes but this node is not connected with any other node and it's in a separate island in its own, still this is part of a graph. It can be possible on Facebook that I have created a profile where I don't have any friends and no one is friends with me, so I am still a profile, I'm still a node, but I just don't have any edges, and that is absolutely valid. Now when we talk about traversing graph, we mainly talk about two methods, depth first search and breadth first search, and which is typically defined by DFS and BFS. Now DFS simply means that let's say I'm currently located at this particular node. So from this node, I can see that I have edges pointing towards these 5 different nodes, which means from this node, if I have to travel, I can very easily traverse to all of these 5 nodes, and through these 5 nodes then I can traverse to subsequent nodes. Now if I follow the depth first search methodology, then the logic is going to be that I pick a neighbor, and for that neighbor I would keep on going subsequently down to its neighbor. Once again I would pick a neighbor and then once again I would keep going down towards that path. Now let's say that I exhausted all the possibilities and I reached out to this neighbor where it currently does not have any more neighbors that I can visit. In this case I can do a backtracking operation. I can check that whether there is any other node whose neighbors I haven't visited. In this case, once again this does not have any neighbors, so once again I would do a backtrack operation. Once again this does not have any more neighbors, and once again I would do the backtrack operation to my root node from where I started and repeat the same operation in the other direction as well, and so on and so forth. So I'm going down in a particular direction in depth first search manner. Second option to traverse is that instead of traversing in depth, I can start traversing in breadth. So what does that mean? Well, for any particular node, I will visit all the nodes that are currently associated with that particular node or all the neighbors, and then I would start visiting subsequent neighbors. So let's say that once again I start to traverse from this end and I want to traverse in a breadth first search fashion. So first I would visit this node, then I would visit this node. Now notice that this node has some children of its own, but I'm not going to visit those. I'm going to visit all the neighbors of this node first. After visiting that, now I would pick on this node and once again start visiting its neighbors. So let's say that this node, and if let's say that this node also had these two neighbors. So once again I would visit this node, then I would visit this node and this node, and after visiting all of the children, then I will start visiting these nodes. So in one fashion you are moving out in breadth, and in other fashion you are going in one particular direction in depth till you reach to the end of the path, and then you do the backtrack operation. So this is just couple of ways to understand or traverse over the graph. Now one last thing, and that is that if I have to define that what are the different ways to represent a graph, then there are actually couple of ways. First way is, let's say that let me just draw a quick graph. So one way is to define them using adjacency list. What adjacency list means is that I typically use a hash map like data structure where I say that all of these nodes, so 1 2 3 4 and 5, all of these nodes I am defining. And now for these nodes I can define in these values that what are the neighboring nodes of that. So for 1 I can define the neighboring nodes are going to be 2 and 3. Now for 2 I can define the neighboring node to 1, because remember this is an undirected edge, so which means 1 is neighbor of 2 and 2 is also neighbor of 1. So once again for 2 I only have one neighbor, that is 1. For 3 I only have one neighbor, that is 1. For 4 I only have one neighbor, that is 1, and I did not define 4 over here but 4 over here as well. And for 5 I only have one neighbor, that is 4. And this would be a representation of this graph in adjacency list manner, where we are clearly defining what the nodes are and what are all the different neighbors connected with each. And the second way to represent the graph would be using adjacency matrix. And in the adjacency matrix, we are simply defining all the nodes that we currently have. And then whenever we see an edge between them, so let's say that we currently have an edge from 1 to 4 and 4 to 1. So from 1 to 4, we can mark as true or 1. And same way for 4 to 1, we can mark it as true or 1. And for all the other values, we can define it as 0 or false, something like this. So this would be two different ways that we are going to represent graph inside our computer programming, and both of them are very useful and very popular. Just a quick suggestion when to use which one. If you are dealing with less edges, then it would make sense to use adjacency list, because you are only dealing with small number of connections. But if you are dealing with lot of edges and lot of dense graph, then it would make sense to use adjacency matrix, because remember over here the retrieval would be big O of one time, because you can directly see that whether two nodes are edges of each other or not. In this case, in the worst case scenario, this can be big O of n, because notice that over here we are facing some contention. So that's why it would make sense. But the thing is, the time complexity for space complexity for this one is big O of n square. That is more expensive, and for adjacency list it is much less expensive. So I explained, I gave you a brief intro. Now let's try to learn the 22 most asked, most popular, most like LeetCode problems. And by the end of these 22, after completing these 22 questions, you would be pro in all sorts of graph questions. That is my guarantee. So without any delay, let's get started. So the question is number of provinces. This is a LeetCode 547 problem, and this problem has been popular amongst top tier companies. So companies such as Amazon, Bloomberg, Apple, Two Sigma, DoorDash, Goldman Sachs, Google, Uber, they have all asked this problem. So that's why I hope that you pay enough attention to this one. If we see the problem statement defines that there are n cities that we are given, and we are told that some of these cities are connected, some of these cities are not connected. Now if say city A is connected with city B and city B is directly connected with city C, then city A is indirectly connected with city C. So A is connected with B is connected with C. Suppose this is the relationship, then we can define that A is also connected with C. This is what this problem is, the statement is referring to. Now going back, we are given the definition that what a province is. A province is a group of directly or indirectly connected cities and no other cities outside of this group. So suppose we are given cities like A, B, C, D, something like this. And we are given that A is connected with B, B is connected with C, and we can also refer that indirectly A is connected with C as well. Currently this D is not connected with anyone. In this case, we can define that this A, B, C makes a province, and this D by itself, currently since it is not connected, it is not making a province. But suppose we identify that another city E that exists that is connected with city D, then we can define this to be the second province as well. Okay, so now we know that what the problem statement has given us. We are given n cities and we are given the connection between those cities, and we are also given the definition of what a province is. Now we are given an n cross n matrix, and wherever there is a connection between any two entities, that particular value has been marked as 1. That defines that the ith city and jth city is connected. And if the value is not 1, if the value is 0, which means that those values are not connected. Now based on this given input, we need to define the total number of provinces. This problem is very similar to one of the previous problems we solved, and that is the number of connected components. And how? Let me just quickly show it to you. What we are given is that we are told that we are given a matrix, and inside the matrix, using the values 0 and 1, we are going to define that whether any two values are connected or not. Okay, so suppose the values are a, b, c, d, and here a, b, c, d. Okay, all the values are by default going to be connected with each other, so I'm going to mark it as 1. Suppose, let's just take the same example. So these are all the items we are given. This is true. Based on all of these items, what we are given is that this is actually not a matrix, but actually this is an adjacency matrix, and adjacency matrix is one more way to represent a graph. Since this is one more way to represent a graph, we can, rather than considering these as cities and these are connection between them, let's just try to think of these as nodes and edges, where nodes are the cities and edges are the connection between them. And now this becomes a very simple problem that we can solve using BFS quite easily. And the whole problem statement now becomes is that we need to identify that how many number of connected component exist inside any given graph, and those connected components, we need to return them as the answer. So I have already solved this one in past, but I'm going to quickly show you the solution again. And simply we are going to use breadth first search. For breadth first search, we all know we need two items. First one we need is a queue, and we need some way to keep track of all the visited nodes so far. So let's just do that. I'm going to initialize our queue, and also I'm going to initialize our hash set that is going to keep track of the visited hash set. Okay, so this one is for visited and this one is queue. Now we can start at any given node. So suppose this is the input we are given. Currently nodes are 1, 2, 3. These three cities are connected, and city 4 and 5 is connected. We are also going to mark one more variable called provinces, and initially the value of the provinces is going to be 0. Okay, so currently this is the variable that is going to keep track of the number of provinces we have been able to find so far. Currently the value is 0. Now let's just pick any arbitrary value. So we start with node 1. So let's just run a BFS starting with node number 1. So first we are going to, since 1 has not been visited, we are going to mark as visited because we are visiting it. We are going to add 1 inside our queue. Now the moment we find a value inside a queue, we are going to iterate through its neighbors. Currently 1 has two neighbors, value 2 and value 3. Both value 2 and value 3 are not visited, so we are going to mark them to the number of visited nodes, and we are going to mark 2 and 3 here. Now we iterated over all the neighbors of 1, so we are going to dequeue 1 out, and we are going to remove it from the queue. Now currently we only have values 2 and 3. For value 2, the number of node is 1 and 3 as its neighbor. Both 1 and 3 have been visited, so since they are visited, we are not going to revisit them, and we are going to pop 2 out as well, that stating that we visited all the nodes of 2. And at the same time we are going to pop 3 out as well, since the neighbors of 3, 1 and 2 are already been visited. Also, I forgot one key important thing, and that is that the moment initially when we started iterating through 1 and we found that 1 has a neighbor 2, immediately we needed to add the number of provinces to 1 because we found at least one province. So we would have found one province, and in order to finding that province, we already visited all 3 nodes. So we are going to mark these 3 nodes as visited. Now since in the input we are already given n is equal to 5, we initially started with n is equal to value number 1 because it was not visited. Now we will start with n is equal to 2, but that has also been visited, so we will simply skip over. N is equal to 3 has also been visited, so we will simply skip over. Last value is n is equal to 4. N is equal to 4 has not been visited, so marking 4 to our visited list, adding 4 to our queue, and now 4 has a neighbor 5. So again, the moment we find a neighbor, we are going to increase the number of provinces to 2. We are going to add 5 to our visited list. We are going to add 5 to our queue, and then we are going to pop 4 out because we visited all the neighbors of 4. But we haven't visited all the neighbors of 5. Currently for 5, since 5 has already been visited, we do not care, but 5's neighbor 4 has also been visited, which means 5, we also visited all the neighbors of 5. So now we get rid of 5. Now initially for this n is equal to 5, we had gone through 1 to 4. For the 5th value, 5 is also present inside the number of visited list. So we can define that 5 has also been visited, and because of that, we went through all the nodes or all the cities that we were given, and the number of provinces that we were able to make was 2. and which we are going to return as the answer. If we see solution for the time and space solution for this one, basically the time complexity is going to be big O of V plus E, where V is the number of vertices or number of cities in this case, and E is the number of edges or the connection between the cities that we are given. Pretty simple, and this is pretty standard. Space complexity also going to be big O of V, because the space complexity is based on the visited hash set and the queue that we have to generate, which can hold maximum up to 5 cities for this example. So it is directly related to the number of vertices that is present inside our given example. Awesome. So see how knowing BFS made our life so much easier. Let's move on to the coding explanation for this problem. Let's see the coding solution for the number of provinces problem. This is a really unique problem, and the solution is actually quite simple. First of all, in the main method, we are given the 2 by 2 matrix that defines that what are the number of connected components. Based on that, we would be able to easily identify that what is the total number of edges or total number of nodes present. And once having that, we are going to initialize our visited Boolean array, and initially the number of provinces is going to be 0. Now we are going to run our for loop where we are going to call the BFS method. Inside the BFS method, first of all, we are going to check that whether the current node has been visited or not. If the node has not been visited, we are going to call BFS method to visit all the connected components or all the cities that are connected with each other that form a province. And we are going to increase the number of provinces. So we are going to do provinces plus plus, that was initially set it up as 0. Now let's see that what is going to happen inside our BFS helper method. The answer is quite simple. In the BFS, we are going to initialize our queue, and we are going to have a visited array that to keep track of all the nodes that we have visited so far. For any single input that we are given, we are going to keep on iterating all the neighbors of that particular node that it is currently connected to, and we are going to mark all of them visited. So even when we encounter the same city that has already been processed, we do not reprocess it again because it has already been marked visited. And after this entire process ends, currently in this loop, this provinces variable should have all the answers populated. We can simply add them over here and return provinces as the answer. So let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs 99.26% faster. So this is pretty fast solution. And don't worry about this. I'm going to paste the solution inside my GitHub, and the link is in the description, so you can check it out from there. Hello friends, the problem we are going to do today is one of the most versatile, most asked question in the history of LeetCode questions. Like if you just look at the sheer numbers of the amount this question has been asked and the range of companies this question has been asked, it's just mind-boggling. Whatever your dream company might be in the entire world, and if they do good technical interviews, they must have asked this question probably at least 2, 3, 5, 10 times to their candidates. If I only had 10 minutes to prepare for a technical interview, I'm going to choose this question at the top of my choice. Like just look at the companies over here, like Amazon, Microsoft, Bloomberg, Facebook, Google, LinkedIn, Oracle, Apple, ByteDance, which is basically TikTok, DoorDash, Yahoo, Paytm, Walmart, Tesla, Samsung. So I doubt that there are any companies left that didn't ask this question. And the question we are going to do today is number of islands, and I'm going to pay my utmost attention to this problem. Now in the input problem, we are given a grid of m cross n as a 2D binary matrix, and in this particular grid we are all the cells are filled with either values of 1 or value of 0, and whatever the value that represents as value of 1 actually represents land in the real life, and all the values that are marked as 0 is actually water. And we need to find that what are the total number of islands inside this particular grid. Now based on the definition, we know that suppose if we have some sort of body of land, something like this, and if it is entirely covered by a body of water, we can say that this particular body of land is actually an island, and we that is what we are trying to find in this given problem. Now we are also told one more thing, that at the edges of this particular grid, like all of these values, this is also water, which means that suppose we are given an input like this, where all of these values are zeros, and we only have just one single one over here, this we can also conclude as an island, because on these three sides of the island is already water, and on the outside is also water, because we are told that everything on the outside is also water. So just keep this in mind, that if we find some place at the edge of the grid, we still consider it to be surrounded by water if all the other side inside the grid is also water. And our aim is to find that how what is the maximum number of islands that are present inside the given grid. Now this problem is actually pretty simple. Like if we just see over here, like in this particular input, if we try to find for this example one, that how many number of islands there exist, actually there only exists just one island, and that is this one. Because notice this, that these all ones are actually able to be connect with each other because they are adjacent to each other. If for any particular cell, suppose this is marked as 1 and this is a part of land, and any cell adjacent to this cell is also marked as 1, we can say that both of these are a common part of a land, because there does not exist anything in between. They are right adjacent to each other, and this is what we are given over here. So in this example, we can only find one island. Now if we take the second example, we can see that there are actually more than one islands. So this is the first island that we can find. This one is by itself, and if we see all four sides of it, this is 0, this is 0, this is 0, and this is 0. So this is also an island, and these two ones, they are also an island. So in this example, we actually have three distinct islands. Okay, suppose we are given a custom example like this, and I have mentioned in my previous videos that it is really important to come up with your own custom examples, because it shows that you can think on your own and you can create test cases on your own. It's a really important skill for any computer engineer to have. Now suppose this is the grid that we are given, and this blue line indicates the body of water we have outside of our original grid. So this is just for understanding purposes. I'm just going to get rid of it now, so it does not become an issue, and I can explain the problem better. So we know that there is water outside. Now the most basic approach is that we start traversing through the entire grid in some manner. Like there are bunch of different ways to traverse through the given grid, and we try to see that at any moment if we find one, which means that so far we have find a body of land. Now since we have found this one, we need to see that what are the different islands we can create, and we can create bunch of different islands if all the values are are connected with one. Like no matter how many number of values are connected with any single one, we would mark all of them as just one island, as long as they are connected with each other. And basically what we are doing is we are trying to find separate set of ones. Understand what I'm saying? I will repeat, we are trying to find separate set of ones. So in this example, if we just see that how many different sets we can find, like we can find this one set of 1, we can find this another set of ones, and we can find this third set of ones, and over here we only have one individual element, but still that is a set on its own. Like even if we only have just 1 acre of land, it's still a piece of land which we can consider as island. So that is what we are trying to find. And let me just revert back. Okay, so now we know that what we are trying to find. The most basic approach is we start traversing through the given input array, and we start traversing. Okay, suppose we traverse the first row, we don't find anything. Okay, now again we start traversing over here, we don't find anything. Now at this point we find that okay, there exists an element 1 over here. The moment we find that there exists an element 1 over here, we are going to call our function, and basically what that function is going to do is it is going to iterate over all the adjacent cells, and it is going to keep on iterating till we exhaust all the ones that are connected with this one. So till we exhaust all the sets that are associated with this particular one. So let me just go back a bit, and this is the approach we are going to take. That initially, currently we came to this particular item, we find that okay, there exists a 1 over here. Now because there exists a 1, we need to find all the ones that are connected with this one. So what we are going to do is we are going to mark this coordinate, and once we have this coordinate location, first of all we are going to increase the number of islands we have. Like initially the number of islands we have is 0. Now because we find at least a single one, which means that we have found at least one island, so we will update the number of islands we have. Now since we have already updated the number of islands, and we already have coordinates for this one, first of all we will mark this one as 0. So let's mark this one as 0. Okay, and now from this coordinate we will try to find all of its neighbors to see that there exist any adjacent ones. So over here we find that okay, this one is also 1 and this one is also 1. So we are going to repeat the same process, and remember, we are not going to update our islands in this case because we are still connected with whatever the previous value we had found before. So we are still in the same set of 1 that we were dealing with, so there is no point in updating that, but we have to exhaust all the ones that are connected with this original one we had found before. So we will check over here. Okay, this is 1. So because this is 1, we will we'll change its value to 0, because it now it becomes part of this original set we had. Now again we are from here we are going to repeat the same process. Okay, we don't find any ones from this point, so we are good. But remember, over here we didn't exhaust all the possibilities from our original coordinate, so we still have to do some work. So again we will come back, we will find 1 over here, which means we will have to turn it to 0. So we will convert this 1 to 0 as well, and now from this particular position we will try to repeat the same process. So we will check all of its neighbors, and all of its neighbors in this scenario are now 0, which means we are good. Like we have at least exhausted some possibility, and we have at least found one set of island. Okay, now we will again repeat with our process, and notice that I convert all these 3 values to zeros because we already found an island over here. And now we will repeat the same process. So again we will start traversing our matrix, and over here we encounter the 1 again, which means now we have encountered a new set of island. So we will update the value in our islands, we will update this to 2. Again we are going to repeat the same process. So first of all we will update this one to 0, and now this is 0. We still have to check its neighbors. We find an adjacent neighbor, again we flip it to 0 first, and again we go to the next element, again we flip it to 0, and now we won't find any more neighbors that are basically 1, which means that again we will start traversing. So we keep on traversing over and over and over, and we don't find any ones. But now we are at this point, again we find a 1, we update our island, so our number of island becomes 3, and now we need to find all the neighbors that are present in this particular island, and we set up all of those values to 0. So these values are set up to 0, and now we check that okay, no neighbor actually has a value of 1, which means we have exhausted all the possibilities of number of neighbors that could be a part of the island. And now again we repeat the same process, and now we find this one, and this is the last element. So again we increase the number of islands that we have found to 4, and we set this up to 0. And now because we have exhausted all the possibility and we reach to the end of the grid, we can simply return whatever the value we find in the number of islands, and that would be our solution. Suppose we were given an input with all the zeros, like over here we wouldn't have found any island, and we can simply return 0 in that case as well. But this is like a very basic approach, and the approach we took in this scenario is actually depth first search, to find the set of ones that are adjacent to each other. Like we could have used BFS as well, but I mentioned earlier, like I'm trying to learn graph theory, and first I'm going to master DFS, then I will start working on the BFS. So that's why I decided to choose the approach of depth first search in this scenario. Okay, and the time complexity in this case would be actually big O of m cross n time complexity, because that is in we have to iterate over entire grid that is given. And the space complexity would also be big O of m cross n in the worst case scenario. Suppose that we are given a grid where all the values are just ones, which means that for any single element we will have to iterate over all the entire grid, and that could be the worst time and space complexity. First we'll create two parameters, row and column, to calculate the current row and column values for the given grid. Okay, and we'll also create a variable called island, and initially we will set it up to value 0, and we would update this every time we encounter 1 inside the given matrix. And inside the loop we will have a condition that if the current I and jth position inside the grid is actually equal to 1, then only we are going to call our DFS function. So first we'll do island, we'll increase the value of islands, and now we'll call our DFS function. In the DFS we are going to provide the ith position, the jth position, and we'll also provide the grid that we are working on. And once this loop ends, like we should have all the set of separate ones, and we should have all the values of the total number of islands. So we can simply return the number of islands we have found. Okay, now we need to create the logic to implement this DFS function. So first we'll create a function. Inside the function we will need the values for the row and column again for the entire grid. So we'll just name them new row, and this would be grid's length, and we will also create a parameter called new column. This would be the first position's length. And this is basically the same as finding the row and column we found over here, but we need to use it, so I'm just giving different names. We'll also create a 2D array of called directions. This would make our lives easier and allow us to iterate over all the adjacent values of any current position, and we are going to initialize it with default values. We have this established. First we will put a condition that if the current row and column are they out of bounds or not. We will also put an additional condition that if the current value we are at inside the grid, if that is already 0 or not, because if that is already 0 we won't have to do anything. So if any of these conditions satisfy, we can simply break out of the DFS function, and this would be our terminating case. If this is not true, first of all we will update the current position we are at inside the grid, and will enter the value as 0, because remember we have already updated the islands. And now we will just run a for loop, and iterate over all the 4 directions. So that will allow us to go over all the neighboring candidates of this row and column that we have. And now we are simply going to call DFS on row plus direction of 0 and column plus direction of 1, and we'll also provide the value of grid as well. And yeah, I guess this should be our logic, and we can try to run this code. Okay, looks like we messed something up. Oh, okay, seems like our solution is working. Let's try to submit the code. Seems like our solution is also working, but it's not the most efficient solution, and I'll try to make my solution better, because maybe there is some other way we can solve this problem, and if I find out, I'll probably make a video on that sometime in the future. Meanwhile, let me know in the comments if you have any thoughts regarding this problem. So the LeetCode problem we are going to solve now is called maximum area of islands, and we can see that this one is a medium problem and also a very well-liked problem. The statement is quite straightforward. We are given an m cross n binary matrix named grid. Now for this particular grid, we are given bunch of different ones and bunch of different zeros. Now we are being told that ones represents an island and 0 represents just water. Okay, then we need to return the maximum area of an island that we can make inside the grid, and if there are no islands that we can form, we need to return 0. Plus we are being told that every single cell with value 1 is the island, and if there are bunch of different ones connected with each other, then we need to basically do the addition of all of those cells, and then we can consider them as one entire block of an island. So let's try to understand this with an example. Here is an m cross n grid we are given, and we can see that there are bunch of different zeros and bunch of different ones. Now some ones are isolated, so this is just an island in its own, and we can see that the area of this particular island is going to be value number 1, because it is only connected with just one island by itself. But if we take a look at some other islands, we can see that they actually form bunch of different ones that are adjacent to each other amongst all 4 horizontal values, and that increases the area of those particular islands. So we will have this island that is of size 4, same way this island of size 5, and so on and so forth. Now we need to return the island that contains the maximum value. So in this case, this island chain or this connection of ones are actually total area of 6. So in this case, we will need to return the maximum area of islands as 6 as the answer. So this is what we need to return. Now let's try to understand that what are the different logic we can take to solve this problem. Now we know it's a very straightforward problem. The idea is that we are going to iterate in one single direction from the starting point, and the moment we identify that there exists some island or value number 1, then we need to iterate over every single possible neighbor of this particular one. And the moment we exhaust all the possibilities by exploring every single neighbor, we can determine that that has been the current area that we have been able to find. Plus we will also need to keep track that what is the maximum island chain we have been able to identify it so far. So let's try to understand the most common basic approach to solve this problem. Let's say that we start iterating from this very first cell in sequence, in just regular sequence. So we say that this is water, this is water. So there is no area we can find. We come to this node. This value is 1. So the moment we identify 1, we will have to take a look in all 4 directions to see if there are any possible island chains that we can make. Since in this case there are no island chains we can form, we can say that the area of the current value we have been able to identify so far is 1, and so far we have only found one island with area 1, so the maximum area we found so far is also 1. After doing this, we will have to mark this one as being visited because we have already visited this node. And why are we marking it visited? I'll just explain it to you later. So let's say that we mark this one as visited as well. Okay, that this one has already been taken care of. We iterate again, nothing, we don't find anything. Once again we find one more one over here, which means we will have to do the iteration for our current updation right now. So once again we start looking in all four directions. The moment we go to this direction, we find one more one. So once again for this particular one, we will have to repeat the same operation, look in all four directions. And here the problem may arise. Let's say that we look in this direction and this direction, and then we decide to look up into this direction. So this is also a neighbor of 1, and we can also by mistakenly calculate this one once again, so as part of the island, which means we may stay inside an infinite loop. And that's why, in order to prevent that issue, the moment any particular value that we have visited, we are just going to mark that that value has been visited, so we don't recount those values again. So let's say that we count this value, then we go into this direction, and so far we have visited all of these four ones, and the current area so far we found is 4, which means maximum area also needs to be updated. So we are going to update the maximum area once again. Now we start our iteration in the similar fashion. These are all zeros, so nothing to do with this. Once again, this one would have been 1, but since we already visited this one, there is no point in redoing the same operation. So we are just going to go and ignore this case completely. And once again, we are going to ignore all of these cases. Once again, we identified 1, 1. So far the area is going to be 4. We cancel out all of these 4 nodes as well, and we keep on repeating the same operation until we find the maximum area, which we would find when we get to this particular one as value number 6. And this is what we need to return in this case. So the moment I was explaining this solution, it should completely come to your head that this is actually a graph problem, where this given m cross n grid is actually the matrix we are given that represents a graph. It's an adjacency matrix. And for this adjacency matrix, all we need to do is we will have to find that what are all the connected components for any particular graph, and the cluster of the connected components, whichever has the highest value, we simply need to return that as part of the answer or as part of the area we have been able to calculate so far. Now we know with any particular graph problem, the most important thing is that how we are going to iterate over the graph. So we know that iterating over an m cross n grid is quite straightforward. We simply need to run 2 for loops to iterate over that. The moment we identify any particular one, then we will have to explore in all 4 directions and iterate over the entire set of directions where whichever the value is 1, and we will have to keep on repeating the same operation. So logically, all we are doing is a depth first search whenever we identify any particular one that exists. We can also do a BFS, but DFS in my opinion would make much more sense in this case because we need to go in any particular direction. It won't change the result, but I just like to use DFS for this particular type of case. Then in order to complete the DFS and not run into the issue of recounting the same value, we will have to keep track of all the visited nodes. For that, we have 2 options. One option is that we can try to manipulate the existing input, but let's say that your interviewer is very picky and he or she does not want you to play around with originally given input. So instead of playing around with originally given input, you can also create a m cross n matrix and just mark all the values by 0, whichever the ones that you have visited so far. So that way also you can just keep track of all the nodes that you have visited, and you are only going to do a DFS on unvisited nodes. So that's it. That is the whole solution. And on top of it, for the entire duration, you are going to keep track of the current area that you have found so far and the maximum area that you have been able to find so far. And combination of this would actually solve this problem quite simply, quite easily. Let's try to understand the time and space complexity in this case. Time complexity is simply going to be big O of m cross n, because we will have to iterate over every single cell, and even for our DFS operation, we are going to mark those nodes as visited. In terms of space complexity, because we are using an extra space to store all the visited nodes, it is also going to be big O of m multiplied by n, or nodes multiplied by edges. So in this case, overall, this is a very good time and space complexity. Once you understand that this one is actually a graph problem, it becomes very simple to solve and also move forward. So now let's quickly see the coding solution for this one. So the coding solution is quite straightforward. We are given our max area of island that we need to find, and we are given the grid as part of the input. First thing we are going to do is to check that if the given grid is equal to null, then we are simply going to return 0. It's an edge case. Then we are going to initialize a variable called max area, and initially the value is going to be 0. Then we are going to iterate over every single value that is currently present inside our grid using two loops, I and j. And for every single value, first thing we are going to check is that if the given grid position, if that is equal to 1, then we will start calculating the area of this current one that we have been able to identify so far, and we will have to iterate over in all 4 directions, and that's where we are using the DFS method. Next thing, for every single one that we have been able to identify so far, it could be possible that that particular value could be the maximum area we have been able to identify so far. So we are going to compare the maximum area we have so far and the new area or the current area we just found for this particular through this DFS call. Now let's understand this DFS call and how does it work. In the input, we are providing the grid that we are working with. We are also providing the current I and jth position. Very first thing we are checking is that if the given grid is going out of bounds, in either one of these cases, we are simply going to return 0, or if the given grid position I and j that we are working with, if that is also 0, then also we can return 0. If that is not the case, we are going to mark this cell as visited. Now in this case, I'm not using an extra hash set. I'm just using the same grid to update the call. But if your interviewer asks you that you cannot change the given input, then you might need to create a new instance of new m cross n matrix and repeat the same operation. Then we are going to add value of area by 1, and then we are going to make 4 different calls in all 4 directions, and we are going to do the plus and equal to operation for the area, which means for every single one that we are being able to identify in each of these 4 areas, we are going to add that value to our existing area, and we are simply returning the area in the end. So this is our helper method, where recursively we are using the DFS operation and we are updating the area of the current area we have been able to identify it so far. In the end, we simply need to return the max area we have been able to identify so far once this for loop call ends. So now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs 100% faster than all the other solutions, which is exceptionally good. So once again, the solution is present in our GitHub repository, so feel free to go ahead and check it out. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do number of connected components in an undirected graph LeetCode problem. This is a graph theory problem, as you can see from the name. And this problem has been asked in one of my favorite companies: Amazon, LinkedIn, Facebook, Pinterest, Microsoft, Google, Bloomberg, Apple, Twitter. So these are all my dream companies. I want to get a job at any one of them, and that's why I'm making these videos. So I would be paying my utmost attention. I hope you enjoy the video. So this is a LeetCode medium problem, but in my opinion, this should have been an easy problem. And if we look at the problem statement, we are given n nodes of a graph, and we are given an array of edges, and those edges are undirected, which means if we are given an edge like this, that A to B, which means we can say that we can go from A to B and we can also come from B to A. Now we need to return that based on this given input, how many different kinds of connected component there exist inside the given graph. So over here we are given an example with 5 nodes, 0, 1, 2, 3 and 4. These are the 5 vertices of a graph, and we are given some array of edges. Based on these arrays, we are able to see that there exist these this is the graph and there exists these two different set of connected components. So over here, because there are two connected components, we need to return to. Suppose we could have given some example like this, that 0 1 2 3. So this is one connected component inside the graph. Then there is also one more node that is isolated, and then there is one more node that is something like 5 6, something like this. So in this case, how many different connected components we can find? So if we see over here, the number of different connected components we can find is 1 2 and 3. So in this case, we would iterate over this given input and we would say that, hey, there exist 3 separate connected components. And let's see that what could be the intuition behind the solution for this one. Okay, suppose we are given a custom example like this, and always remember that it is really important to come up with your own custom example in any interviews. So suppose we are given a custom example like this, where the number of nodes we are given is 8, and these are list of edges that we are given. Now based on these edges, we are able to form a graph like this, and we can imagine that there exists a graph like this. Now over here, if we just look at it, we can understand that there exist 3 separate components that are connected with each other inside this given graph, and in this case the answer is going to be 3, and we need to return that. Now the idea is that first of all, based on this given input, we will need to find a way to iterate over this given graph. Now to iterating over this given graph can be a little bit tricky, and the best way to do it in any computer language is to use adjacency list or adjacency matrix. So we can use either one of them. So in this case, we are going to use adjacency list. Usually we use adjacency matrix when the number of edges are far more than the number of nodes, and we don't have any clear indication that that would always be the case in this scenario. So it's better to go with adjacency list. Now once we have our adjacency list, it becomes easier for us to iterate over these given nodes, right? So we have solved a part of problem, but the other part of problem is that we need to find that how many number of connected components there exist. Now in order to do it, basically we need to find a way to keep track of whatever the nodes we have visited so far, and the best way to do is to create a hash set. So suppose we create a hash set, and we keep track of all the visited nodes that we have visited so far. Now the approach we are going to use is that initially we are going to start at the 0th position. Now from the 0th position, we are going to run a DFS in this case. And then why DFS? Because the DFS has a very particular property that it starts iterating from one element, and it will continue to iterate till it can reach all the subsequent elements or all the subsequent neighbors of this initial element. So we are not going to stop up until then. And how we are going to use visited hash set is, let me show it to you. So essentially we will start our function with the 0th position. We are first of all going to check that whether the node we are currently visiting, is it present in our visited hash set or not. So 0 is not present, right? Which means we will have to add 0 over here. So we add 0 over here now. And at the same time, we are starting our DFS function from the 0th position. So we are going to have a variable called counter, and initially this counter is going to be initialized at 0. But now since we have started our DFS function, so we are going to initialize our counter as 1. Now from this 0th position, we are going to see that okay, it has a neighbor 1. So we will check that whether 1 exists in the visited hash set or not. It does not exist, so we will add 1 over here. So now this 1 has been visited, and then we see that 1 has a neighbor 2. So again we will come back at 2. 2 has not been visited, so we will add the value 2 over here. Now all the nodes in this case have been visited. That 0 has been visited, 1 has been visited, and 2 has been visited, which means we don't have any more nodes to go to. So we will just end our loop over here. And now in our adjacency list, because we have already checked this 0 1 and 2 nodes, so we won't be doing anything for them because they have already been visited. Now we will come at this node number 3. Now again this node we are at this node number 3, and this has not been visited, and this is a new starting for the DFS function. So every time we do that, we are going to increment our counter function. So now the value of counter is going to be 2. So we will add the count to be 2, and again we are going to repeat the same process. So this 3 has not been visited, so we will add an entry over here called 3. from this 3 it has neighbor 4 and 5. So again 4 and 5 have also not been visited, so we will add an entry over here, and once all of them has been visited, which means that we no longer needs to iterate over these nodes because they have already been visited and their count has been accounted for, and because they were connected, so we only need to increase counter once when we start the DFS function. We do not want to increase the counter for all the nodes that are present, and once that is done, so these all nodes are taken care of. Now we are at node number 6, so again we start the DFS function from the scratch. So we will have to increase our counter, so we are going to increase our counter to value number 3, and now we are going to add the values to hash set. Inside our hash set we are going to add value number 6. So we are done with this one, and now we visit value number 7 as well, and we are done with this one. So now essentially we in our visited set we have visited all the number of nodes that were originally given as part of input, and at the end of this we simply need to return whatever the value of counter function we have found. So in this case the counter we have found is 3, and this would be our answer. So basically this is the simplest approach. It's very easy to understand, very easy to explain in any interview, and I don't know why LeetCode put this as a medium problem. This should have been easy problem, as I mentioned it from the beginning. Now if we calculate the time and space complexity, in terms of time complexity, essentially we are doing a couple of things over here. So first thing we are doing is we are creating an adjacency list. Then after creating this adjacency list, we are iterating over all the values that are present inside the adjacency list in form of graph. So the time complexity in this case is actually going to be big of v plus e, where v represents the number of vertices or nodes and e represents the number of edges, because at any given moment we will have to iterate over all the number of nodes and all the edges that are present. In terms of space complexity, so for the space complexity, essentially it's going to be the same. It's going to be big O of v plus e. And why? Because we are storing this adjacency list, which is essentially the combination of vertices and edges, and we are also storing this visited hash set. So but in this visited hash set we are only storing all the vertices, so this is actually big O of v only. So essentially the space complexity is going to be big O of v plus e for adjacency list plus big O of v, but generically we can write it as big O of v plus e. Any interviewer would be satisfied with this answer. So first of all we are going to create a variable counter, and we are going to initialize it to value 0, and now we will initialize an array called visited. And I know that I mentioned that we are going to use a hash set, but we can also use an array as well. And initially we are going to initialize this array with the size n. The reason we are not using hash set is because it was causing some issues with in Java by passing by reference and passing by value. So I'll try to probably work upon that separately. And now we will create an adjacency list, and we are going to store all the nodes and edges inside our adjacency list. We will run two for loops, one to add all the nodes and one to add all the edges. And now we are going to iterate over every single node, and we are going to check that whether that node has been visited or not. If not, we are going to initialize, we are going to call basically our DFS function, and we are going to increase the counter as well. And when this for loop ends, essentially we only need to return whatever the counter whatever the result of counter variable we got. Okay, now let's create our DFS function. So first of all we are going to mark the current node as 1. So we know that we have already visited this node. And now we are going to run a for loop for all the neighbors of this particular node, and we are going to call the DFS function again recursively. And notice that we are only calling DFS function for all the nodes that we haven't visited. And this should be it. Let's try to run our code. Okay, seems like our solution is working after a bunch of different compilation errors. Let's try to submit this code. some solution seems to be working as expected, and I would be posting this in the comments so you can check it out from there. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important LeetCode graph problem, graph valid tree. Basically we are checking that whether the given graph is actually a tree or not. And this question has been asked in a bunch of different top tier companies, companies like LinkedIn, Google, Amazon, Bloomberg, Microsoft and Facebook. So these are my dream companies, so I'm paying my utmost attention. I hope you enjoy the video. Okay, so this is a LeetCode medium problem and we are given n number of nodes. We are also given a list of edges and we are told that these edges are actually undirected edges. Now we need to see that whether the given graph is actually a valid tree or not. If it is a valid tree, we'll return true. If it is not a valid tree, we'll return false. And we are also given an example to understand this problem. Like in this example, we are given these 5 nodes and we are given some list of edges. Based on this list of edges, they have shown that this could be a pictorial representation. And over here, they are saying that, yeah, this is a valid tree. So that's why they are returning true. Now the question is, in order to understand this, first of all, we will have to understand that what is the relationship between any graph and a tree. What is the difference between a graph and tree, and how can from the given input we can identify that, okay, this is a valid tree or not, right? That every single tree is also a graph, but that is not the case for every single graph, that it will always be a tree. Because if I put it in Venn diagram, essentially graph is actually a superset and tree is just one of its subset. So this can be a tree and this is a graph. There are a lot of real life cases to understand that as well. Like the person who got slapped by Will Smith is always going to be a human, but not every single human has been slapped by Will Smith. It is something, that kind of relationship, right? Now the thing is, what are the differences between a graph and a tree? That inside the tree, all the components are connected, or all the nodes are connected. There is no restriction for graph that all the nodes should be connected. And the second difference is, inside any tree, we will never encounter any loops. So we can just say no loops, while inside the graph there can be loops. Let's try to understand this with some examples. Is this a valid tree? Actually, yes, this is a valid tree, because notice over here that from one node, like every single nodes are connected with each other, and we do not find any single loops. But the thing is, say for example, in this case, if I had an additional edge, something like this, I can clearly see that there exists a loop between these 4 nodes. And because we have identified a loop, we can clearly say that though this is a graph, but this is not a tree. Now let's take another example. Now this is a valid tree. Like all the nodes, they satisfy these 2 properties, that they are connected and there are no loops. The same graph, if I had some components like this, some additional nodes, though they are not connected with all the nodes, they are connected with each other, or there are some isolated nodes, something like this. If this is the case, this will always be true, that okay, this is a graph. We can put it in the category of graph, but this will not be a tree. And in this case, we will need to return false. Now, before we move on towards solution, I just have a simple request. If you see, a lot of people, they watch my content, but they are actually not subscribed to my channel. It takes me a lot of time and a lot of effort to make these kind of videos, and I would really appreciate if you can just show your support and subscribe the channel. Like, now this problem actually can be solved in so many different ways, and I'm going to show you few different ways on how we can do things. Now the question is, what we need to find basically we need to find that whatever this given input is this a valid tree or not. In order to find that whether it's a valid tree or not, we need to check 2 things: whether all the nodes are connected, and if there are any loops or not, right? So what I'm suggesting is that we break this problem in 2 parts. In the first part, we check that what could be the different ways we can see that whether these nodes they are connected or not. If they are all connected, we are good, and if they are not connected, we can return false immediately, that this is not a valid tree. And once that is done, we will find all the ways on which we can identify that whether there are any loops or not, right? So first let's go with the first approach. Now our aim is to check that whether all the nodes are connected or not. What could be the different things we can do over here? In order to check that, essentially what we will need to do is we'll have to traverse over whatever this given input graph is. Now traversing over this given input graph based on the structure we are currently given in the input is going to be a little bit tricky, based using this number of nodes and edges. So the question is, like, first thing we need to do is we will need to convert this given input in either adjacency list or adjacency matrix. Either of them can be used and it will work perfectly fine, but in this case I will suggest to use adjacency list. We only use adjacency matrix when there are too many edges. We don't have any clear indication in this case that there would be too many edges, and we would try to use an adjacency list, right? So now we are trying to check that whether all the nodes are connected or not, and we have already created our adjacency list. Now what I'm suggesting is that through this adjacency list, we know that we would be able to iterate over this given input, and through this given input, what we do is we create a hash set. Inside the hash set, initially it would be empty. Whenever we are at any point iterating over any single node inside this given hash set, we will check that whether that particular node already exists in the hash set or not. If it does not exist, we will add a new entry inside the hash set. And at the end, once we have traversed all the values inside the given input through this adjacency list, what we are going to do is we are going to check that what is the total size of hash set and what is the total number of n given. If both are same, we can conclude that from any single point we are able to reach to all the other elements. And because we were able to reach to all the other elements, all the elements are connected, and we at least satisfy one condition. So let's see that how it would work. Suppose in our adjacency list, we start traversing through this position number 1, right? So initially we check that whether this value number 1 exists in the hash set or not. It does not exist. So we'll add an entry over here that, okay, value number 1. Now through this value number 1, we can traverse in two directions. We can either traverse to the neighbor on the right or neighbor on the left. So let's say that we go to this node number 0. Again, we add 0. From this 0, we go to node number 2. Again, we come to 2. Now from this 2, we can't go any way forward, right? But the thing is, we still need to go back. We'll need to do backtrack. We'll go back to 1. Again, through 1, we will go back to 3. Now at this 3, this is not added, so we add it over here. From this 3, we will go to 4. So we will add 4 over here. From this 4, again we will do a backtrack, and we would come back at 3, and then we will come to 5, and then we will add 5 over here. Now at the end of this hash set, we are able to iterate over all the elements inside the given input, right? And we check that what would be the size of this hash set. So size of this hash set would be 6. And what is the given n? So n is also 6, which means in this case we are at least able to conclude that this given hash set is actually satisfying our condition, and inside this given graph all the nodes are connected. So we are good. Now suppose in this case, if we had another node, something like this, and this was not connected to any of them, basically this would not have been entered inside our hash set, and our n in this case would have actually been 7 rather than 6. So we can clearly see that if our size of our hash set is going to be lesser than whatever the number of n we have, if that was the case, we could have written false immediately, because we found that there exists some not connected component, and which was not the case in this case. So this is one of the very good approaches to identify that whether the graph is connected or not. Okay, now we have taken care of the first part, and now we need to take care of the second part, that we need to check that whether in the given graph does there exist a cycle or not. So first thing that comes to our mind is that why don't we use the visited hash set that we have already created. And in that visited hash set, what we are going to do is at any point in time, we are going to start exploring from one of the node in the given input graph. From that node, we are not going to stop exploring till we exhaust all the neighbors of this particular graph. and at every single time we are planning to come to next element, we would first check that whether that element exists in the visited hash set or not. If it exists, then we would consider that there exists a loop and we would break out of it. If it does not exist, we would add that entry over here. So first we will start traversing this value number 0. So it does not exist in visited, so we will add an entry over here. From this 0 we will start exploring its neighbor. So one of its neighbor is this value number 1, and remember that we are going in depth first search, so we will not stop until we exhaust all the possibility in one direction before going to the other neighbor. We could do it breadth first search way as well. It's up to us. Now from this one, again depth first search, we see its neighbor, that there is a neighbor 2, so we add an entry over here because it does not exist. Now remember that this is actually an undirected edge. So what does an undirected edge means? Undirected edge means that from 0 we have an edge to go towards 1, and from 1 we have an edge to go towards 0. Same goes from 1, that we have an edge to go towards 2, and from 2 we have an edge to go towards 1, and same goes from 2, that we can go to 0 and we can come back. Now over here from this position number 2, because we have an edge that goes to 0, we can consider that 0 is also a neighbor of 2. In this case, from this 2 we will try to go to this 0, and the moment we try to go to the 0, we will see that okay, it has already been visited, it is part of this hash set. So we would say that okay, there exists a cycle, and we are pretty happy with ourselves that hey, we have identified a cycle and now we are done with our case. The thing is, this is actually a wrong approach, and the reason why it is a wrong approach, it is wrong approach because there exists this undirected edge. And let me show you by an example that what could be the problems if we keep using this visited hash set only, and how can we find false positives. So suppose we are given an example like this, that 0 calls 1 and 2, and that's it. This is the input we are given, right? And now we don't have any entry inside our hash map. Now the thing is, all the edges are undirected edges. Now because they are undirected edges, we can represent them in different manner. So let's represent them in slightly different manner. So from 0 we have an edge that goes towards 1, from 1 we have an edge that goes to 0, same goes from 0 to 2, and 2 to 0. Now initially we start traversing from this 0. Now we have our algorithm that initially we are going to add the entry to visited hash set. So 0 does not exist, so we add the entry towards our visited hash set. Now from the 0 we need to check all of its neighbor before we move on to some other node. Now from this 0, first of all, let's say that we go down this path and we check its neighbor 2. Because there exists an edge like this, we are able to check its neighbor, right? So we are at this position number 2. Now at this position number 2, we don't have an entry in the visited hash set, so we enter an entry over here that this is 2. Now from this 2, again we will need to repeat the same process, that we will need to check for all the neighbors or all the edges that this 2 can point to. Now it does not have any edges that go further, but it has an edge that goes back to 0. Now the thing is, in this case, again we will use our same logic. So from this 2 we can still go to 0. So we will check that whether we have visited this element 0 or not, and over here we find that hey, we have already visited this element 0, which means by our logic that we were previously trying to impose, we could have said that okay, we have found a cycle that looks like 0 to 2 and 2 to back to 0, and we in this case say that hey, we have found a cycle and this is not a tree and we will need to return false and blah blah blah. The thing is, this is actually not the case, and why it's not the case is because of this correlation of having an undirected edge that is causing all this problem, which means that we cannot rely only on having a visited hash set. If we do that, then essentially we are not going to be able to find an answer, because in this case we know that from there does not exist an edge, and from this 2 we are coming back to 0 only because there exists an undirected edge from this 2 to 0, and that's why we can consider this 0 to be 2's neighbor. But in reality, this 0 is actually parent of this child 1 and 2. So if that's the case, why are we still doing things like this? What could be a better approach we can use to find that what would be the solution to detect these cycles? There are a couple of different ways where you can tackle this problem. One way to tackle this problem is that initially, remember, the only reason we are causing this problem is because there exists an undirected edge, which means that there exist two directed edges from any two nodes. So what we can do is we can put a condition that from any point, if we travel from this 1 to is 0 or 2, if we are able to travel in one direction, we would get rid of the remaining edge. And let's see that how it would work. So what I'm proposing is that initially we are at this 0th position. So we check in our visited hash set, we don't have any entry. So we add an entry over here that, okay, we are at the 0th position. Now from the 0, first let's say we travel to 1, which means that now we have traveled from 0 to 1 in this direction. So our aim is that we get rid of this reverse edge in our adjacency list. So if we get rid of that, now we are at this position number 1. At this position number 1, again, we add an entry over here in our visited hash set. Now from this position number 1, what we have to do is we will have to check that what are all the neighbors that we can travel to, or all the children we can travel to. But this one does not have any neighbor or children, so which means we don't have to worry about anything. So over here we can say that, okay, from this one we can't go anywhere, but thing is there still exists some nodes that we haven't traveled to, and we are using either BFS or DFS in any manner to traverse over entire graph, right? So which means that we will have to do a backtrack. So now from this one we do a backtrack. Now again we end up at this 0. But the thing is, in this scenario, remember, we are not ending up at this 0 because from 1 there existed an edge like this where we consider 0 to be 1's neighbor. We are coming back to this 1 because we are using backtracking through any BFS or DFS algorithm. We can implement this recursively or iteratively, doesn't matter. In any scenario, we will have to iterate over all the nodes that are present inside the given graph, and since we haven't traveled all the nodes, that's why we are coming back to the 0. So again, this would be a new entry in the visited hash set. So again we come back at the 0, and this 0 we check that, okay, we have already explored one of the neighbor of the 0, but we still have to explore another neighbor. So again we repeat the same process. From the 0 we explored another neighbor of 0, we come back at 2, and immediately we get rid of this this edge that was coming back to it, and then we add an entry over here that, okay, we are at this position number 2. Now from this 2, again we don't have any more neighbors to go to, so now we have explored all the neighbors of 1, so we can mark 1 as being done. We have explored all the neighbors of 2, so we can mark 2 as being done, and now we come back at the 0, and we can mark 0 as being done because we have explored all the neighbors of 0 possible as well. And in any scenario we did not find any single loop because we did not find repeated value inside our visited hash set, so we can determine that there does not exist a cycle, and which means in this case we can return true because there are no cycles. So we can say that there is no loop for this one. And the only reason we are able to come up to this conclusion is because at every single position we were removing the edge where in one direction we have already traveled. So that is one way to take care of this problem, and the solution would work as expected as well, right? Now the thing is, there could be another solution where we can use the little bit different logic, little bit different data structure, and we can do things in better manner. And let's see that what would be that approach. So the second approach is that rather than using this visited hash set, we don't need to do anything with this visited hash set. Let it be used for the purpose of counting that whether all the elements are connected components or not. What I'm proposing is that we created another data structure, a hash map, and in this hash map, what we plan to do is we as a key we have parent, and as a child we as a value we have the value of its children. Now let's see that how can we use this combination to do things a little bit differently. Also over here, let's say that we are given a graph like this, that 0 1 2 3, something like this, right? So 0 is connected to 1, 1 is connected to 2, 2 is connected to 3, and now we have this 3 connected back to this 1 as well, which means that there exists a cycle over here. Now because these are undirected edges, which means that they are bi-directional edges as well. So from this 0 we can go to 1, from this 1 we can go back to 0, and blah 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 whatnot. So initially, let's say that we are at the 0th position. From the 0th position, we start exploring its neighbor or children or whatever we want to call. So the moment from the 0 we are able to reach to this one, we would add an entry over here in this hash map, and the entry we are going to make is that 0 is actually a parent in this case, and one of the children that we could find for this 0 is actually node number 1. So node number 1 is the children of 0, and just stay with me that why we are using this approach. Now again, from this node number 1, we need to explore its neighbors, right? So what are the neighbors of this node number 1? We can explore neighbors based on the number of edges that goes out from this node number 1. So from this node number 1, we actually have 2 edges that goes out. First edge is that from this node number 1 we can go to node number 2. Now we check in this hash map that does node number 1 exist. Node number 1 does not exist as a key, so we add an entry over here. So we say that okay, parent is node number 1, and from this node number 1 we can actually travel to node number 2. So we are good with that. Now again, from this node number 1 we still have possibility that we can go back to this node number 0. So again we check in this hash map, okay, that whether there exists an entry for this node number 0 that we are trying to reach. Remember this very importantly. We will check that whether this node number 0 that we are trying to reach from this node number 1, does that exist in the hash map or not. Okay, so 0 exists in this hash map. Again we check that from this 1 we are trying to reach to this 0, is this one of the children of this node 0 or not. In this case, yes, 1 is the children of node number 0. If that is the case, we can identify that this connection from 1 to 0 is actually not a cycle, it's just a trivial loop, and that is being caused because there exists an undirectional edge on both the sides. So that's why we will ignore this case, we will ignore this connection. We are not removing the edge. Again, remember, we are not removing the edge, we are just ignoring this case because in the hash map we are able to find that okay, this 0 to 1 connection is actually just a trivial cycle, and we move on with our life. So from this 1, again, since we have reached to this 2, right, and 2 is not existing, and 2 is one of the children of 1. Now again we are at this position number 2. Now again, from this position number 2, what are the different ways we can travel? We can either go back to 1 or we can go to 3. Let's say that we go to 3 first. So we check that whether 3 exists inside the hash map. 3 does not exist, which means we can create an entry that where 2 is a parent and 3 is a child. We are good with this so far. Now again, from this 2, when we try to check that from 2 we are trying to go back to 1, is that a cycle? So first we check that whether this 1 exists in the hash map or not. So 1 exists in the hash map over here, and 2 is one of its children. So because 2 is one of its children, we are going to ignore this case, and we are going to ignore, and because we are ignoring this particular, we are just going to move on with our lives. Now we are at this position number 3. From this 3 we will check that okay, what are the different places we can travel back to. So from this 3 we see that okay, one edge that goes to 1, one edge that goes to 2. First of all, let's explore this edge from 3 to 2. So over here we will check that we are trying to reach to this node number 2. So 2 already exists and 3 is one of its children, which means we are going to ignore this edge, so we don't have to worry about anything. Now again, from this 3 we check for this value number 1. So okay, from this 3 we try to see that whether we are able to reach to node number 1. Node number 1 has already been visited inside the hash map, and that's why we are able to determine that there exists a loop inside over here, from where we are actually going back to one of the places that was actually not that is already been visited inside our hash map. And this hash map acts as both. It acts as a visited hash set that we were planning to use, and also it acts as a way for us to determining that whether we are detecting the correct cycles or we are detecting the trivial cycles between the unidirectional edges. And this would be a way on how we can check the cycles, which means that the combination of this, using this hash map to identify that whether cycle exists or not, and using this visited node and iterating over using BFS or DFS inside our graph, original graph, using these two data structures, we can actually get rid of both of our cases where we need to check that whether the graph is connected, and we need to check that whether the graph contains any cycles or not. And because we are able to do both of these things, at the end, if we are able to reach to end node, we will return true. If we are not able to reach to end node, we can return false. And this solution actually works perfectly fine. There are no issues with this solution. It is a very elegant solution. If you tell it in any interview, they are going to be very impressed with the depth and breadth of your thinking capabilities. What are the space and time complexity over here, and can we do something better? So let's first try to determine that. So space complexity, in this case, we know that we will have to use the hash map, and we will have to use the visited array as well. Inside the hash map, we are going to iterate over all the nodes plus all the edges, which means that over here the space complexity would be big O of v plus e, because we are iterating over all the vertices and all the edges. The time complexity in this case would also be big O of v plus e, because we will have to iterate over every single node and every single edge multiple times in order to come to this solution. But the thing is, we are not doing loop inside loop work, so which means we are not doing repetitive work at any given moment. Okay, after such a long explanation, let's see that there be a better approach. And yes, there is actually a very elegant, very beautiful solution, where actually we don't even have to go through all of these mess to detect that whether cycles exist or not. In order to do that, actually we need a higher knowledge of graph theory. What do I mean by that? Okay, at any given moment, suppose we are given a graph like this, that 0, 1, 2, 3, 4. Suppose we are given a graph like this, right? Now, if we want to identify that whether this is a tree or not, like in this case, we can clearly see that, yeah, this is a tree. There is a very legitimate scenario. There are no cycles. All the nodes are connected and blah, 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 whatnot. Everything is good with this, right? Can you notice an important property over here? The important property that I'm talking about is, if you count that what are the number of nodes and what are the number of edges, does there exist a correlation? Yes, actually there exists a correlation, and the correlation is that suppose we are given the number of nodes equal to n, and if we are given the edges that are n minus 1, and we determine that all nodes are connected. If we determine that all nodes are connected, because remember, in our solution, when we are trying to finding that whether the nodes are connected or not is much simpler. We simply need to use a hash set. We need to iterate over whatever the given input we have, and basically we can determine that, okay, whether the nodes are connected or not. But checking for the cycle is slightly more complicated. Actually, not slightly, much more complicated, because either we have two options and both options require us modifying a lot of things or managing a bunch of different data structures. Either we can choose to remove the edges like this, or we can choose to create a hash set like this. In both the cases, we are actually doing a lot of work. So what if we actually don't need to encounter that whether we need to find the cycles or not? If we only encounter that whether the given nodes are connected or not, if that is true, and at any given moment we identify that, okay, all the nodes are connected, and then we identify this property, that whether the number of nodes that are given and number of edges that are given, if there is the difference between them is only 1, if that is the case, then the given graph will always be a tree. Let's see in this scenario. In this scenario, we can identify that, okay, from this 0, all the nodes are connected, that this 1, 2, 3 and this 4, we are able to connect to all of them, right? What is the number of nodes? So number of nodes in this scenario is actually 5. This 1, 2, 3, 4, 5. Now let's see that what are the number of edges. So if we calculate the number of edges, the number of edges is, okay, this is one edge, this is second edge, this third edge, and this is fourth edge. There are only 4 edges that are possible. If we have any more edges, then for sure there would be a loop. Because remember, where would you add an edge in this scenario? You can add an edge over here. Okay, that creates a loop. Let's say that you don't add an edge over here. Suppose you add an edge over here. Again, it creates a loop. Well, you don't even add an edge over here. You add an edge like this. So again, this creates a loop like this. Eventually, as long as the difference between the number of nodes and number of edges is actually not exactly 1, and if the number of nodes are one number higher than whatever the number of total edges are given, if that is the case, and we determine that all the nodes are connected, then we can clearly say that, okay, everything is good with our life and we don't have to worry about anything. Why we need to check that whether all the nodes are connected or not? The only reason we need to check if all the nodes are connected or not is, suppose we are given a scenario like this, that we are given these three nodes. Suppose we are given these 4 nodes, right? And in these 4 nodes, so remember our equation is that number of nodes and edges. So if nodes are 4 and if edges are 3, so we can say that okay, everything is good with our life. In this case the number of node is 0 1 2 3. Okay, so total 4 nodes, we are good. Number of edges 1 2 3, so this is also good. The thing is, over here you can see that there exists a cycle over here between these 3 edges. And why there exists a cycle? Because this particular node is not connected. So always at any case we will have to check that whether all the nodes are connected or not. And once we identify that all the nodes are connected, we are good, and then we can just wrap up our solution. So using this solution, actually everything becomes so smooth that if we calculate the time and space complexity, the time complexity in this case is actually big O of n, because we only need to iterate over the given number of nodes, and where n defines the number of nodes. If we calculate the space complexity is also big O of n, because we only need to maintain a hash set to take care of all the number of connected edges. So once we find out that what are the number of connected, if all the elements are connected, we can immediately identify that whether this given graph is a tree or not. So let's move on towards coding now. First of all, we are going to check that whether the given number of edges, if its length is 1 less than the number of nodes or not. If that is not the case, we can return false immediately. So, and if that doesn't happen, we will have to make an adjacency list. So we will create an adjacency list, so it becomes easier for us to iterate over the given input array. So for all the given n, we are going to treat them as vertices, and all the values that are provided in the edges, we are going to treat them as edges basically. Notice over here that for every single edge, we are actually adding 2 entries inside our adjacency list, and that is because the given edges are actually undirected. So that's why we will have to add an edge for both the nodes. So if there is an edge between 0 to 1, so we will have to create 2 edges, and those 2 edges would be 0 to 1, and from node 1 to 0. So that is what we are doing by this second for loop. Okay, now we will start iterating over the given graph inside the adjacency list. And I want to learn that how to iterate over the graph using stacks. So I'm going to do it using stacks, and I will be doing iterative depth first search. So first I'll initialize a stack of integer values and just name it as stack. And we will also have to create a hash set of integers called visited. Inside our stack, we will add the first entry. So we will add the node 0. And inside our hash map visited, we'll mark the first node as visited. We will pop the first node that is inside our stack, and then we will start iterating over its neighbors. And we'll see that if that neighbor has already been visited, then we will simply ignore that case. If that is not the case, we will start iterating, we'll start adding those neighbors to our stack as well. And we will also add that neighbor to our visited hash map as well. It would be neighbor, not node. Okay, and after this loop ends, we only need to check that what is the size of our hash set. So if, or else we will return false. And let's try to run the code. Okay, seems like our solution is working. Let's try to submit this code. Okay, our solution works pretty efficiently. So the LeetCode problem we are going to understand now is called redundant connections. This is one of the most popular questions in my opinion. Why? Because we are going to be dealing with graphs. On top of it, we are also going to be learning about the trees, a data structure, and we will learn a new data structure called disjointed set union. So this problem contains two of the most popular data structures that we already know, and one very popular method that can come in handy in all sorts of different cases. So let's understand what this problem statement is asking us to solve. First, we are given the difference between a tree and a graph. The only difference between a tree and an undirected graph is that graph is connected and it can have cycles. Meanwhile, tree is completely connected and it can never have any cycles. That is the only difference. Now we are told that we are given a graph that was originally a tree, which means it could be possible that this graph may be not connected or it may contain cycles. Okay, this is the important clue, that originally this was a tree but then it turned graph and now it is no longer tree, which means there has to be some cycle existing inside this given graph that contains total n nodes, and we are given the number of nodes as to be 1 to n. On top of it, we are also given an edges array that defines that any particular edge between any two array 1 to 2. Now the thing is, we need to return an edge that if we remove it, so that the resulting graph actually becomes a tree of n nodes. That's it. So we need to basically remove an edge that is part of the cycle, that removing that edge would not have any impact on all the nodes of this particular graph or tree from being connected. And if we can remove that, then basically there should not be any cycles inside the existing graph. So let's try to understand this with few examples. Let's say that we are currently given three nodes, 1, 2 and 3, and we are given bunch of different edges between them like this one. So in this case, we can clearly see that this is not a tree. Why? Because there exists a cycle inside this loop, and wherever there is a cycle, it can never be a tree. So this is currently a graph. But imagine in this case, if I just remove this particular edge between these three nodes, then this is a very clear example of a tree. Why? Because we can see that it currently has three nodes. All three nodes are connected with each other, because that is one of the conditions of being a tree, that all the nodes has to be connected. On top of the connected portion, we can also see that there are no cycles, which means that removing 2 to 3 was one of the good decisions. And in this case, we need to return 2 3 edge as part of the answer, that if we remove this edge, then we can completely generate our answer. Now the question comes that why do we only decided to remove edge 2 to 3? In this case, if we had removed an edge, let's say 1 to 3, then also the answer would have been perfectly fine. We would still have a tree that looks like this. But thing is, we are given in the problem that if there are multiple answers that we can remove the edge, then we need to return the answer that occurs in the last input, which means like the last edge in this case made sense to be 2 to 3. So that's why we removed 2 to 3 and not 1 to 3. Okay. So now we already understood that what does the problem statement is asking us to solve. Basically, we are given a graph that contains bunch of different endpoints, and amongst some endpoints there exists some sort of cycle, and we need to first of all detect that which particular cells contain are part of the cycles, or which edge is part of the cycle, and then try to see if we are able to remove that edge or not. So if we once again take one more example, in this case once again we can see that removing this edge from 1 to 4 makes no sense. Now, why? Because it does not solve our problem. Number one, there is still a cycle persisted, and number two, now we have unconnected components. So this is no longer a tree. This is always going to be a graph. So logically, in this case, the answer once again has to be the same one, that we need to remove the edge between this 2 and 3. And by doing so, we are still going to have a tree like structure where this one node is parent of 3 different nodes, that is 2, 3 and 4, and this is what we need to do. So once again, we need to remove this 2 to 3. Now let's understand that what I'm suggesting we use to solve this problem. And for that, I'm suggesting to use a very popular data structure that is called disjointed set union. Now, first let's understand that what does this disjointed set union data structure is. So this data structure actually only has 2 properties, but these 2 properties are very important and very awesome properties. So first let's understand that what are the 2 properties. Basically, disjointed set union allows us to create a groups of set, and that's it. So it can show us that if we have like bunch of different objects or values, it can show us that that particular object belongs to which group. And if we provide 2 different objects, it can say that whether those 2 objects are part of the same group or not. So let me explain it to you, then it would make more sense to you. Let's say, so I mentioned that this disjointed set union works with 2 methods. First method is a find method, where if you provide in some value, then it can say that this value belongs to which group. Okay. On top of it, second one method is a merge method. So for the merge method, basically, if you provide 2 distinct data structure, like 2 distinct objects that belongs to separate groups, then it merges into one common group. So let's see how it works. Let's say that currently I have these 3 nodes that are part of this one particular group. Okay. And let's say that I have these 2 nodes that are part of this second separate group. Typically in a disjointed union set, all the nodes are typically represented by some node that is currently present already inside that particular group. So let's say we randomly select that this one is the leader or the representative of this entire group. So we will call this as a group 1. Okay, that every single node that is currently present is being represented by this value 1, so we can call this as group 1. Same way over here, the representative is this value number 4, so we can call this as group 4, where every single node is being represented by group 4. Now we know that we can do 2 methods. We have the find method and we have the merge method. So let's say that if I try to do a find method and if I try to find value number 3, so if I try to find value number 3, all I am going to get in the return is that this value number 3 is part of this group 1. So in the answer, I would only get value as group 1 and in the return. Why? Because all of these nodes are represented by their parent node or by their representative, and representative in this case becomes like the parent of all the nodes that are part of this particular group. Same way, if I try to do a find operation and if I want to find value number, let's say 5, then in this case the answer we are going to get back is going to be group 4, because this value number 5 is part of this group 4. Now let's say that we wanted to do a merge operation. So the moment we do merge operation between group 1 and group 4, then both of these are going to be merged into one single set, one common set. And how it is going to operate? Number one thing, this property is going to remain as it is. Now we have 2 options, which who is going to be the representative from 1 to 4, either 1 or 4. We can pick whoever we like. So let's say that in this case we decide that representative is going to be 1 of this common jointed group. So how this group is going to look like, that 1 is the representative. It already had values 2 and 3, so it is going to continue to have values 2 and 3 that represents or who has parent value as 1. But same way, now we are also going to add one more node 4, whose parents or representative is now going to become value number 1. And for this value number 5, it is still going to have 4 as one of its parents. But now for this newly created group, if we try to find that any particular character, let's say if we want to find value number 3, then for value number 3 we are going to say that value number 3 is part of group 1. So in the answer we are going to return the value as group 1. Same way for value number 5, if we try to do that, in this case once again we are not, previously we were returning value number 4, but remember now value number 4 is also being represented by value number 1. So once again for value number 5 the same property is going to be inherited to value number 5 as well. And now for value number 5 we are also going to say that this is part of group 5. So this is the whole concept of a disjointed set union. But the thing is, why the hell am I explaining you this concept? What purpose this serves us? Now let me show you that how we can use this method to actually solve our problem and very effectively find or detect that whether there exists a cycle inside any particular graph or not, or cycle does not exist. And remember, whenever you have to find a cycle in an undirected graph, then this is a very popular method in order to do this one. So not only we are learning about the redundant connection LeetCode problem, we are also learning a new method, a new algorithm, a new data structure with our existing tree and graph data structure. And that's why this is a beautiful problem. Okay. So coming back to the solution. Now remember the problem statement that we needed to find that amongst these 3 nodes, let's say that if there exists a cycle, like amongst these 4 nodes, we don't know where the cycle exists. If there exists a cycle, we will need to remove the node that is causing the cycle, or sorry, remove the edge that is causing the cycle. And once we find that, we need to return that as part of the answer. So let's say that currently we are given these 4 nodes, okay? And we are being told that these are the edges we are currently given. So what we can do is, currently we can create 4 separate groups, and these groups are not connected with each other. So if we create 4 separate groups, how it is going to look like? We will have a group 1, we will have a group 2, we will have a group 3, and we will have a group 4. Currently these 4 groups are not connected with each other. So we can actually have a disjointed union set that is currently present, that represents that for every single node, who is the representative or who is the parent of that particular node. So if we want to define that, currently we can have a parent array, let's say, and for every single node we will try to define that who is currently the parent of that particular node. So since this one is being represented by its own, so the parent is going to be 1. Same way the parent for this one is going to be 2. Same way the parent for this one is going to be 3, and so on and so forth. So currently all of these 4 nodes are unique on their own. They don't share any parents so far. Now what we are going to do is we currently have 4 edges that we need to deal with, and let's mark these 4 edges. So the first edge is 1 to 4, same way second edge is 1 to 2, the third edge is 1 to 3, and fourth edge is 2 to 3. Okay, so logically if this is the case, now we currently have parent for each 4 separate sets. We are going to start iterating over the edges. For every single edge, we are going to check that what are the current parent groups we have. And if we identify that they contain separate groups for both the vertices of this edges, then we are going to do a merge operation. Okay, let's start doing that, and then you will understand. So currently we are dealing with edge 1 to 4. Now for this edge 1 to 4, we will have to check that which are the vertices involved. So number 1 vertices is value number 1, number 2 vertices is value number 4. So for both of these, we will check we will do a find operation that who is the parent of those particular sets. For 1, the parent is already 1. For 4, the parent is currently 4. So both are separate sets. There is no commonality. So if there is no commonality, we will do the merge operation over here. So if we do the merge operation, what will happen is we are essentially establishing a link between this node 1 and node 4. So by doing the merge operation, now we will have to select that who is going to be the representative. So let's say that we are going to choose the smaller value as the representative. So I choose representative to be 1. Now if I choose the representative to be 1, which means now even for this 4, the parent is going to be 1 because 4 is being represented by 1, and for the value number 1 the parent is going to be itself. So we will have to make some adjustments to our parent array. So this value number 1 is going to stay as it is, that it is currently the parent of its own, but for this value number 4 the parent is going to change, and now this is also going to be represented by value number 1. Okay, we completed this operation, and now we have made the updation on the parent block, and we also are done with this 1 to 4 edge. So now let's take care of 1 to 2 edge. Once again repeating the same operation, we have two nodes 1 and 2, and for both of them the one has parent as 1 and 2 has parent as 2. We can see over here, but now since both are separate, so we will have to do the merge operation. If we merge these two cells, once again we are establishing a link between this 1 and 2, establishing a link between 1 and 2 now, which means we are also updating the parent of this 2 to be value number 1. Okay, and now the next edge we currently have is once again edge 1 2 3. So once again for 1 2 3 it currently has 1 and 3 as separate nodes. If we take a look at the parents, it is going to be 1 and 3. If we do the merge operation, because they are separate links, so if we do the merge operation, we are going to have our parents array that is going to look like all four values are being represented by 1, because we are also establishing this link as well. Now this is our parents array, all four values contain 1, but we still have one more link that we haven't tested, and that is this link 2 to 3. So let's do that. For this 2 to 3, if we see, we currently have vertices 2 and 3 as part, but now when we check for the parents, we can see that the parent is going to be common, that is going to be 1 and 1 for both 2 and 3. So this is going to be common. The moment we identified common parents amongst any two vertices, we can clearly say that if we were to create an edge between these two nodes, that edge is already part or is going to be part of the common nodes that are already connected in a common set. So creating this new edge is only going to lead to creation of cycle. And the moment we identify any two nodes that share a common parent, basically we can just return that edge as the answer. And this is the whole solution basically. So you understood how beautiful the solution was. We first of all understood that how a disjointed union set works. Then we understood that what is the difference between tree and a graph. Then we understood that how we can use disjointed union set and its property to find or update the parent values or create new links between any two vertices. And then we find the edge that is causing all sorts of trouble and return that as part of the answer. So this is a beautiful solution and a beautiful approach. So now let's quickly see the coding solution for this one. Okay, now the coding solution for this one is not so complicated. So let's try to understand what is being asked us to solve. First of all, we need to check that for any particular given node, we will have to define that what are all the different parents. So first we are going to initialize a new array called parents, and notice that we are setting the value as edge length plus 1. Now we are starting to iterate parent from 1, not from 0, because initially each node is its own parent, and we are being told that the current nodes we have are 1 to n, not 0 to n. So that's why we are starting from 1, and we are marking all the values as their own parent, which means all the nodes are currently individual sets of their own. Then we are going to iterate through every single edge in order to find the redundant one. The moment we identify a new edge, we are going to break both the values in part of two nodes, node 1 and node 2. For both the nodes, we are going to be finding the parents of those nodes, node 1 and node 2. And for that, we are going to be calling our find method that we have defined. Next, we need to check that if at any given moment we identify that the roots are same for both node 1 and node 2, we need to return that edge as the answer, because that edge is causing all the trouble and creating the cycle. If that is not the case, then we need to update the root of that particular second, like the parent of second root, to become the value of the first root. And this is what we are doing, is the union or the merge function amongst our two values. So let's quickly try to see the helper function we have created, that where we can actually use to find that who is the parent of that particular node. Basically, we are simply checking that if the node is not the node we currently have, if that is not equal to the parent node, we are simply going to keep traversing up in order to find that which is the parent node, and we are going to be updating the value of the parent node. That's it. It's very simple, and we are returning that value. So basically we should be able to calculate everything. Now this is just a return statement that is ideally just returning the value 0. Basically this should never happen, because we are being told that for every single input we do have a graph that contains a cycle and we need to return proper edge. So we should be able to find a scenario like this. Now let's quickly try to run this code and see if our solution is working as expected or not. Seems like our solution is working beautifully. Let's submit this code. And our code beats 100% of all the other solutions, which is awesome. In terms of memory usage, it is exceptionally well. So in both aspects, this is doing wonders, and this is a really good solution. Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Graph problems have always been a big no-no for me. I have always been afraid of graph problems, but the thing is now I have decided to take them heads on, and today we are going to start doing more graph videos. So this is the first of many graph problems to come. And this question has been really popular with Facebook recently. It's been asked 44 times, which is a huge number. Also, key other companies like Amazon, Google, Bloomberg, Microsoft, Twitter, they are also asking this question. But the thing is, Facebook for some reason has been really interested. So I highly urge you to go and check this video if Facebook is one of your dream companies to join. Okay, this is a LeetCode medium problem, and we are given a reference node in a connected undirected graph. So first let's understand the meaning of these two values. Suppose we are given a graph like this. Notice that there are only 4 nodes, and from any single node we can reach to all the other nodes in the given graph, which means that this is a connected graph. So this is what connected means. And undirected graph means, suppose we are given a graph like this, and we establish that A is B's neighbor, which means that we can traverse from A to B, and also we can traverse from B to A. So there is no restriction regarding the direction of any edge between two nodes. So we are given a reference point to that, and we need to return a deep copy of the graph. So what does a deep copy of the graph means? That suppose we are given a graph like this. So we need to return a graph like this, where if you see the values of the nodes, they are all the same. But the thing is, we are not using the exact same nodes. We are using different nodes with same node values, which means that this would be a legitimate case where we can consider this as a deep copy of this original input. The thing is, if we create a graph like this, over here we are using the same node to represent over here, which means that we are not creating a copy of this original graph. We are just referencing this point to whatever value we had over here. So this is not what we want to give. And also if we create some graph like this, if we see the values of the nodes, the values remains the same. But the thing is, the ordering is different, that in terms of neighbor selection and how they are perceived, they are different. So this is also a false case. We need to return a copy of this exact same input, just with the nodes that are copied from this one. So at the beginning, the most basic idea we are going to have is that okay, we are given an input, we are given a reference point, we know that the input graph is connected, which means that there are no loose ends that we have to worry about. So why don't we just traverse through the given input graph? At every single node we start creating a copy of it. We start creating the same sort of neighbor connections that we have in the original graph, and then just try to return the new graph. That would be a perfectly good logical rational person would think, and that would be a good entry point to start our solution. But the thing is, we are going to see that with that approach, what would be the issue, how can we remediate that issue, and what would be the final solution. So let's start. So first of all, suppose in this given input we start at this one position. So we create a new node 1. Okay, now from this 1 we can go to any neighbor, we can go to 2 or we can go to 4. Let's say that we go clockwise, so we go to 2. So we create a new neighbor over here called 2. Again from this 2 we go to 3, and over here, keeping the same logic, we create a new node. Now notice one thing, that initially we created a clone over here, we went to its neighbor. Again we created a clone over here, we went to its neighbor. Again we created a clone over here, we will go to its neighbor. So basically we are doing the same problem again and again for different kinds of input. So that should immediately click in your mind that this we are going to solve recursively. So just keep this in mind, that this is a very good way to use the recursive approach. And now at this 3, again we go to its neighbor. So we'll create an edge and we'll create a new node 4 for this one. So from this 4, again we go to its neighbor. Again we go over here. But the issue with this approach is that for this our recursion to end, we need to have a terminating case. But in this scenario we are not terminating it anyhow, because the thing is the graph is connected. We are terminating in a scenario where if the graph is empty, we return something empty or something like that. But the thing is over here, again when we come back to this 1, we are still going to see that okay, this is 1, we need to create the clone of it. We will create a clone of it again over here, which means that we are going to overwrite whatever value we have, which would be the same value. Again we would go to 2, we would again create another clone. Again we would go to 3, again we would create another clone. Again 4, again another clone. So basically we are going to end up inside the loop again and again infinitely. This is almost like Infinity War. Thanos is gonna snap his fingers, something like that, because we are completely destroying our company's resources, because it's an infinite loop. It's never gonna stop. So, and the reason it's never gonna stop is because we are doing the repetitive work again and again and again, and that is the issue. So somehow we need to resolve the issue. So how we are going to resolve the issue? Well, basically the idea is simple. If at any point, suppose we create an additional data structure, in that additional data structure we keep track of whatever the value we have traversed already or we have cloned already. If we know that, which means that initially when we start, we are going to check in that new data structure first that hey, this element, have I cloned it already? If I have cloned it already, I would skip over, I would go to next element. If I haven't cloned it already, I would create a new clone of it, and then I will put the same entry in the hash map first before I go to the next element. So that way, when after this first circle comes and when I come back to the same position, I would know that okay, I have already calculated this one, which means that I don't need to calculate it again and I can skip over it. First of all, let's see that what kind of additional data structure we are going to create, where we can immediately find that whether we have visited any particular element or not, which means that we are going to do a lot of searching. Hence we will need a data structure that is very quick and efficient in terms of finding the any element, that whether it contains that element or not. And the answer is pretty simple. If that kind of scenario happens, we need to use hash map or hash stat or something with the hashing. We cannot use the linked list over here. It would work fine, but it's going to add that much more additional time strain or on our system. So make sure that you justify your reasoning. I mean, in the interviews, people are not typically gonna ask that why did you use hash map? This is a given. But the thing is that thinking should be clear in your mind that why you are using it. And in most of the graph problems, uh, typically hash map is being used. Now inside this hash map, we are going to store two values. So as a key, we are going to store a node, and as a value, we are also going to store the node. But the thing is, as the key, we are going to store this input node, and as the value, we are going to store the cloned node that we will create. So let's see that what should be the algorithm for our solution and how we are going to approach it. So initially we start at this position 1. Now at this position 1, first of all, we check that whether we have this entry inside our hash map or not. Okay, we don't have the entry inside the hash map because we can find it in constant time. If the entry does not exist, we first of all create a clone node. Okay, clone node has been created. Now after creating the clone node, immediately before even we check for the neighbors of this one, immediately we are going to add an entry inside the clone node. So the value would be the cloned value that we have created, and the key would be the original input we are given. Now this is done. Now we are going to check for this one's neighbor. So one, let's say we end up at this neighbor number 2. So again, for this neighbor number 2, first of all, we are going to check that whether neighbor number 2 exists in this hash map or not. It does not exist, so we will create a clone. Now the clone has been created. First we will add the value to the hash map, and after adding the value, we would again go again recursively do find for the 2's neighbors. So in this case, the 2's neighbor would be 3. So we will create first we will check that whether 3 exists in the hash map. 3 does not exist, so we create the node, and then we create this one. Now again we check for the value number 4. 4 does not exist, so again we create an entry inside the hash map. We provide the key value, and then we create the clone node 4 again. Now for the 4th, we again check for its neighbor. So 4's neighbor, one neighbor is 1, which we already have it in hash map, which means that now we can ignore this case because we have already dealt with 1. Now second neighbor for 4 is 3, which already exists in the hash map, which means we can be dealt with it. We go back, 2 is already done, 1 is already done, which means that now we are running out of neighbors to track from inside the given original input. And we know that the original input is completely connected graph, which means that there is at no point there is a possibility that there exists some value 5 over here that is part of this graph, but it is not provided using this connection, because all the elements are connected, which means that this would be our final clone graph that we need to return. So after the loop ends and the recursive termination cases trigger, we can simply return whatever the clone graphs we have found, because from any single location we are able to guarantee to reach all the other elements, and once that is done, essentially we are done. So this is a very effective solution. Basically all we are doing is just we are traversing over the given graph, and during the traversal we are doing something. So in this case we are cloning it. We are using the hash map to keep track of whatever the visited elements that we have been through, and this solution is pretty efficient. It's not the most difficult problem in the world, but the thing is, I am very bad at graph problems. So and I have always been scared of graph problems, but the thing is, now I have decided to spend more time on graph problems, because if you want to join Facebook, you can't even think about not doing graph problems. Okay, so today is first of many problems to come. If we see the time and space complexity, time complexity in this case would be big O of V plus E, where V is the vertices and E are the number of edges, because notice that over here we are only doing this much work, we are not doing any additional work. So that's pretty simple. And in terms of space complexity, it would actually be big O of V in terms of number of vertices, because over here we had 4 vertices, and in the hash map we created 4 entries. So whatever the number of vertices we are provided, we are going to use that, and that would be our space complexity. So this solution is actually pretty efficient. We are using depth first search to solve this problem, but even we can solve it with using breadth first search. So it makes no difference in terms of time complexity. The thing is, I just did this using depth first search. Next one I'm going to use breadth first search maybe. So first of all, we are going to create a new hash map, and we are going to name it visited to keep track of whether we have already visited the node or not. Now inside the method, first of all, we are going to check that if the given node is null, which means that we can return the node. Okay, and also we are going to check that if we have already visited the existing node, then we are simply going to return whatever the value we have stored inside the visited hash map. Okay, if this is not the case, first of all, we are going to create a clone node. So let's just name it clone node. and inside the clone node we are going to give it the value of whatever the node value that we currently have, and we are going to assign a new array list. We are going to add the new clone node to the visited node. We are going to run a for loop for all the neighbors of existing node. So inside the loop, we are going to iterate over the neighbors of the existing node, and we are going to create the clone nodes for that. And inside the current clone node, we are going to put the neighbor as an array list. So, and over here we are going to make the recursive call with the neighbor. After this loop ends, we are simply going to return the clone node. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit the code. Okay, our solution works, and it works pretty efficiently. There is still room to make a lot of improvisation, as we can see that our solution is not the most efficient. But the thing is, I'm really bad at graphs. So it took me a lot of time to make this video because I need to understand very thoroughly by myself first before I can create the video. But soon I'm going to do a lot of graph videos. So so my video quality is gonna improve, and also my coding is gonna improve. So hope for the best, and let me know in the comments what do you think about the video. And yeah, see you next time. Thank you. Hello friends, hope you are having a fantastic day. So now we are going to do an awesome LeetCode problem called rotting oranges. We can see that this one is a medium problem and also an extremely well-liked problem. The statement is quite straightforward. We are given an m cross n grid where each cell have one of these three values. First value is 0, that represents that there is an empty cell, which means there are no values over here. Second potential value can be 1, which represents that there exists a fresh orange on that particular cell in the m cross n grid. And next value is 2, which represents that there could be a rotten orange or a bad orange placed in that particular cell. Now there comes the interesting part, that with every single minute, any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. So after every single minute iteration, we will start finding more and more rotten oranges, and they would keep on growing. Now we need to return the minimum number of minutes that must elapse until no cell has fresh oranges. That is number one thing that we are being asked. If that is the case, we need to return the minimum number of minutes. And if it is impossible to rotten every single oranges, then we need to return -1 as part of the answer. So let's try to understand this awesome LeetCode problem. Okay, so suppose this is one of the exampled input that we are given. Now notice that the values are 2, 1 and 0 given in different sections of this 3x3 cell. Now we know that value number 2 refers to a bad orange. So I have denoted that as like B over here in this grid, and 1 refers as normal orange. So I have just marked O or like 0, that represents a fresh orange. Okay, don't confuse this with like value 0, because value 0 I have left it as empty because there are no oranges or nothing on that particular place. So now let's focus on our input. Now the way we are given this problem, this is a bad orange. Now let's say that this is the current starting position. So at minute number 0, this is currently what is happening right now. But we know that after every single minute, all the oranges that are adjacent in 4 direction to this bad orange will start getting bad. So after 1 minute passes, we are going to have 2 more oranges that have gone bad, and that are these 2 oranges. So we can mark them as bad oranges, and all the other oranges that we have are going to remain as it is. This happens during the first minute. During the second minute, once again more oranges are going to get bad. So since this orange is right adjacent to this one, this will go bad, and this orange will go bad in the next minute. So these 2 oranges will go bad. So if we mark the number of bad oranges, it is going to keep on increasing in this fashion, and now we are only left with 2 fresh oranges. And during the third minute, basically we are also going to have this orange go bad, because notice that this is directly adjacent to this orange. So during the third minute this orange will also go bad, and all the other oranges we already have, they are bad. And during the fourth minute, basically, because in the third minute this orange is fresh, but during the fourth minute this orange will also go bad, and now we don't have any fresh oranges. So we can say that after 4 minutes, basically every single oranges that could go bad, they have all gone bad. So in this case we need to return 4 as the answer. Now let's say for the same example we are basically given one more scenario. Let's see that what would happen in this case. Well, we know that during the first minute the adjacent orange is going to get bad. So now we are going to be left with 2 bad oranges and few other good oranges. During the next iteration, once again the same thing is going to happen, and now in this next iteration basically this orange is going to go bad. So then we are going to be left with these 3 bad oranges and then these 3 good oranges. During the next minute, once again same thing is going to happen, and basically we are going to be left with this orange as becoming bad orange as well, and all the other oranges would remain good. And during the next iteration, basically this orange will also go bad. But notice one thing, that despite every single orange being bad, we do not have any particular way for this particular orange to go bad, which means no matter how many iterations we take, even if all the oranges went bad, this orange will still remain fresh. So in this case, because we cannot have every single orange becoming rotten, we need to return -1 as the answer. So this is what is being asked us to solve in this problem. Now I know this problem looks really interesting and really important in terms of many different aspects. So first let's try to start breaking the problem down and start understanding different things on what we can do to solve this problem. Let's say that in this problem we are given oranges like this and all the other cells are simply empty. Logically, what is the most simple thing we are going to do? Well, we need this is the initial position, so we are going to have a value called minute, and in this particular minute we are going to mark that all the minutes that has elapsed so far. So during the 0th minute this is the position. So during the first minute what is going to happen, we are going to start noticing that this orange will go bad. Okay, then during the second minute this orange will go bad, during the third minute this orange, and during the fourth minute this orange will go bad. So this case it's going to take 4 minutes for every single orange to get rotten. So the thing is, we can visualize it very quickly and very easily, but how can we implement this programmatically? So that's where few important concepts come into the place that let me start describing. Number one concept is that basically for every single position we will have to understand that what is the rotten or bad orange, and then we will have to start iterating from that particular element. So far we were lucky that the very first element was actually a rotten element, but let's say in the same scenario, instead of this being rotten, what if this was a rotten orange? Once again the answer would still be 4 minutes, but in this case we would have iterated over all of these cells before finding this rotten cell, before we start branching out. So that is number one thing, that we need to first of all find that what is a rotten orange. Okay, that is number one thing. Next thing is, the moment we find the rotten orange, what we do is we start branching out. But the question is, are we branching out in the depth first manner or a breadth first manner? Well, logically in this case we are actually iterating in the breadth first search manner, because for every single node that we iterate over, we try to iterate all of its neighbors before visiting before visiting their neighbors. And let me give you a very simple example for that. Let's say in this example, during the very first iteration we simply visit this neighbor. Okay, so we are going to mark this as a bad orange. But in the next iteration, rather than going in one particular direction, we are going to branching out in two directions and marking both of these as bad apples. And then after exhausting all the neighbors of this particular orange, then only we will start exploring more neighbors of these remaining oranges. So this is also another important point to be understood. Okay, that we will actually have to use breadth first search in this case to solve this problem. Okay, we took care of two items. Now let's try to understand that how we are going to keep track of the number of minutes. Well, logically, the answer is quite straightforward, that whenever we have to make any single new BFS call, we are going to keep track or keep incrementing the number of minutes that we will have to make. So this would be our minute counter that we are always going to update with every single new BFS call we make. Now we know that in order to use a breadth first search, we will have to use a queue, and logic is quite straightforward, that first of all we are going to iterate over all the oranges that we are given and try to find all the bad oranges we have. In this case we only have one bad orange, but it could be possible that we may be given multiple bad oranges. So let's say that we are only given just one bad orange, so we are going to put this bad orange in the queue, and with every single iteration we are going to branch out in all four directions from this bad orange. The moment we identified a good orange, we are going to mark that also as a bad orange and push it down the queue in order to be processed in the next iteration, and that next iteration will happen in the during the next minute. So this is the second important logic that we will have to understand, that how we are going to be processing the queue. Now comes the interesting question, that how would we know that we have actually isolated or completed every single oranges that we could, and whether we need to return the minutes or do we need to return -1. So for that, during the first time when we are actually iterating over to find all the bad oranges and pushing them on the queue, at the same time we are also going to have a counter that stores the number of good oranges we have. And what we are going to doing is that, let's say in this case we realize that we have 4 good oranges. Now every single time we add one value to the B, we are going to reduce one element from the good oranges. We are going to be doing the breadth first search as long as we are able to reach some oranges, and then once we get out of our loop, we will try to check that, hey, do we still have any more good oranges. So in this case we would not have any good oranges, so we can simply say that we did not find any good oranges, so we can return the minutes. If we do find some good oranges, then we need to return -1. That's it. This is the whole problem and this is the whole solution. Now I know that we can use queue plus we can use recursion to complete the BFS call. Also for this given m cross n grid, we are actually treating it as an adjacency matrix for our graph kind of problem, and every single node we are treating it, every single node that contains the value of either a bad orange or an orange as a node, and connection or the neighbors of each other are being treated as sort of like edge between them. If we see time and space complexity, in this case time complexity is going to be simply big O of V multiplied by E, vertices multiplied by edges. And for the space complexity, well, since we are not using much space except storing a queue, the space complexity would be directly dependent on the number of bad oranges or number of total oranges present, because in the worst case we might have all the oranges that might go rotten. So this is the whole time and space complexity. Now let's quickly see the coding solution, so my solution would make much more sense over there. So the very first thing we are doing is to check that if the given grid is equal to null, we can simply return -1. If that is not the case, we are going to define the values of m and end. Then we are going to initialize a count called fresh count. This is to store the fresh oranges that we have at the beginning of the queue. And then we are going to start our queue where we are going to be storing all the rotten oranges that we found so far. Now, the first thing is count the fresh oranges, and we are also going to push down all the rotten oranges down to this queue. So we simply use 2 for loops to iterate over all the values, and we are going to be counting that what are all the fresh oranges we found. And if we identified that the value is 2, which means that particular cell position is a position of a rotten orange. Okay, so now that's good. Now the very first thing we are going to check is for the edge case, that if there are no fresh oranges, we can simply return 0, that during the 0th minute all the oranges are rotten. If that is not the case, we are going to initialize a variable called minutes with the starting position 0, and we are going to have direction array to iterate over all 4 neighboring directions for any particular cell. So these are nothing special, just the 0 and 1 combinations of adjacent cells, and that we can simply add to the current I and j positions. Now we start our BFS operation, where we first check that if the given queue, we are going to iterate until the given queue is not empty. First thing we are going to check is the size of the given queue. Then we are going to check that for any particular given I position, while it is less than the size of the queue, we are going to first of all pop one element out, marking it as rotten, and then we are going to be iterating in all four directions. So notice that with the by using the direction variable, we are actually going to calculate the x and y positions of all the adjacent cells. Then we check that are we going out of bounds. If we are not going out of bounds, then we are going to be turning the fresh oranges into the rotten, and we are going to be reducing the count of the fresh oranges that we found so far. On top of it, we are also going to be updating the rotten queue and adding those values inside our queue as well. Lastly, we are going to be updating the minute variable for every single new breadth first search operation that we make, because this is the increment timer for every single level of BFS. Now, in the end, we simply have to check that if the given fresh count is equal to 0, we are going to return minutes. If that is not the case, we are going to be returning -1. That's it. Now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs extremely fast, and it beats 99.99% of every single solution, which is pretty great, pretty awesome. Once again, you can see the coding solution on our GitHub repository, so feel free to go ahead and check it out. Thank you. So the LeetCode problem we are going to solve now is called walls and gates. We can see that this UI looks slightly bit different than our typical LeetCode problems, and that is because this is actually a very popular LeetCode premium problem. So that's why I took this screenshot from a website called leetcode.ca. So whoever is operating that, thank you so much. Now let's understand the problem statement. We are given an m cross n 2D grid that is initialized with three possible values. First possible value is -1. So -1 defines that there is a wall or an obstacle that we cannot cross over. Next value is 0. 0 defines that there is a gate. And third value is an INF. So INF is a very large number basically. And if we are given this very large number, that defines that the given room is empty. So basically we are given three distinct values. One value defines that on that particular cell position, there could be a wall, or it could be a gate, or it could be an empty room. So for the rest of this problem, let's just try to use only these three values, so it would make sense for us to understand. Okay, now we need to fill each empty room, so each cell that contains the value E, with the distance to its nearest gate. So this is the gate that we are given. We need to calculate the distance from every single empty room to its subsequent nearest gate, and if it is impossible to reach a gate, then it should be filled with an infinite value, or which means like an empty room. So let's try to understand this with an example. Basically, we are going to be given a grid like this that contains three different values, infinity, -1 and 0. But the thing is, I have presented them slightly nicely over here. So let's try to understand and figure out that what does this problem statement is actually asking us to solve. So we can see that there are a bunch of different empty rooms that are currently given to us, and we are only given two different gates that these empty rooms can try to reach to. Plus, for some empty rooms, we actually have walls that are coming in between. So we will have to ignore those walls and try to figure out that what is the best way to reach to those particular gates. So let's just create an empty like empty m cross n grid, and we will try to fill out these values. So we can see that for this very first position, this one is an empty room. So what are the closest gate to this empty room? One closest gate is located over here. If we calculate the distance, this is actually 3 cells away. So in this case, one option is that we can fill value 3 over here, or if we have to calculate the distance between second gate, it looks like this is very close. This feels like that this is only 2 steps away, but that is not the real case. Why? Because there is a wall in between, so we cannot cross the wall. So if we have to reach to this particular gate, we will have to go down this path and then this path and then this path. So that actually makes the total distance as 4. But the thing is, we need to calculate the shortest distance. So over here, shortest distance to the gate is going to be value number 3. Same way, shortest distance over here is actually going to be this gate, that is this value number 2. Shortest distance over here is once again this gate, and that is this value number 1. Now this value is already gate, so we can define it as 0, or let me just mark it as gate for our understanding. Now at this particular position, the closest gate is actually this one, and this is only 2 steps away, so we can actually mark value 2 over here. Same way, this is only 1 step away through this gate. Same way, this is also 1 step away through this gate. Same way, this is 2 and this is 3, and this one is actually 4 steps away from the gate, and that path is actually going to be this one. So this is going to be 4. For all the other ones, the walls are always going to remain the walls, so we can simply mark the walls as it is, and the gate is going to be as gate, and this is what we need to return as part of the answer. Now for some reason, let's try to understand that suppose this value is also a wall. Let's say that over here, let's say that this value is also a wall, okay, just for the understanding purpose. So then now at this position, we have no way to reach to a gate because both adjacent doors contains a wall. So in this case, we are still going to make put this as an infinite value or mark it as an empty cell. So just for our understandings. Okay, so let's break down the problem in subtask and we will try to calculate the result. Number one thing we need to check is that distance of any particular cell from the gate. This is the number one thing. Second condition we have is that if there is a wall, we cannot cross, so we cannot go to the wall. We should not consider. If there is an empty room, we will try to find that how many steps it take from empty room to reach to the gate or from gate to reach to the empty room. So now what the approach I'm suggesting is that if we try to calculate at every single gate that every single empty room, that where is the closest gate, and if we try to find this one, this problem can get like slightly more expensive. Why? Because remember that at this gate location we will have to do like either a BFS operation or a DFS operation, and we need to keep on iterating over of every single possible neighbors in order to calculate that where does the nearest gate lies, and it could take potentially big O of like m cross n times for every single grid in order to find both the gates in the worst case scenario. So this problem can become like m cross n multiplied by m cross n. That is going to be very expensive problem. So rather than finding out the from like distance from empty room and searching for the gates, it would make much more sense that from any particular gate we can start iterating over and branching out in like different traversal fashion and try to find the empty rooms. And for each traversal that we make, we simply have to do one iteration because we know that it is one step further from the gate in order to reach to that particular empty room. So what the approach I'm suggesting is that first of all, we simply iterate over the given input array and given input matrix, and try to mark all the positions that contains gate. We identified that this contains gate. Now from this gate, we start traversing in all the possible directions until we exhaust every single possibility of finding an empty room from any particular gate. That is number one thing. Second thing is that we also take care or take into the consideration that if I have to reach to any particular empty room, how many hops did I had to take in order to reach to that empty room. Also, it could be possible that some other gate can also reach to same particular empty room. Then we will try to put the value that contains like the lower value compared to the current value we have as part of the empty room. So let me explain the solution, then it would make sense. Now the question is, let's say that we identify that these two are the gate positions. We know where we want to iterate from, but the question is how are we going to iterate? Are we going to use depth first search or breadth first search? So logic is quite straightforward, since in this case we will have to calculate how many hops it take to reach to any particular location, we don't want to do the backtrack and keep on going in just one direction. We actually wants to branch out in each of the directions. So logically, it would make more sense to use breadth first search in order to calculate our result. So if we have to use breadth first search, we will actually have to use a queue in order to generate the result. So idea is we are going to initialize a queue. In the queue, we are going to mark all the positions that contains the current gate values. Then from this particular gate value, we will keep on iterating over until the next element, and all of its neighbors that we are able to reach that are currently empty rooms, we would mark them to the gate as well, and we would try to update the value of those empty rooms by 1 plus. And the moment we do the next iteration, we will add one more value. The moment we do the next iteration, we will do one more value. So let's say that we start our iteration from this value. So currently this one is a gate. Okay, these are all the walls that we cannot use or we cannot go over. So let's try to start populating our array using this gate value and see that how is the result we get. During the first iteration, we are going to go down this path. So we know that for both of them, the distance is going to be 1, 1. And currently, remember, the distance is infinite. So we are always trying to put the smaller distance on the place of the gate. Next is from here we cannot go anywhere because this is a wall. We already visited this node, and so there are no other ways to go. But from here we still have two ways to go down. So let's mark the values for both of them. So this is going to be 2, this is going to be 2. Once again, from this 2 we have one more way to go, so this is going to be 3, and from 3 we have one more way to go, this is going to be 4. That's it, we exhausted all the possibilities down this path, but over here we still have more paths that we haven't traversed over. So this is going to be 3, then this is going to be 4, this is also going to be 4, then this is going to be 5. So, or sorry, no, this has to be a gate value, so we are not going to do anything. So now we exhausted all the possibilities at this gate. Once again, we are going to repeat the same process from this gate and try to fill in the lower value. So if we branch out, this value actually becomes 1 because this value is, and 1 is less than 4, so we are going to put 1 over here. Then this value becomes 2 because 2 is less than the current value we have, so this becomes 2. Then this value becomes 3 because this value is actually smaller than this one, so we can mark this as 3. Now from this 2, if we have to go this way, this becomes 3, but we already have a 2 which is already a smaller value, so it makes no sense for us to go down this path. From this 3 we cannot go anywhere else, so that's it. Now this state actually contains every single possible like distance of empty room to the gate that we have been able to identify, and all we had to do was to use a breadth first search starting at the gate and keeping track of all the graph related principles. So basically keeping track of all the visited nodes and updating the value from the current position, or every single new BFS we make, we simply have to add value by 1, and then we need to branch out in all 4 directions where the given gate is the given cell value is not a gate and it's not a wall, which means any place that is an empty room, we need to calculate that what is the distance from a gate. And if we do this for all the gates, eventually we would left with what is desired from us that we can return. So if we have to understand the time and space complexity, in this case the time complexity is going to be big O of m multiplied by n, but we will have to do this by the number of gates that are present. And if we see space complexity, well, we will have to use a queue in order to do that, and queue depends on the number of elements, so it is also going to be big O of m multiplied by n, and this is what we need to return. This is a pretty good time and space complexity, and congratulations, you just learned an awesome LeetCode problem. That is a premium problem, and you didn't have to pay for the LeetCode premium. So anyways, now let's quickly see the coding solution. So this is going to be the solution, and I cannot run this in LeetCode because this is a premium problem, but I would still paste the solution in our GitHub repository so you can check it out from there. So we have our infinite marked as a very large number. Then we are creating a static position called direction to iterate over all 4 directions. Basically this will help us during our breadth first search calls. Now this one is the main method, the walls and gate method, where we are given the rooms as part of the input. We first check for an edge case, that if the given rooms are null, we can return. If that is not the case, we define the values of m and n. Then we also initialize a new queue, which we are going to use to do a breadth first search. Then we are going to find all the gates that are currently present inside our given array by using two for loops, and we are checking for the value that is equal to 0. After that, we are simply going to do a BFS for every single gate, where we are checking that for this particular gate position, what are all the four directions that we can explore into. For each of the four directions, we are going to check that number one, we are not going out of bounds, and number two, if the given value of room that we are reaching to or the cell is actually infinite, then we are simply going to update the value of the distance, and in the end we can simply add that value to our queue as well to keep on updating the distance. So basically we are going to be storing like the smallest distance possible from every single gate, and this is what we need to return in the end. So this solution would work as expected. And now let's I won't be able to run it, but you will be able to find the solution at my GitHub repository, so feel free to check it out from there. Thank you. So the LeetCode problem we are going to solve now is called surrounded regions. We can see that this one is a LeetCode medium problem and also very well like problem. Now the statement is quite straightforward, that we are given an m cross n matrix named board that contains bunch of different x's and bunch of different zeros. Now we need to capture all the regions that are four directionally surrounded by x. And if a region is captured, then we need to flip all the zeros into that particular region into the axis that is a surrounded region. So let's try to understand what they are trying to ask. We are given in this example an m cross n board where we can see that there are bunch of different x values and bunch of different zero values. Now in this case, what is the definition of any particular zero region to be surrounded? A region is surrounded if in all four directions it is connected by some sort of x in each one of them. If that is the case, we can determine that this particular region is surrounded. Now notice one important thing. We are not concerned with its immediate neighbor, but even if the neighbor of the neighbor is still a value x, then we can determine that that particular value is still surrounded by x's. So the moment we identify a surrounded region, all we need to do is convert all the zeros into x's, which means we can see that this node is surrounded by 4 x's in these four directions. Same way with this particular zero, it is surrounded by these 4 x's, and same way for this particular zero, it is surrounded by these 4 x's. So logically all of these would be converted into the x's, which we can see over here. But for this particular region, it is only surrounded by x in 3 different directions, not 4. So we are not going to flip this 0 into x, we are going to leave it as it is, and then we need to return this state of the m cross n grid as part of the answer. So let's try to see that what is the simplest logic we can use to solve this problem. Now let me give you one example of bunch of different zero potential values in all of these different grids. Let's say for this particular grid, if we have any single value 0, then that value has to be not surrounded region. Why? Because currently this particular value is located over here. Even if in all the other directions we have access, then also we would never be able to get a 4 directional pattern where this region becomes a surrounded region. So in the answer, we are always going to have a scenario where this 0 is going to remain 0. Same way for this 3 by 3 grid, let's say that if we have any particular 0 present over here, and let's say that all the other values are currently x's, then we can very easily determine that this 0 is actually surrounded by x's in all 4 directions. So in the answer, when we try to create, basically this 0 has to be flipped into x. That is true. But let's say instead of doing that, instead of this being 0 in this middle portion, let's say if we have 0 located at any of these edges, any of these, okay, I'm not saying all of them are zeros. Let's say any one of this is a zero, and let's say that all the other values are x's. So I'm currently marking these by a bunch of different x's. This region would never be surrounded. That's a given fact. Why it would never be surrounded? Because there is always going to be one or two directions where it is located on the edge, which means there can never be an x planted over here. So if the node is in the middle, then it has the possibility of being a surrounded region. But if we identify 0 at any particular edge, then that 0 is always going to be a not surrounded region. So it does not needs to be changed. That is what I'm trying to explain. Now let's try to see one more example in this case. Let's say if we have any particular these 4 zeros placed like this and all the other values are x's. In this case, all of these zeros has to be converted into the x's because all of this becomes a surrounded region. But for some example, if we have any particular zero located over here, we already established that this does not needs to be changed. That is number one thing. Second thing is that not only this does not needs to be changed. Let's say that if there are any particular other zeros connected with this value, then also they are also going to be not surrounded regions. Once again, I repeat, if there are any particular zeros that are connected with this edge, then we can determine that this is also going to be not a surrounded region, and we are going to exploit this property to its fullest. Because remember, in this case, particular this zero is actually always going to have one more zero located over here, which means it can never be four directionally challenged by another zero. And this is what we are going to use to solve this problem. What we are simply going to do is that we are going to treat this as a graph problem. Not only a graph problem, we are also going to treat it as a graph traversal problem, where we need to do the depth first search. At any given moment, we identify a value that is currently 0. The thing is, we are not just going to blindly start looking for zeros in all of these particular grids. That it makes no sense. If there is any particular 0 in the middle, there it might be possible that there might be excess in all four directions that could prevent it from becoming a not surrounded region. What we are going to do is we will try to only traverse into the edges of this particular matrix, and for each of the edges we will try to find that if there exists any particular 0, then we are going to start doing the DFS, and all the values that we identified through this iteration, we are just going to mark those numbers that they are always going to be four directionally not surrounded regions, and all the other regions or all the other values we can simply mark them by X. So let's try to understand this with an example that I'm trying to show you. Let's say that in this case we are currently given that these two nodes are currently zeros, and let's say that this is connected with this 0, and let's say that this one is not connected with anyone else, and then we have this 0 connected like this, and all the other values are currently X values. So logically, the algorithm I'm proposing is that we start iterating over this m cross n grid in first of all the edges. So let's say that these four are the edges, and then we once again identify this edge and this edge, and then this edge and this edge. So we found a one edge that contains a value 0. The moment we identify one edge that contains the value 0, first of all, we are going to mark this one as a special 0. So let's say that I'm keeping track of all the zeros that I have been able to identify so far. And let's say that this one is a special character that contains a 0 at the edge. Then we are going to do the DFS operation in all four directions to find all the connected zeros. But we can see that this one does not have any connected zeros. So we are just going to say that this is the only 0 we find, and then continue with our iteration. Once again, we are at this position. This is also X. Once again, we identified one more 0. So the moment we identify one more 0, we are going to mark it as a special character, and then we are going to start doing the DFS operation in all four directions. This one is an X, so we don't do anything. This one is an X, so we don't do anything. But this one is not an X, so this one is also a 0, and a 0 that has been found by reaching a 0 that was present in the edge. So once again, we are also going to mark this as a special character, and then now from now on we cannot move ahead anywhere forward, so we cannot do anything. On top of it, for our DFS operation, we will have to keep track of all the visited nodes. So we are also going to mark all the visited nodes as well. So it's just simply for our convenience, and that's it. So once again, we don't find any more access. So then we simply say that we iterated all the edges. We did the DFS on whenever we found a 0 at the edge, and we marked those nodes. And apart from these nodes, everything else should be converted into the x's, which means this node has to be converted into an x, and that's it. This is the state of m cross n that we need to return of all the zeros that are not surrounded, and all the surrounded regions are being converted into the x's. So that's it. This is the whole solution. If we try to understand the time and space complexity, in this case time complexity is going to be big O of m cross n, because we will have to iterate over every single nodes, and this is an example of adjacency matrix kind of representation for the graph. Space complexity, well, this is debatable. If you have to create a new snapshot, then you might have to use m cross n space. If you can modify this current existing node just by changing this character from something else from 0, maybe something like a hash or something, then also we can use the same pattern or same logic. So it's up to you how you want to approach that, or how your interviewer wants to do that. It can be a common space complexity, or if you are not allowed to change the input, then it is going to be big O of n cross n space complexity. So now let's try to see the coding solution for this one. So the coding solution is quite straightforward. We need to solve the given board, and first we are going to check for the edge case, that if the given board is equal to null, we can simply return. If that is not the case, we are going to define our m and our n. Then we are going to start iterating over the boundary and start marking all the zeros that we find on the boundary as like a temporary character or a temporary variable. So let's say that we run 2 loops. We have this if condition that if the given node is equal to 0 or m cross m minus 1, and j is equal to 0 or n minus 1, which means we are checking for the edge nodes. On top of it, we are also checking that if the given board position marks the value as 0. If that is the case, then we are going to call our DFS method. In the DFS method, we are checking that all the surrounded regions that we need to find. So this is our DFS method, where we are first of all checking that if the given node is equal to null, or we exhausted all the possibilities, we can simply return. If that is not the case, we are going to mark that particular value as a temporary character t, stating that this has been visited, and we are going to run the DFS operation in all 4 directions repetitively, which means we are only going to be left with temporary values that are currently visited by us after this DFS operation, that are connected with the zeros that are located at the edge. Then once that is done, we simply need to check and capture all the surrounded regions. So for that, we can simply iterate over the given input array and check that if the given input board position is equal to 0, which means it is not t, then we are going to simply mark it as x. If that is not the case, and if that value is t, which means it is not a surrounded region, so we are going to mark it as 0. And that's it. This is the whole solution. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code is exceptionally faster compared to all the other solutions, which is great to see. And once again, you can find the solution on my GitHub repository. Link is in the description. Thank you. Hello friends, we are still not employed by FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do course schedule LeetCode problem, and this is one of the most versatile problem that has been asked at bunch of different companies, like huge number of companies. We can see the companies like Amazon, Microsoft, Facebook, Google, TikTok, Snapchat, Robinhood, Twilio, Uber, eBay, Tesla. All the companies have asked this question, and this question is very practical, real life application. So that's why a lot of companies like to ask this question. So this is a LeetCode medium problem, and we are given a number of courses, and we are also given an array of prerequisites, where any single entity in array is defined like this, where we are given 2 values, suppose a and b, separated by a comma, which means that we must complete course b first, in order for us to complete course A. So suppose we are given an entity in the prerequisites like this 1 and 0, which indicates that this course 1 actually has a prerequisite called course 0. So we can define it like this, that course 1 has a prerequisite on course 0, and in terms of the practical manners, we first complete this course 0 in order for us to complete this course 1. And based on the information given, we need to check that whether we can finish all the courses or not. And if we can finish all the courses, depending on whatever the prerequisites we are given, we need to return true, otherwise we need to return false. Okay, now that we understand the problem statement, let's take a custom example to understand the problem. Suppose we are given the list of prerequisites like this, and we are given the number of courses as 4, which means that we need to complete the 0, 1, 2 and 3. These 4 courses we need to complete, and this is the list of prerequisites we are given. Now we can consider this as actually graph problem. We can consider these as graph nodes, and the prerequisite information we can treat them as graph edges. So over here we can say let's plot it on a graph and let's see that how it would look. So over here 1 has a dependence on 0, so I mentioned this. 0 has a dependence on 3, so let's also mention this. And 2 has a dependence on 0, so 2 has a dependence on 0. Okay, so this is how we can plot this on a graph, and we need to see that whether we can complete all of these forces or 4 courses or not. So the most intuitive solution is to check from the beginning. We check at this course number 0, that can this course number 0 be completed or not. Now in order for us to complete this course number 0, we see that this course 0 actually has a edge pointing towards course number 3, which means that course 3 is a prerequisite for course 0. So we need to complete this course 3 before we can complete course 0. Now we are at this course 3 again. We check the same thing, that whether we can complete the course 3 or not. Now course 3 does not have any prerequisite, which means it can be completed on its own. So we say that okay, course 3 can be completed. Now again we backtrack to 0. At 0 we check that does 0 have any other prerequisites that we need to take care of. No, 0 only has one prerequisite on course 3 which we can complete, which means that we are able to complete course 0 as well. So we can mark this and the square box indicate that we are able to complete that course. So we are good. So we already know that 0 can be completed, 3 can be completed. Now we check for this course number 1. So at course number 1, we check that what are the prerequisites for course number 1. Well, course number 1 has a prerequisite on course number 0. So since we already know that course 0 can be completed, which means we can also conclude that course 1 can also be completed, which we can mention over here. And we can check for this course number 2. So course number 2 also has a prerequisite on course 0, which is already done, which means we are able to complete course number 2 as well. So in this case, for all the 4 courses, we are actually able to complete them, and we can return true in this case, that yes, based on the given number of courses and prerequisites, we are able to complete all the courses. Now we need to check that what could be the scenario if we cannot complete the course. So suppose we are given an additional edge like this in the same example. Suppose we are given this additional edge. Now let's see that how the dynamic would change. Let me clean this up a bit. Okay, now we have this additional edge 3, 2, which means that in order for us to complete this course number 3, we would need to complete course number 2 as well. Now let's see that can we complete. So initially we would check that can we complete this course 0. So in order for us to complete course 0, we would need to complete course 3. Okay. Now in order for us to complete course 3, we would need to complete course 2. Okay. And again, in order for us to complete this course 2, we would have to complete this course 0. So notice that we are constantly stuck inside a loop. It's the same scenario where you need experience to gain a job and you need a job to gain experience. It's somewhat similar kind of example, that we are stuck inside the loop, which means that no matter what happens, we are not able to complete any of these 3 courses without completing the other one, because there is an interdependence between each other. And essentially in this case, we would have to return false, that we cannot complete all the courses. But the thing is, why did we have to return this false? Well, the reason is quite simple. Basically, we, in terms of graph manner, if we speak, what was the difference from this graph compared to this previous graph? Only this edge. And when we added this edge, what essentially we did was we introduced a loop inside our graph amongst these three values 0, 2 and 3. So we can conclude one thing, that at any given moment, if we've identified that there exists a loop inside our graph, we would be able to immediately return false. If there does not exist a loop and we are able to, from every single element, we are able to complete all these prerequisites, in that scenario we need to return true. So now we have these two information. Let's see that how can we use them and how can we solve this. So suppose we are given an example like this, and these are all the prerequisites that we are given, and we need to complete the total six number of courses in order for us to conclude that this graph can be scheduled or not. So essentially we are going to apply the same logic. We are going to first of all take these inputs, we are going to convert them in a graph like this. Inside the graph, for every single course, we are going to see that whether we can justify these prerequisites or not, and at any moment if we identify that there exists a loop, we will immediately terminate and return false. If there does not exist a loop, we would keep going, and eventually we would return true. So that is the idea. And in order for us to achieve that, first of all, what we are going to need is, we are going to need some sort of graph data structure, because initially the only two values we are given is number of courses and the set of prerequisites. So first of all, we would create a data structure like hash map, and inside of our hash map we are going to store two values. We are going to store, as a key we are going to store the number of courses, and as a value we are going to store the number of prerequisites that every single course has. So initially we would have, so this is the number of courses and these are the prerequisites that we have. And we would try to see that can we complete all the courses or not. So first of all, we are at this course 0. So in order for us to complete this course 0, we need to see that what are the prerequisites for course 0. So for course 0, the prerequisite says course 2. Now for this course 2, what is the prerequisite? The prerequisite is actually course 3. Okay, and now for this course 3, the prerequisite is actually course 4. So here, and for this particular course 4, the prerequisite is actually course 5. So here, now we are at this course 5. We check that can we complete this course 5, and yes, we are able to complete the course 5 because there exists an empty list. So which means we can conclude that course 5 can be completed over here because there is an empty list. So again we backtrack, we go back to course 4. At this course 4, we know that course 5 can be completed. Since course 5 can be completed, we can also have an empty list over here, because it defines that at any moment, if we are at this course 4, that course 4 can always be completed because its prerequisites are already met. So we can have an empty list over here. Now again we go back. If we go back, we are at this course 3. So in order for us to complete this course 3, we would need to set up an empty list over here because course 4 can be completed. That is done. Now again we come back to this course 2. At this course 2, again we will create an empty list, and now we are at this course 0. So at this course 0, we only have dependence on course number 2, so we can also have an empty list over here, basically defining that course 0 can be completed. Okay, so that is one observation that has been done well. Now, and see that we were only trying to calculate that can we complete this course 4, but we already concluded that we can complete all these courses as well, and we have already established them inside our hash map. So at any moment, we only need to identify the remaining courses and not all of these courses that we have solved already, which means we are efficiently improving our solution. Second, we come at course 1. Now this course 1 actually has 3 dependencies, course 2, course 4 and course 5. So let's take care of each of them one by one. First of all, we will check that from course 1 can we complete course 2. So we check for this course 2 and we check that these prerequisites are already met because there exists an empty list, which means that we can eliminate course 2 from over here from the list of prerequisites because we know it can be completed. Again, we check the same thing for this course 4. Over here, this course 4, we again have the empty list, so we can also eliminate the course 4 over here as well. And again, we can repeat the same process for this course 5, that course 5 can also be completed because there exists an empty list, which means even at this position course 1, we can create an empty list over here, And now if we look at all the courses, the only prerequisites we have are just empty lists. And once we achieve that, basically we can conclude that we have already reached our solution and we can return true in this case. So this solution works perfectly fine. But the thing is, we missed the key point over here. Like, because this was a true scenario, we did not identify any issues. But the thing is, if there was a loop, we were not actually checking that whether we are encountering any loop or not. So let's see that if we want to encounter any loop at any iteration, what would be the additional steps we need to take. So let's modify our example a bit. Suppose we have an additional prerequisite like this 5 3, that in order for us to complete this course 5, we will need to complete course 3. So we will have an edge like this, and let's modify our prerequisites table. Okay, now in this example we know that there exists a loop between this 3 4 and 5, so we need to take care of it. And in order to take care of it, I'm suggesting that we create an additional hash set at the beginning of checking for any single course. So we create a hash set, and in our hash we just name it as visited or something. And over here we will keep track at any location are we repeating the same element. So let me show you what I mean by that. So initially, suppose that we are at this course 0 and then we start our program. So we want to check that whether we can complete course 0 or not. So first of all, we will check that whether we have already visited this course 0 in this current iteration. So we check in this visited node that have we visited course 0, and because it's a hash set, it's a constant time operation, so we are not adding any additional strain on the time complexity. So we haven't visited this node 0. We would add an entry over here first. Now we will check over here that what are the prerequisites for this course 0. So the prerequisite is course 2. So again we would check our visited node first. So course 2 is not part of it, so we would add an entry over here. And again we would continue over here. So now we need to check this course 3. Again we would add it entry to the visited node. We check over here, we need to check course 4 we haven't visited, so we would add an entry over here. Then we would check the fourth prerequisite 5 we haven't visited, so which means we would add an entry over here. And now at this 5 we would check the prerequisite for 5. So for the prerequisite for 5 is actually 3, so we are again at this position 3. So first of all we will check that whether we have visited this 3 or not, and this time we would know that yes, we have already visited this node 3, which means that we are in a loop. So this is what this hash set confirms, and the moment we find out, we can immediately return false over here. We don't even need to check any additional items in this given graph, and we would be able to terminate our case immediately. Which means, and in case if this edge was not existent, this entry for this value number 5, we wouldn't have to check anything, and we would have been able to complete all our code, and we would have been able to return true, but which is not the case this time, because there exists an additional prerequisite as specified over here. So this would be our final solution. And now let's calculate the time and space complexity for this one. So for time complexity, we can actually complete this whole thing in big O of v plus e time, because at any moment the maximum traversal we will have to do is from one node to all the single nodes, and throughout all the single edges. So this would be the time complexity. And space complexity, because we are creating an additional data structure like this hash map and also this hash set, but the thing is hash set is going to be smaller, so we are only concerned with this hash map. For general time complexity, it would be space complexity, it would be big O of v plus e as well. Okay, first of all we will create a hash map, and we are going to store integer and list inside it. We will name it course graph. Okay, now we will have to build our graph. So essentially we are going to iterate over every single prerequisite in the given prerequisites And first of all, we will check that whether this prerequisite is already added in our graph or not. So if it is added already, we only need to append the new prerequisite. And if it does not exist, we will need to create a new one. We'll have to create a new entry in our course graph. So we will create a new list and add the list, and then we will add the entry of the course and the list to our graph. Okay, so after this loop ends, we should have our graph structure ready. So now we will create a hash set that will take care of integer values, and we'll name it visited. And now we will have to run a loop for all the courses that we are given. And now we will have to create a method to check that whether there exists a cycle inside the loop or not. And let's name our method that course schedule, which indicates that whether we can schedule a course or not. In this course schedule method, we are going to provide the current course, the visited node, and the graph that we had created. And if this responds back to false at any given moment, we would know that we cannot create the course schedule, so we will return false immediately. And if this loop ends and we don't return false, which means that everything was successful and we can return true. Okay, now we will have to create this course schedule method. So let's create a boolean method. Now let's test our terminating cases. So if our set contains the current course, which means that we have detected a cycle, so we can terminate immediately, so we can return false. Also we check that if for the current course, if we already have an entry in the graph where it has an empty array list, we can return true. If that is not the case, we will have to iterate over all the prerequisites for any particular course. So first of all, we will add the current course that we are iterating over in our visited hash set. Then we will iterate over every single prerequisite for that particular course. We would call our recursive function. So and we will provide the current prerequisite we are at. We will provide the visited hash set, and we will provide the graph. And if at any point this returns false, we can return false immediately. However, if this loop executes, we know that for that particular course we are actually able to complete the course, and we can schedule it. So first of all, we will remove it from the visited node, and then now since we know that this particular course can be completed, we would update the entry for that course in our course graph. So we would set the prerequisite to null, which means that in future at any point if we identified this particular course, we know that we are able to complete it and we can just move forward quickly. And at the end we can simply return true in this case. So I guess this would be our course schedule function where the main logic happens. And let's try to run the code. Okay, seems like our code is working. Let's try to submit the code. Okay, our solution works, and it works pretty efficiently. So I would be putting this solution in the comments, you can check it out from there. And this was a really long video. It took me a lot of time to make it. So I hope you like it, and let me know in the comments on what are your thoughts about this problem. See you next time. Hello friends, I'm a cloud solutions architect at Microsoft, and my aim is to empower every single person to become better at technical interviews. Keeping with that goal in mind, today we are going to solve a very important LeetCode problem. So let's get started with the problem. So today we are going to do course schedule 2 LeetCode problem, and if we see some of the popular companies who have already asked this question, there are companies like Amazon, Google, Microsoft, TikTok, Apple, Plantier, ByteDance, Roblox, Uber, Facebook, Robinhood, Snapchat, Bloomberg, DoorDash, Lyft, and Goldman Sachs. So this has been a very popular question at many different companies. I'm going to pay my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem and also very well liked problem on LeetCode. In this case, we are given two items. First item is number of courses. Now the number of courses, it says that suppose we are given number of courses to be 3, which means that we are given the courses 0, 1 and 2. Suppose we are given the number of courses to be 5. In this case, the courses are 0, 1, 2, 3 and 4. So this is what the number of courses define. Second item we are given, which is more important, is the array of prerequisites. Now, what does an array of prerequisites define? Well, there can be a structure that looks like this, A, B. What this means is that course B is a prerequisite for course A. We all know that we need to complete like the prerequisite course in order to go and do the more advanced level courses. So in this case, if we complete course B, then we are eligible to complete course A. But say for example, for some reason we are not able to complete course B, we are guaranteed that we would never be able to take part in or be eligible to complete course A. Now, after having these two items, number of courses and prerequisites, basically what we need to do is we need to return an ordering of courses such that we are able to finish all the courses. And what does finishing all the courses means? That we are abiding by the list set of or the all the prerequisites that we are given amongst all the courses. And definitely there could be many different answers to that. We can complete the courses in many different ways, so we need to return any of the valid answer. And for some reason, if we are not able to complete all the courses, we need to return an empty array. So let's try to understand this with few examples. So in the first example, we are only dealing with 2 courses. So the 2 courses are going to be 0 and 1. Now for these 2 courses, we are only given one prerequisite, and this prerequisite says that course 0 has to be done in order to be eligible to complete course 1. So if we complete the courses in the ordering of 0 and 1, then this is going to be a legitimate answer, where we complete the course 0 because it has no prerequisites, and since we have already completed course 0, we are eligible to complete course 1, and this is going to be a valid answer, so we can return this as the answer. If we take the second example, this is a little bit more complicated. Now we are dealing with 4 courses, which means courses are 0, 1, 2 and 3. Now in this case, if we see, there are a bunch of different prerequisites, so let's go every single one of them and try to find some answer. So first one, it says that course 0 has to be done before we can do course 1. Okay, that is good. Second one says that course 1 needs to be completed before we are eligible to do course 2. So we have already completed course 1 over here. So let's try to do course 2 after that. Then it says that course 2 has to be done before we are eligible to do course 3. So over here we are already done with course 2. So let's complete course 3 after that. So this is one of the valid orderings. And in this case, if we return 0, 1, 2 and 3 as the answer, this is going to be a perfectly valid answer. And in this manner, we are keeping track of all the prerequisites and we are also completing all the courses. Let's take one final example. So if we see in this final example, this is a little bit different example. So over here, we are given 3 courses. So courses are going to be 0, 1 and 2. Now we are given some prerequisites. So let's try to go through each one of them. So first one is 0 to 1. Okay, we need to complete course 0 in order to complete course 1. That's good. Now second one, it says that we need to complete course 1 in order to complete course 2. So 1 we have completed over here. Let's create it for 2. But now this prerequisites, it's a little bit tricky, and the tricky part is that we need to complete course 2 in order to complete course 0, which is the tricky part, because now if we see, there is no way for us to complete like all 3 courses, because every single time we are going to be bounded by some other course, because definitely in order to complete course 1 we need to complete course 0. In order to complete course 0 we need to complete course 2. In order to complete course 2 we need to again complete course 1, but we cannot complete course 1 because 0 hasn't been done. So this is going to be keep running in the round and round, and this is a huge problem. So in this case we are simply going to return an empty array because we cannot find an ordering that satisfy all the properties. So based on my drawings and all the logic I'm trying to show you, it becomes pretty trivial that how we are going to solve this problem. The way we are going to solve this problem is using graph theory, and for the graph we need two items. We need nodes and we need edges. So as the nodes, we are actually going to use the number of courses, that all the courses are going to represent a node in itself. And for the edges, we are going to take all the values that are present inside the prerequisite table, and based on that we are actually going to create an edge, and that is going to give us very interesting results. Now in this case, say for an example, just consider this example and let's try to draw a graph in this case. So first one, okay, we are given 4 courses, so we are going to draw 4 nodes. So first prerequisite is that we need to complete course 0 in order to complete course 1, which means 0 is actually a prerequisite for course 1. So we can have an edge between 0 and 1, where 0 is a prerequisite and 1 is the node that needs the prerequisite of 0. So notice in this case I'm only drawing one directional edge. Why? Because for 1, 0 is a prerequisite, so that's why there is an edge between 0 to 1. But the thing is, for 0 there is no edge coming back from 1, because so far we haven't find that there is a prerequisite in this case. So because it is not the case, we are simply going to keep progressing. Now next one is that we need to complete course 2 in order to complete course 1, right? So basically from 1 to 2 there is also going to be an edge, because course 1 is a prerequisite of course 2, and course 1 has to be done before we can proceed to course 2. So that is why there is an edge from 1 to 2. Same way, we must do course 2 before we can proceed to course 3. So we must do course 2 in order to proceed to course 3, and this is also a prerequisite. And this is a graph that is being made based on the number of courses and the array of prerequisites that we are given. Now our aim is to find any legitimate offering. So in order to find any legitimate offering, the logic is going to be quite simple. What we are going to do is we are going to pick any single node and we are going to do a depth first search. Now in the depth first search, we will have to keep track of like 2-3 items. First thing we will have to keep track of is that there are no cycles. If we find cycle, basically we have entered a scenario where we are not able to complete all the prerequisites. Say for example, in this case, if we are given an additional node that looks like this, or sorry, an additional edge that looks like this. So in this case, we have actually detected a cycle, and because we have detected a cycle, there is no way for us to complete all the courses. So definitely in this case, we will have to return an empty array. But lucky for us, in this case, we are not given a prerequisite that looks like this, right? So we found no cycles. Second thing we need to do is we can pick any single node, and from that node, if we start iterating over all of its neighbors in the DFS manner, and then keep a track of all the elements that we have visited, by doing that we won't be able to find any cycles, and also we will try to order them in a manner that we match all the dependencies, and in the end we simply need to return the ordering. So this is going to be a perfect logic to solve this problem, that we are taking consideration of everything. Now let's see that we know the core logic, that how we are going to use it. Let's see how we are going to implement it. So in this case, we have total 7 courses that we need to take care of. And for all of these 7 courses, I also have a prerequisite array. Now, based on these two things, we know that for any single graph problem, we need a way to represent the entire problem in a graph manner. So how we can do it is we have two ways. We have adjacency list and adjacency matrix, right? So in this case, I think we are good with going with adjacency list rather than adjacency matrix, because the graph is not going to be too sparse, and so let's try to stick with adjacency list. Now based on this given array, we would be able to create our adjacency list. Now how we are going to create our adjacency list? Well, basically for adjacency list, we are going to create a hash map, Now inside this hash map, we will have to take care of two values. First one is like the key and second one is its value. So as a key, we are going to take all the courses that are present, and as the value, we are going to take that which courses, like for that particular node, for whom it is the prerequisite. Again, I'm repeating myself. So as the node, we are going to take all the courses. So basically the nodes are going to be 0, 1, 2, 3, 4, 5, 6, 7 over here. And as its value, we are going to see that for what are all the courses it is a prerequisite for. So let's try to draw our graph and also fill up our prerequisite table. Okay, so based on the given prerequisites, we have been able to draw our graph. Now, if we see on the graph, our graph is only for our explanation. Basically, all we will have to do is we will have to create our prerequisite adjacency list that I mentioned. Now in the hash map, these are all the nodes or the number of courses as mentioned. And now let's try to keep on mentioning their prerequisites. So first we will see that for what are the courses, 0 is a prerequisite. So from the graph, we can actually take a look at this prerequisite array as well. But the thing is, I feel it would be better if we just do it from the graph. It would be easier to visualize. So in this case, basically course 1 and course 2, these are the two neighbors, or these are the two edges that derive from course 0, which means unless completing course 0, we cannot complete course 2 or course 1, because for both the courses 0 is a prerequisite. Same goes, okay, let's see for course 1. Course 1 is actually a prerequisite for course number 6. Okay, that's cool. For course 2, okay, course 2 is a prerequisite for course number 4. And 6 actually has no prerequisites. Okay, now we have done half of the work. We have created our graph. Now the question is how we are going to traverse the graph, how we are going to make sure that we are finding cycles, and how we are going to keep track of all the answers, that what should be the correct ordering. So these are the three tasks we will have to do. So the traversing part is pretty easy to solve. We are simply going to use the DFS and we will keep on iterating. The question is how we are going to detect cycles, whether they exist or not. In order to do it, basically from any single node, if we are going to do a DFS, we will have to keep track of that at any given position. We are not coming back to that particular node that from where we started. So we will have to find a way to keep track of all the visited nodes. So one of the best way to keep track of visited node is using hash set. So we are going to use couple of hash sets. There is also another trick where we can give the nodes some numbers and or some colors where we can treat them as such that whether they have been visited or not. But for explanation purposes, let's just keep track of hash set. When we go to the coding, we are going to use it differently. Now we also need to keep track of the ordering. The idea we are going to use over here is that we are actually going to use a stack. Initially the stack is going to be empty, and from whatever the node we started visiting, we will keep on visiting until we reach to a point where it does not have any prerequisites or all the prerequisites has been met. Once we get to that point, we would add that course into our stack. Eventually our stack is going to be full. And remember, the idea of a stack is that in the stack we keep on adding all the values. When we pop off all the values in the reverse manner, then we add it. So basically we are adding the first value inside that contains basically all the prerequisites, and then we will keep on adding values on top of it. So the top value inside our stack is going to be a value that contains no prerequisites, and then we will keep on popping one value at a time, and in the end we should be able to get our answer. So after this long explanation, let's see all of these things in action. Okay, so now we have our structure ready. I have created an adjacency list over here. Now for this adjacency list, first of all, we are going to do DFS. So I'm going to keep track of that what element we are DFSing over. We are, for any single DFS that we are doing, we will also have to keep track of the current visited nodes that we are going through, because during the DFS we do not want to find any cycles. So if any element appears in the currently visited elements during the same DFS, we would know that we have encountered a cycle, right? Suppose we do not encounter a cycle and we reach to an element, say for example like 6, that does not have any prerequisites, then we can simply conclude that that node is a good node to be added to the stack. So we will simply add it to the stack. Once adding to the stack, we will also add it to the node of visited nodes. what this would do is, this would allow us not to do redundant work or not to do duplicate work. So let's see the whole calculation in action. Okay, so first we are going to start DFSing over the first element. So we are going to start with element number 0. If we start with element number 0, what are the neighbors or what are the values for element number 0? Okay, so first value is value number 1, right? So currently we are visiting, okay, initially we started our visit with element number 0, then first element we are visiting is currently 1. Now we are going DFS, which means we are going in depth. So even for node number 1 we are going in depth. So node number 1 has is a prerequisite for course number 6. So which means if we want to get to course number 6, we will have to go through 1. So now we will go to course number 6. So currently we are visiting course number 6. Now course number 6 does not have any is not prerequisite for any of the courses, which means this is wonderful. So now what we can do is we can conclude course number 6 to be done. So we will take the course number 6 value from here and we can actually add it to our stack. So if we add the value number 6 to our stack, okay, now we have added a value number 6, which means course number 6 we have already put the ordering for that. If we put the ordering for that, which means we have already visited that course. So we are going to add an entry in our visited hash set. Now let's go back. Now if we go back, okay, we still have one more element 1 that we haven't processed, right? So if we check for element 1, does it has any other prerequisites or is it a prerequisite for anything else apart from 6? No. So which means this is done. So for 1 we do not have any more courses where 1 could be a prerequisite, which means 1 can also be added to stack. So we will add entry number 1 to the stack as well, and also at the same time we would define 1 has also been visited. Now we go back to course number 0. So for course number 0, currently we have taken care of this course number 1, but we haven't taken care of this course number 2. So we will keep on iterating. So currently now we would visit course number 2. For course number 2, do we have any ways to go to next course? Yes, we need to go to course 4. We will have to go through course 2. So we can go to course 4. Now for course number 4, is it a prerequisite for anything else? Yes, it is a prerequisite for course number 5. So in order to go to course number 5, we have to go through course number 4. Now for course number 5, okay, course number 5 can go to course number 6, but the thing is 6 has already been visited, so we can ignore this case. If we ignore this case, course number 5 is no longer prerequisite for any other courses, which means now course number 5 is actually ready to be added to our stack and also visited hash set. So let's do that. We will remove course number 5 from here. We will add that 5 has been visited and we will add an entry 5 over here. Awesome. Now we have course number 4. So for course number 4, okay, apart from 5 it did not add anything else, so which means course number 4 is now also eligible to be added to the stack. So we will visit course number 4 and we will visit course number 4 to our stack. Now for course number 2, let's see if there are any more entries. No, there are no more entries. Awesome. So now we will put course number 2 over here as well. So 2 added and also 2 added, 2 removed from the current stack, and now we are back to the course number 0. For course number 0, okay, we already took care of course number 1. Now we also took care of course number 2, which means 0 is now also eligible to be added. So awesome. Let's do that. So we add 0 over here and we add 0 over here. That's great. Now if we go back, there this has been jumbled up, so let me clean this up a bit. Now in this case, okay, now we took care of course number 0, right? Now for node number 1, we will check our visited hash set. So in the visited hash set, yes, we have already visited course number 1, so we don't need to do anything. Course number 2 has already been visited. Awesome. Course number 3 hasn't been visited. So now for our current DFS, we will start visiting course number 3. Okay, so for course number 3, it has many different prerequisites. So course number 3, okay, course number 3 is a prerequisite for course number 1. So currently we are visiting course number 3. Let's see, course number 1, okay, 1 has already been visited, so we do not need to visit this one. 4 has also been visited, we do not need to visit this one. 5 has been visited and 6 has been visited, which means all of the courses which could lead us to these courses have been visited, which means course number 3 is no longer prerequisite for any other courses. So it is a good candidate to be added to our stack and our visited hash set. So we can add it to our stack and we can also add it to our visited hash set, right? Awesome. Now if we see our stack is already full, so do we need to worry about adding these more courses or checking for them? No. But if we want, we can do it. It would only be constant time because all of them, they have already been visited, so we don't care. Now since we have our stack ready, let's try to pop out all the values sequentially. If we pop out all the values sequentially, this is going to lead us to our answer. Why? Because okay, first we have to complete course number 3, then 0, then 2, 4, 5, 1 and 6. If we complete courses in this manner, we would be able to meet our prerequisite. So let's see that whether our answer that we received is this a valid answer or not. Let's compare it with the graph that we created. Okay, so now we have both the values side by side. Let's see if we start iterating. So if we first complete course number 3, then we would be able to finish a lot of different courses. So we won't have any prerequisites for course number, all of them have some other prerequisites, but if we do course number 3, there is no harm, so that is good. If we do course number 0, that is also good, right? Now can we do course number 2? Yes, course number 2 only has prerequisite on 0, which we have already completed, so we can do course number 2. Can we do course number 4? Yes, course number 4 can also be done because it had prerequisites on course number 2 and also course number 3. Both of them have been done. Awesome. Now for course number 5. Okay, 5 can also be done because it had prerequisites on course number 3 and course number 4. Both have been completed. Course number 1. Course number 1 only had prerequisites on course 0 and course number 3. Both have been completed, so we can do that. And also for course number 6, it had actually prerequisites on course number 1, 3 and 5. All 3 of them have been completed before. So this is a legitimate valid ordering that we can use. And this is a great way to solve this problem. See, time and space complexity. In this case, the time complexity is actually going to be big O of V plus E, where V is the number of vertices and E is the number of edges. And if we see space complexity is also going to be big O of V plus E. And this is a great example. And also the way to find this ordering is also topological sort. So congratulations to you. You also learned a new algorithm. So since this video is already too long, the code solution for this problem, I'm just going to explain it and then paste this code in the comments so you can check it out from there. Okay, so first of all, we are actually doing things a little bit differently than what I explained. Basically, we are creating 3 different like white, gray and black values. So this is going to be assigned to every single node. White is going to represent that the node hasn't been visited or it hasn't been touched so far. Gray means that during the current DFS, this has already been visited. And black means the code that is already going down into the stack or that we have created, which means from where we can fetch it and use it for the answer. Now let's go to our main method first. First, we have this find order method where as an input we are given number of courses and we are also given prerequisites. Now first thing we need to do is that based on the prerequisite, we are actually going to create the adjacency list. This is what we are going to create as I explained in the explanation. Now after this adjacency list, we are going to assign every single value to the white color for the first time. Why white color? Because it hasn't been added to any list or it hasn't been visited. And then we are going to go over every single values of this adjacency list and call our DFS function. Now what does this DFS function is going to do? It is going to recursively call all of the values or all of the neighbors of that particular node until we reach to the end. Now let's see what happens inside the DFS function. We receive a node as an input. Now we have a boolean value is possible. That is going to check that whether we have been able to find any cycle or not. And how we are going to be able to find a cycle? By using this gray color. So if a node that is already assigned a gray color and somehow in the DFS we find it to be gray again, which means we came back to the same node which we have already traversed during our current DFS. So there is a cycle present. So this is a good way to detect that. And for that we just created a different method that if the given color is gray, we simply get the DFS method. We simply assign the values is possible to be false. Okay, now in this case, first we assign the value to gray for any particular node that we are visiting. Then we start visiting all of its neighbors. Now for every single neighbor, we are only visiting the node that the color where the color is white. If the color is black, we are going to ignore that. If the color is gray, we are going to assign the value is possible to false, which means that this is not possible to do it, and we can simply return an empty array in that case. If not, basically recursively we are going to call our DFS function for every single neighbor, and for every single neighbor we are going to assign the value to gray, and we are going to keep on doing it until we reach to a point where it does not have any more neighbors left. So at that time we are going to put the node and assign it to color black, and also we are going to assign it to a topological order list that we have created. Recursively, if we keep on doing it, basically our topological order list is going to be basically our stack where we would have all the values filled up. And once that is done, from our main method we will check that, okay, if this is possible, if that is true, which means if this is still possible, then we will simply iterate over all the number of courses, and we are going to create a new array called order. For this order, we are going to take all the values in the reverse from the topological order, and we are simply going to return the order list that we just created, and this is the whole solution. So I would be posting this in the comments, so I hope you understood it. And if we try to run the code, this runs perfectly fine. If we try to submit the code runs decently efficiently. And yeah, so let me know in the comments what do you think about. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code problem, Pacific Atlantic water flow. And as you can see that this problem hasn't been asked in too many companies. The thing is, the companies where this problem has been asked are really one of the most important companies in the world. Google, Amazon, Uber, Microsoft, Facebook, Apple, ByteDance, which is a parent company of TikTok, Bloomberg. So you can understand the scale that why this problem is important and what kind of companies ask this problem. And the thing is, main intention for understanding this problem is to not to understand the actual problem, but rather the approach behind the solution, because that can become a base foundation for too many other problems. There is a lot of information in this problem statement, but if we try to comprehend this using the picture, it's really simple to understand. So I'm just going to go over that. Essentially, we are given a grid like this, and we are told that this is actually an island on somewhere in the ocean. But the thing is, it is at the cross junction between Pacific Ocean and Atlantic Ocean. And the way it represents is that this top and this left edges, they are actually Pacific Oceans, and this bottom and this right edges, they are Atlantic Ocean. So this, and the second information we are given is that all of these coordinates inside the given island represents the height of that particular area. And why the height is important? Because we are told that on this particular island, on this particular grid, there happens to be a lot of rain, which means that rain falls, and we know the property of water that it gets transferred from higher height to lower height. We are also told that that rain at any particular cell can can go to four directions. It can go to top, right, bottom, or left, which means it cannot go diagonal in any scenario. And the condition that if it can traverse from one cell to another cell is that if the height at any particular given cell, if it's greater than or equal to the cell we are trying to reach, then the water can travel to that cell. Which means, suppose we take this cell for an example, the height for this cell is 4, which means if the rain falls on this cell, we can conclude that the rainwater will go to cell 3, it will also go to cell 1 and cell 2, but it would not go to this cell 5 because the height at cell 5 is greater than cell 4, which means that this is cell 4 and this is cell 5, so water can't travel like this. Now the interesting part for this question is that we need to understand that what are the cells in the given grid that can travel where if the rainwater falls, it can travel to both Atlantic Ocean and also Pacific Ocean. So let me clean this up a bit. Suppose we consider this cell number 5, and if rainwater falls in the cell number 5, let's see that can it reach Atlantic and Pacific. Like, we know it can reach, but in this cell adjacent to the cell number 5, the height is 3, which means water can go over here from this 3 the water can go to this 1, and because this is at the edge of Atlantic, of course water can go to Atlantic Ocean from here. Now from this cell number 5, we know that water can also go on this side because the height is 4, and from this 4 the water can go because the height is 2, which is less than 4, and from this is at the edge, which means that at any point whatever the height over here is, like 1, 2, whatever value, all of that can go to Pacific Ocean. So we can conclude that water from this cell number 5 can reach to both Atlantic and Pacific Ocean. Let's take another example. Suppose we take an example of this value number 4. So we know that from this cell we cannot go over here, we cannot go to 5, but we can go to 2, and from 2 we can go to Atlantic. So that concludes one option. Now let's try to see that can we go to Pacific Ocean. So first, if we try to go on top, okay, we can go over here because this is 3, but from 3 we cannot go to the top because this is 4, so we can't go Pacific in this direction. If we try to go over here, we can reach to this 1, we cannot go to this 7, which means that from this 4 we can go to Atlantic Ocean, but we cannot go to Pacific Ocean. So we wouldn't include this in our intersections. For every single cell, we are going to check that whether it can reach to both Pacific and Atlantic Ocean. If it can reach, we will just maintain a list or some sort that will take care of all the cells that we are able to reach to both the oceans, and we would keep on adding them in this list. So first we'll start with this first element. We know that it can reach to Pacific Ocean, but it won't be able to reach Atlantic Ocean because height over on both these cases are greater. So we wouldn't include this. We would go to next one. So over this again can reach to Pacific, but it cannot reach to Atlantic because it will traverse in these two directions, but it won't be able to go any further over here and over here. Same happens for this one, and basically this solution would work. We would find our answer. Eventually our list would be filled out. Suppose we are at this location 5. So we know that this is at the exact intersection of both the oceans, and it can clearly go to the rainwater can clearly go to Pacific and both Atlantic. So we would add this particular location in our list, and eventually the list will be filled out. But the thing is, the issue with this approach is that in terms of time complexity, we are actually doing a lot of repetitive work, because for every single cell we are checking all the possibilities, and we might end up doing, in the worst case scenario, big O of. So suppose this is M and these are N cells, so we can say that the time complexity would be big O of M multiplied by N squared, because for every single cell we will have to iterate over all the other cells, and this is not a very good time complexity. There exists a better approach. So in order to solve this problem, we are actually going to use a different approach, and the approach we are using is actually, if mountain cannot come to Muhammad, Muhammad will have to come to mountain. And what I'm trying to say is, suppose that rather than checking at any particular cell that whether it can reach both Atlantic and Pacific Ocean, we create two separate grids. So suppose we create a grid and another grid, so two separate matrix of Boolean values that has the same size of whatever the input size we are given, and at any particular location we just name that okay, this matrix consists the data of all the cells that can actually reach the Pacific Ocean, and this matrix contains all the data of all the cells that can actually reach to the Atlantic Ocean. And once we have these two matrices defined, the moment we find that okay, so over here we know that this particular element 3, this can reach to Pacific Ocean. So over here, suppose this value corresponds to this 3, so we will set the value as true over here. And same goes on this side, that suppose we find out that this particular element at position 4 can reach to Atlantic Ocean via this way. So whatever the corresponding value we have over here, we will set that value as true, and eventually we will have the entire matrices filled out. And once we have those, all we need to do is just intersect both of them and find the common elements between both of these matrix, and that would be our final list of matrix that contains all the cells that can reach to both Pacific and Atlantic Ocean. and this would be our solution. Well, this solution actually works pretty fine, it's pretty efficient, and all we need to do is we need to figure out that how we are going to generate these two matrix and what are all the different logic we are going to take. Let's take the most basic approach. I'll be showing you an example that suppose we want to reach to Pacific Ocean, how can we fill out that matrix. Now, what is the most basic thing we know about Pacific Ocean? Well, we know that for this particular island, all the cells that are present in this row and all the cells that are present in this column, they are actually at the edge of the island. Also, they are at the very adjacent to Pacific Ocean, which means all the water in these positions can actually reach to Pacific Ocean in all the cases. So in our matrix, whatever matrix we have, we can basically define all the elements these positions as true because we know that they can reach to a Pacific Ocean. Now, previously at any particular location, we were actually trying to go outwards to see if water can reach to adjacent cell or not. But rather than going outwards, why don't we come inwards from the cells we already know that can reach to Pacific Ocean? So over here, these cells we already know that they can reach to Pacific Ocean. So if we check that whatever the cells that are adjacent to these cells from this particular cell that can reach to Pacific Ocean, can we reach to these adjacent cells or not? And the moment we find that okay, we can reach to some adjacent cells that we haven't already visited, so we can set that as true. Suppose the value over here is 3 and we know that this is able to reach to Pacific Ocean, and suppose the value adjacent to this one is actually 6. So we know that since the height difference, there is a height difference, and over here we need to check the reverse height difference. Previously in this approach, we were actually checking that whether the height we are currently at and the height the adjacent cell is actually the height is lesser than whatever the current height we have. Over here we are coming inwards, so we will check that whatever the next cell is that we haven't checked, whether its height is greater than whatever the height we currently are at. So in this case, this is 3, this is 6, which means that okay, from this cell we can come to this cell, and over here we know that we are coming to this cell from this particular cell that is already able to reach to Pacific Ocean. So over here we can directly mark this one as true, and we won't have to do lot of calculation over here because we already know that this cell is true and we are reaching to this cell via this cell, and this would be a very good solution. And this is how we can actually fill out this entire matrix or like all the remaining portion in big O of m cross n times in just single traversal, because we are not, for any particular cell we are not going to check the whole thing. We are only going to check the cell that is exactly adjacent to it. Suppose we are at this particular cell and we know that this cell can reach to Pacific Ocean. We have already set this value as true. Okay, now we do calculations like this, and suppose before we come over here from this route, we have already calculated this and we know that this is already true, that this can already reach Pacific Ocean, and we are at this position and we are checking this again. So first we will already find that whether the value for this particular element has been calculated already or not. If it has been calculated, we don't need to do repetitive work and we can just simply skip over it. That way we can also make some runtime adjustments that would be more efficient on our case. Okay, now we need to find a way to somehow create the matrix that stores the information of all the cells that can reach to Pacific Ocean and also to Atlantic Ocean. In order to do that, at first I thought that we are going to use dynamic programming over here, and the reason I thought is because first of all we are defining a set of all the cases that can reach to Pacific Ocean. So this becomes our base case. Once we have our base case defined, we are essentially going in all the directions to see that if we can reach to next cells, and suppose in this case we are able to reach to this cell from over here due to the height difference, so we will mark this as true, and again from over here we will again do the same thing, and we will, so basically at any point we are using whatever the calculation we have calculated before to generate the next results. So that's a very clear indication that we need to use dynamic programming over here. but it turns out that I was not able to solve it efficiently. I was still missing out in a lot of test cases. So apparently dynamic programming is not the way to go, but I still urge that if anyone can solve it using dynamic programming, I would be more than happy to understand your approach. So second thing I tried to do is okay, in order to solve this, we need to iterate over the entire matrix. And in order to iterate over the entire 2D matrix, we have basically two methods. We can use either breadth first search, or we can use depth first search to iterate over all of the elements and do some calculation. Now I'm new to graph theory, and I need to first of all perfect myself on depth first search before I move towards solving the problems using breadth first search. So I chose the approach of taking depth first search, but it can also be solved using breadth first search without any issues. And we know that in order for us to complete this program using depth first search, we need to use recursion over here. And of course we can use recursion, because notice that at every single position, so over here, first of all, we define that this can reach to Pacific Ocean. Now we move on all the directions, and over here we find the height difference. So again, we know that this can reach to Pacific Ocean because this can reach to this cell. So we mark this as true, and then again we repeat the same process that we have just did, and again we would mark this as true, and again we would repeat the same process. So essentially we are doing the same sort of work but for different inputs, and that's a very clear indication that we need to use depth first search using recursion. And let's move on towards coding now. First of all, we are going to check the condition that if the given input is actually an empty matrix, then we just need to return null. Okay, if that's not the case, let's create two parameters to store the value of row and column. Now we'll create two Boolean matrix to see to store the value of cells that can reach to Pacific and Atlantic Ocean, and we are going to name that Pacific reachable and Atlantic reachable. And we are going to create both of them to the size of whatever the initial heights matrix we are given. Now we will run a for loop on for both the matrix to be filled out. In order to fill both the matrix, we are going to create a DFS method, and inside the DFS method we are going to provide the row and column location, and we are also going to provide Pacific and Atlantic matrix. So first we'll do it for Pacific matrix, and we are also going to provide the input heights that we are given. We are again going to call the same function for the Atlantic. We'll iterate using column as well. Now before we calculate the result, first let's create the method. Now inside the DFS method, we will have to iterate over, for any particular cell we will have to iterate over all four of its adjacent cells. So we'll just create a 2D array called directions, and we are going to use it to iterate over all the adjacent or neighboring cells. So we are at this DFS location, which means that we already know that this row and this column pair is already able to reach to subsequent whatever reachable matrix that we are trying to calculate. So which means that we will set that value as true. Now we will start iterating over the neighbors of whatever the current cell we are at, and we are going to create the new row and new column. Now we will have to check that if this new row and new column, are they out of bounds or not. If that's the case, we just ignore that and we continue. We also check that if we have if the new row and column cell if we have that value calculated before, we can also just ignore that case. Okay, if both the cases are not true, we will check that if the height difference of the previous cell and new cell is in our favor or not, which means if the heights for the new row and new column if that is greater than or equal to whatever the previous height was. If that is true, we will need to call the DFS function again with the new row and new column. And this would be our logic for this DFS method, because we are eliminating all the cases and we are also calling the recursive function based on the height difference. So after these 4 entries run, we should have both of our Pacific reachable and Atlantic reachable matrices filled out, and now it's just a matter of finding the common elements between them. So first of all, let's create a list of lists to store our result, and we'll just name it as result. Just going to iterate over the entire array, row and column wise, and we are only going to check that if both the values are true in both the Atlantic and Pacific Ocean cells. So if both are true, we can add it to our list. So after this loop runs, we simply need to return whatever the result we found, and that should be our solution. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit this code. Okay, our solution also works. It is accepted by LeetCode, but the thing is it's not the most efficient solution. So let's see that if we can do some modifications. And one modification I can think of is rather than calling this DFS system right here and checking this condition all the time, what if we revert the condition, and if this condition is satisfied, we can just return it, and we can just continue before. So that's why loop breaks more times before, and if all of these conditions are not true, then only we will call our DFS function. Let's try to run the code. Okay, the code is working. Let's try to submit the code. Okay, we see some improvement in our code, and now it's a little bit faster than what our previous result was. So I'll be posting this code in the solution. You can check it out from there, from the comments, and let me know how do you like the video. Thank you. Hello friends, I'm a cloud solutions architect at Microsoft, and my aim is to empower every single person to be better at technical interviews. Keeping with that goal in mind, today we are going to do a very interesting LeetCode problem. So let's get started with that. So today we are going to find the celebrity LeetCode problem, and if we see some of the popular companies, the problem has been asked at companies like Amazon, LinkedIn, Pinterest, Microsoft, Facebook, Apple, Snapchat, Google, Uber, and Goldman Sachs. So basically all the popular companies have asked this question. So I'm going to pay my utmost attention. I hope you also enjoy the video. This has to be one of the most interesting problems I have been able to find so far. If you look at this, LeetCode categorized this as a medium problem. If you try to understand the problem statement and try to think about it, you will feel like this is actually a hard problem. And once you put like some more thought into it, you are actually going to feel that this is actually an easy problem. So in my opinion, this is actually an all-in-one problem. Let's understand the problem statement to go further deep. It says that suppose we are at a party with n people, and the names of these people are the numbers. So basically numbers from 0 to n-1. So say for an example, we are in a party with 4 people. Basically the people are going to be 0, 1, 2 and 3. So these are going to be the 4 people. Now we are told that in this party there may exist. So this is an important part, that there may exist, which means there might be a celebrity or there might not be a celebrity. Okay. Now we are first of all given that what the definition of a celebrity is. The definition of a celebrity is that every single person in that party knows who the celebrity is. And the second condition is that celebrity does not know any single person in that party, which is how typical celebrities are. So now, given these two definitions, first of all, we are told that we need to check that whether there exists a celebrity or not, and if there exists a celebrity, basically we need to find that who that celebrity is. The question is how we are going to find who that celebrity is. Well, definitely over here the relationship is based on either people knowing who the celebrity is, or the fact that celebrity knows no one, that everyone knows celebrity and celebrity knows no one, right? Now at our advantage, we are given a methodology where we can check between any two entities whether they know each other or not. We have a method boolean knows a to b, which defines that whether a knows b or not. If a knows b, if this gives answer true, which means a knows b. If this gives answer false, which means a does not know b. And why we are using that? Because the only relationship we have to identify whether a person is a celebrity or not is by the amount of people know them or the amount of people they know. And in this case, we either need to find the celebrity or we need to return -1 if no celebrity exists. So I know this is a little bit complicated to understand, but let's try to see some examples for this problem. Okay, so in the problem, we are actually going to have an input that looks like this, where in this input, we are given a list that contains some values that defines the relationship between any two values, that whether they know each other or not. Now, the thing is, this input is kind of messy, so I'm not actually going to show you examples based on this exact input. I'm actually going to show you in the base of something that is easier to visualize. So this is the same input I took from here, but I have actually converted it into a 2D matrix. And basically, as an input, we are given a graph, or we are basically given an adjacency matrix. Okay. So for this adjacency matrix, based on this adjacency matrix, we are given two entities. We are given a person and we are given whether that person knows each other or not. This diagonal line is always going to be 1 because that defines that whether person 0 knows person 0 or not, whether person 1 knows person 1 or not, things like that. And that is always going to be 1. So we can simply ignore this one. This serves no purpose. The important thing in this case is this defines that whether person 0 knows person 1 or not. So this answer is 1, which means that person 0 knows person 1. Let's try to find who the celebrity is in this problem, right? So in this case, we are given basically 3%. So we can actually create a graph that looks like this of 3%, and we are going to name them as 0, 1 and 2, right? Now the thing is, relationship between them is actually going to be the relationship defined by an edge, where a edge would represent that whether one entity knows the other entity or not, or one node knows the other node or not. And this is going to be a directed edge. Why? Because it could be possible that 0 knows 1, but 1 does not know 0. So we cannot just simply have an undirected edge. We must have a directed edge in this case. So let's try to do that as well. So if we draw it from this graph, okay, 0, 0, this does not matter, these three values, so we'll just ignore them. Let's just start 0 with 1. So 0 knows 1, right? So which means 0 knows 1. Yeah, we mark it. Now, does 0 know 2? No, 0 does not know 2. So there is not going to be any edge. Now, whether 1 knows 0? No, 1 does not know 0, and 1 also does not know 2. So 1 does not know anyone. Now in this case, whether 2 knows 0. Yeah, so 2 knows 0. That is good. And whether 2 knows 1. Yeah, 2 also knows 1. So that is also good. And 2 knows 2. Yeah, that is true. So we can ignore that. In this case, if we see the two definitions of a celebrity, that everyone knows who the celebrity is and celebrity knows no one at the party. So definitely in this case, we can say that, hey, if we check out the input for this value number 1, it knows itself. But the thing is, that is not the point. The point is whether it knows anyone else at the party or not. So 1 does not know anyone at the party. That is true. And also 0 knows 1 and 2 also knows 1, which means every single one who is every person other than 1 knows who the 1 is, and 1 does not know anyone, which means 1 perfectly fits on our category of celebrity, and in this case 1 is going to be celebrity. So we will simply return 1 as the answer, and this is what we need to return. Okay, let's see one more example. In this case, again 0, 1 and 2. Let's draw 3 lines. Now ignore these 3 cases, and 0 knows 1, no, 0 knows 2, yes, so 0 knows 2. Okay, Does 1 know 2? Yeah, 1 also knows 2. That's good. Whether 2, okay, 2 knows 0. So in this case, 2 knows 0 and 2 knows 1 no. So in this case, can we find any celebrity? Actually, we cannot find any celebrity. Why? Because in this case, okay, 0 and 1, both of them know 2. So that is good. 2 qualifies for one of the property of being a celebrity. The thing is, second property of being a celebrity is that it has to know no one at the party. But in this case, 2 actually knows who the 0 is. So because 2 know one person, 2 does not qualify for the second entity of our answer. So in this case, we cannot find any celebrity. So because there is no celebrity present, we are simply going to return -1 is the answer. And this is what we need to return. Okay, so first approach is a brute force approach. In the brute force approach, what we are going to do is we are simply going to check that whether all the person that are given, can any single one of them is a celebrity. So for one by one, we are going to check for every single person whether they are celebrity or not. So in this case, what we are going to do is first we will take consider person 0. Okay, so for the person 0, we will try to see whether 0 is a celebrity or not. How can 0 be a celebrity if everyone else knows who the 0 is and 0 knows no one? So in this case, we can see that 0 knows someone, so 0 is not a celebrity. Now we will have to check whether 1 is a celebrity or not. So in this case, okay, 1 still knows someone, so 1 cannot be a celebrity. But and in this case, we'll try to see whether 2 is a celebrity or not. So 2 knows no one, and let's see that if everyone knows 2 or not. So this one knows 2, but this one does not know 2. So 2 is also not a celebrity. So in this case, we will return a -1. And this logic leads us to the correct answer. Some maybe if you make some modifications or tweaks, it can be an acceptable solution as well. The thing is, this is still not the most optimal way to solve this problem. So basically, we would end up solving this problem in big O of n square time. So which is not too bad for some of the problem, but it is really bad for this problem because this can be done very efficiently with other methods. So let's try to see what that other methods could be. So in this scenario, if we see, okay, 0 knows 1 and 2. So 0 knows 1 and 2, right? Same way, 1 does not know anyone and 2 knows 1 and 1 and 0. So 2 knows 0 and 2 knows 1. So basically answer is going to be 1. That is a given fact. The thing is, what is one smart trick we can use? The smart trick is the knows function. The knows function that we are given in the input, that is there for a reason. And what knows function does is that if we provide any two values, say for example, if we provide the values of 0 and 1, it is quickly going to tell us that whether 0 knows 1 or not. So in this case, okay, 0 knows 1, that is a true fact. Now the thing is, if we know for sure that 0 knows 1, what is one thing we can say for guarantee? We can say for guarantee or for certainty that 0 cannot be a celebrity. Why we can say that? Because remember the definition of a celebrity. The definition of a celebrity is that everyone knows the celebrity and celebrity knows no one. Which means in this case, if we try to find or if we try to see this knows function between 0 and 1 and the answer is true. If the answer is true, definitely we can say that 0 cannot be a celebrity. Which means we are eliminating 0. Now, what could be the second possibility? Second possibility could be, say for an example, if we try to use the knows function for values 1 and 2. If we try to use the function 1 and 2 knows, the answer is going to be false. Why the answer is going to be false? Because 1 does not know 2. If 1 does not know 2, what is also one more thing we can say for certainty? Well, we can say for certainty that in this case 2 cannot be celebrity. Why 2 cannot be celebrity? Because we found at least one element that does not know 2. And in order for 2 to be celebrity, celebrity has to be known by everybody else in the party. So because we find one entry over here who does not know 2, we can say for sure that 2 is not a celebrity. Which means depending on the result of this knows function, if the value is true, we can eliminate one value, that is the first value in the knows function. If the value is false, we can eliminate the second value inside this given input, which means with every single knows call, we are getting rid of one element. So in this case, after just making two calls, we were able to get rid of 0 and 2, which means if there exists a celebrity, it has to be 1. So now all we need to do is that since this is the last item or last value pending, do we need to check that whether everyone knows 1 or not? No. Why? Because since we know for sure that these two are not the celebrities, right? So all we will have to worry about is that whether one knows no one. If one knows no one, which means one has to be the celebrity. If one knows at least one person, which means there are no celebrities inside this input, and we can simply return -1. And this is the whole logic behind this problem. Let me try to explain very quickly with a big example. So now we have bunch of different values over here. Basically, we are simply going to use the knows function, and we are going to go through every single value and try to see whether it knows the next value or not. So first we'll try to see that whether the 0 knows 1 or not. So, and we can ignore all of these values because diagonals doesn't matter. We do not care if they know their own self or not. So in this case, okay, 0 to 1. 0 does not know 1, which means we can say for sure that 1 cannot be celebrity. If 1 cannot be celebrity, we can simply skip over to the second value. Now in this case, we will check that whether 0 knows 2. So in this case, 0 to 2, 0 knows 2. So because 0 knows 2, we can say for sure that 0 cannot be a celebrity. So we ignore this. Now we are at this value number 2. So we'll try to see whether 2 knows 3 or not. So 2 to 3, if we check, okay, 2 knows 3. So if 2 knows 3, definitely 2 cannot be a celebrity. So we will ignore that. Now we are at this value number 3. So we'll check for 3 to 4. So 3 to 4, if we check, yeah, 3 knows 4. So in this case, 3 cannot be a celebrity because 3 knows 4 because of this value. Now we are at this 4 position number 4, 4 to 5. So if we see 4 to 5, so 4 to 5, this value is actually 0, which means 4 does not know 5. So because 4 does not know 5, 5 cannot be a celebrity. So in this case, we have actually got rid of all of these elements and only 4th value is pending. So now we know that if there exists a celebrity, it has to be 4, otherwise there are no celebrities. So now we are simply going to check that whether 4 knows anyone or not. And for that, we simply have to do one check at this 4th row to see whether apart from 4 by itself, does it know anyone else? And it knows no one. So definitely 4 is the only candidate left and 4 knows no one. So in this case, 4 is definitely our celebrity, and this we can simply return as the answer. And this is the whole logic behind our answer. Say for an example, in this case, by chance, if 4 knew this value number 1, if this was answer 1, then simply we can say that, okay, 4 is also not a celebrity, and we can simply return -1 in this case. But thing is, because this value is actually 0, so in this case, answer is actually going to be 4, and we are solving this problem most efficiently. If we see time complexity in this case, the time complexity is actually going to be big O of n. And if we see space complexity, well, apart from using a couple of variables, we are not using any additional space. So space is actually going to be constant. First, identify few things. So I created a new global integer to use the number of people, and I have assigned it to the value of n. And basically in the problem, we need to resolve this find celebrity problem. And also for this problem, I have created is celebrity a helper method. So that is going to define that whether any single candidate that we have been able to identify from this find celebrity method, if that is a celebrity or not. And now first let's start implementing this find celebrity method, and then we will implement our is celebrity method. So first of all, we are going to initialize a variable called celebrity candidate. Now we are going to run our for loop, and for every single value we are going to check, or we are going to call our knows function. And for the knows function, we are basically providing the value of the celebrity candidate and the value of current I. Now depending on the answer we get back, we are going to update the value to the I. So what this is going to do is, this is simply going to eliminate every single value for us except one last remaining candidate, and that we are going to consider as the celebrity candidate. And once we get out of the loop, all we will have to do is we will have to call our is celebrity method. If this value is actually true, if this value is a celebrity, we are going to return this. And if that is not the case, we can simply return -1. Now in this method, we will first of all run a for loop. Inside the for loop, first we will have to check that if the given value of I is equal to j, which means we have found a diagonal value. So in this case, we simply ignore that. And if that is not the case, we are going to check that whether J satisfy all the properties of being a celebrity or not. If any of these is true, we can simply return false. And if that is not the case, and if we get out of the loop, we can simply return true. And I think this has to be the whole logic behind this input. So let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions, and it is also really efficient in terms of time complexity. So this was a great problem to solve and to understand a lot of different concepts. I would be posting this solution in the comments so you can check it out from there. Hello friends, I'm a cloud solutions architect at Microsoft, and my aim is to empower every single person to be better at technical interviews. Keeping with that goal in mind, today we are going to do a very interesting LeetCode problem called word ladder that has a real life application, because this is a game by itself as well. And if we see some of the popular companies who have already asked this question, there are companies like Amazon, Bloomberg, LinkedIn, Microsoft, Google, Uber, Apple, Facebook, Lyft, ByteDance, and Goldman Sachs. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode hard problem and also a very well-liked problem, which is a rare combination to be seen. Now in this problem, we are given two words, a begin word and an end word, and we are also given the list of words called dictionary or word list. Now our aim is to reach or go from the begin word to the end word by a transformation sequence. The question is, how does this transformation sequence works? Well, the transformation sequence works is that suppose we are currently at word 1, we can only jump to word 2 if the difference between the characters is only 1. So say for an example, if we are given a word like cat and we are given the second word like caught, we can go from cat to caught because there is only difference of a single character A. The C and T are common across both the words. So this is a valid transformation sequence. The idea is that from the begin word, we need to keep on doing the transformation sequence amongst many different words, and our aim is to reach to the end word somehow. And if we are able to do it, we need to see that what is the minimum number of ways we can do it, and these words, they has to be present inside the word list that we are given. So we cannot just create words out of fly. This is the purpose of this word list set that we are given, a bunch of different words. And if somehow we are not able to reach to this end character using the transformation sequence, we need to return 0. And if we can, we need to return the minimum number of hops needed to reach to there. So let's try to understand this with a couple of examples. If we see this first example here, the begin word that we are given is called hit and the end word is cog. And these are the different words that we are given. So one of the ways we can solve this problem is by creating a word sequence that looks like this. In this case, we are starting from the first word and we are reaching to the end word. And these are all the different hops that we are making using the transformation sequence. So this is a valid example. But if we see in this case, we are actually taking 6 different hops to reach to the end word. Can we do something better? And the answer is yes. There exists a better solution for this problem. So let me quickly show you the better one. Again, even for this example, we are able to reach from this beginning word to the end word. But in this case, we are doing the whole journey by only 5 different hops. So in this case, we need to return 5 as the answer because we are only taking 5 steps to reach from the first word to the end word. And this is going to be our word ladder. If we take a look at the second example, in the second example, the word we are given is hit and again end word is cog. So that is true. But the thing is, in this case, we need to return 0. Why we need to return 0? Well, because this cog is actually not at all present inside this word list that we are given. So since the end word is not present, we cannot reach the end word. So basically we need to return 0. So I hope this explanation makes sense and you are able to understand the problem statement. Now let's see that what is going to be the approach we will take. Okay, so before we come up with the optimal solution, first let's see that what kind of pattern we can see in this problem. Basically, we are given a beginning word and an end word, and we are told that there are some series of words that we need to go to in order to reach to this end word, and we need to return the minimum sequence possible, right? The thing is, in this problem, we are not only guaranteed to given all the words that would be used between this beginning and end word, and it could be possible that we are given some different words that are not being used, or they can be used, but the thing is that leads to like a longer answer, and we do not need to like go through all of them, and we only need to find the shortest path. Now if you see this kind of structure, what does this reminds you of? Well, you are absolutely correct. This is actually a very similar structure to a graph, where you can see the words that are given, they can be treated as different nodes, and the relationship between these nodes can be treated as edges. So we have our vertices and edges, and we have a way to define edges. Now how does a vertices connects to an edge? A vertices connects to an edge through the mechanism that the number of characters of word 1 and word 5 in this case, they only have one differing character, and that's it. That is the only way we can define a relationship between them. Once we have a structure like this ready, now let's see what is our aim. Our aim is to find a path from the beginning word to the end word, and if we want to find the path, what we can do is we can simply iterate over the given input and see that what are the different paths we can take, and try to find the most optimized path or the shortest path that leads us to the correct answer. So in this case, we can actually find two different paths that leads us to the answer. First one is the one that I indicated in blue, and second one is the one that I indicate in this purple color. Now in both the cases, this path is actually the shortest path that leads us to the answer, and we need to read in the end we need to return the distance between the words amongst these paths. So in this case, the answer is going to be 5. But you get the idea that basically we can, if we are able to generate this graph structure, then all we need to do is we need to do the breadth first search traversal. And the question is, why breadth first search? Because we are trying to find the shortest path, and if we do depth first search, it could be possible that in practice it might take us longer. So breadth first search would be a better candidate in this case. So if we are able to create a graph structure, and if we do the breadth first search, we can actually find the shortest path. Okay, so now we are going to use the same example that we have been given as the input. Now first of all, we need to find that the beginning word that we are given is the word hit, right? And say for example, we devise some mechanism to easily traverse through these words to make sure that whether these words exist or not, right? Now the question is, from the hit, we are treating this hit as one of the nodes, right? Now we need to find that what are all the different edges this hit is able to connect to. The idea we can do is that we can see all the possible words that this hit can have with just one differing character. The logic is we can start with the first character and keep all the characters from A to Z, and then keep the remaining two constant. So what we will do is we will try to check for the words such as AIT, then BIT, all the way up to ZIT, right? These are all the different words we can make. Then same way we can keep the H and T common, and then do ABC all the way up to Z. And we can keep on repeating the same process. So basically, at every single word, what are the different possible words we can have? Well, say for example, if the length of this is equal to M, then basically we can have M multiplied by 26 differing characters or differing word possibilities. Now amongst these 26 word possibilities, all we need to do is we only need to find the words that exist inside this word list. And since this is a dictionary, basically we can access pretty fast and check that whether any word exists or not. We can do it in constant time. So this is not going to be an extra overhead. So by using this logic, we are actually able to generate all the graph pairs for our given input. So first value is going to be hit, and now let me just quickly draw the graph structure. Okay, so we can actually make a structure that looks like this, and this is a pretty decent representation of the input that we are given. Now this is going to be our start node, and this is going to be our end node, or the beginning word and the ending word. Now basically we need to iterate over the given graph, and we are also going to keep track of all the nodes that we have visited so far. That is to not end up inside any like unexpected loop or infinite loop. Now all we need to do is, from starting point, we already mentioned that we are going to run a BFS, and we are also going to have a variable called min that is going to keep track of what is the minimum path we have found so far. So if we just see the input, one of the path we can take is that we start from hit, and then we can go down this path, and eventually we would be able to reach to the end word. So in this case, if we see, and definitely we are going to keep track of all the visited nodes, and everything is going to be taken care of. If we see this path, basically it is going to take us 6 words, and currently this is the minimum value we have because we haven't identified any other path, right? So 6 is the correct answer. Now what is, let's see that if there is any second option that we are missing. So yes, there is another option that we are missing, and the option is that if we start from this hit, we can go down this path, and through this path the number of words we encounter is actually 5. So because we are encountering 5 words, basically we need to update the minimum number of answer we can get. Let's see if there is any another path that we can take that we are missing. And yes, there is also still one more path that we haven't taken, and the path that looks like this. And in this path also we are encountering 5 words. So again the answer is going to remain 5, and we have explored all the possibilities. So in this case we can simply return 5 as the answer, because that is what we need to create. And you see, once we have this graph kind of a structure ready, things becomes much easier to comprehend, and we can simply return the answer pretty fast, pretty efficiently. So this is the whole logic behind this problem. Now in this problem, currently we are only going in just one single direction, but in practice there can be like a bi-directional BFS, where we start iterating from here and we also start iterating from here, and we can do like BFS from this direction, BFS from this direction, to reach somewhere in the middle and to find the answer. And we can do things slightly faster in that cases, but I don't think anyone is going to expect you to do this in any of your interview, so don't even bother. If we see time complexity, in this case the time complexity is actually going to be big O of m. So m is the number of length of any character, and I mentioned that length is going to remain constant amongst all the word list characters, so we don't have to worry about that. So number of m square. Now why m square? M square is taken in order for us to generate this graph like structure. So it takes big O of m square time, and for every single character there can be one possibility that we need to iterate, because we know the starting and ending point. So basically it's going to be m square times n in terms of the number of time complexity, where n is the total number of words given. And if we see space complexity, well, basically we are anyway storing this graph like structure, and that is going to give us like big O of m square space. So we also need to take care of that. So in my opinion, this was a tough problem, but once you know the logic, you can solve it easily. And this goes to show you that if you know the logic about different data structures, things becomes much easy, because this word ladder game is actually a real life game that people use and people play. So yeah, this is not just a random out of the blue question. Now let's move on to the coding. So since this word ladder problem was already becoming such a big video, so that's why I'm just going to explain you the code rather than typing all of it, and I will go through the explanation. So first of all, we are going to initialize a variable to note down the word length, because that is pretty important. And we are also going to initialize our hash map that contains the information of all the combinations inside the dictionary that could be possible. Now what we are going to do is, for every single word that is present inside this given word list, we are basically going to iterate over all of its characters, and we will try to see that for all the differing characters, what are all the transformations possible. And whenever if a transformation is possible, we will basically add it to our all combination dictionary. Because this is a hash map, inside the key we are going to store the value that is being present and inside the word list, and as its subsequent value we are going to have a list of all the possible combinations that any particular word can have. So this is going to give us our dictionary, and this is going to take basically m square time to do it, or l square time to do it. Now, in order to iterate over the breadth first search, we are going to have our queue where we will keep on adding, or we will begin with the first word, and we will not rest until we have iterated over all the neighbors of this first word, and we will keep on repeating the same process iteratively. So we are not doing recursion. We can do recursion, but we are doing it iteratively. And also, as mentioned, that because we do not want to get inside a position where we end up in any infinite loop, we are basically going to initialize a hash map. And now we are going to basically put the first word or the begin word that we are given as the input, and then we will start iterating over our given queue in the BFS fashion. So first of all, we are going to create a pair, or so first of all we are going to remove the node that is existent inside the priority queue, and then we will try to get its word value. Then we will see that what level it is, and basically we will iterate over all of the different possible words that can be present, and we will keep on repeating the same process for all the adjacent words. And every time we go to the new level, we are basically going to increase the size of the level. So this is going to return us that how many different paths that we have taken so far. And somehow if we get out of the loop, then basically we need to return 0. So this is the whole logic behind the whole problem. And this condition refers to if we have reached to the end word, and this condition refers to in the scenario where we have not reached to the end word, we are somewhere in the middle. So basically we are going to add a new entry inside our queue, and we are going to increase the current level we are at. So I think this solution makes sense. I would be posting this code in the comments, so you would be able to check out the code. Don't worry about it. Let me try to run this code, and our solution works as expected. Let's submit this code. And our code runs decently efficiently in terms of space complexity and time complexity. Both are really good. And this is the BFS solution from the LeetCode. So the LeetCode problem we are going to solve now is called network delay time. This is a pretty popular LeetCode problem. So let's understand the statement. Basically, we are given a network of n nodes marked from 1 to n. So in total, we are given 3 items. First one is times, that defines that in order to reach from one particular node to next node, how much time it takes. So if we take a look at this example, let's say 2, 1, 1, then we can say that in order for us to reach from node number 2 to node number 1, it is going to take 1 unit of time. So this is how bunch of different times we are given. Then we are given told k as a starting point, and that says that we will have to start iterating over our journey from k is equal to 2. So in this case from second node, and this n defines the total number of nodes that we currently have. Now the problem is asking us to solve is that we need to return the minimum time it takes for us to travel all the n nodes to receive the signal. And if it is not possible for all the n nodes to receive the signal, then we need to return -1. So let's try to understand this with an example. Say for an example, in this case, we are given an input like this. So we can see that in total, we are dealing with 4 different nodes, and we are given 3 different edges. So first edge is from node 2 to node number 1, it takes 1 time. Same way from node 2 to node number 3, it takes 1 time. And same way from node number 3 to node number 4, it takes 1 time in order for us to reach. Now we are given k is equal to 2, which means starting from k, we will have to make sure that are we able to send a signal that reach every single node, and what time it takes for to reach all the nodes in the minimum. So during the very first minute, we will have a signal that can go to node number 1 and node number 3. So we can say that these two nodes would have been visited after 1 minute. And then from node number 3, we still have to visit node number 4. So we can say that in order to reach node number 4, it is going to take 1 more minute, which means it took 1 minute to reach over node number 3, and then 1 more minute to reach to node number 4. So in total, it took us 2 minutes to reach to node number 4 and 1 minute to reach to node number 1 and 3. So in the minimum time 2, we can reach or a signal can reach every single node starting from node number 2. So this is what the problem statement is asking us to return. Let's say in this case, instead of 2, if we are being told that our k starting value is at 3. So in this case, now we are starting our iteration from value number 3. So once again, we will have to check that how many nodes can we reach. So we know that in the K3 only points to one node. So during the first minute, we would visit node number 4. But the thing is, we don't have any way for the signal to visit to node number 2 and node number 1. So in this case, we will have to return -1. So this is the whole problem statement. Now let's say that this is the input we are currently given, and we are trying to deal with that how we can actually find the network delay time starting from any particular node. The thing is, we don't know that what node we are going to be starting our code with, but all we have is the information about the total number of nodes that are currently present and the distance it takes in order to reach from one particular node to other particular node. The logic is quite straightforward. We treat this one as a classical graph problem where starting from any particular node, we will try to see that if there exists a shortest distance that can cover all the nodes that are currently present. If we are able to reach to all the nodes, then we will have to check that which is the farthest node and how much time it took us to reach to that particular level. Let's try to understand this with this example, that we were starting our node at node number 2, and it took us 2 minutes to reach to node number 1. Then the amount of time it takes to reach to this node number 3 and node number 1 is obsolete, because we are only concerned about the minimum time it takes to reach to every single node, and that should be our key focus. So few assumptions we can make is that number one, we can use this as a graph problem. This one is going to be the Dijkstra's problem, that in order to reach us to the shortest minimum span, and I don't know the spelling of Dijkstra, so sorry about that. And no worry. Now coming back to the question, basically we need to, number one thing is, have a graph like structure. So what I'm suggesting is we create some sort of an adjacency list or adjacency matrix kind of a structure. So let's say that we do create an adjacency matrix or hash map that contains all the information related to nodes and what are all the different distances that we can travel from those nodes. Now we all know that what are the different edges it takes us from any particular node that we can iterate over. So because we are given the information in this fashion, like x, y and t, where x and y are the nodes and t is the amount of time it takes to reach there. So we can just simply take this x, put it in the node section. So this would be the key for us to search inside our hash map. And this y and t defines that in order to, let's say that in order for from x, we can have an information like this one, that y and 1. So we can say that the node is x. If we have to reach to y, it takes us 1 time. So let's try to build a graph like that for all the nodes that are currently present in this case. But the thing is, we are also going to do one thing smarter, and that is that instead of just pointing out the nearest neighbor any particular node can visit, we will also try to sort these values based on the shortest value first and the longest value later. Why are we doing that? Because we are trying to, we have two objectives. Number one objective is to reach to all the nodes, and second objective is to do it in the minimum time. So we will have to find the quickest route possible. Next objective is that we will have to iterate over all the nodes that are currently present. So we are going to fulfill all of these goals by making some adjustments in the way we do our calculation. So for that, first let me just set up the graph structure that I'm suggesting, and then we will start tackling over the other problems. Now in this case, we are only dealing with 4 nodes. So starting with node number 2, we have two options. If we have to reach to node number 3, it takes us 2 times. So it makes sense that this is the shortest distance. So we can mark the values as, in order to reach to node number 3, it takes 2 times, and in order to reach to node number 1, it takes 3 times. So we are going to mark things like this. Same way, starting at node number 3, once again we have two options. In order to reach to node number 4, it takes us 3 times, and same way in order to reach to node number 1, it takes us 6 times. Same way, from node number 1 we only have one option, and that is in order to reach to node number 1, it takes 5 times, and from node number 1 we don't have any option. So at the node number 1, we basically just don't have any edges that are going out, so we will not mark anything. Now we knew that these are the 4 edges that we will have to traverse over. Next thing is that we also need to keep track that what are the nodes that we have visited so far. And also the other thing is, we need to know that is the node visited if that is the shortest distance that we found so far. Now, in order to tackle both of this problem, what I'm suggesting is we create a new array that is of size n. So we will have values like this one, like 0, 1, 2, 3, and 4. But the thing is, in this case, we are only dealing with nodes starting from 1 to n, so not from 0 to n. So the thing is, for the very first value inside the array, we are just going to ignore this one. Okay, so let's say that we ignore this, and initially we will set this array up to a very large value. So let's say that we are populating the entire array with the maximum value possible, and then the only time we will update this array is, number one, if we find out a path to reach to that particular node by some smaller value, and number two, if we cannot find that, in the end it would be able to show us that there are some nodes we are not able to reach, so we can just return -1 in those cases. So let's try to start iterating over our solution now. It would make much more sense. Let's say that in this case our given k is equal to 2. We are starting our iteration from node number 2. So what is the minimum time it would take us to reach to all the nodes? Now from at node number 2, we can see that the very first possibility is that if we have to reach to node number 3, then we can do it in 2 times. Currently node number 3 has not been visited. So we found a shorter way to visit node number 3. So we will mark it by 2. And then same way we are going to ignore or pop this case out from our given list. Basically we are dealing with a priority queue or a hash map like a structure. So inside the hash map we will add the value number 3, but we will pop out this value from the priority queue. Now from this node number 3, once again we are going to repeat the same process. And by the way, currently inside the priority queue we only have these two values present. So first value was 3 2, and second value was 1 3. Now we add one more value, that is the value 4 3. So now notice that we popped one value out, and we have two more values that we will have to deal with. Okay, and we would keep on iterating in terms of priority queue, and we would always try to find the shortest distance that we will try to kick out. In this case both values are 3. So let's say that we decide to update node number 1 first. So in order to reach to node number 1, we can do it in 3 times. So let's mark this one. Now once again at node number 1 we don't have anything, so we cannot add anything to our priority queue. Then we are located at our node number 4. So sorry, node number 3. So at node number 3 we added one value, that is 4 3, and we also have to add one more value, that is 1 and 6. So for the 4 3, currently 4 has not been visited, so we would mark value number. In this case we would not mark value number 3. Why? Because in order to reach to node number 3 it took us 2 times, so we will have to do the sum with 2. So in order to reach to node number 4, it is actually going to take us 5 times, so we are going to mark 4 and 5. And same way, if we have to follow this path and reach to node number 1, then it would have taken us 8 times. So we are going to mark this as 1 and 8 inside our priority queue. And this is the important step where we are updating the total number it takes in order to reach to that particular node based on the previous value we had in order to reach to that node. So in this case, once again, the node for 4 has not been visited, so we will update it by value number 5. But notice that this 1 8 does not need to be updated, because we already know that we can reach to 1 in 3 times. Then why would we choose a path that reaches 1 in 8 times? So we will ignore this one. And then now we are at value number 4. So from 4 we have one more path then we can go in order to reach to node number 1, and this takes 5 times. So if we choose that, then it becomes 5 plus 5, so 10. But the thing is, we still don't need to update because we already have value number 3. Now the thing is, because we are starting from k is equal to 2, which means from k is equal to 2, in order to reach to k is equal to 2, it is only going to take 0 time. So we should have updated this at the beginning. So I forgot to update, but let me just do it right now, that in order to reach to k is equal to 2, we can do it in 0 times. And now we can see that we are done with our entire iteration. Our priority queue has to be empty because we took care of all the nodes, and we are left with this array. Now in this array, all we need to do is we need to iterate over all the nodes. Ignore the first node because we are only concerned with between 1 to n nodes. Check that if we found at any particular moment any value that was the original max value that we started with. If that is the case, then we can simply return -1 saying that there were few nodes that we were not able to reach. If we don't find any value with -1, we are going to find that what is the maximum value we have in this current array, and currently the maximum value is 5. So we can say that 5 is the minimum number of time it takes for a signal to reach to every single node starting from k nodes, and this is what we can return. So this is a beautiful solution. It has a lot of practical application like aviation industry, network routing industry. All the things use methods like this in order to compute that what is the shortest distance to travel from one point of the plane to the other point of the plane, which is pretty awesome and pretty nice. Now let's try to understand the time complexity. Now it makes sense that we will have to do big O of n multiplied by v work for every single node, and at every single node we will have to check that what is the shortest distance. For that we will have to add those entries inside our priority queue. So it is going to be multiplied by logarithm of n, and this is a pretty decent solution where n is the total number of nodes and v is the total number of vertices, and sorry, not vertices, but this should have been edges, so n multiplied by e. If we look at the space complexity, well, we are using quite number of additional data structures. We are using a graph like data structure to store all the values. We are using a priority queue. We are using bunch of different pointers and stuff like that. So overall, the biggest one is the graph like structure, that is big O of once again vertices multiplied by edges. So this is going to be the space complexity that we would be dealing with. So now let's quickly see the coding solution for this one. So the very first thing we are going to do is that we are going to create a graph-like representation using an adjacency list. And for that we are using a hash map to store the nodes as integers and its subsequent edges as the linked list type of structure. We are simply iterating over every single edges. We are marking the very first node that we currently have as part of a key, and then the second value and the third value is being represented as the edge and the time it takes to reach to that particular level. Then we are initializing a new priority queue where this is going to be a min heap, and we are going to be checking that what is the minimum amount of time it takes to reach to any particular node. Then we are going to be adding the very first value as saying that in order to reach to node k, it takes 0 amount of time, and this would be the starting point for our min heap or priority queue. Next thing is that we will have to initialize the distances of an array with the starting value as maximum value. So we create a new array starting with n plus 1 nodes, plus we fill out all the values that we currently have with the maximum value possible, and the value at the kth position. In order to reach to kth distance, we mark it as 0 because it takes 0 amount of time to reach to node number k. Now then our priority queue iteration starts, that while the priority queue is not empty, number one thing we are going to do is pop out the very first element that is present inside the priority queue, mark the current node with the very first value inside the priority queue and the current distance in order to reach to that node as the second node of the tuple. Then we are checking that if the current distance is greater than the current distances that we have already found, then which means we can simply ignore that case and we don't need to do anything with that particular node. But if we don't have calculated or we found some value that is smaller, then we are going to check that what are all the neighbors for that particular node, and we are going to be marking all of those neighbors in our graph like data structure and adding those to the priority queue. On top of it, we are going to be updating the distance that we need to calculate by adding the current distance plus the new distance that we found in order to reach to that particular neighbor. So this way we are continuously updating all the values we can inside our array. Lastly, all we need to check is that inside the new maximum distance array that we have created, that we need to check that in the given array what is the maximum value we currently have. Notice we are skipping the very first element inside the node because we are starting from n is equal to 1 index, not 0th index. And then we can simply check that if we found that the maximum distance to be the maximum value possible, then we need to return -1. If that is not the case, then we simply return whatever the maximum distance we found inside the array. So let's try to run this code. Hopefully it should be working. Seems like our solution is working as expected. Let's submit this code. and our code beats almost 70% of all the other solutions, which is pretty great and pretty awesome. So once again, you can find the coding solution for this problem in our GitHub repository. Link is in the description. Take care. Hello friends, hope you are having a fantastic day today. So now we are going to solve an awesome LeetCode problem that has tons of practical use cases. We are going to solve a problem called cheapest flight within K stops, and all the travel companies and airlines uses the logic we are going to solve in this problem. So this is a really important and informative problem with lot of useful properties. So basically in the problem statement we are given n cities that are connected by some flights, and we are given an array called flights where we have three values. We have the source city, we have the destination city, and we have the price it takes to get from like the source city to the destination city, and we are given bunch of entries like this. Now we are also given three additional integer called source, destination, and k, that defines that we want our travel to start from the source city, end at the destination city, and k is the maximum number of stops we are allowing ourselves to take. And our aim is to find the cheapest tickets that we can find within the constraint of given k stops from source to destination. And if we can find the cheapest ticket, that's great, we need to return that value. If we cannot find any tickets, then we need to return -1. So let's try to understand this problem with a real life example. So here I have given bunch of different values inside our flights array, and we also have three different values called source, destination, and k. Now we can see that every single entry inside this array contains three values, and we all know that this defines the source city, the destination city, and the price it takes to reach to that particular destination city. We are also being told that we are planning our journey from source city 0 and destination city 3. Now this 0 and 3 can be replaced by any real life values like New York and Paris, France, New Delhi, you name it. And we are saying that we want to take at most one stops, nothing more than that. And now let's try to see that what is the amount or what should be the answer in this case. So I have drawn the whole information that we have provided in this flights array in this beautiful graph like description. And now we can see that we are starting our travel from city number 0, and we need to reach to destination number 3. Now we can see that one route is that we go from 0 to 1, and then once we reach to stop number 1, this would be our first stop, and then from 1 we have to go to 3 because we are only allowing ourselves to only take just one stop. Now from 0 there are no other stops that we can take in order to reach to 3, so this is the only path that we are allowed to take within the given constraint. And the cost to reach to city number 3 in this case is going to be 100 plus 600, so in total 700, and this is what we need to return as the answer. Now say for an example, in the same scenario, instead of k being 1, if we are given the value k being 2 as allowed to be given. Now in this case, let's see the scenario. First stop we can take is that from 0 we can reach to city number 1. This is going to be our first path. Now from the city number 1 we have two options. One option is that we reach to city number 3, that gives us the answer that we can reach to the destination within $700. But the other option is that since we are allowed k to be 2, we can take one more intermediate city as a stop, and we decide to take a stop at city number 2. Now in order to reach to city number 2, it takes $100 plus $100, so $200 to reach to city number 2. And from city number 2 we also have a direct connection to city number 3, and that is also going to be adding the cost of 200. So it takes 200 to reach to city number 2 and plus 200 more to reach to city number 3, so in total it's going to be 400. So in this case the cheapest flight would be 400 that we can return as part of the answer if we are given our k to be 2. So this is what we need to return in this example. Now the first logic that comes to our mind is a very simple brute force approach, where logic is going to be quite straightforward, that we go through every single possibility of all the nodes that we can visit and all the edges that we can visit, and then try to see that what is going to be the cheapest price to reach to the city number 3. In order to do that, we can actually use the graph based representation of this given input flights array, and after converting it into the graph, we can actually do like breadth first search or depth first search from any particular node for all the other subsequent nodes. So we are iterating over all the possible edges and recording the values. We can also use backtracking, recursion, you name it, in order to solve this problem. The thing is, uh, that solution would be okay in terms of like coming up with just a solution to have, but the thing is, think of the real life scenario. We are dealing with hundreds or millions of cities, flights and costs. So that's not a scalable solution. We need to find a better approach, and that's where a beautiful solution or algorithm that comes into the picture, and that is called Bellman-Ford algorithm. So now let's see that how can we utilize this algorithm to solve this problem. So once again, we are going to be using the same example to solve this problem using the Bellman-Ford algorithm. The logic is quite straightforward. We are actually going to be focusing on the only thing that for every single k iteration, how much time it takes to reach to any particular destination city and what is the cost associated with that. And in the end, for all the given k entries, we will keep on running this same process until we reach to the end that we are looking for. And then if we found any particular cost for the associated destination city, in this case we have value number 3, then we can return that. If that is not the case, then we can return -1. So let's try to understand the logic I'm suggesting to solve this problem. For that, we are actually going to be using some sort of placeholder values where we can store that how much time it took or how much money it took to reach to any particular destination city. For that, number one thing we need is to have an array called cost that defines that in order to reach to any particular destination city, what is the cost associated with this. Now the second layer of complexity in this case is value of k, because notice that in our one of the examples we saw, if we only have to make one stop, then we come up with a different cost. But if we are allowed to use two stops, then we are able to come up with a different stop or different cost. So once again, we are going to be using the same logic. And in order to justify the value of k, if we, in order apart from using this one, we will also have to use a temporary array for every single value of k. So now let's try to understand the logic I'm suggesting. Currently I have defined an array called cost, and we are going to be seeing that in order to reach to any particular destination city, what is the cost associated with this one. This is the number one thing. And second one is this temporary array would be reset for every single k value. And once we calculate that how much time and effort and money it took to reach to any particular destination city around any of the k iteration, then we are going to be copying this temporary array to this cost array and repeat the same process for the upcoming subsequent k values. Now in this case, let's say that for first we are going to be calculating that what would be the logic for k is equal to 1. Then we will see that what would be the logic for k is equal to 2. Okay, so let's stay with me. This is going to be pretty interesting to understand and learn the whole process. Now we don't know that how we can define that whether we have a city cost associated that is cheaper or not. In order to do that, what I'm suggesting is that initially I put the cost to the maximum value possible, and after putting the cost to the maximum value possible, whenever we find some value that is smaller than the current value, then we update that value, because it is in our benefit to update the cost it takes to reach to that destination city. And now let's start our process. Now we know our source city is 0, so by default, logically, in order to reach to city number 0, the cost has to be 0 because we are already there, that is our source city. So we are going to be checking first of all updating that value inside our array. So for city number 0, currently it takes maximum value to reach to that particular city, but we are going to be defining it as 0. Okay, and now we are starting our process. So we are going to go through edge by edge for every single array, we are going to be updating the temporary value for that kth element, and then temporary array is going to be flipped over to the cost, and then we are going to repeat the same process. So currently for the temporary array, we are going to take a copy from the cost for this first iteration. So this is 0 and all of these are max in order to reach to any particular city. Now first thing is that in order to reach to city number 1, it takes us $100. So we are going to be updating that information, that in order to reach to city number 1, it takes $100. But the thing is, first we are going to check that the source city that we are traveling from, that already has some value and it is not the maximum value. Because if any particular city has the maximum value, that means that that city is not reachable. So if the source city is not reachable, how can we reach the destination city from that source city? Now in this case, source is 0 and destination is 1 and the price is 100. So we already know that we can reach to the source city because this value is 0 inside the current array. So then we are going to be updating this one as 100 because it takes $100 to reach to that particular city. Next thing is, in order to reach to city number 2, it takes $100 from city number 1. But the thing is, in our original cost array, we cannot reach to city number 1. So once again for this one, we should not be able to reach to city number 2 as well because city number 1 is not reachable. So notice this is going to be for k is equal to 1, only one city. So we can only make one stop, so that is this stop. And if we, so that's it. So now next thing is, in order to reach to city number 0, the cost is 100 from source city 2. Once again, for 2 source city 2, we cannot reach inside the cost array, so we cannot update any value. And also in this case, this would not be updated because currently in order to reach to city number 0, the cost we have is 0 and this is 100. So why would we pay higher money if we already have a lower value? So this would not be used. Next value is, in order to reach to city number 3, it takes $600. The thing is, we cannot reach to city number 1. So currently, and notice that currently we are iterating over k is equal to 0 and we have maximum value of k is equal to 1. So we are going to be running this iteration twice. So currently for k is equal to 0, this one is from 1 to 3, it takes $600. But the thing is, we cannot reach 1, so we cannot reach 3. Once again, next iteration, we cannot reach any other city because 2 to 3 is 200, but we cannot reach 2, so we cannot reach 3. So these are also going to be blank. Now notice that after the first iteration, we only traveled one city, that was the immediate neighbor of this node number 0. And this is the whole point of this exercise, that every iteration we are going in like breadth manner for all the cities that we can iterate over, and we are updating the cost accordingly. Now for the next k iteration, we also need to update the value of this temporary value inside our current cost array. So first we will update this one. So this is going to be 0, 100, and then these two are going to be max value and max value. And once again, we are going to be starting with a blank temporary array, but we are going to take the copy of this cost array. So this is also going to be 0, 100, and then max value and max value. Now let's see the same iteration again. Now 0 to 1, 100, we already have this value stored, so we don't need to update. 1 to 2, 100. Now in this case, we are able to reach to city number 1 with 100 cost. So in order to reach to city number 2, the cost has to be 200. So we can update this value to be 200. And notice that this time we are iterating over for k is equal to 1. We initially started for k is equal to 0, and now we are going to keep on repeating the same process. Now next thing is 2 to 0, it takes 100, but we don't need to update that because in order to reach to 0, we already have the value as 0. Next one is 1 to 3 as 600. Currently, in order to reach to 1, we have the value 100. So we can reach to city number 3, and 1 to 3 is going to be 700. So we are going to updating the value as 700. And now next thing is 2 to 3 is 200, but we cannot reach 2 in this case because cost array is still showing 2 as maximum value, so we are not able to reach this one, so we are not going to be considering this edge. And next thing is, next would be the k is equal to 2, but the thing is, notice we only have k is equal to 1 as max. So the moment we are done with this one, we will break out of all the loops. And sorry, before this one, we are actually going to updating the temporary array to the cost array as well. So now inside our cost array, we will have a couple of more entries. So in order to reach to city number 2, it's going to be 200, and in order to reach to city number 3, it's going to be 700. Now after this one, once we end our loop, we are going to be checking our cost array. We are going to be seeing that if the destination city is 3, and if this value is not maximum, then whatever value is, we need to return this one. So answer is going to be 700. And if we cannot return 700, like if the value would have been maximum, then we would have returned -1. Now let's take one more example for k is equal to 2, just to solidify your understanding. Once again, 0 to 1 100, we already have updated this value. 1 to 2 100, we also have updated this value as 200. 2 to 0 as 100, we don't need to update this one because we have 0 as 0. 1 to 3 is 600, so this has also been updated. And next value is 2 to 3 is 200. So this value, we can see that we are able to reach to city number 2. That means we can reach to city number 3. The cost is going to be 200 plus 200 400, but the current maximum cost to reach to that particular city is 700. So we need to remove 700 with 400, because now we can reach to city number 3 with 400 cost. And now, since this is k is equal to 2, once we are done with our loop, we will update this value over here. So this becomes 400. And then in the end, if we have to return the answer, we can return 400. That after with k is equal to 2 stops, we can reach to city number 3 in 200 cost. So imagine, see how beautiful the solution is. And now I hope you understood that what we are trying to do over here. If we have to calculate the time and space complexity, it's quite obvious that for k times, we will have to iterate over all the given edges that we currently have and all the given nodes that we currently have. So it's going to be k multiplied by the number of nodes and edges. So O multiplied by V. So yeah, and this would be the time complexity. And if we see space complexity, we are using couple of arrays to store the values. This is going to be the temporary storage, and this is going to be the constant storage, but both are dependent on the number of cities. So let's say if the number of cities are the number of nodes, so it's going to be big O of n, where n defines the number of nodes. And this is the whole solution. Now let's quickly see the coding solution for this one. So the coding solution is actually quite straightforward. First, we are going to initialize our cost array. Then we are going to be filling the cost array with the maximum value possible. Then we are going to define that in order to reach to source city, it takes us 0 amount. So we are going to mark it as 0. And then we are going to initialize our two loops. First loop is only going to run from 0 to k value, where we are going to be starting a temporary array, where that is going to be the clone of our cost array that we have created so far. Next, we are going to be iterating over every single edge. Now for this edge, first thing we are going to be doing is defining the value of u, v, and the cost to reach to that particular city, where u is the source city, v is the destination city, and cost defines that how much money it takes to reach to the destination city. The values are extracted from our flights input array. Next, first thing we are checking is that in the original cost array, if in order to reach to city u, that is the source city, is maximum value, that means we cannot reach source city in that kth iteration. So we need to continue that operation. If that is not the case and we are able to reach to the source city, then we are checking that in order to reach to the destination city v, what is the current cost we have. And if the current cost is actually greater than the cost we are able to achieve using the cost it takes to reach to city u plus the current cost for the based on the current edge, whichever is the smaller, we are going to be keeping that value inside our temporary array. And once we are done iterating over all the flights for that kth iteration, we are going to be copying the temporary array inside our cost array and repeat the same process for the next kth iteration. In the end, the answer is quite straightforward. We simply need to check that if the cost to reach to that particular destination city, if that is the maximum value possible, then we need to return -1. If that is not the case, whatever the cost value is, we can simply return this one. And this is the whole solution. Look how beautiful it looks. Now let's try to run the solution. Seems like it's working as expected. Let's submit this code. And our code runs beautiful. It beats almost 97% of all the users, which is pretty awesome. And I would be posting this solution inside our GitHub repository. So if you want, you can go ahead and check it out from there. Thank you. So the LeetCode problem we are going to solve now is called minimum cost to connect all points. This is a very popular question in my opinion. Why? Because we are going to be dealing with something very important that is called Prim's algorithm to solve this problem. And this Prim's algorithm actually has a lot of different practical applications that you can use it in all sorts of different questions and different techniques. So let's understand the problem statement. We are given an array points that represents an integer coordinates of few points on a 2D plane, which means x and y type of graph. And we are told that any particular point value is defined as xi and yi, so the coordinates of that location. Now we are told that the cost of connecting 2 points x and y is the Manhattan distance. So let's say that if you typically has like 3 values, and if you are trying to, let's say, connect any two like this one, in this case the cost of this one is going to be the Pythagoras if we try to choose the diagonal. But the thing is, Manhattan distance is that instead of picking out the value of the straight diagonal between these 2 points, you first go to a common point and then go to right. So in this case you are actually doing the delta of x and you are also doing the delta of y, so absolute values of x1 and x2 amongst these 2 points, and the sum of this is going to be the total distance you are going to cover. So this is called Manhattan distance, and this is what we are going to follow. So it's slightly better for us so that we don't have to spend so much time on calculating the Pythagoras or root values. Now we need to return the minimum cost to make all the points connected. Now let's try to understand this with an example. In this case, suppose these are the different points we are given. Now we need to make sure that number one, we connect all of these points in some fashion. And after connecting these points, we also need to make sure that the distance we are traveling by connecting them is the minimum distance we can. Now let's try to understand first of all that how does a Manhattan distance is going to work. So let's say you want to find out that what is going to be the distance between these 2 points, then logic is going to be quite straightforward. You are first going to do the difference between x pointers, so this y pointers, and you are going to add it to the difference between x pointers. So in this case the distance between these 2 nodes is going to be 4. Though it's not a diagonal, I'm just writing it diagonally so it becomes easier for us to understand. Now the thing is, the solution of this problem is something where we will have to deal with minimum spanning tree. Now minimum spanning tree is a very important concept in the graph theory, where you are given bunch of different points on any particular plane and you are trying to connect all of these points in some fashion such that there are no cycles being formed, and you are trying to span the tree in like only the places where it is absolutely needed, nothing more than that. But the question is, the first thing that should come to your mind is that, hey, in this case we are only given points, we are not given the edges, which means these are simply just the nodes we are given. We know in order to solve any particular graph problem we need two items. We need a nodes and we also need edges. But the thing is, good thing for us is we already know how to calculate edge between any 2 points. And the thing is, in this case there is possibility that from every single point you are able to connect to every other point in order to treat it like an edge. But the thing is, if I try to draw the whole solution by that matter, it's going to look very bad, because imagine how many number of different edges you can form amongst all of these points, and then it is only going to look so much more messy and complex if you have to understand all the different flows and data entries and data points and whatnot. So what we will try to do is we will understand that what is the most simplest logic we can use to solve this problem, and we will also understand that how we are going to be using the Prim's algorithm and the solution of basically Prim's algorithm plus the graph theory concept to solve this problem. So let's start working on the solution of the problem. I hope you must have understood that what the problem is asking us to solve. So now let's very quickly and very simply think one by one that what are all the different possibilities we have across all of these 5 different points. Well, number one possibility is that if we are at this point, we don't know that what are all the points that are currently present inside the remaining graph, which means we don't know that if we have to generate a minimum spanning tree that crosses or that goes through every single nodes that are currently present, which node should this node 0 be connected to. So we don't know this question, number one thing, that what is the minimum cost to reach to any particular point from this node 0. And remember, we need to make sure that we don't form any cycles, because we simply need to connect all the points, and if there are cycles, basically our cost of connecting all the points would increase. So the shortest way to connect all the points is through like some sort of a straight line or a tree kind of structure where there are no cycles. So now at this 0, the number one thing we will have to do, if we have to find the shortest distance or the closest point, we will first have to calculate every single distance we can from all the remaining points to this 0th node, and the distance between these points would be treated as the edges, because we are basically connecting 2 different points, and amongst those edges we will have to find the edge with the smallest value. So these are actually weighted edges. And the other thing is, the connection in this case is going to be bidirectional. Why? Because whatever the distance from this 0 to this node is, same distance is going to be from this node to 0 as well. So we don't need to do any directed distance calculation in this matter. All we are concerned about is unidirectional transfer, and to understand that what is the minimum place to reach that place. Now comes another problem. Let's say that from the 0, it makes logical sense that this is going to be the smallest distance that we can calculate, and we also know that the distance amongst this one is going to be 2. So sorry, 2 plus 2, so total, let's say that this distance is 4, that we already know that this is going to be the smallest distance. But once again, when we come back to this place, now we still have 3 more nodes that we will have to iterate over. We are not going to iterate over node number 0. We are going to treat that this 0 has already been visited, but once again we will have to repeat the same operation. And from this position, we know that the shortest distance we should be able to find is going to be this value. So if we calculate this, I think this distance is going to be 3. Okay. And same way, from this 3, the shortest distance that we calculate for any particular node is going to be this one, and this distance is also going to be 4. But the thing is, now we still have one more node remaining, and we already found the results for these 4 different nodes. So question is, how do we know that which node is actually going to call to this particular node? So for that, we will actually have to find a way that while we are calculating the distance from 0th node to all the other nodes, and same way from this first node to all the other nodes, we will still have to keep track of all the nodes that are still remaining. Because the thing is, it could be possible that there are some nodes that are not down the path of the shortest nodes, but the thing is, we need to connect all the points, so we will still have to find a node that is still closest to this node, that it makes sense to make that connection. Now I know what I just said might sound confusing, but the thing is, try to understand this from an example point of view, that if you are if we only traversed, or if we only use the greedy approach where we are just iterating in the minimum fashion, then we are always going to be stuck with one node that is not following this beautiful path. And the thing is, if we try to find the path to that node, that remaining node from here, this might be much longer compared to this distance. So in order to do that, what logical solution I'm suggesting is that we first start at the 0th position. From the 0th position, we make the calculation that how much time it is going to take to travel to this first node, second node, third node, fourth node, all of these nodes. Same way, then we find that amongst these 4 nodes, which one has the smallest value to reach to there, so smallest edge, and we realize that the smallest edge is 1 in this case. Then from this 1, we know that we already calculated the distance for 0. 1 is a self node in its own, which means now from 1 we will have to keep track that how much time it takes to reach to node number 4, 2 and 3, and keep all of these results stored somewhere as well, and then try to pick the smallest value that we can. Once again, from the smallest value, repeat the same operation for the remaining elements. So even from this smallest value, we will calculate these two distances. Once again, pick the smallest one, and then from the smallest one, see that what is the remaining value, and for all the remaining values, so for this remaining node, see that currently we should have three results. One result is between node 1 and this one node number 4. Second result is node 2 and node number 4, and third result is node 3 and node number 4. And amongst these three, whichever is the smallest one, pick that one, and that would be our solution. So now let's just try to walk through the whole solution that we just talked about and see that what are all the different concepts we will have to use to complete the solution in a manner that we are proposing. Now, first of all, what we need to do is we will need to make sure that there are no cycles. In order to make sure that, we will have to keep track that all the nodes that we have currently visited. So we can use some data structure like a hash set or an array or a boolean array of size n to keep track of all the values that we have visited so far. So let's say we will use hash set for now for our understanding purposes, but at the same time we are also going to be using array during the implementation. Okay, so let's say that we currently have our hash set that we are going to be storing to make sure that there are no cycles. Next thing is we will have to make sure that for every single node we calculate the distance to all the remaining nodes, find their distance, and we need to sort those distances. So in order to do that, one of the beautiful data structure we have is actually a heap, and we can have a min heap where from every single node that we start iterating over, for all the remaining values we will try to calculate the distance and put them in the min heap, so that it would be stored in like from in a ascending order. So smallest value would be at the beginning that we should be able to find. And how we are going to be storing the value inside the heap would be in this fashion, where the first value is going to be the distance and second value would be the point. So we would say that in order to reach to that particular point, what is the smallest distance that we will have to cover? That's it. That's all we need, because we are only concerned about the cost to reach to that point. So now let's see that first node is 0. In order to reach to 0, and let's say that we decide to start from 0. It's not necessary that we have to start from 0, but let's say that we decide to start from 0. So in order to reach to 0, what is the minimum cost it takes? So minimum cost it takes is still going to be 0. So we are going to be adding the value 0, 0 over here. Next thing is from 0, now we have 4 different options to choose from, that in order to reach to all of these values. So first value is in order to reach to, let's say this one is node number 1, node number 2, node number 3 and node number 4. So in order to reach to node number 1, the smallest distance it's going to take is going to be value number 4, and we will mark it as by 4, 1. Same way, if we have to reach to this value number 3, let's say that the distance is going to be 5 plus 2, 7. So we can mark the values as 7 and 3. Same way, if we have to reach to this value number 2, then the distance is going to be 13. So we can mark 13 and 2. And next thing is same way, if we have to reach to value number 4, then the distance is going to be 7. So we can still mark 7 and 4. And notice that we are going to be sorting these values because this is a min heap, so it would automatically be sorted. So the value would be something like this one. So 7 and 4, and then I think it was 13 and 2. So these are the currently 4 values that, or 5 values where we have so far. We will pop, and now we have started our iteration. So we will pop the very first element, which means we pop this value 0, 0, and we know that the cost to reach to value number 0 is 0. So we will also need to have a variable to store all the cost. So let's say that we have a variable that where we are storing all the cost. In the cost, we first add 0 because that is the cost to reach to value number 0. Let's say we kick out value number 0. The thing is, because we already visited 0, we are also going to be marking 0 inside our hash set. So let's say that this is our hash set and we already visited node number 0. So from now on, any subsequent entries that come in with value number 0, we are simply going to ignore that because we have already visited that inside our hash set. Okay. And let's keep on doing the iteration. Now the next entry inside our heap is node number 1. From node number 1, it takes 4 cost to reach to node number 1. So let's mark the cost to 0 plus 4. We are also going to be marking that one has already been visited so far, and we have this channel being established. Okay, now from once again, from one we will have to repeat the same operation, because remember, from every single node what we are trying to do is we are going out in the breadth first search manner, not depth first search manner. So we went to one of the neighbors of 4, and then we are going to be visiting one of the neighbors of 1. Same way we are going to be visiting one of the neighbors of 3, and same way we are going to be visiting one of the neighbors of 4. So this is a BFS traversal, not a DFS traversal. And now let's just mark one, and okay, so now once again we are going to leave all, we are going to be popping these two entries, but these three entries like 7 3 7 4 and 13 2 is still going to be present inside our heap. Now from this one we have once again three options. First option is this one, the cost of this is 9. Second option is this one, the cost of this one is 3. And the third option is from 1 to 4, so the cost is going to be 2 and 5, so 7. So once again we are going to be having one entry, that is 3 and 3, which is in order to reach to node number 3 we are going to be using distance 3. Next entry is in order to reach to node number 4 the distance is going to be 7. So next entry would be 7 4, so we can also put one more entry over here, 7 4. Okay, and we are going to be having one more entry, that is 9 2. In order to reach to 2 the distance is going to be 9. So we will have one more entry, 9 2 over here, and then the 13 2 would be like succeeded to the back end, and this is going to be the current values inside our min heap. Now once again we are going to be popping out the very first element, that is the smallest element, that is node number 3. And in order to reach to node number 3 we will have to add cost as plus 3. So we will mark plus 3 cost over here. We will mark 3 as being visited because we already visited this one, and we will get rid of this entry. So now you can see that now the moment, let's say that suppose I'm just giving you for an example, suppose we say that this is the next closest node and we will try to extract this one. The moment we see that in order to reach to node number 3 it takes 7 cost, the thing is we already visited 3 inside because it's present inside the hash set, so we can simply ignore this case. And same way we are going to be ignoring all the cases that are going to be like different from the nodes that we have not visited so far. Same way from 3 to 4 we have this type of distance, and that distance to 4 is going to be 4 once again. So we can mark 4 4 because that is the smallest entry, and from 3 we will have to calculate one more distance, that is 2 up to this 2, and that distance is going to be 10 2. So we can mark one entry over here, that is going to be 10 2. So once again we are going to be adding cost 4 because we visited node 4. It takes 4 unit of time to reach to node number 4, and we have visited all of these entries. Now the thing is we visited all of these. Now from 4 we will once again calculate the distance to 2. So let's say that this distance is going to be 15, so 15 to 2. So currently these are all the entries we have inside our heap, and let's see that what we need to do. So we already visited 0 1 3 and 4. We haven't visited node number 2, so we start popping values out. So we first pop this value 7 4 because we have visited 4, so we can just ignore this one. Same way we can just ignore the 7 4, and then we have this node 9 2. So we pop 9 2 out. 2 we haven't processed, so we are going to be marking the node 2 visited over here and add this cost 9 over here as well. And now you can see that the size of our hash set is exactly same as the size of all the number of points that we are given, which means we have visited all the nodes and we can stop our conclusion. So in order to do this one, the moment we the size of our hash set becomes the number of nodes present, we can stop our calculation, and whatever the cost we found so far we can return that as the answer. So in this case the answer is going to be 20, and this is the whole solution. So I hope it makes sense to you that how did we calculated this. We dealt with a lot of concepts that how not to detect cycles. Then we also make sure that we had a hash set to understand that what are the nodes visited so far. We had a heap to find the smallest entry from any particular point, and we were doing all of this while calculating the cost of the minimum spanning tree. So this is a beautiful solution. If we understand the time and space complexity, time complexity is going to be big O of, first of all, let's imagine we will have to do n square work for any single node. Why? Because at this position we will have to calculate distance between all of these 4 points. Same way at this particular location we will have to calculate the distance between all of these 4 points. So we will have to do big O of n square work to calculate all the distance, and then we will have to find the shortest distance, and shortest distance we are finding by using a heap. So it takes n log n time in order to find the solution from the heap. So overall the time complexity is going to be big O of n square log n. If we see space complexity, because we are storing all the entries inside our heap, it is also going to be big O of n square. So overall this is an expensive time and space complexity, but given the scope of problem we cannot do anything better than this one. So now let's quickly see the coding solution. So the very first thing we are going to do is to define the total length of given all the points that we currently have. This we are going to be using to check against that whether we have collected all the points or not. Then we are going to be initializing our priority queue, and this is going to be our min heap. Then we are also initializing a new boolean array to store that all the values that we have currently visited so far. So we are marking it as in MST, whether it is present in the minimum spanning tree or not. Then we are defining a new class called point. So let's understand this one. So we have a new class called point, and it only contains two values. First one is a distance and second one is an index. And we can see that we are going to be using this instance of this class to store values inside our min heap, where we are storing that in order to reach to any particular index, what is the distance that it takes, and then heap would sort it out for us. And the very first element we are adding inside the heap is that we are adding the very first value, value located at index position number 0 inside the points, and we are saying that it takes 0 cost to reach to those points, and this is how our priority queue works. We are also having a variable to store the minimum cost that we have been able to find so far, and we have a value called points connected, so which we can use it to compare it against the total given length of points to define that whether we should complete our iteration or not. Then we are running our loop until our points connected reaches to the total number of n that is currently present. Then we are fetching the very first value that we currently have out of the priority queue. So we are doing a poll operation and then checking that whether this point that we found out, this current point, have we already visited that current point. So we can check that using the boolean array that we have created. Then we are checking that if we have not visited, then we are going to be marking it as visited, and we are also going to be updating the minimum cost to reach to all the nodes by the distance that it takes to reach to that particular node, and we are also updating the value of points connected so far. So now we already calculated and visited that particular point, but the thing is we will have to still calculate the distance to all the remaining points from that point. So we are going to be running another for loop that is going to span across every single n that is currently present. First we are checking that any particular index that we are checking, have we already visited or not. If we have already visited then we can ignore. If we have not visited, we will calculate the distance by using the math.absolute points, and then we will add a new entry inside our priority queue by adding that ith location and the distance to reach to that ith location, and it would sort it automatically. In the end, we simply need to return the min cost that has occurred so far to reach or connect all the points, and this is the whole solution. So let's try to run our code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs beautifully compared to a lot of other solutions. It's almost 80% faster in terms of time complexity, and also 80% faster in terms of space complexity. So which is pretty great. Once again, the solution is present inside our GitHub repository, so feel free to go ahead and check it out from there. Thank you. So once again, we are going to do a very awesome LeetCode problem. This one is a reconstruct itinerary. We can see that this one is a LeetCode hard problem. Also, constructing an itinerary is actually a very popular real life use case that we see in like aviation industry all the time. So this is an important problem. Let's pay our utmost attention. Now we are given a list of airline tickets where any particular position we are given like a tuple value inside the array that defines that where what is the departure and arrival for locations based on that particular unit. Now we need to reconstruct the itinerary in in like a particular order and return that reconstructed itinerary. Now let's see that what are the constraints around reconstructing the itinerary. Number one thing is all the tickets belong to a man who departs from JFK, which means JFK is the starting position for our entire itinerary. Then next thing is that if there are multiple valid itineraries that we are able to construct, then we should return the itinerary that has the smallest lexicographical order. So what does lexicographical or lexical order means? It means that we need to sort them in like A to Z manner, basically, which means if we, let's say if we have two tickets, first one is from JFK to LGA and second one is another ticket from JFK to LGB, then we must return LGA first before returning LGB, because remember that we are sorting lexicographically. So this one has character A and this one has character B. So A comes before B, which means this has a smaller lexical order. So we need to put this in priority. Now we are also told that we may assume that all the tickets are valid and we must use all the ticket once and only once. So let's try to understand this problem and try to see that what could be the potential solutions. Number one thing is this is the type of input we are given. Now we can see that there are a bunch of different tickets we are given. In this case we are given a ticket that is from Munich to London Heathrow. We are given a ticket from JFK to Munich, then San Francisco to San Jose, and London Heathrow to San Francisco. So these are the 5 tickets we are currently given. I have just plotted all the 5 airports over here, and now let's see that what is the solutions we can make. So let's just take a simple approach, and let me just keep on marking all of these nodes or like all the flight connections. So we know that we have a connection between Munich and London Heathrow, so let me mark this one. Then we have a connection from JFK to Munich, so let me also mark this one. Then we have a San Francisco to San Jose, so marking this one. And then we have London Heathrow to San Francisco, so let's mark this one. So this is a valid order. We can see that every single ticket we currently have, that are 4 tickets we have, we used all of these 4 tickets over here. After using all of these 4 tickets, we need to reconstruct itinerary starting from JFK. So we can see that if we start our journey from JFK, the direction is going to be JFK to Munich, then Munich to London Heathrow, Heathrow to San Francisco, and San Francisco to San Jose. This is the reconstructed itinerary that we need to return in this order. Let's take one more slightly complicated scenario. So we have like bunch of different tickets in this case, and we only have 3 airports to deal with. So first ticket is JFK to San Francisco. So let's just mark this one. So JFK to San Francisco, this is one option. Second option is JFK to Atlanta. So let's mark this one. Then San Francisco to Atlanta, okay. Then Atlanta to JFK, okay. And then Atlanta to San Francisco, okay. So currently these are all the different options we have. Now let's see that what is the optimal option we need to choose. We know that we need to start our journey from JFK. Now notice at JFK we have 2 different tickets going outwards. First ticket is going to the San Francisco and second ticket is going to the Atlanta. So question is, which ticket should we choose? Now here comes the lexicographical ordering that we need to pick from, and we can see that Atlanta is lexicographically smaller than San Francisco. So we are going to pick ATL first. So in our path, this is going to be the first path we are going to take. All the markings that I'm marking with red is like the correct marking, okay. So we took care of one ticket. Then from Atlanta, once again we have 2 options. We can either go to JFK or we can either go to San Francisco. So once again it makes sense to pick the smaller amount, and that is once again going back to JFK. So let us go back to the JFK. Now at JFK we only have one option, that is go to San Francisco. So we go to San Francisco, and then from San Francisco now we only have one option, that is to go to Atlanta. So we go to Atlanta, and now from Atlanta we still have one more edge that is remaining, and that is to go back to the San Francisco. So we will once again go back to the San Francisco. So this is the sequence we are going to follow. where first we are going to go from JFK to Atlanta, then this is the second, this is the third, this is the fourth, and this is the fifth flight we are going to take. So this is what we need to return. Now I know understanding this question took way longer than expected, but don't worry, the solution is not that complicated. So let's just try to understand a simple logical scenario just for this particular input that we are given. What is the one thing that we did to solve this problem? Well, it is quite obvious what we did to solve this problem. We first of all mark that from every single airport, what are all the different possibilities we can take, and then we started iterating over our journey from JFK. On top of it, not only marking all the different possible journeys, we also mark that what under what order should we start picking and start moving in any particular direction. So what I'm suggesting in this case is that we are only given the tickets, we are only given these values from any particular two nodes. What I'm suggesting is that we actually treat this as a graph problem, and which is pretty obvious. Why are we treating it as a graph problem? Through this one, we are going to be marking every single airports we currently have as the nodes and all the tickets that we currently have as the edges. Okay, we already got our nodes and edges. On top of it, what we need to do is we need to iterate over the given graph. Now, iteration of the graph is quite simple. We know that we have two methods. We have a breadth first search method and we have depth first search method. Now in this case, going in one particular direction makes more sense, because notice that over here we are going in like a depth first search fashion. Even in this example, we saw that we were doing bunch of different back and forth in order to complete all of our transaction, and that was also being done in depth first search fashion. So in this case, we are also going to be using DFS to iterate over all the nodes. Next thing is we need a starting pointer to iterate over. We already have a starting pointer, and that is starting from the JFK. So we know that we first of all need to treat it as a graph. We will need to do a DFS. We will need to start iterating over from JFK. Next thing is when we are constructing a graph, we will have to set up ordering in which sequence are we going to go to any particular airport, and for that we will have to follow the lexicographical ordering. So for that, what I'm suggesting is that we actually use an adjacency list kind of a scenario where we store the adjacency list for our graph and we do it in lexicographical ordering. So what I'm suggesting is that we initialize a hash map. As part of the hash map, we need two items, key and value. As part of the key, we mark the nodes or the airport. As part of its values, we mark that from that airport, how many different tickets that we can traverse over. So, or how many different airports or destinations we have. Okay. Then once we have these two values, then we need to populate these arrays. So let's start populating this value for this given input. Okay. So currently let's go one by one in these throughout all of these tickets. So first one is we are starting from JFK. So one node is JFK. Okay. Now from the JFK, we need to have a ticket. The destination is San Francisco. So let me mark this as SF. Then we have one more ticket from JFK and the destination is Atlanta. Now we know that JFK is already present. The thing is we are trying to insert Atlanta over here. So one logical thing is that rather than just doing anything, let me just create a linked list over here where I'm storing Atlanta as well, that from JFK I have one more ticket that goes to Atlanta. Okay. Same way, we have a San Francisco and the destination is Atlanta. So let me also do that. And we have Atlanta and JFK. So Atlanta and JFK. Okay. And last one is Atlanta to San Francisco. So we are going to have one more destination, San Francisco from Atlanta. Now we have our key or our graph, our adjacency list being created, okay, inside our hash map. But the thing is, we need to sort this in lexicographical manner. So what we are going to do an intermediate step where we are simply going to update this given graph that we have created so far. And for this one, we are simply going to sort all the values or all the inputs we have in the destination in lexicographical manner. We know that this can be done in n log n time. So we are going to spend that extra time in order to complete that. So let me just start marking this one. So first entry is JFK. Okay. For JFK, we currently have two values. First one is San Francisco and second one is Atlanta, but this is not sorted correctly. So we are going to sort it. First one is going to be Atlanta and second one is going to be San Francisco, as this is going to be the sequence of linked list. For San Francisco, we only have Atlanta. So let's just mark this one. And the last one, even for the Atlanta, we have JFK and San Francisco, that is already sorted in correct order. So let's just mark this one. So JFK and we have Atlanta. Okay. San Francisco. Okay. So let's just mark this one as well. And now we have everything we are looking for. Now all we need to do is just do the DFS operation from our adjacency list on the graph, and every time we iterate over one destination, we are going to remove that from the list. So next time when we are at the same airport, we simply pick the next lexicographical entry in sequence. So let's try to run the solution. So we start our journey from JFK. So we are initially at this JFK location. We saw that the first ticket we need to find, or first flight, is Atlanta. So let's just traverse to Atlanta, marked as A. Now we need to go to the Atlanta because we are currently presented in Atlanta. Also at the same time, we are going to remove Atlanta from here, and we are going to go to the Atlanta. Now Atlanta, the very first flight is JFK. So once again we are going to come back to JFK. So after coming back, we are going to remove JFK from here. So now at the JFK, the next flight in sequence is San Francisco. So let's just make another journey to San Francisco. And now we are going to remove San Francisco from here. Now at San Francisco, next flight is Atlanta. So let's just mark a journey to Atlanta, and we are going to remove Atlanta from here. And now from the Atlanta, let's just mark one journey to the San Francisco. So we are going to mark a journey to the San Francisco, and we are going to remove San Francisco over here. Now the moment we come to any particular position, let's say we came to San Francisco, now there are no more entries or no more destinations for us to visit, which means we can conclude that we have iterated over every single possible tickets that we currently have present, and we can simply say that we iterated over all the entries, and this is the path that we created. We can just keep track of the path in like a backtracking function, and because we are making recursive calls to use the DFS and solve this problem quite easily, quite beautifully, quite simply, and this is an awesome LeetCode problem. If we understand the time complexity in this case, that is going to be big O of vertices multiplied by edges plus big O of n log n in order to do the sorting, but this is already greater than n log n, so we don't need to factor that in. And if we talk about the space complexity, it is going to be big O of once again vertices multiplied by edges, because we are creating a new hash map that is going to be of length v. So actually this is only going to be big O of size v, but in the value section we are going to have all the edges that we currently have, so it's going to be v plus e. Okay, so this is still a good time and space complexity. Now let's quickly see the coding solution for this one. Okay, so the very first thing we are going to do is to create a map to store the list of destination for every single departure airport. So we are going to create a new hash map where as a key we are going to store the string that is going to store the name of the airport, and as part of its value we are going to be storing a linked list or list of strings. Now we are going to iterate over every single tickets that we currently have and keep on marking all the values inside our graph hash map that we have just created. After having a representation, now we are going to be sorting all the values that we have in the destination of the graph. So we are going to run a for loop and just do a sort operation. After sorting it out, we simply need to start our journey from the JFK terminal. So we are going to have a linked list that is going to be creating an itinerary that we need to return as part of the answer. And we are going to have a DFS operation that is going to start from the JFK airport, where we are going to pass in the graph that we have just created that contains all the sorted destinations, and the itinerary linked list where we are going to be storing all the values in sequence. Now let's see our DFS method. So first thing we are doing is that we are adding the current airport we are at the destination. After that, we are checking that while the given destination is not null and the list of destination is not empty, then we are going to remove that destination to avoid revisiting the same path. So we are simply going to removing that inside our array, and we are also going to be calling the next value that we need to iterate over and calling our DFS function once again. So that's it. This is the whole solution, where instead of passing in JFK, we are passing in the next airport that we have to iterate over. And we are also adding the airport to our itinerary as well, just so that we know that what airport we are beginning at, and we are generating the itinerary in the reverse order. So now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs beautifully compared to like almost 75% of all the other solutions, like 71%. It can still be improved in terms of space complexity. So let me know in the comments if you want to see that. But anyways, you can still see or find the solution on our GitHub repository. So feel free to check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do alien dictionary lead code problem, and not only it is a very important problem, this problem can actually be asked in multiple ways. It can be asked directly as a graph question, or it can be asked as a follow-up question for the previous question that we solved, verifying an alien dictionary. Because both questions are very similar, and if you want to check that where the solution for this problem is, you can check it out from over here. Also, another reason why this problem is really important is if you just take a list of companies that have asked this problem: Airbnb, Facebook, Google, Amazon, Bloomberg, Microsoft, Uber, they have all asked this question in last 6 months. Also, IT giants like Pinterest, Apple, Twitter, eBay, they all have asked this question in last 6 months to 1 year. And ByteDance, Snapchat, and Flipkart, so they have asked this question not fairly recently, but still it's important. And I will be paying my utmost attention, because my aim is to clear any FAANG interview, and I hope you also enjoy the video. This is a LeetCode hard problem, and it justifies this hard tag. So let's understand the problem statement. Essentially, we have identified a new alien language that uses English alphabet. However, the order of those letters is unknown to us. Now we are given a list of strings inside this words, and we are told that they are from this alien languages dictionary. And in that string, the important property these words have is that they are sorted lexicographically. And we need to return a string of unique letters that are present in these words, and we need to return them in lexicographically increasing order. Now also, there could be possible that there might be multiple solutions. So if there are multiple solutions, we only need to return any one of them. And there could be some cases where this given string of words is invalid, and if it is invalid, we need to return an empty string. So in order to understand this problem, first of all, we will have to identify that what does this lexicographically increasing order means. The second thing we will have to understand is that what are the cases where this particular input is going to be resulting in falsified information, and what does this string of unique letters with lexicographically increasing order means, because this unique word is actually really important, and I'll come to that later. So suppose if we just talk about what is lexicographically sorted means. If we talk about English language, if we talk about the words A, B, C, D, all the way up to Z, this is plain English language that we use on a day-to-day basis. Now in the English, suppose we are given any 4 letters. Suppose we are given letters like Q, A, E, B, R, C, and Q, E. Suppose we are given letters like this, right? And if we want to sort these 4 in plain English language, how we are going to sort them? Like, of course, the answer is simple. We are only going to check that what is their position in this given order, and based on that particular order, we will sort them. So if we sort them, the sorted result would look something like EA, QA, QE, and RC, something like this, right? And the reason we are able to generate this is because we know that the position of E comes before Q, and in this case there are two entries QA and QE. So which means like if we will have to identify that what is the second letter, and second letter A comes before E, and then this R actually comes before Q. So we are able to determine a sequence like this. Now in this given problem, we don't need to generate a sequence like this. Basically we are told that we are not given this information. We don't know that what is the order of words are, and we are directly given this particular sequence that is already sorted in that particular language. So suppose this was to be an alien language, and if we want to identify that what should be the answer we need to return in this case, the few things we can determine from this input is that okay, over here we are checking first at any point we are checking any two adjacent words. In those two adjacent words we go letter by letter and we try to see that what is the first differing letter that comes to the existence, and based on the differing letter, whatever the word is presented first should come first in that order rather than second second letter. So if we compare these two words E, A and QA, we can see that the first differing word comes as E, and over here it is Q. So which means we can determine that E will always come before Q in this particular alien language. Now don't forget this, that this is plain English. Just imagine this as an existing scenario. So we know one scenario, okay, that E should come before Q, right? Now over here again, if we compare next two words, the next two words are QA and QE. Okay, so in QA and QE, notice that the first letter is Q, so it is common, which means we cannot identify much information from that. But the second letter is A and E, which means we can determine that at any given scenario, A will always come before E. So we can notify that, we can also create a scenario like that, that A will always come before E. And over here I am denoting this relation by an arrow, which indicates that at any given moment E should always come before Q, because it is on the beginning end of the arrow, and the where it is pointing to should comes later. And again we will compare these two words QE and RC. So if we compare these two words, we can identify that okay, Q should come before R. So we can also denote that relationship, that Q will become will be before R, right? And over here now we have these three relations. So based on these three relations, we can actually establish something over here, that we can establish that A will always come before E, and E will always come before Q, and Q will always come before R. So one of the sequence that we can return over here is that A, E, Q, R. Okay, so this is one of the sequence that we have to maintain at any given cost, because we are given these conditions based on the words that were given. But the thing is, will this be our answer? And actually this will not be our answer. And the reason this will not be our answer is because over here we are given this particular line that we need to return a string of unique letters from this words in the new alien language, that is lexicographically increasing order. But the thing is, over here if we look the original input, in the original input we actually have one more unique character that we are missing, and that particular unique character is, so we already took care of E, we took care of A, we took care of Q, A, Q, E, R, all of this we took care of. But C, the letter C, we did not take care of it. And the thing is, over here, based on whatever the input that we were given originally, we cannot determine the position of C. But the thing is, we know that C is also a unique character. And the only thing we know about the positioning is that for these four characters, we can define some positioning like this. For C, we cannot determine any positioning, but the thing is, it has to be part of the answer as well. And that is why we are told that there could be multiple solutions and we need to return any of them. So in this scenario, this could also be a solution where A, E, Q, R and C we are placed at the end. Or this could also be a solution where A, we put C somewhere in the middle, and E, Q, R is also placed like that. The important thing is that we need to maintain this order. As long as we are maintaining this order, because this C is one of those unique letters where we cannot find the dependency for that. So we will need to take care of it as well, and this is a very important detail that lot of other videos have missed out, and that is why it took me a lot of time to make this video. I want to make sure that I go through it completely. Now let's take one more example from the given input, and we will again try to find that what should be the answer for that. So in the given input, we are given the following words. These are the words that we are given in the alien dictionary, right? And our aim is to find that what should be the answer in this case. Well, the first thing is that what we are going to need in order to generate the solution. In order to generate the solution, we are going to need two things. We are going to need list of all the unique characters that exist, and second thing we are going to need is what are the dependency on all between characters, and based on these two things we will try to generate some sort of order or some sort of pair. And also remember that we will have to consider the scenarios where we could find invalid strings as well. So I'll be explaining that in this example. So over here, if we see the list of unique characters, the unique characters are W, R, T, F, E. Okay, these are all the unique characters that we can find in this particular input. Okay, now let's start making dependencies. Now, in order to make dependencies at any given moment, we will have to compare two adjacent words, and we are going to find first differing character, and based on the differing character, we are going to establish some dependency. So first of all, the first two words we are going to compare are WRT and WRF. Okay, in this case, W is common, R is common, which means that first differing character is T and F, and we already know that these words are sorted. So because they are sorted, we can determine that T should come before F. Okay, we already know that. This is good. Now what are the next two words? Next two words, and we are done with this WRT. The next two words are WRF and ER. Okay, so WRF and ER. Now in this case, what is the first differing word? Well, the first differing word is first letter by itself, or W and E, which means we can make another dependency that W should always come before E. Now we can ignore this. Again, we compare next two words. So ER and ETT. So over here, what is the first so EE is common. The first differing letter is R and T, which means that R should come before T. Next one is ETT and RFTT. So over here, the first differing character is E and R. So we can also mention that E should always come before R. Okay, now we have these four dependencies for these 5 unique characters. Now let's try to create a dependency tree from this given input. So if we see, we can clearly see that, okay, W is dependent on E, and E, so W comes before E, then E comes before R. Okay, then for R comes before T, and T comes before F. So this becomes all the dependencies, and if we notice all the unique characters, they are already part of these dependencies. So we are good, we don't need to do anything more over here. Now if we make that what should be the order of letters, the order of letters in this case would be W, E, R, T, F, and this would be the correct solution. Now notice that in order to generate the correct solution, what we had to do is we had to find all the unique characters, all the dependencies. Once we had all the dependencies, we actually had to iterate over all the dependencies, see that which dependencies are interconnected. Based on their interconnection, we actually had to generate this order. And in order to do that, we are actually using graph theory. And how we are using graph theory is basically all the unique characters in this case are actually nodes, and all of these dependencies are actually edges between those nodes, and those edges can be represented as in some form of adjacency list in some sort of hash map. And then we will need to iterate over all of the entire graph, and then at any moment we will have to go through the graph and find the solution, that what should be the order in which we are able to iterate over all the unique characters, which means that all the nodes inside the graph. And we need to generate this order of pairs, and if we are able to successfully generate this order of pair, we will return whatever we find. And if for somehow we find out that the input is invalid, we will have to take care of that scenario as well. So first let's take a couple of examples where we can find that the input could be invalid. Now, based on the English language, we know that at any given moment, if there are two words present, W1 and W2, and we know that any single word, so suppose W1 is actually prefix of this W2. If that is the case, then W1 should always come before in the dictionary than W2. Let's take it by an example. Suppose we are given two words like bat and Batman. If we are given two words like this, so if we start comparing these two words and see that what should be their order, we check that okay, B is common, A is common, T is common, right? Now over here, this actually ends. There is actually an empty list. There is nothing over here. While over here, there are still some values. So if that is the case, we can determine that this W1 is actually prefix of this W2, because these three characters are also present over here. And in that scenario, this W1 should always come before W2. At any given moment, we identify that this particular character is not present in correct manner. And suppose we are given an input like this, that Batman and bat. If we at any moment encounter this scenario, we can immediately return false, because, or we can immediately return an empty string, because this is a wrong ordering. So this is one of the failed scenarios where we cannot do anything, right? So this is very important to understand, and we will have to take care of this in our solution. The second thing that will not work is that at any given moment, suppose we are given list of words. Suppose the words are like X, A, B, X. Suppose we are given list of words like this, and what this means is that the first letter X should always come before A. Okay, so based on these two, we can establish this dependency. Based on these two, we can also establish that A should always come before B. Okay, and over here, the next thing is that B and X, which means that what this is saying, that B should always come before X. So if you notice over here, that we are actually stuck inside a cycle, that X needs to come before A needs to come before B, and B needs to come before X. So at any moment in our graph, whenever we are traversing over all these unique characters and dependencies, at any moment we encounter that okay, there exists a loop, and if we detect that there is a loop from any particular node, then we can return false immediately, or we can say that okay, this is an invalid case where the string actually doesn't exist, and we will need to break out of the loop. Suppose we are given a custom example like this, words, and we are told that all of these words, they are lexicographically sorted in the alien dictionary, and now we need to return the order of words of all the unique characters that we can find. So what should be the approach? Well, in order to do that, we are going to need two things. First thing we are going to need is all the list of all the unique words or all the unique characters, and we are also going to need the entire dependency between any two letters, that which should come first and which should come later, right? So let's start working on it. So first of all, we have B and A. Okay, so we will just add list of unique letters B and A, and second word is BY, which means that first differing characters A and Y. So we can establish a dependency like this, that A should come always before Y. Okay, now again moving forward with next two values. So over here the first differing character is B and A, which means that B should always come before A. And also I forgot to add one more unique character Y over here, right? Now this B should come before this A, so we will add that to our dependency list as well, that B should come before A, right? So this is one dependency, and over here we have the unique character D, so we will add the unique character D as well. Now we have this other word, these two words, and in these two words A is common, which means that D and L are differing characters. So first of all we will add the word L over here, and over here we have this D, right? So we know that D at any given location will come before L. Okay, so we'll just mention that. Now over here we have one more unique character T, so I'll also mention that. Now the next two words are these two words. Over here the A is common, L and I are different, and also we have one more unique character I. Now we know that there is a dependency between L to I, so we will also mention that L should come before I. Now the next two words are AI and AIR. Now notice over here that this AI is actually prefix of this AIR, right? Which means that this AI will always come before this word AIR, but we cannot determine anything regarding this R, because this R by itself, it has no other thing to compare its result with, which means that though we have a unique word, we don't know that what is the intention for that particular word is. And now let's see that in the dependency list that we have created, amongst these unique words, what are all the words that we are able to find a pair for. So one pair we were able to find is for this one, this BAY. Let me just draw everything in same color. So BAY, this is one pair, which means we know that at any given moment this BAY order has to be maintained, like B always has to come before A and Y. And same goes for this DLI, that D always has to come before L, and L always has to come before I. But in the list of unique characters, we are given this R and T as well, that are not represented by any dependency, which means we can say that this R and this T, they are unique characters by themselves, which does not have any sort of dependency, right? So if we want to see that what could be the potential different pairs we can make over here, well, there could be bunch of different results. Like there can be so many different permutations and combinations. Let me just give you a few of them. Like most simple one would be BAY DLI RT. So this is one combination where notice that we are just maintaining the entire order. Now second combination could be B D A L Y I R T. Now notice over here that at any given moment we need to make sure that these two orders are met up. So B is always coming before A and A is always coming before Y. So that is satisfied. Over here D is always coming before L and L is also coming before I. So that is also satisfied. This RT, they don't have any dependency, so it doesn't matter. We could have some pair like this, that B R T D A Y L I. This is also a valid pair, because notice that this B A and Y, this is maintained, this D L and I, this is also maintained, and this position of R and T doesn't matter. So there can be bunch of different options that we can choose from, and I'm just showing you that these are the different results we can have, right? Because we need to take care of unique characters as well, so don't forget the unique characters, they are really important. Now what should be the approach in this case? Well, one approach is actually quite simple. Because we know that we have unique characters, we have the dependency, we can choose some data structure like hash map. We can iterate over at any point whenever we identify the dependency, we can iterate over the entire hash map. We can, from any point, we will try to see that whether it has any dependency or not. If it has dependency, we will go to that dependency, we will try to iterate over those values, and we will try to generate the order list, right? So let's see that how it can work. Suppose we create a hash set like suppose we create a hash map like this. Okay, suppose this is our hash map, and based on these dependencies we know something, that we know that okay, in order for us to put down this B, we know that A has to come after B, which means A has dependency on B, right? We will mention it over here. Now for this A has to come before Y, so A has to come before Y. Now for this y, we don't have any dependency, so we'll just leave this value as blank. Now for this particular d has to come before l, right? So we'll just mention l over here. Now this l has to come before I, so we'll just mention I over here. For this I, we don't have any dependency, so we are good. And same goes for this t and r, that we don't have any dependency, so we are good. Now since we have this dependency tree, let's see that what would be the approach we can take over here. So in this scenario, suppose if we want to calculate that what would be one of those ordering pair, what we can do is we will start traversing through all of these values, all of these unique characters. And remember that this is hash map. So in hash map, we are treating these as key values, and these are actually values. So in the keys, we are mentioning all the unique characters. In the value, we are mentioning all the dependencies. Now over here, we will start iterating at this b. So first I'll just mark b as that we are iterating over it, right? Now from this b, we identify that, okay, we need to have a before b. So again, we go to a, because we will have to check all the dependencies, right? We cannot just put any letter randomly any place, right? Because this b has some dependency, so we will have to go over that. Now this a has actually dependency on y. So again, we'll go to y and we'll just mark a as being as part of being visiting. And over here we reach at this y don't have any dependency, so we are at this y. Now notice that we are actually traversing this graph in DFS manner, depth first search manner, right? And in depth first search, at this y, we identify that, okay, this y does not have any dependency, so we can just put y to our order list. So we can just put y to our order list. Now from this y, we will do a backtrack. We'll again come back to a. Again, we will do a backtrack. Again, we will come back to b, and then we would be done with this b, right? That, okay, we are done with this. Now again, we ignore all of these. Now we start with this second position. Now in the second position, first we determine that whether we have calculated this value already or not. So since a is already calculated over here, so we ignore that. So we can ignore the second case. Again, we check that whether this y we need to calculate it or not, but y we have already calculated, so we can ignore this, right? So we'll ignore this, and now we'll move on towards this d. Now do you see any problem with this one? Well, definitely we are seeing a problem with this one, and the problem is that over here the dependency is like this, that b has to come before a and a has to come before y in order for us to generate the dependency order. But over here, when we started traversing, the actual dependencies we are getting is actually in reverse order. You see that y comes before a and a is coming before b. So one way we can do it is that we can start traversing like this one, that over here we again come to this d. For this d, we find a dependency as l. For this l, we find a dependency at I. For I, we don't find anything, so we'll just put I over here. Then we backtrack, so again we put l over here, and then again we backtrack, and then we will put d over here, and then we come to this t, like this I, this l, and this has already been done, so we ignore that. We come to this t does not have any dependency, we put it there. I has already been processed, and we reach at over here at r. Now this order list we got is actually correct, but in reverse order, because the dependency should be like b a y, and this should be d l I, but over here it's d l I in reverse order, and same goes for b a y. So what we will have to do is when we calculate the answer, we will have to return the reverse of this answer, and that would actually satisfy these dependencies. So that is one way of doing it, right? And there is also another way of doing it, and the better way is that when we are actually creating this hash map, we can actually do something different. Previously in the hash map, what we are doing is that over here we had a key as all the unique characters, and as the value we had these dependencies exactly as they were mentioned, that for this particular b it is dependent on a, for this particular a it is dependent on y. But the thing is, that is not true. The actual true thing is that actually this y, the position of y should be dependent on a, that y cannot be present unless there exists an a value before that. If we start, so if we rather than storing the dependency on value that is taking care of the value that comes after it, if we start taking care in reverse order. So let me show you what I mean by that. So suppose if we have a hash map like this, and over here in the value we actually present at any given value what should be the previous value that has to be present in order for us to reach at that particular value. So what that would do is that if we want to calculate this b, we don't need to basically have any value, right? So over here we will leave this as blank, that for b we don't have any dependency. But for this particular a, we actually have dependency on b, that b has to be there in order for us to process this a. So we will put a dependency over here saying that okay, b needs to be there for us to calculate this value a. Same goes for y, that a needs to be there in order for us to calculate this value y. Again we reach at this d, and for the d we don't have any dependency, so we'll just leave it blank. But for this particular l, again we will have to have a d over here, so we'll put a d over here. For this t we don't have any dependency, so we can leave it blank. For this particular I, we actually have to have an L before that, so we'll put a dependency over here. And for this R, we don't have any dependency, so we'll leave it blank, right? So this is the table this is the hash map that we work with. And over here, now let's try to iterate over this hash map. Essentially, our aim is to iterate over this entire hash map. Identify that at any point, if you are inside the DFS function, you are not finding the repeated character. So that is now item number 1. Second thing to make sure is that you go through all the characters and you start building up the order list. So over here we will get, we initially start at B, and at B we don't have any child, so we are good to put B over here. Now next, and we can mark that B is already done. Now we are at this A. So for A, we need to check that whether B is done or not. B, we check over here, B is already done, so we are good, which means that we can put A over here. So we'll put A over here. Again, we will mark A as being done. Again, we are at this Y, we check that, okay, Y has dependency on A. So we check, okay, A is already done, so we can put Y over here as well. Now we are at this D. So D does not have any dependency. So we can just simply put D over here, and we can just mark this as done. Again, from L we check for D. D is already marked, so we put L over here. T does not have any dependence, and we mark L. T does not have any dependency, so we mark T is done. We can put it over here. Now this I has dependency on L. L we have already marked that it is done, which means we can complete this I as well. And for this particular R, it does not have any dependency, so we can put it over here. Now if you notice this scenario, we are actually fulfilling both of these dependencies. And notice that this B comes before A and comes before Y, so we are good with this dependency. This D comes before L and I, so we are also good with the second dependency as well. And this T and R, they were actually separate values, so it doesn't matter wherever we put them, as long as they are there, it fulfills our purpose. And this is the actual solution that we need to take care of, that where initially we will iterate over all the words, we will create all the unique characters. Based on the unique characters, we will create the dependency list. Based on the dependency list, we can actually create a hash map that we are going to use to traverse as a graph. But the thing is, rather than traversing the original hash map, we can actually create a reverse list of dependencies, and we can iterate over that just once using DFS or BFS, anything, but we are going to use DFS because I want to master DFS for myself, and that would be our solution. So it took me a lot of time to come up with this solution. It took me a lot of time to understand this problem. Okay, let's calculate time and space complexity for this problem. So the time complexity for this one is going to be big O of C, where C is actually total number of characters that are given in this original input words. Because notice that there are actually three parts of this problem. The first part is that we need to find all the unique characters. Like in order for us to generate all the unique characters, we will have to iterate over all the characters that are given in the original input words. So that is one part. Now second part is that we need to create a dependency, and in order to generate the dependency, again we will have to traverse all the words. And the third part is that we will have to so we are generating some sort of hash map, and inside the hash map we will have to iterate over all the values inside the present hash map. So at any given moment, the maximum work we are doing is iterating over the sum of all the characters that are given inside this words. So that is why that would be the time complexity. And if we want to calculate the space complexity would actually depend on the number of unique characters. So suppose that in English language, the number of unique characters maximum we can have is only 26, right? And we are also told that for this alien language, the maximum number of unique characters we can have is also going to be 26. So space complexity actually has a finite number, and there is only so much it can grow. So we can treat space complexity to be big O of 1 or constant space complexity for this one, even for us to creating this additional hash map. The second thing is that suppose if we want to calculate based on the number of unique characters, there is also one equation where the space complexity would actually be big O of u plus whatever the u square or n, whatever the minimum value of this is. And let me know in the comments if you want me to explain the space complexity in a scenario where the number of unique characters are actually not finite and not 26. Like in this case it's 26, so I will just leave it as it is, but let me know if you want me to explain that. First of all, we are going to create our hash map, and we are going to actually create it outside of this alien order method that is given, because we want to use that hash map to our DFS method as well. So, and as a key we are going to use unique characters, and as a value we are going to use the dependency. So it would be list of characters, and we are going to name it reversed list, because essentially we are just reversing the adjacency list. Also we will create another hash map to essentially store the value of any parameter that we are already currently visiting inside our DFS method. And we'll need to create an output of strings, so we can create a string builder variable. Now the first thing we need to do is find all the unique letters inside our given word string of words. Now this is done. Now we will have to find all the edges, and we will have to add the reverse edges to our reverse list hash map. Now at any given moment we need to check that whether the word 2 is actually prefix of word 1 or not. If that is the case, we can return false immediately, and we have found a terminating case where the given string of words is not valid. Okay, if that's not the case, we will find the first differing character between two words and add it to our hash map. And notice that we are actually adding the value to the second word's differential character. And the moment we find the first differing character, we can actually break out of that particular word. Now we are going to iterate over the reverse list hash map that we have created, and we are going to run our DFS function. Okay, for all the keys present inside the reverse list hash map, we are going to run the DFS function, and we are also going to check that at any given moment have we receiving the result as false. So we are just going to create a boolean variable result, and now we are going to call the DFS function, and we are going to provide the character inside the reverse list. And at any moment, if we identify that the result is for this result character is actually fault, we will return empty list immediately. Okay, now all we need to do is that once this DFS step runs, we should have our output inside the result. So we will have to check that whether all the unique characters have been taken care of or not. So we are going to check that whether the length of output, if that is less than the size of our list, if that is the case, we can return false immediately because we haven't taken care of all the unique values present. And if none of these cases happen, we will return whatever we find inside the output. Now the only thing we need to do is we will have to create the DFS method. Now first of all, we are going to check that whether the current character C we are checking, if we have already visited that or not. If we have already visited that, we are simply going to return false. If that's not the case, which means first we'll add the current character to our scene hash map, and we are going to mark the entry as false. So that way, whenever if we encounter the repeated value, it will always return false. Otherwise, by default, the value would be true. Okay, now for every single character inside the current, for the given character, we will iterate over inside the reverse adjacency list, and at any point if we encounter the result false, we will return false immediately. If that is not the case, we will remove the entry from the scene hash map. So we'll set the entry as true, and inside our output string we will append the value. And for that particular character, we are going to return true. Okay, so I know this is a very long and too many lines of code. I'm going to put this in the comments. Let's try to run the code. Okay, seems like our solution is working. And also remember, I was talking to you that we will have to take care of all the unique characters. Here, let me show you an example. So suppose we only have two characters, H and P. If we are only given input like this, and we know that H comes before P, right? Which means that in the result we should be getting HP. So let's see that what, okay, so this is accepted, right? But now let's say that we have additional character HA and PB. Now over here we don't have any mechanism to measure this A and this B, so they become unique characters, right? And now let's try to run the code for this particular test case. So if we do that, you are going to see that A and B would be at weird locations. So over here, see, the important thing is in our output we are maintaining the order for this H and P, and that is what it matters. Like A and B over here in our output is actually behind this HP, while over here the A and B are actually at the beginning, and then there comes HP. So it doesn't matter as long as the order that is given in the input is maintained. And now let's try to submit this code, and oh wow, our solution is actually 99% faster than all the other solutions. And I used lot of help from the solutions tab from this LeetCode premium, because it took me a lot of time to understand this problem. So I'll be posting this in the comments, you can check it out from there. And hope you like the video. So the LeetCode problem we are going to solve now is called swim in rising water. This one is a hard problem, but a very interesting and intriguing problem. So let's try to understand this. We are given an n cross n integer matrix called grid, where every single value inside the grid represents the elevation or height at that particular point in this I and jth location or any particular cell. Now we are told that the rain starts to fall, and at t times, which means rain is falling, let's say from 1 minute, then 1 minute it keeps on falling like 2 minutes, 3 minutes, 50 minutes, up all the way up until t times. Then the depth of water everywhere is t, which means rain is proportional to the amount of time that has passed linearly. Now we can swim from any particular square to all the four adjacent squares if and only if the elevation of both the squares individually are at most t, which means we can swim from one square to any four directions as long as, let's say that the current t is, let's say, 15. So any particular square that has the value 15 or less in all these four directions, we can swim from this current place. So the amount of t becomes the critical point for us to compare that are we able to traverse in between any two squares or not. Now we need to make sure that we need to reach to the bottom right square where we are starting from the top left square, and we need to make sure that what is the least amount of time we need to wait before we can reach to the bottom right square. So let's try to understand this with an example. The aim is we are given a grid like this. Now our objective is to traverse from this particular node to this particular node. We are being told that at every single moment what is the elevation or what is the height at that particular point. Now the thing is, let's say that we are currently t is equal to 0 point, right? Which means and we are currently located at this moment. So the thing is, currently only 0 units of rain has fallen, which means this particular portion is entirely filled up with rainwater. So we are able to swim within this cell. But the thing is, this cell has a height of 2, this cell has a height of 7, and this cell has a height of 4. So we cannot traverse in any four directions right now. Let's say now enough time has passed, and right now currently t is equal to 3, which means we can assume that, let's say, 3 meters of rain has fallen. So if 3 meters as rain has fallen, then this portion would have filled up completely because it only requires 2 meters to fill up. But thing is, all the other squares are still not filled up, and because current t is equal to 3 and we are currently initially located at this very first spot, then we can traverse to this particular spot anytime after t is equal to 2. So at t is equal to 3 we can still travel. When t becomes 4, then at t becomes 4 this portion also gets filled up and we can also swim in this direction as well. So our aim was to reach from this particular square to this particular square, and we can only do that once the t amount of t gets 4. So notice in this case we are avoiding this path going down because this path is more expensive. So our answer in this case would be t is equal to 4. Let's try to take one more slightly complicated example. Our aim is to reach from here to here. Now we notice that there are a bunch of different ways for us to we can go from here to here. We can take as many paths as we want, and actually if we have to calculate mathematically how many paths it's going to take, I think it's going to be n divided by number of ways we can move and factorial of that. So this is going to be a very expensive operation if we have to manually brute force our way to check every single path. But lucky for us, logical thing is that we need to check only for some t positions. So let's say that initially if we are at the position of t is equal to 5, so let's see that where up until what point can we reach if t is equal to 5. We know we can swim from here, no issues with this one. Then we cannot swim into this cell because this is a higher t, but this is a lower t value, so we can go over here. Then nextly from this we can also go over here because this is also lower than 5, but we cannot go anywhere further. So we will have to increase the value for t to t is equal to 6. Still we cannot go anywhere further. If we do t is equal to 7, then we can traverse up until this point, and notice that at t equal to 7 we can also traverse to this point because this is lesser than the current t value we have. So the minimum amount of t we need to complete all the values is not going to be t is equal to 6. Even though this value is 6, it is going to be t is equal to 7. So one more way to explain this is to find a path that traverse from this one to the last, like top left to bottom right corner, and in that path find the minimum like the maximum value of t that is required. So that would be our answer. So now let's try to reverse engineer our way through this one. We already know that, let's say if we are being told that you have this particular example, and for this example you need to make sure that you need to iterate over all the values only and only if for any particular given t. So let's say that we ask you that if the t is equal to 3, are you able to reach to all of these values? So logically what we will do is we will start from here, and then we will see that what are all the cells that has less value than t. So this cell has less value than t, then next this value has less value than t, and then we can say that now we cannot go anywhere further. We can also try to do a backtrack and check for the other possibility, but still we won't be able to do it. So logically we need to do like depth first search or breadth first search in order to find the path we need to take to reach to the end. That is number one fact. The other thing is, after finding the DFS or BFS, we don't know that what should be the optimal value of t in order for us to reach to the very end. So for that there are bunch of different possibility, but one common way that is for sure is that the minimum value of t can be 0. So whatever the smallest value is, so let's say the smallest value is 0. So let's see, the possible values of t can be 0, or t has to be less than the maximum value we currently have. So in this case the maximum value we have is 24. So t has to be somewhere between 0 and 24. That is a given fact, like less than or equal to. Why? Because all the time if t is equal to 24, then we have access to traverse to every single cell in this given entire architecture. So if we can traverse to all the cells, for sure we can find a path that can lead us from top left to the bottom right corner. But so now we found one condition on where the t should be able to move. This is number one thing, that what could be the potential value of the t. Second thing is, we already know how to calculate that for any particular given value of t, are we able to traverse to all the cells and reach to the bottom right corner or not. We can do this in both the ways. We can use a breadth first search, or we can use a depth first search in order to do this one. And it's a pretty common and standard method that logically we are going to be traversing over all the different paths wherever this condition meets up, and the moment we find out that the condition is currently satisfactory, we can actually move to all four directions to find the value we are looking for. So what I'm suggesting is, instead of checking for all the potential values of t, which is going to be pretty expensive operation, why don't we use binary search in order to find the correct value of t that makes sense. So what I'm suggesting is, let's say that for this particular given value, we know that the t has to be somewhere between 0 and 24. So what we can do is we can treat this 0 as the left pointer, this 24 as the right pointer. Then we will try to find the mid pointer. Mid pointer is going to be 12. So let's see that if we use the t is equal to 12, are we able to reach to this bottom right corner? So we can go down this path, that's for sure. But now after this 5, we cannot go anywhere because this is 16 and this is 21. So 12 does not work, which means the answer of t has to lie somewhere between 12 and 24. So we update, so sorry, not 12, like 13 and 24. So we update our left pointer and right pointer once again. We try to find the mid pointer. So in this case, the mid pointer is going to be, I think somewhere between 18. So let's see at 18, are we able to figure out? So yes, we can go down this path. Yeah, for sure at 18, we can take this path. And once again, we should be able to complete our answer in this manner. No issues with this one. So yes, 18 works. So once again, now we have our left pointer as 13 and right pointer as 18. Once again, we will do the binary search. So we will find the middle pointer to be 15. Let's see, at 15, are we able to find the correct value we are looking for? No, right? Because the 16, we would not be able to cross this threshold. So next possible value is going to be 15 and once again 18, sorry, 16 and 18. So the logical step would be 17. 17 would work because we would be able to find out Then once again, from between 16 and 17, we also have to find that are we able to do it. So if we do the mid pointer, once again the value would be 16, and for 16 we should be able to find the answer. So logically, we had to do, like, instead of doing 0 to 24 steps, we only did 5 steps to find that value to 16, and that we did it using binary search. So logically in this problem, what I'm suggesting is that we use breadth first search or depth first search, whichever one you would like to choose, in order to iterate over all the cells. And we do this with doing the binary search on the different values of t, and the range for t is going to be the smallest element, like 0 less than or equal to t less than or equal to whatever the maximum element we have inside our grid, and somewhere between that we will try to find the value of t. So this solution would work perfectly fine. If we have to calculate time and space complexity in this case, the BFS or DFS would take big O of n square work, because we have n cross n grids and for one iteration, and we will have to do this log n time, because we are trying to find different values of t. So it's going to be n square log n in terms of time complexity. In terms of space complexity, depends on how you implement your breadth first search or depth first search. If you are using recursion, and if you are using like a stack, recursive stack to store those values, then it might take big O of n square space as well. So just be mindful of that. Now let's quickly see the coding solution for this one. So the very first thing we are going to do is, we are going to mark the value of n. Then we are going to initialize our left pointer and right pointer. This is going to be the cell locations. And then we are checking that while our left pointer is less than right pointer, we are going to find the mid pointer that we will have to iterate over. And on top of it, we are also going to check, or we are going to call our helper method call swim, can swim, and which checks that for any particular given grid, depending on the mid pointer, are we able to reach. If we can, then we shift our right pointer to the mid pointer. If we cannot, then we update our left pointer to go right +1. So this is our binary search method. Now let's understand our can swim method. So in the can swim, we have the given grid as the input and the different values of t we are working with. On top of it, we are checking that first of all, what is the length of the given grid. We are also having a visited boolean hash set that defines that these are the cells we have visited so far, because we don't want to be stuck inside the infinite loop in breadth first search or depth first search. And we are going to call our DFS method in this case, where we are passing in the grid, the nodes that we have currently visited, the I and jth location, and we are also passing in the different values of t. Now this is going to be our recursive DFS method, where first thing we are checking is that what is the given length of n. Then we are checking for the scenarios that if we are going out of bounds, so these 4 conditions are for going out of bounds, or we have already visited that node, or we notice that the location of the grid position is greater than the current t value, then we can return false, that we cannot go to that particular cell. If that is not the case, and we check that the current ith and jth position is at the bottom right, then we can simply return true, saying that yes, we are able to reach to bottom right corner. If that is not the case, then we mark the current node as visited, and then we call the DFS method in all 4 directions, and once again recursively repeat the same process. So this is the coding solution. So basically, after this recursive process ends, we should either receive true or false for any particular t value. And inside our main method, we are trying out bunch of different t values and making these various calls. So this is the whole solution. Now let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. And our code beats almost 98% of all the other solutions, which is like one of the fastest solutions for this particular hard problem. So I hope you find it useful. Once again, the solution is present on our GitHub repository, so feel free to go ahead and check it out from there. Thank you.